2019-2. Forward. The National Curriculum Framework (NCF) 2005 recommends that children's life at school must be linked to their life outside the school. This principle marks a departure from the legacy of bookish learning which continues to shape our system and causes a gap between the school, home and community. The syllabi and textbooks developed on the basis of NCF signify an attempt to implement this basic idea. They also attempt to discourage rote learning and the maintenance of sharp boundaries between different subject areas. We hope these measures will take us significantly further in the direction of a child-centered system of education outlined in the National Policy on Education 1986. The success of this effort depends on the steps that school principals and teachers will take to encourage children to reflect on their own learning and to pursue imaginative activities and questions. We must recognize that, given space, time and freedom, children generate new knowledge by engaging with the information passed on to them by adults. Treating the prescribed textbook as the sole basis of examination is one of the key reasons why other resources and sites of learning are ignored. Inculcating creativity and initiative is possible if we perceive and treat children as participants in learning, not as receivers of a fixed body of knowledge. These aims imply considerable change in school routines and mode of functioning. Flexibility in the daily timetable is as necessary as rigor in implementing the annual calendar so that the required number of teaching days are actually devoted to teaching. The method used for teaching and evaluation will also determine how effective this textbook proves for making children's life at school a happy experience, rather than a source of stress or boredom. Syllabus designers have tried to address the problem of curricular burden by restructuring and reorienting knowledge at different stages with greater consideration for child psychology and the time available for teaching. The textbook attempts to enhance this endeavor by giving higher priority and space to opportunities for contemplation and wondering, discussion in small groups, and activities requiring hands-on experience. The National Council of Educational Research and Training (NCERT) appreciates the hard work done by the Textbook Development Committee responsible for this book. We wish to thank the chairperson of the Advisory Group in Science and Mathematics, Professor J.V. Narlikar, and the Chief Advisor for this book, Professor B.L. Khandelwal, for guiding the work of this committee. These several teachers contributed to the development of this textbook. We are grateful to their principals for making this possible. We are indebted to the institutions and organizations which have generously permitted us to draw upon their resources, material and personnel. As an organization committed to systemic reform and continuous improvement in the quality of its products, NCERT welcomes comments and suggestions which will enable us to undertake further revision and refinement. Director, New Delhi National Council of Educational, November 20, 2006. Research and Training. Preface. Chemistry has made a profound impact on the society. It is intimately linked to the well-being of humankind. The rate of advancements in chemistry is so high that curriculum developers continuously look for strategies to cope with these advancements. Also, the students have to be inspired to be the future leaders who would make fundamental contributions. The present textbook is a sincere effort in this direction. The structure of the textbook, presented in 2 parts, comprises of 16 units. Although the titles of various units indicate a sort of compartmentalization into physical, inorganic and organic chemistry, readers will find that these subdisciplines have been intermingled, at least to a certain extent, to have a unified approach to the subject. The approach of presentation of the subject matter discourages students from rote memorization. The subject has in fact been organized around the laws and principles of chemistry. As students master these laws and principles, they will soon get to the point where they can predict much of what will come. Efforts have been directed towards making the subject stimulating and exciting by references to the historical developments and its usefulness to our lives, wherever appropriate. The text is well illustrated with examples from surrounding environment to facilitate grasping of the qualitative and quantitative aspects of the concept easily. Physical data are given in SI units throughout the book to make comparison of various properties easier. IUPAC system of nomenclature has been followed along with the common system. Structural formulae of chemical compounds showing functional coordinating groups in different colors are drawn using electronic system. Each unit has a good number of examples, as illustrations, with their solutions and some in-text questions, the answers of some of which are given at the end of the unit. The end-of-unit exercises are designed to apply important principles and provoke thinking process to solve them. Answers of some of these exercises are given at the end of the book. A variety of materials, e.g., biographical sketches of some scientists, additional information related to a particular topic, etc., is given in boxes with a deep yellow colored bar. This box material with a deep yellow bar is to bring additional life to the topic, however, it is non-evaluative. The structures of some of the more complex compounds incorporated in the book are for understanding their chemistry. As their reproduction would lead to memorization, it is also a non-evaluative portion of the text. The information part has been significantly reduced and, wherever possible, it has been substantiated with facts. However, it is necessary for students to 8. Be aware of commercially important chemicals, their process of manufacture and sources of raw materials. This leads to descriptive material in the book. Attempts have been made to make descriptions of such compounds interesting by considering their structures and reactivity. Thermodynamics. Kinetics and electrochemical aspects have been applied to chemical reactions, which should be beneficial to students for understanding why a particular reaction happened and why a particular property is exhibited by the product. There is currently great awareness of environmental and energy issues which are directly related to chemistry. Such issues have been highlighted and dealt with at appropriate places in the book. A team of experts constituted by the NCERT has developed the manuscript of the book. It gives me great pleasure to acknowledge the valuable contribution of all the members of this team. I also acknowledge the valuable and relentless contribution of the editors in bringing the book to the present shape. I also acknowledge with thanks the dedicated efforts and valuable contribution of Professor Brahm Parkash, who not only coordinated the entire program but also actively involved in writing and editing of this book. Thanks are also due to the participating teachers and subject experts of the review workshop for their contribution, which has helped us to make the book learner-friendly. Also, I thank the technical and administrative staff of the NCERT for their support in the entire process. The team of this textbook development program hopes that the book stimulates its readers and makes them feel the excitement and fascination for this subject. Efforts have been made to bring out this book error-free. Nevertheless, it is recognized that in such a book of complexity, there could inevitably be occasional errors. It will always be a pleasure to hear about them from readers to take necessary steps to rectify them. B.L. Khandelwal. 9 Elements. XI acknowledgements. The National Council of Educational Research and Training NCERT gratefully acknowledges the valuable contributions of the individuals and organizations involved in the development of chemistry textbook for Class 12. The acknowledgements are also due to the following practicing teachers and subject experts for reviewing the draft manuscript and giving useful suggestions for its improvement in a workshop, DRDS. Rawat, Department of Chemistry, University of Delhi, Delhi, Dr. Mahendranath, Reader, Chemistry Department, University of Delhi, Delhi, Dr. Sulek Chandra, Reader, Zakir Hussain College, New Delhi, Ms. Amita K., PGT Chemistry, Vidyalaya No. 3. Haloalkanes PB, DRGT Banj, Professor and Head, DESM, Regional Institute of Education, Mysore, Dr. Nidhi Mishra, Senior Lecturer, Department of Chemistry, Acharya Narendra Dev College, New Delhi, DR. SPS Mehta, Department of Chemistry, Human University, Nainital UA, Dr. and V.S. Naidu, Assistant Professor Chemistry. SVU College of Mathematics and Physical Sciences, SV University, Tirupati AP, DRAC Handa. Hindu College, Delhi University, Delhi, DRAK Vashishtha, GBSSS Jafrabad, Delhi, Dr. Chiranjit Kaur. Head, Department of Chemistry, Sri Satya Sai College for Women, Bhopal, P.O. Habibganj, Ms. Alka Sharma. PGT Chemistry, SLSDAV Public School, Musamvihar, Delhi, DRHH Tripathi, Reader Retired. Regional Institute of Education, Bhubaneswar, Sri C.B. Singh, PGT Chemistry, Kendraya Vidyalaya No. 2, Delhi Kant, Delhi, Dr. Nidhi Mishra and Dr. Sunita Huda, Acharya Narendra Dev College, Delhi University, New Delhi. The Council also thanks the members of Editorial Committee for their unrelenting efforts in editing the manuscript and bringing it to the present shape. The Council also acknowledges the contribution of Sri Vijay Singh, Sri Narendra K.R., Verma, DTP Operator, DRKT Chitralekha. Copy Editor, Sri Abhimanyu Mohanty, Proofreader, Sri Deepak Kapoor, in charge, Computer Station in shaping this book. 2019-2. From our earlier studies, we know that liquids and gases are called fluids because of their ability to flow. The fluidity in both of these states is due to the fact that the molecules are free to move about. On the contrary, the constituent particles in solids have fixed positions and can only oscillate about their mean positions. This explains the rigidity in solids. These properties depend upon the nature of constituent particles and the binding forces operating between them. The correlation between structure and properties helps in the discovery of new solid materials with desired properties. For example, carbon nanotubes are new materials that have potential to provide material that are tougher than steel, lighter than aluminium, and have more conductive property than copper. Such materials may play an expanding role in future development of science and society. Some other materials which are expected to play an important role in future are high-temperature superconductors, magnetic materials, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. Thus, the study of this state becomes more important in the present scenario. In this unit, we shall discuss different possible arrangements of particles resulting in several types of structures and explore why different arrangements of structural units lend different properties to solids. We will also learn how these properties get modified due to the structural imperfections or by the presence of impurities in minute amounts. After studying this unit, you will be able to describe general characteristics of solid state, distinguish between amorphous and crystalline solids, classify crystalline solids on the basis of the nature of binding forces, define crystal lattice and unit cell, explain close packing of particles, describe different types of voids and close-packed structures, calculate the packing efficiency of different types of cubic unit cells, correlate the density of a substance with its unit cell properties, describe the imperfections in solids and their effect on properties, correlate the electrical and magnetic properties of solids and their structure. Objectives: the vast majority of solid substances like high-temperature superconductors, biocompatible plastics, silicon chips, etc. are destined to play an ever-expanding role in future development of science. The solid state 1 Unit 1 The solid state 2 Chemistry. In Class Psi you have learnt that matter can exist in 3 states, namely, solid, liquid and gas. Under a given set of conditions of temperature and pressure, which of these would be the most stable state of a given substance depends upon the net effect of 2 opposing factors. These are intermolecular forces, which tend to keep the molecules or atoms or ions closer, and the thermal energy, which tends to keep them apart by making them move faster. At sufficiently low temperature, the thermal energy is low and intermolecular forces bring them so close that they cling to one another and occupy fixed positions. These can still oscillate about their mean positions and the substance exists in solid state. The following are the characteristic properties of the solid state. They have definite mass, volume and shape. 2 intermolecular distances are short. 3 intermolecular forces are strong. Their constituent particles, atoms, molecules or ions have fixed positions and can only oscillate about their mean positions. They are incompressible and rigid. Solids can be classified as crystalline or amorphous on the basis of the nature of order present in the arrangement of their constituent particles. A crystalline solid usually consists of a large number of small crystals, each of them having a definite characteristic geometrical shape. The arrangement of constituent particles, atoms, molecules or ions in a crystal is ordered and repetitive in 3 dimensions. If we observe the pattern in one region of the crystal, we can predict accurately the position of particles in any other region of the crystal, however far they may be from the place of observation. Thus, crystal has a long-range order, which means that there is a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. Sodium chloride and quartz are typical examples of crystalline solids. Glass, rubber and many plastics do not form crystals when their liquids solidify on cooling. These are called amorphous solids. The term amorphous comes from the Greek word amorphous, meaning no form. The arrangement of constituent particles, atoms, molecules or ions in such a solid has only short-range order. In such an arrangement, a regular and periodically repeating pattern is observed over short distances only. Regular patterns are scattered and in between the arrangement is disordered. The structures of quartz crystalline and quartz glass amorphous are shown in Fig. 1.1a and b respectively. While the 2 structures are almost identical, yet in the case of amorphous quartz glass there is no long-range order. The structure of amorphous solids is similar to that of liquids. Due to the differences in the arrangement of the constituent particles, the 2 types of solids differ in their properties. 1.11, 11, 11, 11, 1 General, capital C, H, A, R, A, C, T, E, R, I, S, T, I, C, S, capital C, H, A, R, A, C, T, E, R, I, S, T, I, C, S, of solid state 1.21, 21, 21, 21, 2 2 amorphous and crystalline crystalline solids Fig. 1.1 Two-dimensional structure of the quartz and B-quartz glass. Crystalline solids have a sharp melting point. At a characteristic temperature they melt abruptly and become liquid. On the other hand, amorphous solids soften, melt and start flowing over a range of temperature and can be molded and blown into various shapes. Amorphous solids have the same structural features as liquids and are conveniently regarded as extremely viscous liquids. They may become crystalline at some temperature. Some glass objects from ancient civilizations are found to become milky in appearance because of some crystallization. Like liquids, amorphous solids have a tendency to flow, though very slowly. Therefore, sometimes these are called pseudosolids or supercooled liquids. Amorphous solids are isotropic in nature. Their properties such as mechanical strength, refractive index and electrical conductivity, etc., are same in all directions. It is because there is no long-range order in them and arrangement of particles is not definite along all the directions. Hence, the overall arrangement becomes equivalent in all directions. Therefore, value of any physical property would be same along any direction. Crystalline solids are anisotropic in nature, that is, some of their physical properties like electrical resistance or refractive index show different values when measured along different directions in the same crystals. This arises from different arrangement of particles in different directions. This is illustrated in Fig. 1.2. This figure shows a simple two-dimensional pattern of arrangement of two kinds of atoms. Mechanical properties such as resistance to shearing stress might be quite different in two directions indicated in the figure. Deformation in CD direction displaces row which has two different types of atoms while in AB direction rows made of one type of atoms are displaced. The differences between the crystalline solids and amorphous solids are summarized in Table 1.1, DCBA Fig. 1.2. Anisotropy in crystals is due to different arrangement of particles along different directions. Table 1.1, distinction between crystalline and amorphous solid shape melting point cleavage property heat of fusion definite characteristic geometrical shape melt at a sharp and characteristic temperature when cut with a sharp-edged tool. They split into two pieces and the newly generated surfaces are plain and smooth. They have a definite and characteristic enthalpy of fusion. A regular shape gradually soften over a range of temperature when cut with a sharp-edged tool. They cut into two pieces with irregular surfaces. They do not have definite enthalpy of fusion property. Crystalline solids, amorphous solids. Besides crystalline and amorphous solids, there are some solids which apparently appear amorphous but have microcrystalline structures. These are called polycrystalline solids. Metals often occur in polycrystalline condition. Individual crystals are randomly oriented, so a metallic sample may appear to be isotropic even though a single crystal is anisotropic. Amorphous solids are useful materials. Glass, rubber and plastics find many applications in our daily lives. Amorphous silicon is one of the best photovoltaic material available for conversion of sunlight into electricity. In section 1.2, we have learnt about amorphous substances and that they have only short-range order. However, most of the solid substances are crystalline in nature. For example, all the metallic elements like iron, copper and silver, non-metallic elements like sulfur, phosphorus and iodine, and compounds like sodium chloride, zinc sulfate and naphthalene form crystalline solids. Crystalline solids can be classified in various ways. The method depends on the purpose in hand. Here, we will classify crystalline solids on the basis of nature of intermolecular forces or bonds that hold the constituent particles together. These are I van der Waals forces, 2 ionic bonds, 3 covalent bonds, and I metallic bonds. On this basis, crystalline solids are classified into 4 categories, viz., molecular, ionic, metallic and covalent solids. Let us now learn about these categories. Molecules are the constituent particles of molecular solids. These are further subdivided into the following categories. Non-polar molecular solids. They comprise either atoms. For example, argon and helium are the molecules formed by nonpolar covalent 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, capital C, L, A, S, S, I, F, I, C, A, T, I, O, N, capital C, L, A, S, S, I, F, I, C, A, T, I, O, N, capital C, L, of crystalline solids 1, 3, 1 molecular solids in text. Questions and text questions and text questions and text questions and text questions 1.1 Why are solids rigid? 1.2 Why do solids have a definite volume? 1.3 Classify the following as amorphous or crystalline solids. Polyurethane, naphthalene, benzoic acid, Teflon, potassium nitrate, cellophane, polyvinyl chloride, fiberglass, copper. 1.4 Refractive index of a solid is observed to have the same value along all directions. Comment on the nature of this solid. Would it show cleavage property? Anisotropy, nature, order and arrangement of constituent particles. Anisotropic in nature, true solids. Long range order. Isotropic in nature, pseudo-solids or supercooled liquids. Only short range order. 5. The solid state 1, 3, 3 metallic solids 1, 3, 4 covalent or network solids 1, 3, 2 ionic solids bonds, for example, H2, Cl2 and I2. In these solids, the atoms or molecules are held by weak dispersion forces or London forces, about which you have learned in Class I. These solids are soft and non-conductors of electricity. They have low melting points and are usually in liquid or gaseous state at room temperature and pressure. 2. Polar molecular solids. The molecules of substances like HCl, SO2, etc. are formed by polar covalent bonds. The molecules in such solids are held together by relatively stronger dipole-dipole interactions. These solids are soft and non-conductors of electricity. Their melting points are higher than those of non-polar molecular solids, yet most of these are gases or liquids under room temperature and pressure. Solid O2 and solid NH3 are some examples of such solids. 3. Hydrogen-bonded molecular solids. The molecules of such solids contain polar covalent bonds between H and F, O or N atoms. Strong hydrogen bonding binds molecules of such solids like H2O's. They are non-conductors of electricity. Generally they are volatile liquids or soft solids under room temperature and pressure. Ions are the constituent particles of ionic solids. Such solids are formed by the three-dimensional arrangements of cations and anions bound by strong Coulombic electrostatic forces. These solids are hard and brittle in nature. They have high melting and boiling points. Since the ions are not free to move about, they are electrical insulators in the solid state. However, in the molten state or when dissolved in water, the ions become free to move about and they conduct electricity. Metals are orderly collection of positive ions surrounded by and held together by a sea of free electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electrons towards this sea of mobile electrons. These free and mobile electrons are responsible for high electrical and thermal conductivity of metals. When an electric field is applied, these electrons flow through the network of positive ions. Similarly, when heat is supplied to one portion of a metal, the thermal energy is uniformly spread throughout by free electrons. Another important characteristic of metals is their luster and color in certain cases. This is also due to the presence of free electrons in them. Metals are highly malleable and ductile. A wide variety of crystalline solids of nonmetals result from the formation of covalent bonds between adjacent atoms throughout the crystal. They are also called giant molecules. Covalent bonds are strong and directional in nature, therefore atoms are held very strongly at their positions. Such solids are very hard and brittle. They have extremely high melting points and may even decompose before melting. They are insulators and do not conduct electricity. Diamond figure 1.3 and silicon carbide are typical examples of such solids. Although graphite figure 1.4 also belongs to this class of crystals, but it is soft and is a conductor of electricity. Its exceptional properties are due to 6. Chemistry. Its typical structure. Carbon atoms are arranged in different layers and each atom is covalently bonded to 3 of its neighboring atoms in the same layer. The 4th valence electron of each atom is present between different layers and is free to move about. These free electrons make graphite a good conductor of electricity. Different layers can slide one over the other. This makes graphite a soft solid and a good solid lubricant. The different properties of the 4 types of solids are listed in Table 1.2. Figure 1.4, Structure of graphite Fig. 1.3, Network structure of diamond Table 1.2, Different types of solids. Type of solid. Constituent bonding. Examples: physical, electrical, melting particles. Attractive nature. Conduct. Point forceivity. 1 molecular solids. I nonpolar molecules. Dispersion or R. CCl4, soft insulator. Very low London forces. H2, I2, CO2. 2 polar dipole HCl. SO2, soft insulator. Low interactions. 3 hydrogen H2O. Ice, hard insulator. Low bonding. 2 ionic solids. Ions, Coulombic or NaCl. MgO, hard but insulators. High electrostatic. ZnS, Ca2, brittle in solid state but conductors in molten state and in aqueous solutions. 3 metallic solids. Positive metallic Fe. Ag, hard but conductors. Fairly ions in a bonding. Mg, malleable in solid high C even state as delocalized ductile well as in electrons molten state. 7. The solid state. You must have noticed that when tiles are placed to cover a floor, a repeated pattern is generated. If after setting tiles on floor we mark a point at same location in all the tiles, e.g. center of the tile, and see the marked positions only ignoring the tiles, we obtain a set of points. This set of points is the scaffolding on which pattern has been developed by placing tiles. This scaffolding is a spaced lattice on which two-dimensional pattern has been developed by placing structural units on its set of points, that is, tile. In this case, the structural unit is called basis or motif. When motifs are placed on points in space lattice, a pattern is generated. In crystal structure, motif is a molecule, atom or ion. A space lattice, also called a crystal lattice, is a pattern of points representing the locations of these motifs. In other words, space lattice is an abstract scaffolding for crystal structure, when we place motifs in an identical manner on points of space lattice. In text questions 1.6 classify the following solids in different categories based on the nature of intermolecular forces operating in them: potassium sulfate, tin, benzene, urea, ammonia, water, zinc sulfide, graphite, rubidium, argon, silicon carbide. 1.7 Solid A is a very hard electrical insulator in solid as well as in molten state and melts at extremely high temperature. What type of solid is it? 1.8 Ionic solids conduct electricity in molten state but not in solid state. Explain. 1.9 What type of solids are electrical conductors? Malleable and ductile. 4 Covalent or atoms. Covalent CO2 hard insulators. Very network solids. Bonding quartz. High SiC, C diamond, ALN. C graphite. Soft conductor. Exception 1.41, 41, 41, 41, 4 crystal lattices and lattices and lattices and lattices and lattices and unit cells. Lattice point. A motif to make crystal structure. B space lattice or a crystal lattice. Two-dimensional lattice point. C hypothetical two-dimensional crystal fig. 1.5 A motif. B space lattice. Two-dimensional. C hypothetical two-dimensional crystal structure. We get crystal structure. Figure 1.5 shows a motif, a two-dimensional lattice, and a hypothetical two-dimensional crystal structure obtained by placing motifs in the two-dimensional lattice. Spatial arrangement of lattice points gives rise to different types of lattices. Figure 1.6 shows arrangement of points in two different lattices. Figure 1.6, arrangement of points in two different lattices. Lattice A, lattice B. In the case of crystalline solids, space lattice is a three-dimensional array of points. The crystal structure is obtained by associating structural motifs with lattice points. Each repeated basis or motif has same structure and same spatial orientation as other one in a crystal. The environment of each motif is same throughout the crystal except for on surface. Following are the characteristics of a crystal lattice. A. Each point in a lattice is called lattice point or lattice site. B. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule group of atoms, or an ion. C. Lattice points are joined by straight lines to bring out the geometry of the lattice. We need only a small part of the space lattice of a crystal to specify crystal completely. This small part is called unit cell. One can choose unit cell in many ways. Normally that cell is chosen which has perpendicular sides of shortest length, and one can construct entire crystal by translational displacement of the unit cell in 3 dimensions. Figure 1.7 shows movement of unit cell of a two-dimensional lattice to construct the entire crystal structure. Also, unit cells have shapes such that these fill the whole lattice without leaving space between cells. In 2 dimensions, a parallelogram with sided length A and B and an angle R between these sides is chosen as unit cell. Possible unit cells in 2 dimensions are shown in Figure 1.8. Figure 1.7, generating hypothetical two-dimensional crystal structure by shifting square in the direction of arrows. Unit cell. 9. The solid state A portion of 3-dimensional crystal lattice and its unit cell is shown in Fig. 1.9. In the 3-dimensional crystal structure, unit cell is characterized by I its dimensions along the 3 edges A, B and C. These edges may or may not be mutually perpendicular. 2 angles between the edges, Greek letter alpha between B and C, Greek letter beta between A and C, and Greek letter gamma between A and B. Thus, a unit cell is characterized by 6 parameters A, B, C, Greek letter alpha, Greek letter beta and Greek letter gamma. These parameters of a typical unit cell are shown in Fig. 1.10. Unit cells can be broadly divided into 2 categories, primitive and centered unit cells. A primitive unit cells when constituent particles are present only on the corner positions of a unit cell. It is called as primitive unit cell. B-centered unit cells. When a unit cell contains one or more constituent particles present at positions other than corners in addition to those at corners, it is called a centered unit cell. Centered unit cells are of three types. I. Body-centered unit cells. Such a unit cell contains one constituent particle atom, molecule or ion at its body center besides the ones that are at its corners. 2. Face-centered unit cells. Such a unit cell contains one constituent particle present at the center of each face, besides the ones that are at its corners. 3. N-centered unit cells. In such a unit cell, one constituent particle is present at the center of any two opposite faces besides the ones present at its corners. 1. 4. 1 primitive and centered unit cells. Figure 1.10. Illustration of parameters of a unit cell. Fig. 1.8. Possible unit cells in two dimensions. A 90 masculine ordinal, a B90 masculine ordinal, a 60 masculine ordinal, a B. Figure 1.9. A portion of a three-dimensional cubic space of a crystal lattice and its unit cell. Unit cell lattice point. 10. Chemistry. Crystal system. Possible axial distances, axial angles. Examples: variations or edge lengths. Cubic primitive. A BC, Greek letter alpha, Greek letter beta, Greek letter gamma. 90 degrees NaCl, zinc blend. Body-centered, Cu face-centered tetragonal primitive. A BC, Greek letter alpha, Greek letter beta, Greek letter gamma. 90 degrees white tin, SNO 2, body-centered SiO2, Caso 4 orthorhombic primitive. A BC, Greek letter alpha, Greek letter beta, Greek letter gamma. 90 degrees rhombic sulfur. Body-centered, NO 3, Baso 4 face-centered, end-centered hexagonal primitive. A BC, Greek letter alpha, Greek letter beta. 90 degrees graphite. ZNO, CDS, Greek letter gamma. 120 degrees rhombohedral or primitive. A BC, Greek letter alpha, Greek letter beta, Greek letter gamma. 90 degrees calcite. CaCO 3, HGS trigonal cinnabar. Table 1.3, 7 primitive unit cells and their possible variations as centered unit cells. Fig. 1.11, 7 crystal systems. Inspection of a wide variety of crystals leads to the conclusion that all can be regarded as conforming to one of the 7 regular figures. These basic regular figures are called 7 crystal systems. To which system a given crystal belongs to is determined by measuring the angles between its faces and deciding how many axes are needed to define the principal features of its shape. Figure 1.11 shows 7 crystal systems. A French mathematician, Bravais, showed that there are only 14 possible three-dimensional lattices. These are called Bravais lattices. Unit cells of these lattices are shown in the following box. The characteristics of their primitive unit cells along with the centered unit cells that they can form have been listed in Table 1.3. A primitive or simple body-centered face-centered unit cells of cubic lattices, all sides of same length. Angles between faces all 90 degrees. Primitive body-centered unit cells. 2 tetragonal lattices, one side different in length to the other. 2 angles between faces all 90 degrees. Unit cells of 4 orthorhombic lattices, unequal sides, angles between faces all 90 degrees. Primitive body-centered face-centered end-centered unit cells of 2 monoclinic lattices, unequal sides. 2 faces have angles different to 90 degrees. Primitive end-centered more than 90 degrees less than 90 degrees. Unit cells of 14 types of Bravais lattices. 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 Monoclinic primitive. A BC, Greek letter alpha, Greek letter gamma. 90 degrees monoclinic sulfur. End-centered Greek letter beta. 90 degrees NO2 SO4.10 H2O triclinic primitive. A BC, Greek letter alpha, Greek letter beta, Greek letter gamma. 90 degrees K2CR2O7 QSO4 5 H2O H3BO3. We know that any crystal lattice is made up of a very large number of unit cells and every lattice point is occupied by one constituent particle atom, molecule or ion. Let us now work out what portion of each particle belongs to a particular unit cell. We shall consider 3 types of cubic unit cells and for simplicity assume that the constituent particle is an atom. Primitive cubic unit cell has atoms only at its corner. Each atom at a corner is shared between 8 adjacent unit cells as shown in Fig. 1.12, 4 unit cells in the same layer and 4 unit cells of the upper or lower layer. Therefore, only 1/8th of an atom or molecule or ion actually belongs to a particular unit cell. In Figure 1.13, a primitive cubic unit cell has been depicted in 3 different ways, each small sphere in Fig. 1.13 represents only the center of the particle occupying that position and not its actual size. Such structures are called open structures. The arrangement of particles is easier to follow in open structures. Figure 1.13b depicts space-filling representation of the unit cell with actual particle size in Fig. 1.13c shows the actual portions of different atoms present in a cubic unit cell. In all, since each cubic unit cell has 8 atoms on its corners, the total number of atoms in one unit cell is 1818x atom. 60 a BCCAB unit cell of hexagonal lattice, one side different in length to the other two. The marked angles on two faces are 60 degrees. Unit cell of rhombohedral lattice, all sides of equal length. Angles on two faces are less than 90 degrees. Unit cell of triclinic lattice, unequal sides A, B, C, A, B, C are unequal angles with none equal to 90 degrees, less than 90 degrees. 1.51, 51, 51, 51, 5 number of atoms in a unit cell 1, 5, 1, primitive cubic unit cell Fig. 1.13, a primitive cubic unit cell. A open structure. B space filling structure. C actual portions of atoms belonging to one unit cell. Figure 1.12, in a simple cubic unit cell, each corner atom is shared between 8 unit cells. 13. The solid-state A body-centered cubic BCC unit cell has an atom at each of its corners and also one atom at its body center. Figure 1.14 depicts the open structure B space filling model and C the unit cell with portions of atoms actually belonging to it. It can be seen that the atom at the Fig. 1.15, an atom at face center of unit cell is shared between two unit cells at B. Figure 1.16, a face-centered cubic unit cell. A open structure B space filling structure. C actual portions of atoms belonging to one unit cell. 1, 5, 2 body-centered cubic unit cell. 1, 5, 3 face-centered cubic unit cell. Figure 1.14, a body-centered cubic unit cell. A open structure B space filling structure. C actual portions of atoms belonging to one unit cell. A BC body center wholly belongs to the unit cell in which it is present. Thus in a body-centered cubic BCC unit cell, I8 corners x1 8 per corner atom 188 x1 atom 2 1 body center atom 1 x1 1 atom. Total number of atoms per unit cell 2 atoms. A face-centered cubic FCC unit cell contains atoms at all the corners and at the center of all the faces of the cube. It can be seen in Figure 1.15 that each atom located at the face center is shared between two adjacent unit cells and only 1/2 of each atom belongs to a unit cell. Figure 1.16 depicts the open structure B space filling model and C the unit cell with portions of atoms actually belonging to it. Thus, in a face-centered cubic FCC unit cell, I8 corners atoms x1 8 atom per unit cell 188 x1 atom 2 6 face-centered atoms x1 2 atom per unit cell 6 x1 2 3 atoms. Total number of atoms per unit cell 4 atoms. B. 14. Chemistry in solids. The constituent particles are close-packed, leaving the minimum vacant space. Let us consider the constituent particles as identical hard spheres and build up the three-dimensional structure in 3 steps. A close packing in one dimension. There is only one way of arranging spheres in a one-dimensional close-packed structure, that is to arrange them in a row and touching each other. Fig. 1.17. In this arrangement, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in one-dimensional close-packed arrangement, the coordination number is 2b. Close packing in 2 dimensions. Two-dimensional close-packed structure can be generated by placing the rows of close-packed spheres. This can be done in 2 different ways. The second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the first row as A-type row, the second row being exactly the same as the first one, is also of A-type. Similarly, we may place more rows to obtain AAA type of arrangement as shown in Figure 1.18. 1, 6 1, 6 1, 6 1, 6 1, 6 close-packed 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 close-packed. Capital S T R U C T U R E S capital S T R U C T U R E S capital S T R U C T U R E S. In text questions 1.10 give the significance of a lattice point. 1.11 Name the parameters that characterize a unit cell. 1.12 Distinguish between hexagonal and monoclinic unit cells. 2 Face-centered and end-centered unit cells. 1.13 Explain how much portion of an atom located at I corner and 2 body center of a cubic unit cell is part of its neighboring unit cell. Figure 1.17, close packing of spheres in one dimension. Figure 1.18, a square close packing. The hexagonal close packing of spheres in 2 dimensions. The solid state. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, the 2-dimensional coordination number is 4. Also, if the centers of these 4 immediate neighboring spheres are joined, a square is formed. Hence this packing is called square close packing in 2 dimensions. 2. The second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of the first row. If the arrangement of spheres in the first row is called A-type, the one in the second row is different and may be called B-type. When the third row is placed adjacent to the second in staggered manner, its spheres are aligned with those of the first layer. Hence this layer is also of A-type. The spheres of similarly placed fourth row will be aligned with those of the second row B-type. Hence this arrangement is of a BAB-type. In this arrangement there is less free space and this packing is more efficient than the square close packing. Each sphere is in contact with 6 of its neighbors and the 2-dimensional coordination number is 6. The centers of these 6 spheres are at the corners of a regular hexagon. Figure 1.18b. Hence this packing is called 2-dimensional hexagonal close packing. It can be seen in figure 1.18b that in this layer there are some voids, empty spaces. These are triangular in shape. The triangular voids are of 2 different types. In one row, the apex of the triangles are pointing upwards and in the next layer downwards. See close packing in 3 dimensions. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. In the last section, we discussed close packing in 2 dimensions which can be of 2 types, square close packed and hexagonal close packed. Let us see what types of 3-dimensional close packing can be obtained from these. A 3-dimensional close packing forms 2-dimensional square close packed layers. While placing the second square close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically as shown in Fig. 1.19. Similarly, we may place more layers one above the other. If the arrangement of spheres in the first layer is called A-type, all the layers have the same arrangement. Thus this lattice has triple A-type pattern. The lattice thus generated is the simple cubic lattice, and its unit cell is the primitive cubic unit cell. See Fig. 1.192 3-dimensional close packing from 2-dimensional hexagonal close packed layers. 3-dimensional close packed structure can be generated by placing layers one over the other. Figure 1.19, simple cubic lattice formed by AAA arrangement. 16 Chemistry of placing second layer over the first layer. Let us take a 2-dimensional hexagonal close packed layer A and place a similar layer above it such that the spheres of the second layer are placed in the depressions of the first layer. Since the spheres of the 2 layers are aligned differently, let us call the second layer as B. It can be observed from Fig. 1.20 that all the triangular voids of the first layer are not covered by the spheres of the second layer. This gives rise to different arrangements. Wherever a sphere of the second layer is above the void of the first layer or vice versa, a tetrahedral void is Fig. 1.20. A stack of 2 layers of close-packed spheres and voids generated in them. Tetrahedral void, a octahedral void formed. These voids are called tetrahedral voids because a tetrahedron is formed when the centers of these 4 spheres are joined. They have been marked as T in Figure 1.20. One such void has been shown separately in Figure 1.21. Figure 1.21 tetrahedral and octahedral voids. A top view, the exploded side view, and see geometrical shape of the void. 17. The solid state at other places. The triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap. One of them has the apex of the triangle pointing upwards and the other downwards. These voids have been marked as O in Fig. 1.20. Such voids are surrounded by 6 spheres and are called octahedral voids. One such void has been shown separately in Fig. 1.21. The number of these two types of voids depend upon the number of close-packed spheres. Let the number of close-packed spheres be n. Then, the number of octahedral voids generated and the number of tetrahedral voids generated 2n be placing third layer over the second layer when third layer is placed over the second. There are two possibilities I covering tetrahedral voids. Tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spheres is repeated in alternate layers. This pattern is often written as a BAB pattern. This structure is called hexagonal close-packed HCP structure Fig. 1.22. This sort of arrangement of atoms is found in many metals like magnesium and zinc. Figure 1.22. A hexagonal cubic close-packing exploded view showing stacking of layers of spheres B4 layers stacked in each case and see geometry of packing. 2. Covering octahedral voids. The third layer may be placed above the second layer in a manner such that its spheres cover the octahedral voids. When placed in this manner, the spheres of the third layer are not aligned with those of either the first or the second layer. This arrangement is called C-type. Only when fourth layer is placed, its spheres are aligned with Fig. 1.23. ABC arrangement of layers. When octahedral void is covered, B fragment of structure formed by this arrangement resulting in cubic closed-packed CCP or face-centered cubic FCC structure. ACBA. 18. Chemistry. Those of the first layer as shown in figures 1.22 and 1.23. This pattern of layers is often written as ABC. This structure is called cubic close-packed CCP or face-centered cubic FCC structure. Metals such as copper and silver crystallize in this structure. Both these types of close packing are highly efficient and 74 space in the crystal is filled. In either of them, each sphere is in contact with 12 spheres. Thus, the coordination number is 12 in either of these two structures. Earlier in the section, we have learnt that when particles are close-packed resulting in either CCP or HCP structure, two types of voids are generated. While the number of octahedral voids present in a lattice is equal to the number of close-packed particles, the number of tetrahedral voids generated is twice this number. In ionic solids, the bigger ions, usually anions, form the close-packed structure and the smaller ions, usually cations, occupy the voids. If the latter ion is small enough, then tetrahedral voids are occupied. If bigger, then octahedral voids. All octahedral or tetrahedral voids are not occupied. In a given compound, the fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula of the compound, as can be seen from the following examples. We know that close-packed structures have both tetrahedral and octahedral voids. Let us take CCP or FCC structure and locate these voids in it. Locating tetrahedral voids, let us consider a unit cell of CCP or FCC lattice. Figure 1a. The unit cell is divided into 8 small cubes. Example 1.1, Example 1.1, Example 1.1, Example 1.1, Example 1.11, 6. 1. Formula of a compound and number of voids filled. A compound is formed by two elements X and Y. Atoms of the element Y as anions make CCP and those of the element X as cations occupy all the octahedral voids. What is the formula of the compound? The CCP lattice is formed by the element Y. The number of octahedral voids generated would be equal to the number of atoms of Y present in it. Since all the octahedral voids are occupied by the atoms of X, their number would also be equal to that of the element Y. Thus, the atoms of elements X and Y are present in equal numbers or 1:1 ratio. Therefore, the formula of the compound is XY. Atoms of element B form HCP lattice and those of the element A occupy 2/3 of tetrahedral voids. What is the formula of the compound formed by the elements A and B? The number of tetrahedral voids formed is equal to twice the number of atoms of element B, and only 2/3 of these are occupied by the atoms of element A. Hence the ratio of the number of atoms of A and B is 2:3:1 or 4:3, and the formula of the compound is A4B3. Example 1.2 Example 1.2 Example 1.2 Example 1.2 Example 1.2 Solution locating tetrahedral and octahedral voids 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 locating tetrahedral and octahedral voids. 19. The solid state. Each small cube has atoms at alternate corners. Figure 1a. In all, each small cube has 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there is 1 tetrahedral void in each small cube and 8 tetrahedral voids in total. Each of the 8 small cubes have 1 void and 1 unit cell of CCP structure. We know that CCP structure has 4 atoms per unit cell. Thus, the number of tetrahedral voids is twice the number of atoms. Figure 1. 8 tetrahedral voids per unit cell of CCP structure. B. 1 tetrahedral void showing the geometry. B. Locating octahedral voids. Let us again consider a unit cell of CCP or FCC lattice. Figure 2a. The body center of the cube, C, is not occupied but it is surrounded by 6 atoms on face centers. If these face centers are joined, an octahedron is generated. Thus, this unit cell has 1 octahedral void at the body center of the cube. Besides the body center, there is 1 octahedral void at the center of each of the 12 edges. Fig. 2b. It is surrounded by 6 atoms, 4 belonging to the same unit cell, 2 on the corners and 2 on face center and 2 belonging to 2 adjacent unit cells. Since each edge of the cube is shared between 4 adjacent unit cells, so is the octahedral void located on it. Only 1/4th of each void belongs to a particular unit cell at B. Figure 2. Location of octahedral voids per unit cell of CCP or FCC lattice at the body center of the cube and B at the center of each edge. Only 1 such void is shown. 20. Chemistry. Thus in cubic close-packed structure, octahedral void at the body center of the cube. 1/12 octahedral voids located at each edge and shared between 4 unit cells. 1/12 3/4x total number of octahedral voids. 4. We know that in CCP structure, each unit cell has 4 atoms. Thus, the number of octahedral voids is equal to this number: 1, 7, 1, 7, 1, 7, 1, 7, 1, 7, capital P, A, C, K, I, N, G, 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 capital P, A, capital E, F, F, I, C, I, E, N, C, Y, capital E, F, F, I, C, I, E, N, C, Y, capital E, F, F, I, C, I, E, N, C, Y, in whatever way the constituent particles, atoms, molecules or ions are packed, there is always some free space in the form of voids. Packing efficiency is the percentage of total space filled by the particles. Let us calculate the packing efficiency in different types of structures. Both types of close packing HCP and CCP are equally efficient. Let us calculate the efficiency of packing in CCP structure. In figure 1.24, like the unit cell edge length BN face diagonal ACB. In ABCAC2 B2 BC2 OB2 A2 A2 2 A2 or B2A. If R is the radius of the sphere, we find B42 or A42 R2. We can also write R22. We know that each unit cell in CCP structure has effectively 4 spheres. Total volume of 4 spheres is equal to 3443 Rx Greek letter pi, and volume of the cube is a 3 or 322 R. Therefore, volume of PB 4 spheres and Plunitzel 100 packing efficiency total volumia of Thunitzel x 33443 R 122 Rx Greek letter pi x 33163 R 17416 to R Greek letter pi x 1, 7, 1 packing efficiency in HCP and CCP structures. Fig. 1.24, cubic close packing. Other sides are not provided with spheres for sake of clarity. 21. The solid state. From figure 1.25, it is clear that the atom at the center will be in touch with the other 2 atoms diagonally arranged. In EFD, B2 A2 A2 2 A2 B2 and now in AFD C2 A2 B2 A2 2 A2 3 A2 C3. The length of the body diagonal C is equal to 4. Where R is the radius of the sphere atom, as all the 3 spheres along the diagonal touch each other. Therefore, 3 A4 A4 3. Also we can write R3 4A in this type of structure. Total number of atoms is 2 and their volume is 34 to R. 3x Greek letter pi volume of the cube, A3 will be equal to 34 R3 or 334 R3. Therefore, Volumia occupied by 2 spheres in the unit cell 100 packing efficiency total volumia of the unit cell x33243R143R x Greek letter pi x33A3R1686433R Greek letter pi x in a simple cubic lattice. The atoms are located only on the corners of the cube. The particles touch each other along the edge figure 1.26. Thus, the edge length or side of the cube and the radius of each particle are related as a to r. The volume of the cubic unit cell 32R38R3. Since a simple cubic unit cell contains only one atom, the volume of the occupied space 34R3 Greek letter pi 1, 7, 2 efficiency of packing in body-centered cubic structures 1, 7, 3 packing efficiency in simple cubic lattice fig. 1.25 body-centered cubic unit cell sphere along the body diagonal are shown with solid boundaries. 22 chemistry packing efficiency volumia of 1 atom 100 volumia of cubic unit cell x334R3 100 100 68 R Greek letter pi XX 52.36 52.4. Thus, we may conclude that CCP and HCP structures have maximum packing efficiency. From the unit cell dimensions, it is possible to calculate the volume of the unit cell. Knowing the density of the metal, we can calculate the mass of the atoms in the unit cell. The determination of the mass of a single atom gives an accurate method of determination of Avogadro constant. Suppose, edge length of a unit cell of a cubic crystal determined by X-ray diffraction is A, d the density of the solid substance and m the molar mass. In case of cubic crystal, volume of a unit cell 3 mass of the unit cell number of atoms in unit cell x mass of each atom zxm. Here z is the number of atoms present in one unit cell and m is the mass of a single atom. Mass of an atom present in the unit cell, m is molar mass. Therefore, density of the unit cell 333 mass of unit cell volume of unit cell zm or dia.n. Remember, the density of the unit cell is the same as the density of the substance. The density of the solid can always be determined by other methods. Out of the 5 parameters d, z, m, a and na, if any 4 are known, we can determine the fifth. Figure 1.26 simple cubic unit cell. The spheres are in contact with each other along the edge of the cube. 1, 8, 1, 8, 1, 8, 1, 8, 1, 8. Capital C A L C U L A T I O N S. Capital C A L C U L A T I O N S. Capital C A L C U L capital I N V O L V I N G. Capital I N V O L V I N G. Capital I N V O L V I N G. Capital I N V. Unit cell unit cell unit cell unit cell unit cell. Capital D I M E N S I O N S. Capital D I M E N S I O N S. Capital D I M E N S I O N S. An element has a body-centered cubic BCC structure with a cell edge of 288 pm. The density of the element is 7.2 grams cm3. How many atoms are present in 208 grams of the element? Volume of the unit cell 288 pm 3 288 x 10 12 meters 3 288 x 10 10 centimeters 3 2.39 x 10 23 cubic centimeters. Example 1.3 Example 1.3 Example 1.3 Example 1.3 Example 1.3 Solution 23 The solid state. Example 1.4 Example 1.4 Example 1.4 Example 1.4 Example 1.4 Volume of 208 grams of the element 33, 208, 28, 88, 7, 2. G mass GCM density cm number of unit cells in this volume 323 328.88 2.3910 x cm unit cell 12.08 x 1023 unit cell. Since each BCC cubic unit cell contains 2 atoms, therefore, the total number of atoms in 208 grams 2 atoms unit cell x 12.08 x 1023 unit cells 24.16 x 1023 atoms. X-ray diffraction studies show that copper crystallizes in an FCC unit cell with cell edge of 3.608 x 10 centimeters. In a separate experiment, copper is determined to have a density of 8.92 grams cm3. Calculate the atomic mass of copper. In case of FCC lattice, number of atoms per unit cell, Z4 atoms. Therefore, M3ADN is EXXXX minus 323 1838.92 grams cm 6.022 10 atoms mole 3.608 10 centimeters 4 atoms 63.1 grams mole. Atomic mass of copper 63.1 U. Silver forms CCP lattice and X-ray studies of its crystal show that the edge length of its unit cell is 408.6 pm. Calculate the density of silver atomic mass 107.9 U. Since the lattice is CCP, the number of silver atoms per unit cell Z for molar mass of silver 107.9 grams mole minus 1 107.9 x 10 3 kilograms mole 1 edge length of unit cell of 408.6 pm 408.6 x 10-12 meters density. D3ACM.N313122314, 107.910 kilograms mole 408.6 10 meters 6.022 10 mole XXXX 10.5 x 103 kilograms M3 10.5 grams CM3 example 1.5 example 1.5 example 1.5 example 1.5 example 1.5 solution in text. Questions in text questions 1.14 What is the two-dimensional coordination number of a molecule in square close-packed layer 1.15 A compound forms hexagonal close-packed structure. What is the total number of voids in 0.5 mole of it? How many of these are tetrahedral void? Solution 24 Chemistry. Although crystalline solids have short range as well as long range order in the arrangement of their constituent particles, yet crystals are not perfect. Usually a solid consists of an aggregate of large number of small crystals. These small crystals have defects in them. This happens when crystallization process occurs at fast or moderate rate. Single crystals are formed when the process of crystallization occurs at extremely slow rate. Even these crystals are not free of defects. The defects are basically irregularities in the arrangement of constituent particles. Broadly speaking, the defects are of two types, namely, point defects and line defects. Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance. Whereas the line defects are the irregularities or deviations from ideal arrangement in entire rows of lattice points. These irregularities are called crystal defects. We shall confine our discussion to point defects only. Point defects can be classified into three types: I stoichiometric defects, 2 impurity defects, and 3 non-stoichiometric defects. A stoichiometric defects: these are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects. Basically these are of two types: vacancy defects and interstitial defects. I vacancy defect: when some of the lattice sites are vacant, the crystal is said to have vacancy defect Fig. 1.27. This results in decrease in density of the substance. This defect can also develop when a substance is heated. 2. Interstitial defect: when some constituent particles, atoms or molecules occupy an interstitial site, the crystal is said to have interstitial defect Fig. 1.28. This defect increases the density of the substance. Vacancy and interstitial defects as explained above can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality. Rather than simple vacancy or interstitial defects, they show these defects as Frankel-Schottky defects. 1. 91, 91, 91, 91, 9, capital I, M, P, E, R, F, E, C, T, I, O, N, S, capital I, M, P, E, R, F, E, C, T, I, O, N, S, capital I, M, P, E. In solids 1.16 A compound is formed by two elements M and N. The element N forms CCP and atoms of M occupy 1/3 of tetrahedral voids. What is the formula of the compound? 1.17 Which of the following lattices has the highest packing efficiency? I simple cubic, 2 body-centered cubic, and 3 hexagonal close-packed lattice. 1.18 An element with molar mass 2.7 x 10 2 kilograms mole 1 forms a cubic unit cell with edge length 405 pm. If its density is 2.7 x 103 kilograms M3, what is the nature of the cubic unit cell? 1. 9. 1 Types of point defects Fig. 1.27 Vacancy defect. 25 The solid-state 3 Frankel defect. This defect is shown by ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site Fig. 1.29 It creates a vacancy defect at its original site and an interstitial defect at its new location. Frankel defect is also called dislocation defect. It does not change the density of the solid. Frankel defect is shown by ionic substance in which there is a large difference in the size of ions. For example, ZnS, AgCl, AgBr and Ag due to small size of Cn2 and Ag ions. Schottky defect. It is basically a vacancy defect in ionic solids. In order to maintain electrical neutrality, the number of missing cations and anions are equal Fig. 1.30. Like simple vacancy defect, Schottky defect also decreases the density of the substance. Number of such defects in ionic solids is quite significant. For example, in an NaCl there are approximately 106 Schottky pairs per cm3 at room temperature. In 1 cubic centimeter there are about 1022 ions, thus, there is 1 Schottky defect per 1016 ions. Schottky defect is shown by ionic substances in which the cation and anion are of almost similar sizes. For example, in NaCl, KCl, CCl and AgBr, it may be noted that AgBr shows both Frenkel as well as Schottky defect. The impurity defects if molten NaCl containing a little amount of SrCl2 is crystallized. Some of the sites of Na ions are occupied by Sr2 figure 1.31. Each Sr2 replaces 2 Na ions. It occupies the site of one ion and the other site remains vacant. The cationic vacancies thus produced are equal in number to that of Sr2 ions. Another similar example is the solid solution of CdCl2 and AgCl. Figure 1.28, Interstitial defects. Figure 1.31, Introduction of cation vacancy in NaCl by substitution of Na by Sr2. Fig. 1.29, Frenkel defects. Figure 1.30, Schottky defect. 26. Chemistry. C. Non-stoichiometric defects. The defects discussed so far do not disturb the stoichiometry of the crystalline substance. However, a large number of non-stoichiometric and organic solids are known which contain the constituent elements in non-stoichiometric ratio due to defects in their crystal structures. These defects are of 2 types, a metal excess defect and 2 metal deficiency defect. I metal excess defect. A tilde metal excess defect due to anionic vacancies. Alkali halides like NaCl and KCl show this type of defect. When crystals of NaCl are heated in an atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. The Cl ions diffuse to the surface of the crystal and combine with Na atoms to give NaCl. This happens by loss of electron by sodium atoms to form Na ions. The released electrons diffuse into the crystal and occupy anionic sites. Figure 1.32. As a result, the crystal now has an excess of sodium. The anionic sites occupied by unpaired electrons are called F-centers, from the German word for Benzenter for color center. They impart yellow color to the crystals of NaCl. The color results by excitation of these electrons when they absorb energy from the visible light falling on the crystals. Similarly, excessive lithium makes LiCl crystals pink and excessive potassium makes KCl crystals violet or lilac. A tilde metal excess defect due to the presence of extra cations at interstitial sites. Zinc oxide is white in color at room temperature. On heating it loses oxygen and turns yellow. Heating 2,2,1-ZnO, Now there is excess of zinc in the crystal and its formula becomes Zn1-O. The excess Zn2 ions move to interstitial sites and the electrons to neighboring interstitial sites. 2 metal deficiency defect. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. A typical example of this type is Fe, which is mostly found with a composition of Fe 0.95O. It may actually range from Fe 0.93O to Fe 0.96O. In crystals of Fe, some Fe2 cations are missing and the loss of positive charge is made up by the presence of required number of Fe3 ions. Solids exhibit an amazing range of electrical conductivities, extending over 27 orders of magnitude ranging from 10-20 to 107 ohm 1 m1. Solids can be classified into 3 types on the basis of their conductivities. I conductors. The solids with conductivities ranging between 104 to 107 ohm 1 m1 are called conductors. Metals have conductivities in the order of 107 ohm 1 m1 are good conductors. 1.10 101 10 101 10 Electrical properties Fig. 1.32 An F-center in a crystal. 27 The solid state 2 insulators. These are the solids with very low conductivities ranging between 10 and 20 to 10-10 ohm 1 m1. 3 Semiconductors. These are the solids with conductivities in the intermediate range from 10-6 to 104 ohm 1 m1. A conductor may conduct electricity through movement of electrons or ions. Metallic conductors belong to the former category and electrolytes to the latter. Metals conduct electricity in solid as well as molten state. The conductivity of metals depend upon the number of valence electrons available per atom. The atomic orbitals of metal atoms form molecular orbitals which are so close in energy to each other as to form a band. If this band is partially filled or it overlaps with a higher energy unoccupied conduction band, then electrons can flow easily under an applied electric field and the metal shows conductivity Fig. 1.33 A, if the gap between filled valence band and the next higher unoccupied band conduction band is large. Electrons cannot jump to it and such a substance has very small conductivity and it behaves as an insulator Fig. 1.33 B, in case of semiconductors, the gap between the valence band and conduction band is small Fig. 1.33 C, therefore, some electrons may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature, since more electrons can jump to the conduction band. Substances like silicon and germanium show this type of behavior and are called intrinsic semiconductors. The conductivity of these intrinsic semiconductors is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process is called Figure 1.33 distinction among A metals, B insulators and C semiconductors. In each case, an unshaded area represents a conduction band 1, 1, 0, 1 conduction of electricity in metals 1, 1, 0, 2 conduction of electricity in semiconductors. 28 Chemistry doping. Doping can be done with an impurity which is electron-rich or electron-deficient as compared to the intrinsic semiconductor silicon or germanium. Such impurities introduce electronic defects in them. Electron-rich impurities silicon and germanium belong to group 14 of the periodic table and have 4 valence electrons each. In their crystals each atom forms 4 covalent bonds with its neighbors. Figure 1.34 A. When doped with a group 15 element like Puras, which contains 5 valence electrons, they occupy some of the lattice sites in silicon or germanium crystal. Fig. 1.34 B. 4 out of 5 electrons are used in the formation of 4 covalent bonds with the 4 neighboring silicon atoms. The 5th electron is extra and becomes delocalized. These delocalized electrons increase the conductivity of doped silicon or germanium. Here the increase in conductivity is due to the negatively charged electron, hence silicon doped with electron-rich impurity is called N-type semiconductor. B electron deficit impurities silicon or germanium can also be doped with a group 13 element like B, Al, which contains only 3 valence electrons. The place where the 4th valence electron is missing is called electron hole or electron vacancy. Fig. 1.34 C. An electron from a neighboring atom can come and fill the electron hole, but in doing so it would leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. Under the influence of electric field, electrons would move towards the positively charged plate through electronic holes, but it would appear as if electron holes are positively charged and are moving towards negatively charged plate. This type of semiconductors are called P-type semiconductors. Figure 1.34, creation of N-type and P-type semiconductors by doping groups 13 and 15 elements. 29 The solid-state applications of N-type and P-type semiconductors. Various combinations of N-type and P-type semiconductors are used for making electronic components. Diode is a combination of N-type and P-type semiconductors and is used as a rectifier. Transistors are made by sandwiching a layer of one type of semiconductor between 2 layers of the other type of semiconductor. NPN and PNP type of transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy. Germanium and silicon are group 14 elements and therefore, have a characteristic valence of 4 and form 4 bonds as in diamond. A large variety of solid-state materials have been prepared by combination of groups 13 and 15 or 12 and 16 to simulate average valence of 4 as in JRC. Typical compounds of groups 13-15 are in SB, alpine GaAs, gallium arsenide GaAs. Semiconductors have very fast response and have revolutionized the design of semiconductor devices. ZNS, CDS, CDSA and HGT are examples of groups 12-16 compounds. In these compounds, their bonds are not perfectly covalent and the ionic character depends on the electronegativities of the 2 elements. It is interesting to learn that transition metal oxides show marked differences in electrical properties. Shio, Cro2 and Rio3 behave like metals. Rhenium oxide, Rio3 is like metallic copper in its conductivity and appearance. Certain other oxides like VO, VO2, VO3 and CO3 show metallic or insulating properties depending on temperature. Every substance has some magnetic properties associated with it. The origin of these properties lies in the electrons. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motions: I, its orbital motion around the nucleus, and 2, its spin around its own axis. Fig. 1.35. Electron being a charged particle and undergoing these motions can be considered as a small loop of current which possesses a magnetic moment. Thus, each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of this magnetic moment is very small and is measured in the unit called Bohr magneton. Microb. It is equal to 9.27 x 10-24 am2. On the basis of their magnetic properties, substances can be classified into 5 categories: I paramagnetic, 2 diamagnetic, 3 ferromagnetic, I antiferromagnetic, and V ferrimagnetic. I paramagnetism. Paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. Paramagnetism is due to presence of one or more unpaired electrons which are attracted by the magnetic field. O2, Cu2, Fe3, Cr3 are some examples of such substances. 1.11.1, 111, 111, 111, 11. Magnetic properties. Figure 1.35. Demonstration of the magnetic moment associated with an orbiting electron and a spinning electron. 30. Chemistry. Figure 1.36. Schematic alignment of magnetic moments in a ferromagnetic, B antiferromagnetic, and C ferrimagnetic. 2. Diamagnetism. Diamagnetic substances are weakly repelled by a magnetic field. H2O, NaCl and C6H6 are some examples of such substances. They are weakly magnetized in a magnetic field in opposite direction. Diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electrons cancels their magnetic moments and they lose their magnetic character. 3. Ferromagnetism. A few substances like iron, cobalt, nickel, gadolinium and Cro2 are attracted very strongly by a magnetic field. Such substances are called ferromagnetic substances. Besides strong attractions, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. Thus, each domain acts as a tiny magnet. In an unmagnetized piece of a ferromagnetic substance, the domains are randomly oriented and their magnetic moments get cancelled. When the substance is placed in a magnetic field, all the domains get oriented in the direction of the magnetic field. Fig. 1.36 I and a strong magnetic effect is produced. This ordering of domains persists even when the magnetic field is removed and the ferromagnetic substance becomes a permanent magnet. IV antiferromagnetism. Substances like MnO showing antiferromagnetism have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic moment. Figure 1.36b. V ferrimagnetism. Ferrimagnetism is observed when the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel directions in unequal numbers. Fig. 1.36c. They are weakly attracted by magnetic field as compared to ferromagnetic substances. Fe3O4 magnetite and ferrites like Mg Fe2O4 and Zn Fe2O4 are examples of such substances. These substances also lose ferrimagnetism on heating and become paramagnetic. 31. The solid state in text questions. 1.19. What type of defect can arise when a solid is heated? Which physical property is affected by it and in what way? 1.20. What type of stoichiometric defect is shown by IZNS2 at BR? 1.21. Explain how vacancies are introduced in an ionic solid when a cation of higher valence is added as an impurity in it. 1.22. Ionic solids, which have anionic vacancies due to metal excess defect, develop color. Explain with the help of a suitable example. 1.23. A group 14 element is to be converted into n-type semiconductor by doping it with a suitable impurity. To which group should this impurity belong? 1.24. What type of substances would make better permanent magnets, ferromagnetic or ferrimagnetic? Justify your answer. Solids have definite mass, volume and shape. This is due to the fixed position of their constituent particles, short distances and strong interactions between them. In amorphous solids, the arrangement of constituent particles has only short-range order and consequently they behave like supercooled liquids, do not have sharp melting points and are isotropic in nature. In crystalline solids there is long-range order in the arrangement of their constituent particles. They have sharp melting points, are anisotropic in nature, and their particles have characteristic shapes. Properties of crystalline solids depend upon the nature of interactions between their constituent particles. On this basis, they can be divided into four categories, namely, molecular, ionic, metallic and covalent solids. They differ widely in their properties. The constituent particles in crystalline solids are arranged in a regular pattern which extends throughout the crystal. This arrangement is often depicted in the form of a three-dimensional array of points which is called crystal lattice. Each lattice point gives the location of one particle in space. In all, 14 different types of lattices are possible which are called Bravais lattices. Each lattice can be generated by repeating its small characteristic portion called unit cell. A unit cell is characterized by its edge lengths and three angles between these edges. Unit cells can be either primitive, which have particles only at their corner positions, or centered. The centered unit cells have additional particles at their body centered, at the center of each face centered, or at the center of two opposite faces end centered. There are 7 types of primitive unit cells. Taking centered unit cells also into account, there are 14 types of unit cells in all, which result in 14 Bravais lattices. Close packing of particles result in 2 highly efficient lattices, hexagonal close-packed HCP and cubic close-packed CCP. The latter is also called face-centered cubic FCC lattice. In both of these packings 74 space is filled. The remaining space is present in the form of 2 types of voids, octahedral voids and tetrahedral voids. Other types of packing are not close packings and have less summary. Exercises efficient packing of particles. While in body-centered cubic lattice BCC 68 space is filled, in simple cubic lattice only 52.4 space is filled. Solids are not perfect in structure. There are different types of imperfections or defects in them. Point defects and line defects are common types of defects. Point defects are of 3 types: stoichiometric defects, impurity defects and non-stoichiometric defects. Vacancy defects and interstitial defects are the 2 basic types of stoichiometric point defects. In ionic solids, these defects are present as Frankel and Schottky defects. Impurity defects are caused by the presence of an impurity in the crystal. In ionic solids, when the ionic impurity has a different valence than the main compound, some vacancies are created. Non-stoichiometric defects are of metal excess type and metal deficient type. Sometimes calculated amounts of impurities are introduced by doping in semiconductors that change their electrical properties. Such materials are widely used in electronics industry. Solids show many types of magnetic properties like paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism and ferrimagnetism. These properties are used in audio, video and other recording devices. All these properties can be correlated with their electronic configurations or structures. 1.1 Define the term amorphous. Give a few examples of amorphous solids. 1.2 What makes a glass different from a solid such as quartz? Under what conditions could quartz be converted into glass? 1.3 Classify each of the following solids as After studying this unit, you will be able to describe the formation of different types of solutions, express concentration of solution in different units, state and explain Henry's law and Raoult's law, distinguish between ideal and non-ideal solutions, explain deviations of real solutions from Raoult's law, describe colligative properties of solutions and correlate these with molar masses of the solutes, explain abnormal colligative properties exhibited by some solutes and solutions. In normal life we rarely come across pure substances. Most of these are mixtures containing 2 or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass mixture of copper and zinc are quite different from those of German silver mixture of copper. Zinc and nickel or bronze mixture of copper and tin, 1 part per million ppm of fluoride ions in water prevents tooth decay. While 1.5 ppm causes the tooth to become mottled and high concentrations of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentrations that match with blood plasma concentrations and so on. In this unit, we will consider mostly liquid solutions and their formation. This will be followed by studying the properties of the solutions, like vapor pressure and colligative properties. We will begin with types of solutions and then various alternatives in which concentrations of a solute can be expressed in liquid solution. Solutions. Almost all processes in body occur in some kind of liquid solutions. Objectives 2, 1 2, 1 2, 1 2, 1 2, 1 types of solutions 2 unit 2 solutions are homogeneous mixtures of two or more than two components. By homogeneous mixture we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent. Solvent determines the physical state in which solution exists. One or more components present in the solution other than solvent are called solutes. In this unit we shall consider only binary solutions, that is. 36 Chemistry type of solution solute solvent common examples gaseous solutions gas mixture of oxygen and nitrogen gases liquid gas chloroform mixed with nitrogen gas solid gas camphor and nitrogen gas liquid solutions gas liquid oxygen dissolved in water liquid ethanol dissolved in water solid liquid glucose dissolved in water solid solutions gas solid solution of hydrogen and palladium liquid solid amalgam of mercury with sodium solid copper dissolved in gold table 2.1 types of solutions consisting of two components. Here each component may be solid, liquid or in gaseous state and are summarized in table 2.1. Composition of a solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively we can say that the solution is dilute, that is, relatively very small quantity of solute, or it is concentrated, that is, relatively very large quantity of solute. But in real life these kinds of description can add to a lot of confusion and thus the need for a quantitative description of the solution. There are several ways by which we can describe the concentration of the solution quantitatively. I mass percentage WW. The mass percentage of a component of a solution is defined as mass of a component x mass of the component in the solution 100 total mass of the solution 2.1. For example, if a solution is described by 10 glucose in water by mass, it means that 10 grams of glucose is dissolved in 90 grams of water resulting in a 100-gram solution. Concentration described by mass percentage is commonly used in industrial chemical applications. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. 2 Volume percentage VV. The volume percentage is defined as volume of a component x volume of the component 100 total volume of solution 2.22.22 expressing capital CONCENTRATION capital CONCENTRATION capital CONC of solutions of solutions of solutions of solutions of solutions. 37 solutions. For example, 10 ethanol solution in water means that 10 milliliters of ethanol is dissolved in water such that the total volume of the solution is 100 milliliters. Solutions containing liquids are commonly expressed in this unit. For example, a 35 VV solution of ethylene glycol, an antifreeze, is used in cars for cooling the engine. At this concentration the antifreeze lowers the freezing point of water to 255.4 K-17.6 degrees Celsius 3 mass by volume percentage WV. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of solute dissolved in 100 milliliters of the solution IV parts per million, when a solute is present in trace quantities. It is convenient to express concentration in parts per million ppm and is defined as parts per million 6 number of parts of the component x 10 total number of parts of all components of the solution 2.3 as in the case of percentage. Concentration in parts per million can also be expressed as mass to mass, volume to volume and mass to volume. A liter of seawater which weighs 1030 grams contains about 6x10-3 g of dissolved oxygen O2. Such a small concentration is also expressed as 5.8 grams per 106 grams 5.8 ppm of seawater. The concentration of pollutants in water or atmosphere is often expressed in terms of microgmol1 or ppm. The mole fraction, commonly used symbol for mole fraction is x and subscript used on the right-hand side of x denotes the component. It is defined as mole fraction of a component number of moles of the component total number of moles of all the components 2.4. For example, in a binary mixture, if the number of moles of A and B are Na and NB respectively, the mole fraction of A will be Za AABNNN 2.5. For a solution containing I number of components, we have Xi I1 to I NNNNIINN 2.6. It can be shown that in a given solution sum of all the mole fractions is unity, that is x1 x2, Xi1 2.7 mole fraction unit is very useful in relating some physical properties of solutions. Say vapor pressure with the concentration of the solution and quite useful in describing the calculations involving gas mixtures. Calculate the mole fraction of ethylene glycol C2H6O2 in a solution containing 20 of C2H6O2 by mass. Assume that we have 100 grams of solution. One can start with any amount of solution because the results obtained will be the same. Solution will contain 20 grams of ethylene glycol and 80 grams of water. Molar mass of C2H6O2 12x21x6 16x2 62 grams. Mole 1. Moles of C2H6O2 120 grams 62 grams. Mole 0.322 mole. Moles of water 180 grams 18 grams. Mole 4.444 mole 262 glycol 2622 moles of CHOX. Moles of CHO. Moles of HO 0.322 mole 0.322 mole 4.444 mole 0.068. Similarly, water 4.444 mole 0.932 0.322 mole 4.444 mole. X mole fraction of water can also be calculated as 1 0.068 0.932. Example 2.1 Example 2.1 Example 2.1 Example 2.1 Example 2.1 V. Molarity. Molarity M is defined as number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. Moles of solute. Molarity. Volume of solution in liter 2.8. For example, 0.25 mole L1 or 0.25 m. Solution of NaO means that 0.25 mole of NaO has been dissolved in 1 liter or 1 cubic decimeter. Example 2.2 Example 2.2 Example 2.2 Example 2.2 Example 2.2 Calculate the molarity of a solution containing 5 grams of NaO in 450 milliliters solution. Moles of NaO 1 5 grams 40 grams. Mole 0.125 mole. Volume of the solution in liters 450 milliliters 1000 milliliters. L1 using equation 2.8. Molarity minus 10.125 mole x 1000 milliliters. L 450 milliliters 0.278 m 0.278 mole. L1 0.278 mole. DM3 solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. Solution 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 solution. Example 2.3 Example 2.3 Example 2.3 Example 2.3 Example 2.3 Solution 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 7 Molality. Molality M is defined as the number of moles of the solute per kilogram kg of the solvent and is expressed as molality M. Moles of solute. Mass of solvent in kg 2.9. For example, 1.00 mole kg1 or 1.00 meters. Solution of KCl means that 1 mole 74.5 grams of KCl is dissolved in 1 kilogram of water. Each method of expressing concentration of the solutions has its own merits and demerits. Mass, ppm, mole fraction and molality are independent of temperature, whereas molarity is a function of temperature. This is because volume depends on temperature and the mass does not. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of solute and solvent as well as temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in a liquid. 2.3 Solubility 2.3 Solubility 2.3 Solubility 2.3 Solubility 2.3 Solubility. Calculate molality of 2.5 grams of ethanoic acid CH3CU and 75 grams of benzene. Molar mass of C2H4O2 12x21x4 16x2 60 grams. Mole 1 moles of C2H4O2 1 2.5 grams 60 grams. Mole 0.0417 mole. Mass of benzene in kg 75 grams 1000 grams kg 175 x 10-3 kg. Molality of C2H4O2 242 moles of CHO kg of benzene 10.0417 mole 1000 grams kg 75 grams x 0.556 mole kg 1. In text questions 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 2.1 Calculate the mass percentage of benzene C6H6 and carbon tetrachloride CCl4 if 22 grams of benzene is dissolved in 122 grams of carbon tetrachloride. 2.2 Calculate the mole fraction of benzene in solution containing 30 by mass in carbon tetrachloride. 2.3 Calculate the molarity of each of the following solutions: a 30 gram of Co number 32, 6H2O and 4.3 L of solution B, 30 milliliters of 0.5 mH2 SO4 diluted to 500 milliliters. 2.4 Calculate the mass of urea NH2CO NH2 required in making 2.5 kilograms of 0.25 mole aqueous solution. 2.5 Calculate a molality B, molarity and C mole fraction of Ke if the density of 20 mass aqueous Ke is 1.202 grams ml1. 40 Chemistry. Every solid does not dissolve in a given liquid, while sodium chloride and sugar dissolve readily in water. Naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and nonpolar solutes in nonpolar solvents. In general, A solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in solution. This process is known as dissolution. Some solute particles in solution collide with the solid solute particles and get separated out of solution. This process is known as crystallization. A stage is reached when the two processes occur at the same rate. Under such conditions, number of solute particles going into solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is reached. Solute-solvent solution 2.10. At this stage, the concentration of solute in solution will remain constant under the given conditions, that is, temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is the saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. Earlier we have observed that solubility of one substance into another depends on the nature of the substances. In addition to these variables, two other parameters, that is, temperature and pressure, also control this phenomenon. Effective temperature. The solubility of a solid in a liquid is significantly affected by temperature changes. Consider the equilibrium represented by equation 2.10. This, being dynamic equilibrium, must follow Le Chatelier's principle. In general, if in a nearly saturated solution, the dissolution process is endothermic Sol H0, the solubility should increase with rise in temperature, and if it is exothermic Sol H0, the solubility should decrease. These trends are also observed experimentally. Effective pressure. Pressure does not have any significant effect on solubility of solids in liquids. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas HCl is highly soluble in water. Solubility of gases in liquids is greatly affected by pressure, and 1 solubility of a solid in a liquid, 2 solubility of a gas in a liquid. 41. Solutions temperature. The solubility of gases increase with increase of pressure. For solution of gases in a solvent, consider a system as shown in Fig. 2.1a. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume this system to be in a state of dynamic equilibrium. That is, under these conditions, rate of gaseous particles entering and leaving the solution phase is the same. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. Fig. 2.1b. This will increase the number of gaseous particles per unit volume over the solution and also the rate at which the gaseous particles are striking the surface of solution to enter it. The solubility of the gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of the gas above the solution, and thus its solubility increases. Henry was the first to give a quantitative relation between pressure and solubility of a gas in a solvent, which is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in a liquid solution is a function of partial pressure of the gas. If we use the mole fraction of a gas in the solution as a measure of its solubility, then it can be said that the mole fraction of gas in the solution is proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase P is proportional to the mole fraction of the gas X in the solution and is expressed as pKhx 2.11. Here Kh is the Henry's law constant. If we draw a graph between partial pressure of the gas versus mole fraction of the gas in solution, then we should get a plot of the type as shown in Fig. 2.2. Different gases have different Kh values at the same temperature. Table 2.2. This suggests that Kh is a function of the nature of the gas. It is obvious from equation 2.11 that higher the value of Kh at a given pressure, the lower is the solubility of the gas in the liquid. It can be seen from table 2.2 that Kh values for both N2 and O2 increase with increase of temperature, indicating that the solubility of gas is Fig. 2.1. Effective pressure on the solubility of a gas. The concentration of dissolved gas is proportional to the pressure on the gas above the solution. Figure 2.2. Experimental results for the solubility of HCl gas in cyclohexane at 293 K. The slope of the line is the Henry's law constant. Kh. 42. Chemistry increases with decrease of temperature. It is due to this reason that aquatic species are more comfortable in cold waters rather than in warm waters. Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are, to increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. Scuba divers must cope with high concentrations of dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gases in blood. When the divers come toward surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubbles of nitrogen in the blood. This blocks capillaries and creates a medical condition known as bends, which are painful and dangerous to life. If N2 gas is bubbled through water at 293 K, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 exerts a partial pressure of 0.987 bar. Given that Henry's law constant for N2 at 293 K is 76.48 bar, the solubility of gas is related to the mole fraction in aqueous solution. The mole fraction of the gas in the solution is calculated by applying Henry's law. Thus, X nitrogen H nitrogen pK 0.987 bar 76. 480 bar 1.29 x 10-5 as 1 liter of water contains 55.5 mole of it. Therefore if N represents number of moles of N2 in solution, X nitrogen mole 55.5 mole N 55.5 N 1.29 x 10-5 N in denominator is neglected as it is 55.5, thus N 1.29 x 10-5 x 55.5 mole 7.16 x 10-4 mole 47.16 x 10 mole x 1000 mol 1 mole 0.716 mol. Example 2.4 Example 2.4 Example 2.4 Example 2.4 Example 2.4 Solution gas temperature kKh bar gas temperature kKh bar He 293 144.97 H2 293 69.16 N2 293 76 48 N2 303 88 84 02 293 34 86 02 303 46 82. Table 2.2. Values of Henry's law constant for some selected gases in water: argon 298 40.3, CO2 298 1.67, formaldehyde 298 1.83 x 10-5, methane 298 0.413, vinyl chloride 298 0.611. 43. Solutions to avoid bends, as well as the toxic effects of high concentrations of nitrogen in the blood. The tanks used by scuba divers are filled with air diluted with helium 11.7 helium, 56.2 nitrogen and 32.1 oxygen. At high altitudes the partial pressure of oxygen is less than that at the ground level. This leads to low concentrations of oxygen in the blood and tissues of people living at high altitudes or climbers. Low blood oxygen causes climbers to become weak and unable to think clearly, symptoms of a condition known as anoxia. Effective temperature solubility of gases in liquids decreases with rise in temperature. When dissolved, the gas molecules are present in liquid phase and the process of dissolution can be considered similar to condensation, and heat is evolved in this process. We have learnt in the last section that dissolution process involves dynamic equilibrium and thus must follow Le Chatelier's principle. As dissolution is an exothermic process, the solubility should decrease with increase of temperature. Liquid solutions are formed when solvent is a liquid. The solute can be a gas, a liquid or a solid. Solutions of gases in liquids have already been discussed in section 2.3.2. In this section, we shall discuss the solutions of liquids and solids in a liquid. Such solutions may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solutions, that is, the solutions containing two components, namely, the solutions of I liquids and liquids and two solids in liquids. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be total and P1 and page 2 be the partial vapor pressures of the two components 1 and 2 respectively. These partial pressures are related to the mole fractions x1 and x2 of the two components 1 and 2 respectively. The French chemist, François Martin Raoul 1886 gave the quantitative relationship between them. The relationship is known as the Raoul's law, which states that for a solution of volatile liquids 2.42, 42, 42, 4.2. 4 vapor pressure of liquid solutions in text questions 2.6 H2S, a toxic gas with rotten egg-like smell, is used for the qualitative analysis. If the solubility of H2S in water at STP is 0.195 meters, calculate Henry's law constant. 2.7 Henry's law constant for CO2 in water is 1.67 by 108 Pa at 298 K. Calculate the quantity of CO2 in 500 milliliters of soda water when packed under 2.5 atm CO2 pressure at 298 K. 2.4. 1 vapor pressure of liquid solutions. 44 Chemistry. The partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. Thus, for component 1 P1X1 and P101 page X1 2.12 where 01 P is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2 page 20X2 2.13 where page 20 represents the vapor pressure of the pure component 2. According to Dalton's law of partial pressures, the total pressure taught over the solution phase in the container will be the sum of the partial pressures of the components of the solution and is given as total P1 page 2.14. Substituting the values of P1 and page 2, we get total X1 P10 X2 page 201 X2 P10 X2 page 20 2.15 P10 page 20 P10 X2 2.16. Following conclusions can be drawn from equation 2.16. I total vapor pressure over the solution can be related to the mole fraction of any one component. 2 Total vapor pressure over the solution varies linearly with the mole fraction of component 2. 3 Depending on the vapor pressures of the pure components 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. A plot of P1 or page 2 versus the mole fractions X1 and X2 for a solution gives a linear plot as shown in Fig. 2.3. These lines IN2 pass through the points for which X1 and X2 are equal to unity. Similarly, the plot line 3 of total versus X2 is also linear. Fig. 2.3. The minimum value of total is P10 and the maximum value is page 20, assuming that component 1 is less volatile than component 2, that is, P10, page 20. The composition of vapor phase in equilibrium with the solution is determined by the partial pressures of the components. If Y1 and Y2 are the mole fractions of the figure 2.3, the plot of vapor pressure and mole fraction of an ideal solution at constant temperature. The dashed lines IN2 represent the partial pressure of the components. It can be seen from the plot that P1 and page 2 are directly proportional to X1 and X2, respectively. The total vapor pressure is given by line marked 3 in the figure. Components 1 and 2 respectively in the vapor phase then. Using Dalton's law of partial pressures, P1 Y1 total 2.17 page 2 Y2 total 2.18 in general pi E total 2.19 vapor pressure of chloroform CHCl3 and dichloromethane CH2Cl2 at 298 K or 200 mm Hg and 415 mm Hg respectively. I calculate the vapor pressure of the solution prepared by mixing 25.5 grams of CHCl3 and 40 grams of CH2Cl2 at 298 K and 2 mole fractions of each component in vapor phase. I molar mass of CH2Cl2 12x11 x2 35.5 x2 85 grams mole 1 molar mass of CHCl3 12x11 x1 35.5 x3 119.5 grams mole 1 moles of CH2Cl2 140 grams 85 grams mole 0.47 moles of CHCl3 125.5 grams 119.5 grams mole 0.213 mole total number of moles 0.47 0.213 0.683 mole 22 CHClX 0.47 mole 0.683 mole 0.688 3 CHClX 1.00 to 0.688 0.312 using equation 2.16. Total P10 page 20 P10 x2 200 415 200 x 0.688 200 147.9 347.9 mm Hg2 using the relation 2.19 Ye pi total, we can calculate the mole fraction of the components in gas phase Ye. 22 CHClP 0.688 x 415 mm Hg 285.5 mm Hg3 CHClP 0.312 x 200 mm Hg 62.4 mm Hg 22 CH Cli 285.5 mm Hg 347.9 mm Hg 0.823 CH Cli 62.4 mm Hg 347.9 mm Hg 0.18 Note, since CH2Cl2 is a more volatile component than CHCl3, 2,2-CHCl0P 415 mm Hg and 3-CHCl0P 200 mm Hg, and the vapor phase is also richer in CH2Cl2, 2,2-CH0.82 and 3-CH0.18. It may thus be concluded that at equilibrium, vapor phase will be always rich in the component which is more volatile. Example 2.5 Example 2.5 Example 2.5 Example 2.5 Example 2.5 Solution 46 Chemistry. According to Raoult's law, the vapor pressure of a volatile component in a given solution is given by pi xi pi 0. In the solution of a gas in a liquid, one of the components is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that pKhx. If we compare the equations for Raoult's law and Henry's law, it can be seen that the partial pressure of the volatile component or gas is directly proportional to its mole fraction in solution. Only the proportionality constant Kh differs from P10. Thus, Raoult's law becomes a special case of Henry's law in which Kh becomes equal to P10. Another important class of solutions consists of solids dissolved in liquid, for example, sodium chloride, glucose, urea and cane sugar in water, and iodine and sulfur dissolved in carbon disulfide. Some physical properties of these solutions are quite different from those of pure solvents, for example, vapor pressure. We have learned in Unit 5, Class Xi, that liquids at a given temperature vaporize, and under equilibrium conditions the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure Fig. 2.4 In a pure liquid, the entire surface is occupied by the molecules of the liquid, if a non-volatile solute is added to a solvent to give a solution Fig. 2.4b The vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules, thereby the fraction of the surface covered by the solvent molecules gets reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced, thus, the vapor pressure is also reduced. The decrease in the vapor pressure of solvent depends on the quantity of non-volatile solute present in the solution, irrespective of its nature. For example, decrease in the vapor pressure of water by adding 1.0 mole of sucrose to 1 kg of water is nearly similar to that produced by adding 1.0 mole of urea to the same quantity of water at the same temperature. Raoult's law in its general form can be stated as, for any solution the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in vapor phase and contribute to vapor pressure. Let P1 be 2, 4. 2 Raoult's law is a special case of Henry's law. 2, 4. 3 Vapor pressure of solutions of solids in liquids Fig. 2.4 Decrease in the vapor pressure of the solvent on account of the presence of solute in the solvent. Evaporation of the molecules of the solvent from its surface is denoted by B. In a solution, solute particles have been denoted by, and they also occupy part of the surface area. 47 Solutions. The vapor pressure of the solvent, x1 be its mole fraction, pi 0 be its vapor pressure in the pure state. Then according to Raoult's law, P1x1 and P1x101 P2.20 the proportionality constant is equal to the vapor pressure of pure solvent, 0.1 P. A plot between the vapor pressure and the mole fraction of the solvent is linear. Figure 2.5. Liquid solutions can be classified into ideal and non-ideal solutions on the basis of Raoult's law. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. The ideal solutions have two other important properties. The enthalpy of mixing of the pure components to form the solution is 0, and the volume of mixing is also 0. That is, mix 0, mixed 0. 2.21 It means that no heat is absorbed or evolved when the components are mixed. Also, the volume of solution would be equal to the sum of volumes of the two components, at molecular level. Ideal behavior of the solutions can be explained by considering two components A and B and pure components. The intermolecular attractive interactions will be of types AA and BB, whereas in the binary solutions, in addition to these two interactions, AB type of interactions will also be present. If the intermolecular attractive forces between the AA and BB are nearly equal to those between AB, this leads to the formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromothane and chlorothane, benzene and toluene, etc. fall into this category. When a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. The vapor pressure of such a solution is either higher or lower than that predicted by Raoult's law equation 2.16. If it is higher, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from Raoult's law. The plots of vapor pressure as a function of mole fractions for such solutions are shown in figure 2.6. The cause for these deviations lie in the nature of interactions at the molecular level, in case of positive deviation from Raoult's law. AB interactions are weaker than those between AA or BB, that is, in this case the intermolecular attractive forces between the solute-solvent molecules are weaker than those between the solute-solute and solvent-solvent molecules. This means that in such solutions, molecules of A or B will find it easier to escape than in pure state. This will increase the vapor figure 2.5 if a solution obeys Raoult's law for all concentrations. Its vapor pressure would vary linearly from 0 to the vapor pressure of the pure solvent. 2, 5, 2, 5, 2, 5, 2, 5, 2, 5 ideal and non-ideal and non-ideal and non-ideal and non-ideal and non-ideal solutions. Ideal solutions, ideal solutions, ideal solutions, ideal solutions 2, 5, 1 ideal solutions 2, 5, 2 non-ideal solutions. 48 Chemistry pressure and result in positive deviation. Mixtures of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the host molecules and break some of the hydrogen bonds between them. Due to weakening of interactions, the solution shows positive deviation from Raoult's law figure 2.6a. In a solution formed by adding carbon disulfide to acetone, the dipolar interactions between solute-solvent molecules are weaker than the respective interactions among the solute-solute and solvent-solvent molecules. This solution also shows positive deviation. In case of negative deviations from Raoult's law, the intermolecular attractive forces between AA and BB are weaker than those between AB and leads to decrease in vapor pressure resulting in negative deviations. An example of this type is a mixture of phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair on nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone forms a solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecule as shown. This decreases the escaping tendency of molecules for each component and consequently the vapor pressure decreases resulting in negative deviation from Raoult's law Fig. 2.6b. Some liquids on mixing form azeotropes, which are binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. Figure 2.6. The vapor pressures of two component systems as a function of composition. A solution that shows positive deviation from Raoult's law and B a solution that shows negative deviation from Raoult's law. 49 solutions. For example, ethanol water mixture obtained by fermentation of sugars on fractional distillation gives a solution containing approximately 95 by volume of ethanol. Once this composition, known as azeotrope composition, has been achieved, the liquid and vapor have the same composition, and no further separation occurs. The solutions that show large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition. Nitric acid in water is an example of this class of azeotrope. This azeotrope has the approximate composition 68 nitric acid and 32 water by mass, with a boiling point of 393.5 K. 2.62, 62, 62, 62, 6 colligative properties and properties and properties and properties and properties and capital D E T E R M I N A T I O N capital D E T E R M I N A T I O N capital D E T E of molar mass of molar mass of molar mass of molar mass of molar mass. We have learned in section 2, 4, 3 that the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of solutions which are connected with this decrease of vapor pressure. These are 1. Relative lowering of vapor pressure of the solvent, 2. Depression of freezing point of the solvent, 3. Elevation of boiling point of the solvent, and 4. Osmotic pressure of the solution. All these properties depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative properties. Colligative, from Latin, co means together, ligure means to bind. In the following sections we will discuss these properties one by one. We have learned in section 2, 4, 3 that the vapor pressure of a solvent in solution is less than that of the pure solvent. Raoul established that the lowering of vapor pressure depends only on the concentration of the solute particles and it is independent of their identity. The equation 2.20 given in section 2, 4, 3 establishes a relation between vapor pressure of the solution, mole fraction and vapor pressure of the solvent, that is, P1x1 P10 2.22. The reduction in the vapor pressure of solvent page 1 is given as, page 1 P10 P1 P10 P10 x1 P10 1 x1 2.23 knowing that x21 x1. Equation 2.23 reduces to page 1 x2 P10 2.24 in a solution containing several non-volatile solutes. The lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Equation 2.24 can be written as 101 pp 01101 pp px2 2.25 in text question 2.8. The vapor pressure of pure liquids A and B are 450 and 700 mm Hg respectively, at 350 K. Find out the composition of the liquid mixture if total vapor pressure is 600 mm Hg. Also find the composition of the vapor phase. 2, 6, 1 relative lowering of vapor pressure. 50 Chemistry. The expression on the left-hand side of the equation as mentioned earlier is called relative lowering of vapor pressure and is equal to the mole fraction of the solute. The above equation can be written as 01101 p, pp212 NN212 since NXNN 2.26 here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. For dilute solutions N2, N1. Hence neglecting N2 in the denominator we have 01101 ppP21 NN 2.27 or 01101 ppP2121 WXXWMM 2.28 here W1 and W2 are the masses and M1 and M2 are the molar masses of the solvent and solute respectively. From this equation 2.28, knowing all other quantities, the molar mass of solute M2 can be calculated. Example 2.6 Example 2.6 Example 2.6 Example 2.6 Example 2.6 The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 grams when added to 39.0 grams of benzene molar mass 78 grams mole 1. Vapor pressure of the solution, then, is 0.845 bar. What is the molar mass of the solid substance? The various quantities known to us are as follows: P10 0.850 bar, P 0.845 bar, M1 78 grams mole 1, W2 0.5 grams, W1 39 grams. Substituting these values in equation 2.28. We get 0.850 bar 0.845 bar 0.850 bar minus 1 to 0.5 grams x 78 grams mole x 39 gm. Therefore, M2 170 grams mole 1. We have learned in Unit 5. Class Xi, that the vapor pressure of a liquid increases with increase of temperature. It boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 K 100 degrees Celsius because at this temperature the vapor pressure of water is 1.013 bar 1 atmosphere. We have also learnt in the last section that vapor pressure of the solvent decreases in the presence of non-volatile solute. Figure 2.7 depicts the variation of vapor pressure of the pure solvent and solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 K. In order to make the solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent water. Thus, the boiling 2 elevation of boiling point solution 51 solutions point of a solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared as shown in Fig. 2.7. Similar to lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. A solution of 1 mole of sucrose in 1000 grams of water boils at 373.52 K at 1 atmospheric pressure. Let 0 Bt be the boiling point of pure solvent and Bt be the boiling point of solution. The increase in the boiling point 0 BBBTTT is known as elevation of boiling point. Experiments have shown that for dilute solutions the elevation of boiling point TB is directly proportional to the molar concentration of the solute in a solution. Thus TBm 2.29 or TBKBm 2.30. Here M molality is the number of moles of solute dissolved in 1 kg of solvent and the constant of proportionality. Kb is called boiling point elevation constant or molar elevation constant, ebullioscopic constant. The unit of Kb is kg mol 1. Values of Kb for some common solvents are given in table 2.3. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality M of the solution is given by the expression M221 M1000 WW221 1000 XXM WW2.31. Substituting the value of molality in equation 2.30, we get TBB221 X 1000 XXKM WW2.32 square meters 2BB1 1000 XXXKT WW2.33. Thus, in order to determine M2, molar mass of the solute, known mass of solute and a known mass of the solvent is taken and Tb is determined experimentally for a known solvent whose Kb value is known. 18 grams of glucose, C6H12O6, is dissolved in 1 kg of water in a saucepan. At what temperature will water boil? At 1.013 bar. Kb for water is 0.52 kg mol 1. Moles of glucose 18 grams 180 grams mol 1 0.1 mole number of kilograms of solvent 1 kg. Thus molality of glucose solution 0.1 mole kg1 for water. Change in boiling point. Example 2.7 Example 2.7 Example 2.7 Example 2.7 Example 2.7 Solution Fig. 2.7. The vapor pressure curve for solution lies below the curve for pure water. The diagram shows that Tb denotes the elevation of boiling point of a solvent in solution. 1.013 bar or 52. Chemistry. The lowering of vapor pressure of a solution causes a lowering of the freezing point compared to that of the pure solvent. Fig. 2.8. We know that at the freezing point of a substance, the solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to its vapor pressure in the solid phase. A solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent, as is clear from Fig. 2.8. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases and now it would become equal to that of solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Let 0 feet be the freezing point of pure solvent and Ft be its freezing point when non-volatile solute is dissolved in it. The decrease in freezing point 0 at FFTTT is known as depression in freezing point. Similar to elevation of boiling point, depression of freezing point Tf for dilute solution. Ideal solution is directly proportional to molality, M of the solution. Thus, TFM or TFKFM 2.3 for the proportionality constant, Kf, which depends on the nature of the solvent, is known as freezing point depression constant or mole. Example 2.8 Example 2.8 Example 2.8 Example 2.8 Example 2.8 TBKBXM 0.52 kg mol 1 x 0.1 mol kg1 0.052 k. Since water boils at 373.15 k at 1.013 bar pressure, therefore, the boiling point of solution will be 373.15 0.052 373.202 k. The boiling point of benzene is 353.23 K when 1.80 grams of a non-volatile solute was dissolved in 90 grams of benzene. The boiling point is raised to 354.11 K. Calculate the molar mass of the solute. Kb for benzene is 2.53 K kg mol 1. The elevation Tb and the boiling point 354.11 K 353. 23 K 0.88 K. Substituting these values in expression 2.33, we get M21 to 1253 K kg mol x 1.8 grams x 1000 grams kg 0.88 K x 90 grams 58 grams mol 1. Therefore, molar mass of the solute, M2 58 grams mol 1. Figure 2.8, diagram showing Tf, depression of the freezing point of a solvent in a solution. Solution, capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I 2, 6, 3. Depression of freezing point. 53. Solutions depression constant or cryoscopic constant. The unit of Kf is K kg mol 1. Values of Kf for some common solvents are listed in table 2.3. If W2 gram of the solute having molar mass as M2, present in W1 gram of solvent, produces the depression in freezing point Tf of the solvent, then molality of the solute is given by the equation 2.31. MWW221 1000 M2.31. Substituting this value of molality in equation 2.34, we get TFF221 1000 XKMW TFF221 XX 1000 XKMW 2.35 square meters F2F1 XX 1000 XKTW 2.36. Thus, for determining the molar mass of the solute we should know the quantities W1, W2, Tf, along with the molar freezing point depression constant. The values of Kf and Kb, which depend upon the nature of the solvent, can be ascertained from the following relations. KF21 FUS XX 1000 XRMTH 2.37 KB21 BVAP XX 1000 XRMTH 2.38. Here the symbols R and M1 stand for the gas constant and molar mass of the solvent, respectively, and Tf and Tb denote the freezing point and the boiling point of the pure solvent respectively in Kelvin. Further, FUS and VAF represent the enthalpies for the fusion and vaporization of the solvent, respectively. Solvent ppKKB mole 1F. PKKF kg mole 1 water 373.15 52 273 1 86 ethanol 351.51.2155.7 1.99 cyclohexane 353.74 79 279 55 20 00 benzene 353.32 53 278 6 5 12 chloroform 334.43 63 209 6 4 79 carbon tetrachloride 350.05.03 250.5 31.8 carbon disulfide 319.4 2 34 164 2 3 83 diethyl ether 307.82.02 156.9 1.79 acetic acid 391.12 93 290 0 3 90. Table 2.3, molar boiling point elevation and freezing point depression constants for some solvents. 54 Chemistry Figure 2.9 Level of solution rises in the Thistle funnel due to osmosis of solvent. 45 grams of ethylene glycol C2H6O2 is mixed with 600 grams of water. Calculated the freezing point depression and B the freezing point of the solution. Depression and freezing point is related to the molality. Therefore, the molality of the solution with respect to ethylene glycol, moles of ethylene glycol, mass of water in kilogram, moles of ethylene glycol 145 grams 62 grams, mole 0.73 mole, mass of water in kg 1 600 grams 1000 grams kg 0.6 kilograms. Hence molality of ethylene glycol 0.73 mole 0.60 kilograms 1.2 mole kg 1. Therefore freezing point depression A diuresis Tf 1.86 kg mole 1x 1.2 mole kg 1 2.2 k. Freezing point of the aqueous solution 273.15 k 2.2 k 270.95 k 1.00 grams of a non-electrolyte solute dissolved in 50 grams of benzene lowered the freezing point of benzene by 0.40 k. The freezing point depression constant of benzene is 5.12 kg mole 1. Find the molar mass of the solute. Substituting the values of various terms involved in equation 2.36 we get M21 15.12 kg mole x 1.00 grams x 1000 grams kg 0.40 x 50 grams 256 grams mole 1. Thus, molar mass of the solute 256 grams mole 1. Example 2.9 Example 2.9 Example 2.9 Example 2.9 Example 2.9 Example 2.10 Example 2.10 Example 2.10 Example 2.10 Example 2.10. There are many phenomena which we observe in nature or at home. For example, raw mango shrivel when pickled in brine salt water, wilted flowers revive when placed in fresh water, blood cells collapse when suspended in saline water, etc. If we look into these processes we find one thing common in all, that is, all these substances are bound by membranes. These membranes can be of animal or vegetable origin and these occur naturally such as pig's bladder or parchment or can be synthetic such as cellophane. These membranes appear to be continuous sheets or films, yet they contain a network of submicroscopic holes or pores. Small solvent solution, capital S-O-L-U-T-I-O-N, capital S-O-L-U-T-I-O-N, capital S-O-L-U-T-I-O-N, capital S-O-L-U-T-I, solution 2, 6, 4 osmosis and osmotic pressure. 55 solutions molecules, like water, can pass through these holes but the passage of bigger molecules like solute is hindered. Membranes having this kind of properties are known as semi-permeable membranes SPM. Assume that only solvent molecules can pass through these semi-permeable membranes. If this membrane is placed between the solvent and solution as shown in figure 2.9, the solvent molecules will flow through the membrane from pure solvent to the solution. This process of flow of the solvent is called osmosis. The flow will continue till the equilibrium is attained. The flow of the solvent from its side to solution side across a semi-permeable membrane can be stopped if some extra pressure is applied on the solution. This pressure that just stops the flow of solvent is called osmotic pressure of the solution. The flow of solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to osmosis. The important point to be kept in mind is that solvent molecules always flow from lower concentration to higher concentration of solution. The osmotic pressure has been found to depend on the concentration of the solution. The osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis. That is, to stop the passage of solvent molecules through a semi-permeable membrane into the solution. This is illustrated in Figure 2.10. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. For dilute solutions, it has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at a given temperature T. Thus, Greek letter pi CRT 2.39 here. Greek letter pi is the osmotic pressure and R is the gas constant. Greek letter pi N2 VRT 2.40 here. V is volume of a solution in liters containing N2 moles of solute. If W 2 grams of solute of molar mass, N2 is present in the solution, then N2W2 M2, and we can write Greek letter pi V2 2WRT M2.41 or M2 2WRT V2.42. Thus, knowing the quantities W2, T, Greek letter pi and V, we can calculate the molar mass of the solute. Measurement of osmotic pressure provides another method of determining molar masses of solutes. This method is widely used to determine molar masses of proteins, polymers and other Fig. 2.10. The excess pressure equal to the osmotic pressure must be applied on the solution side to prevent osmosis. 56. Chemistry macromolecules. The osmotic pressure method has the advantage over other methods as pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to other colligative properties, its magnitude is large even for very dilute solutions. The technique of osmotic pressure for determination of molar mass of solutes is particularly useful for biomolecules as they are generally not stable at higher temperatures and polymers have poor solubility. Two solutions having same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by semi-permeable membrane, no osmosis occurs between them. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9 mass volume sodium chloride solution, called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cells in a solution containing more than 0.9 mass volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called hypertonic. If the salt concentration is less than 0.9 mass volume, the solution is said to be hypotonic. In this case, water will flow into the cells if placed in this solution and they would swell to 100 cubic centimeters of an aqueous solution of a protein contains 1.26 grams of the protein. The osmotic pressure of such a solution at 300 K is found to be 2.57 x 10³ bar. Calculate the molar mass of the protein. The various quantities known to us are as follows. Greek letter pi 2.57 x 10-3 bar. V 200 cubic centimeters 0.200 liter T 300 kr 0.083 L bar mole 1 K1. Substituting these values in equation 2.42 we get M21131.26 grams x 0.083 L bar K mole x 300 K 2.57 x 10 bar x 0.200 L 61. 0.22 grams mole 1 example 2.11 example 2.11 example 2.11 example 2.11 example 2.11 solution. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses water via osmosis and shrivel into pickle. Wilted flowers revive when placed in fresh water. A carrot that has become limp because of water loss into the atmosphere can be placed into the water making it firm once again. Water will move into its cells through osmosis. When placed in water containing less than 0.9 mass volume salt, blood cells swell due to flow of water in them by osmosis. People taking a lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis. The resulting 57 solutions puffiness or swelling is called edema. Water movement from soil into plant roots and subsequently into upper portion of the plant is partly due to osmosis. The preservation of meat by salting and of fruits by adding sugar protects against bacterial action. Through the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and dies. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called reverse osmosis and is of great practical utility. Reverse osmosis is used in desalination of seawater. A schematic setup for the process is shown in Fig. 2.11. When pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days many countries use desalination plants to meet their potable water requirements. 2, 6, 5 Reverse osmosis and water purification in text questions 2.9 Vapor pressure of pure water at 298 K is 23.8 mm Hg. 50 grams of urea NH2CO NH2 is dissolved in 850 grams of water. Calculate the vapor pressure of water for this solution and its relative lowering. 2.10 Boiling point of water at 750 mm Hg is 99.63 degrees Celsius. How much sucrose is to be added to 500 grams of water such that it boils at 100 degrees Celsius? 2.11 Calculate the mass of ascorbic acid vitamin C. C6H8O6 to be dissolved in 75 grams of acetic acid to lower its melting point by 1.5 degrees Celsius. Kf 3.9 kg mol 1. 2.12 Calculate the osmotic pressure in pascals exerted by a solution prepared by dissolving 1.0 grams of polymer of molar mass 185. 000 in 450 milliliters of water at 37 degrees Celsius. We know that ionic compounds when dissolved in water dissociate into cations and anions. For example, if we dissolve 1 mole of KCl 74.5 grams in water, we expect 1 mole each of K and Cl ions to be released in the solution. If this happens, there would be 2 moles of particles in the solution, if we ignore interionic attractions. 1 mole of KCl and 1 kg of water would be expected to increase the boiling point by 2x 0.52 K 1.04 K. Now if we did not know about the degree of 2.72, 72, 72, 72, 7 abnormal molar masses Greek letter pi Fig. 2.11 Reverse osmosis occurs when a pressure larger than the osmotic pressure is applied to the solution. 2CH3Cu2 dissociation. We could be led to conclude that the mass of 2 mole particles is 74.5 grams and the mass of 1 mole of KCl would be 37.25 grams. This brings into light the rule that, when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. Molecules of ethanoic acid, acetic acid and and benzene due to hydrogen bonding. This normally happens in solvents of low dielectric constant. In this case the number of particles is reduced due to dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated here that if all the molecules of ethanoic acid associate in benzene, then TbRTF for ethanoic acid will be half of the normal value. The molar mass calculated on the basis of this TbRTF will, therefore, be twice the expected value. Such a molar mass that is either lower or higher than the expected or normal value is called as abnormal molar mass. In 1880 Van't Hoff introduced a factor I, known as the Van't Hoff factor, to account for the extent of dissociation or association. This factor I is defined as normal molar mass abnormal molar mass I observed colligative property calculated colligative property total number of moles of particles after association dissociation number of moles of particles before association dissociation I here abnormal molar mass is the experimentally determined molar mass and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. In case of association, value of I is less than unity while for dissociation it is greater than unity. For example, the value of I for aqueous KCl solution is close to 2, while the value for ethanoic acid in benzene is nearly 0.5. Inclusion of Van't Hoff factor modifies the equations for colligative properties as follows. Relative lowering of vapor pressure of solvent. 0.112011 ppn INP elevation of boiling point, TBIKBM depression of freezing point. TFIKFM osmotic pressure of solution, Greek letter pi IN to RTV. 2 grams of benzoic acid C6H5Cu dissolved in 25 grams of benzene shows a depression in freezing point equal to 1.62 K. Molal depression constant for benzene is 4.9 kg mol 1. What is the percentage association of acid if it forms dimer in solution? A given quantities are W2 2 grams, Kf 4.9 kg mol 1, W1 25 grams. TF 1.62K. Substituting these values in equation 2.36 we get M2 minus 1 minus 14.9 K kg mole x 2 grams x 1000 grams kg 25 grams x 1.62 K 241.98 grams mole 1. Thus, experimental molar mass of benzoic acid in benzene is 241.98 grams mole 1. Now consider the following equilibrium for the acid. 2C6H5Cu C6H5Cu2. If X represents the degree of association of the solute, then we would have 1 X mole of benzoic acid left in unassociated form and correspondingly 2 X as associated moles of benzoic acid at equilibrium. Therefore, total number of moles of particles at equilibrium is 1122XXX. Thus, total number of moles of particles at equilibrium equals Van 't Hoff factor I. But normal molar mass, abnormal molar mass I. Example 2.1 to example 2.1 to example 2.1 to example 2.1 to example 2.12 solution table 2.4 depicts values of the factor I for several strong electrolytes. For KCl, NaCl and XO4, I values approach 2 as the solution becomes very dilute. As expected, the value of I gets close to 3 for K2SO4. Salt values of I. Van 't Hoff factor I for complete 0.1 meters 0.01 meters 0.001 meters. Dissociation of solute NaCl 1.87 1.94 1.97 2.00 KCl 1.85 1.94 1.98 2.00 XO4 1.21 1.53 1.82 2.00 K2SO4 2.32 2.72 2.84 3.00 represent I values for incomplete dissociation. Table 2.4, values of Van 't Hoff factor, I, at various concentrations for NaCl, KCl, XO4 and K2SO4. Example 2.13 Example 2.13 Example 2.13 Example 2.13 Example 2.13 122 grams mole 241.98 grams mole or 2x 122 110.540.496 241.98 or x 2x 0.496 0.992. Therefore, degree of association of benzoic acid in benzene is 99.20. 0.6 milliliters of acetic acid CH3Cu, having density 1.06 grams ml1, is dissolved in 1 liter of water. The depression in freezing point observed for this strength of acid was 0.0205 degrees Celsius. Calculate the Van 't Hoff factor and the dissociation constant of acid. Number of moles of acetic acid 0.6 milliliters 1.06 grams ml 60 grams mole x 0.0106 mole and molality 0.0106 mole 1000 milliliters 1 gram ml x 0.0106 mole kg1 using equation 2.35 TF 1.86 K kg mole 1 x 0.0106 mole kg1 0.0197 K. Van 't Hoff factor I. Observed freezing point. Calculated freezing point 0.0205 K 0.0197 K 1.041. Acetic acid is a weak electrolyte and will dissociate into 2 ions, acetate and hydrogen ions per molecule of acetic acid. If X is the degree of dissociation of acetic acid, then we would have N1X moles of undissociated acetic acid, NX moles of CH3COO and NX moles of H ions. 33CH2HCHCOO mole 00 mole mole 1 NNNXNXX. Thus total moles of particles are N1XXX N1X11 1.041 NXIX and thus degree of dissociation of acetic acid X 1.041 1.000 0.041 then CH3COO N1X 0.0106 0.041 CH3COO NX 0.0106 X 0.041 HNX 0.0106 X 0.041 Ca33CHCOOHCHQ 0.0106 X 0.041 X 0.0106 X 0.041 0.0106 1.00 0.041 1.86 X 10-5 Solution 61 Solution Summary A solution is a homogeneous mixture of 2 or more substances. Solutions are classified as solid, liquid and gaseous solutions. The concentration of a solution is expressed in terms of mole fraction, molarity, molality and in percentages. The dissolution of a gas in a liquid is governed by Henry's law, according to which, at a given temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. The vapor pressure of the solvent is lowered by the presence of a non-volatile solute in the solution, and this lowering of vapor pressure of the solvent is governed by Raoult's law. according to which the relative lowering of vapor pressure of the solvent over a solution is equal to the mole fraction of a non-volatile solute present in the solution. However, in a binary liquid solution, if both the components of the solution are volatile, then another form of Raoult's law is used. Mathematically, this form of the Raoult's law is stated as 00 total 1 to 21 ppx. Solutions which obey Raoult's law over the entire range of concentration are called ideal solutions. Two types of deviations from Raoult's law, called positive and negative deviations, are observed, as azeotropes arise due to very large deviations from Raoult's law. The properties of solutions which depend on the number of solute particles and are independent of their chemical identity are called colligative properties. These are lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. The process of osmosis can be reversed if a pressure higher than the osmotic pressure is applied to the solution. Colligative properties have been used to determine the molar mass of solutes. Solutes which dissociate in solution exhibit molar mass lower than the actual molar mass, and those which associate show higher molar mass than their actual values. Quantitatively, the extent to which a solute is dissociated or associated can be expressed by Van 't Hoff factor I. This factor has been defined as ratio of normal molar mass to experimentally determined molar mass, or as the ratio of observed colligative property to the calculated colligative property. 2.1 Define the term solution. How many types of solutions are formed? Write briefly about each type with an example. 2.2 Give an example of a solid solution in which the solute is a gas. 2.3 Define the following terms: I mole fraction, 2 molality, 3 molarity, I mass percentage. 2.4 Concentrated nitric acid used in laboratory work is 68 nitric acid by mass in aqueous solution. What should be the molarity of such a sample of the acid if the density of the solution is 1.504 grams ml1? Exercises. Electrochemistry is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. The subject is of importance both for theoretical and practical considerations. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. The reactions carried out electrochemically can be energy efficient and less polluting. Therefore, study of electrochemistry is important for creating new technologies that are eco-friendly. The transmission of sensory signals through cells to brain and vice versa and communication between the cells are known to have electrochemical origin. Electrochemistry is therefore a very vast and interdisciplinary subject. In this unit, we will cover only some of its important elementary aspects. After studying this unit, you will be able to describe an electrochemical cell and differentiate between galvanic and electrolytic cells, apply Nernst equation for calculating the EMF of galvanic cell and define standard potential of the cell, derive relation between standard potential of the cell, Gibbs energy of cell reaction and its equilibrium constant, define resistivity Greek letter ρ, conductivity Greek letter kappa, and molar conductivity m of ionic solutions, differentiate between ionic electrolytic and electronic conductivity, describe the method for measurement of conductivity of electrolytic solutions and calculation of their molar conductivity, justify the variation of conductivity and molar conductivity of solutions with change in their concentration and define degrees molar conductivity at zero concentration or infinite dilution, enunciate Kohlrausch law and learn its applications, understand quantitative aspects of electrolysis, describe the construction of some primary and secondary batteries and fuel cells, explain corrosion as an electrochemical process. Objectives: chemical reactions can be used to produce electrical energy. Conversely, electrical energy can be used to carry out chemical reactions that do not proceed spontaneously. 3 Electrochemistry Unit 3 Electrochemistry 66 Chemistry Q-Ext 1.1 E Current cathode V anode V Zn Figure 3.2 Functioning of Daniell cell when external voltage Ext opposing the cell potential is applied. In Class Xi, Unit 8, we had studied the construction and functioning of Daniell cell Figure 3.1. This cell converts the chemical energy liberated during the redox reaction ZnSQ2 Zn2 Qs 3.1 to electrical energy and has an electrical potential equal to 1.1 V when concentration of Zn2 and Q2 ions is unity 1 mol dm3. Such a device is called a galvanic or a voltaic cell, if an external opposite potential is applied in the galvanic cell Fig. 3.2 and increase slowly, we find that the reaction continues to take place till the opposing voltage reaches the value 1.1 V Fig. 3.2b When the reaction stops altogether and no current flows through the cell, any further increase in the external potential again starts the reaction but in the opposite direction. Fig. 3.2c. It now functions as an electrolytic cell, a device for using electrical energy to carry non-spontaneous chemical reactions. Both types of cells are quite important and we shall study some of their salient features in the following pages. Strictly speaking, activity should be used instead of concentration. It is directly proportional to concentration. In dilute solutions, it is equal to concentration. You will study more about it in higher classes. 3.13 capital E L E C T R O C H E M I C A L capital E L E C T R O C H E M I C A L cells Fig. 3.1 Daniell cell having electrodes of zinc and copper dipping in the solutions of their respective salts. Salt bridge CN anode cathode occurrence SO4Q SO4 EXT 1.1 V EVEV NI0 ZN SO4Q SO4 EXT 1.1 V when EXT 1.1 VI electrons flow from ZN rod to Q rod, hence current flows from Q to ZN. 2 ZN dissolves at anode and copper deposits at cathode, when EXT 1.1 VI no flow of electrons or current. 2 No chemical reaction, when EXT 1.1 VI electrons flow from Q to ZN and current flows from ZN to Q. 2 Zinc is deposited at the zinc electrode and copper dissolves at copper electrode ABC. 67 Electrochemistry. As mentioned earlier, class Xi, Unit 8. A galvanic cell is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy. In this device, the Gibbs energy of the spontaneous redox reaction is converted into electrical work which may be used for running a motor or other electrical gadgets like heater, fan, geyser, etc. Daniell cell discussed earlier is one such cell in which the following redox reaction occurs. ZnSQ2 Ac Zn2 Ac QS. This reaction is a combination of two half reactions whose addition gives the overall cell reaction. IQ2 2EQS reduction half reaction 3.2 to ZnSCN2 2E oxidation half reaction 3.3. These reactions occur in two different portions of the Daniell cell. The reduction half reaction occurs on the copper electrode while the oxidation half reaction occurs on the zinc electrode. These two portions of the cell are also called half cells or redox couples. The copper electrode may be called the reduction half cell and the zinc electrode, the oxidation half cell. We can construct a numerable number of galvanic cells on the pattern of Daniell cell by taking combinations of different half cells. Each half cell consists of a metallic electrode dipped into an electrolyte. The two half cells are connected by a metallic wire through a voltmeter and a switch externally. The electrolytes of the two half cells are connected internally through a salt bridge as shown in Fig. 3.1. Sometimes, both the electrodes dip in the same electrolyte solution, and in such cases we do not require a salt bridge. At each electrode-electrolyte interface there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, metal atoms of the electrode have a tendency to go into the solution as ions and leave behind the electrons at the electrode, trying to make it negatively charged. At equilibrium, there is a separation of charges, and depending on the tendencies of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentrations of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. According to IUPAC convention, standard reduction potentials are now called standard electrode potentials. In a galvanic cell, the half cell in which oxidation takes place is called anode, and it has a negative potential with respect to the solution. The other half cell in which reduction takes place is called cathode, and it has a positive potential with respect to the solution. Thus, there exists a potential difference between the two electrodes, and as soon as the switch is in the on position, the electrons flow from negative electrode to positive electrode. The direction of current flow is opposite to that of electron flow. 3.2 Galvanic cells 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 68 Chemistry. The potential difference between the two electrodes of a galvanic cell is called the cell potential and is measured in volts. The cell potential is the difference between the electrode potentials, reduction potentials of the cathode and anode. It is called the cell electromotive force EMF of the cell when no current is drawn through the cell. It is now an accepted convention that we keep the anode on the left and the cathode on the right while representing the galvanic cell. A galvanic cell is generally represented by putting a vertical line between metal and electrolyte solution and putting a double vertical line between the two electrolytes connected by a salt bridge. Under this convention, the EMF of the cell is positive and is given by the potential of the half cell on the right-hand side minus the potential of the half cell on the left-hand side, that is SLR. LF. This is illustrated by the following example. Cell reaction. QS2 Ag Ag Q2 Ag 2 Ag S 3.4 half cell reactions. Cathode reduction. 2 Ag Ag 2 E2 Ag S 3.5 anode oxidation. QS Q2 Ag 2 E 3.6. It can be seen that the sum of 3.5 and 3.6 leads to overall reaction 3.4 inches. The cell in that silver electrode acts as a cathode and copper electrode acts as an anode. The cell can be represented as QS Q2 Ag 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 S, and we have SLR. L left E Ag equal to Q 3.7. The potential of individual half cell cannot be measured. We can measure only the difference between the two half cell potentials that gives the EMF of the cell. If we arbitrarily choose the potential of one electrode half cell, then that of the other can be determined with respect to this. According to convention, a half cell called standard hydrogen electrode figure 3.3 represented by PTSH2GHAC is assigned a zero potential at all temperatures corresponding to the reaction HAC E12H2G. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. The concentration of both the reduced and oxidized forms of hydrogen is maintained at unity Fig. 3.3. This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. 3.2.1 Measurement of electrode potential figure 3.3, standard hydrogen electrode sheet. 69 Electrochemistry at 298 K. The EMF of the cell, standard hydrogen electrode second half cell constructed by taking standard hydrogen electrode as anode reference half cell and the other half cell as cathode. Gives the reduction potential of the other half cell, if the concentrations of the oxidized and the reduced forms of the species in the right-hand half cell are unity. Then the cell potential is equal to standard electrode potential, EJR of the given half cell. EJR, EJL is EJL for standard hydrogen electrode is 0, EJR 0 EJR the measured EMF of the cell, PTSH2G. 1 bar HAC, 1 MQ2AC, 1 MQ is 0.34 V and it is also the value for the standard electrode potential of the half cell corresponding to the reaction, Q2AC. 1 M2EQS. Similarly, the measured EMF of the cell, PTSH2G, 1 bar HAC, 1 MZN2AC. 1 MZN is 0.76 V corresponding to the standard electrode potential of the half cell reaction, ZN2AC. 1 M2EZNS. The positive value of the standard electrode potential in the first case indicates that Q2 ions get reduced more easily than H ions. The reverse process cannot occur, that is, hydrogen ions cannot oxidize Q, or alternatively we can say that hydrogen gas can reduce copper ion under the standard conditions described above. Thus, Q does not dissolve in HCl. In nitric acid it is oxidized by nitrate ion and not by hydrogen ion. The negative value of the standard electrode potential in the second case indicates that hydrogen ions can oxidize zinc or zinc can reduce hydrogen ions. In view of this convention, the half reaction for the Daniell cell in figure 3.1 can be written as left electrode, ZNSCN2AC. 1 M2E right electrode, Q2AC. 1 M2EQS. The overall reaction of the cell is the sum of above two reactions and we obtain the equation, ZNSQ2AC ZN2AC EMF of the cell 0 cell E0R, E0L 0.34 V 0.76 V 1.10 V. Sometimes metals like platinum or gold are used as inert electrodes. They do not participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrons. For example, PT is used in the following half cells: hydrogen electrode, PTSH2GHAC with half cell reaction, HAC 1 half H2G bromine electrode, PTSBr2AC BrAC. 70 chemistry with half cell reaction, 1 half Br2AC BrAC. The standard electrode potentials are very important and we can extract a lot of useful information from them. The values of standard electrode potentials for some selected half cell reduction reactions are given in table 3.1. If the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable compared to hydrogen gas. Similarly, if the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. it can be seen that the standard electrode potential for fluorine is the highest in the table, indicating that fluorine gas F2 has the maximum tendency to get reduced to fluoride ions F, and therefore fluorine gas is the strongest oxidizing agent, and fluoride ion is the weakest reducing agent. Lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent, while lithium metal is the most powerful reducing agent in an aqueous solution. It may be seen that as we go from top to bottom in table 3.1, the standard electrode potential decreases, and with this decreases the oxidizing power of the species on the left and increases the reducing power of the species on the right-hand side of the reaction. Electrochemical cells are extensively used for determining the pH of solutions, solubility product, equilibrium constant and other thermodynamic properties, and for potentiometric titrations. In text questions 3.1, how would you determine the standard electrode potential of the system Mg2Mg? 3.2, can you store copper sulfate solutions in a zinc pot? 3.3, consult the table of standard electrode potentials and suggest 3 substances that can oxidize ferrous ions under suitable conditions. 3.33 Nernst equation. We have assumed in the previous section that the concentration of all the species involved in the electrode reaction is unity. This need not be always true. Nernst showed that for the electrode reaction, Mn the electrode potential at any concentration measured with respect to standard hydrogen electrode can be represented by NNMMMEV, RTNFLNMMN, but concentration of solid M is taken as unity, and we have NNMMMEV, RTNFLNN1M. 3.8 NMMEV has already been defined. R is gas constant 8.314 JK1 mol 1, F is Faraday constant 96,487 C mol 1, T is temperature in Kelvin, and Mn is the concentration of the species, Mn. In Daniell cell, the electrode potential for any given concentration of Cu2 and Zn2 ions. We write for cathode, 2 Cu2 EV, RTF2 LN2 1 Cuac 3.9 for anode, 2 ZN to ZN EV, RTF2 LN2 1 ZNAC 3.10. The cell potential, E cell 2 Cu to ZN E2 Cu EV, RTF2 LN2 1 Cuac to ZN EV, RTF2 LN2 1 ZNAC 2 Cu EV to ZN EV, RTF2 2211 LN Cuac ZNAC, cell V, RTF2 LN2 ZN2 Cu 3.11. It can be seen that E cell depends on the concentration of both Cu2 and ZN2 ions. It increases with increase in the concentration of Cu2 ions and decrease in the concentration of ZN2 ions. By converting the natural logarithm in EC 3.11 to the base 10 and substituting the values of R, F and T to 198K, it reduces to E cell V0059222. Log Zn Cu 3.12. We should use the same number of electrons N for both the electrodes and thus for the following cell Ni2 Ag. The cell reaction is Ni2 Ag Ni2 Ag 2 Ag. As the Nernst equation can be written as E cell V, RTF2 LN Niag 2 and for a general electrochemical reaction of the type ABB NCCDD, Nernst equation can be written as E cell V, RTNF1 NQ cell V, RTNF LN CD ABCD AB 3.13. If the circuit in Daniell cell figure 3.1 is closed, then we note that the reaction ZnS Cu2 Ag Zn2 Ag Cu S 3.1 takes place, and as time passes, the concentration of Zn2 keeps on increasing while the concentration of Cu2 keeps on decreasing. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. After some time, we shall note that there is no change in the concentration of Cu2 and Zn2 ions, and at the same time, voltmeter gives 0 reading. This indicates that equilibrium has been attained. In this situation, the Nernst equation may be written as E cell 0 cell V2.332 log Zn Cu2 2 RTF, or cell V2 2.303 Zn log 2 Cu RTF, but at equilibrium, Zn Cu2 2 Kc for the reaction 3.1 and at T 298 K. The above equation can be written as cell V00592. V log Kc 1.1 V cell V 1.1 V log Kc 1.1 Vx 237, 288, 0, 059, VKC 2x 1037 at 298 K, in general. Cell V 2.303 RTNF log Kc 3.14. Thus, EC 3.14 gives a relationship between equilibrium constant of the reaction and standard potential of the cell in which that reaction takes place. Thus, equilibrium constants of the reaction, difficult to measure otherwise, can be calculated from the corresponding EJ value of the cell. 3. 3. 1 equilibrium constant from Nernst equation. Example 3.1. Example 3.1. Example 3.1. Example 3.1. Example 3.1 represent the cell in which the following reaction takes place. MgS2 ag 0.0001 m Mg2 0.130 m2 ag S. Calculate its E cell if cell V 3.17 V. The cell can be written as Mg2 0.130 m ag 0.0001 m ag cell 2 Mgrtln2 F ag V 3.17 V 0059200001 2. Log V 0.130 3.17 V 0.21 V 2.96 V. Solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. 74. Chemistry. The standard electrode potential for Daniell cell is 1.1 V. Calculate the standard Gibbs energy for the reaction. ZnSQ2 aq Zn2 aq QSRGJNF cell Fn in the above equation is 2. F 96487 C mol 1 and cell V 1.1 V. Therefore RGJ2x 1.1 V x 96487 C mol 1 21227 J mol 1 212.27 K J mol 1. Example 3.3. Example 3.3. Example 3.3. Example 3.3. Example 3.3 Solution. Electrical work done in 1 second is equal to electrical potential multiplied by total charge passed. If we want to obtain maximum work from a galvanic cell, then charge has to be passed reversibly. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy, and therefore, if the EMF of the cell is E and NF is the amount of charge passed and Rg is the Gibbs energy of the reaction, then RG/NF E cell 3.15. It may be remembered that E cell is an intensive parameter but Rg is an extensive thermodynamic property and the value depends on N. Thus, if we write the reaction ZnSQ2 aq Zn2 aq QS 3.1 Rg2 phase cell, but when we write the reaction to ZnS2Q2 aq to Zn2 aq 2 QS Rg4 phase cell, if the concentration of all the reacting species is unity, then E cell V and we have RGJNF cell V 3.16. Thus, from the measurement of cell V we can obtain an important thermodynamic quantity, RGJ, standard Gibbs energy of the reaction. From the latter we can calculate equilibrium constant by the equation, RGJ/RT/ln/K. 3. 2 electrochemical cell and Gibbs energy of the reaction. Calculate the equilibrium constant of the reaction, QS2 ag aq Q2 aq 2 ag S cell V 0.46 V cell V 00592. V log Kc 0.46 V R log Kc 0.46200059. VBX 15.6 Kc 3.92 x 1015. Example 3.2. Example 3.2. Example 3.2. Example 3.2. Example 3.2 Solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. 75. Electrochemistry. It is necessary to define a few terms before we consider the subject of conductance of electricity through electrolytic solutions. The electrical resistance is represented by the symbol R and it is measured in ohm Greek letter omega, which in terms of SI base units is equal to kgm2s3a2. It can be measured with the help of a Wheatstone bridge with which you are familiar from your study of physics. The electrical resistance of any object is directly proportional to its length, L, and inversely proportional to its area of cross-section, A. That is, RLA or R Greek letter rho LA 3.17. The constant of proportionality, Greek letter rho Greek, rho, is called resistivity-specific resistance. It says I units are ohm meter Greek letter omega m, and quite often its submultiple, ohm centimeter Greek letter omega cm, is also used. IUPAC recommends the use of the term resistivity over specific resistance, and hence in the rest of the book we shall use the term resistivity. Physically, the resistivity for a substance is its resistance when it is 1 meter long and its area of cross-section is 1 m2. It can be seen that 1 Greek letter omega m 100 Greek letter omega cm or 1 Greek letter omega cm 0.01 Greek letter omega m. The inverse of resistance, R, is called conductance, G, and we have the relation, G1R Greek letter rho Greek letter kappa AALL 3.18. The SI unit of conductance is Siemens, represented by the symbol S, and is equal to ohm 1, also known as mho R Greek letter omega minus 1. The inverse of resistivity, called conductivity-specific conductance, is represented by the symbol, Greek letter kappa Greek, kappa. IUPAC has recommended the use of term conductivity over specific conductance, and hence we shall use the term conductivity in the rest of the book. The SI units of conductivity are SM1, but quite often, Greek letter kappa is expressed in SCM1. Conductivity of a material in SM1 is its conductance when it is 1 meter long and its area of cross-section is 1 square meter. It may be noted that 1 SCM1 100 SM1 3.43, 43, 43, 43, 4 conductance of electrolytic electrolytic solutions in text questions 3.4 Calculate the potential of hydrogen electrode in contact with a solution whose pH is 10. 3.5 Calculate the EMF of the cell in which the following reaction takes place. Ni2ag 0.00 to Mni2 0.160 M2ag S. Given that cell F 1.05 V 3.6 the cell in which the following reaction occurs. 3222 Fe2I2 Fe IAC S has 0 cell 0.236 V at 298 K. Calculate the standard Gibbs energy and the equilibrium constant of the cell reaction. 76 Chemistry electronically conducting polymers. In 1977, McDermott, Heeger and Shirakawa discovered that acetylene gas can be polymerized to produce a polymer. Polyacetylene, when exposed to vapors of iodine, acquires metallic luster and conductivity. Since then, several organic conducting polymers have been made, such as polyaniline, polypyrrole and polythiophene. These organic polymers, which have properties like metals, being composed wholly of elements like carbon, hydrogen and occasionally nitrogen, oxygen or sulfur, are much lighter than normal metals and can be used for making lightweight batteries. Besides, they have the mechanical properties of polymers, such as flexibility, so that one can make electronic devices such as transistors that can bend like a sheet of plastic. For the discovery of conducting polymers, McDermott, Heeger and Shirakawa were awarded the Nobel Prize in Chemistry for the year 2000. It can be seen from Table 3.2 that the magnitude of conductivity varies a great deal and depends on the nature of the material. It also depends on the temperature and pressure at which the measurements are made. Materials are classified into conductors, insulators and semiconductors depending on the magnitude of their conductivity. Metals and their alloys have very large conductivity and are known as conductors. Certain nonmetals like carbon black, graphite and some organic polymers are also electronically conducting. Substances like glass, ceramics, etc., having very low conductivity are known as insulators. Substances like silicon, doped silicon and gallium arsenide having conductivity between conductors and insulators are called semiconductors and are important electronic materials. Certain materials called superconductors by definition have zero resistivity or infinite conductivity. Earlier, only metals and their alloys of very low temperature 0 to 15 K were known to behave as superconductors. But nowadays a number of ceramic materials and mixed oxides are also known to show superconductivity at temperatures as high as 150 K. Electrical conductance through metals is called metallic or electronic conductance and is due to the movement of electrons. The electronic conductance depends on the nature and structure of the metal to the number of valence electrons per atom. 3 Temperature. It decreases with increase of temperature. Table 3.2. The values of conductivity of some selected materials at 298.15 K. Material conductivity SM1 conductors aqueous solutions sodium 2.1 x 103 pure water 3.5 x 10-5 copper 5.9 x 103 0.1 m HCl 3.91 silver 6.2 x 103 0.01 m KCl 0.14 gold 4.5 x 103 0.01 m NaCl 0.12 iron 1.0 x 103 0.1 m HAC 0.047 graphite 1.2 x 10 0.01 m HAC 0.016 insulators semiconductors glass 1.0 x 10-16 CuO1 x 10-7 Teflon 1.0 x 10-18 C 1.5 x 10-2 Jet 2.0 77 Electrochemistry. As the electrons enter at one end and go out through the other end, the composition of the metallic conductor remains unchanged. The mechanism of conductance through semiconductors is more complex. We already know class Xi, unit 7, that even very pure water has small amounts of hydrogen and hydroxyl ions 10-7 m which lend it very low conductivity 3.5 x 10-5 SM1. When electrolytes are dissolved in water, they furnish their own ions in the solution, hence its conductivity also increases. The conductance of electricity by ions present in the solutions is called electrolytic or ionic conductance. The conductivity of electrolytic ionic solutions depends on I. The nature of the electrolyte added, 2. Size of the ions produced and their solvation, 3. The nature of the solvent and its viscosity, I. Concentration of the electrolyte, E. Temperature. It increases with the increase of temperature. Passage of direct current through ionic solution over a prolonged period can lead to change in its composition due to electrochemical reactions. Section 3, 4, 1. We know that accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. However, for measuring the resistance of an ionic solution we face two problems. Firstly, passing direct current DC changes the composition of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. The first difficulty is resolved by using an alternating current AC source of power. The second problem is solved by using a specially designed vessel called conductivity cell. It is available in several designs and two simple ones are shown in figure 3.4. 3, 4, 1. Measurement of the conductivity of ionic solutions connecting wires. Platinized PT electrodes. Platinized PT electrode. Platinized PT electrode connecting wires. Fig. 3.42. Different types of conductivity cells. Basically it consists of two platinum electrodes coated with platinum black. Finely divided metallic PT is deposited on the electrodes electrochemically. These have area of cross-section equal to A and are separated by distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross-section A. The resistance of such a column of solution is then given by the equation, R Greek letter rho LA Greek letter kappa LA 3.17. 78 Chemistry Table 3.3. Conductivity and molar conductivity of KCl solutions at 298.15 kmol L1 mol N3 SCM1 SM1 SCM2 mol 1 SM2 mol 11 000 1000 0 1113 11 13 111 3 111 3 X10-40.100 100.00.01291 29 129 0 129 0 X10-40.010.000 00141 0 141 141.0 141.0 X10-4. Concentration molarity conductivity molar conductivity. The quantity La is called cell constant denoted by the symbol G. It depends on the distance between the electrodes and their area of cross-section and has the dimension of length 1 and can be calculated if we know L and A. Measurement of L and A is not only inconvenient but also unreliable. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations. Table 3.3 and at different temperatures. The cell constant, G, is then given by the equation, GLAR Greek letter kappa 3.18. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for the measurement of the resistance is shown in figure 3.5. It consists of two resistances R3 and R4, a variable resistance R1 and the conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by an oscillator O, a source of AC power in the audio frequency range 550 to 5000 cycles per second. P is a suitable detector or headphone or other electronic device, and the bridge is balanced when no current passes through the detector. Under these conditions, a known resistance R to 143 RRR 3.19. These days, inexpensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation, cell constant GRR Greek letter kappa 3.20. The conductivity of solutions of different electrolytes in the same solvent and at a given temperature differs due to charge and size of the Fig. 3.5. Arrangement for measurement of resistance of a solution of an electrolyte. 79 Electrochemistry. Ions in which they dissociate, the concentration of ions or ease with which the ions move under a potential gradient. It, therefore, becomes necessary to define a physically more meaningful quantity called molar conductivity denoted by the symbol Greek, lambda. It is related to the conductivity of the solution by the equation, molar conductivity MC Greek letter kappa 3.21 in the above equation. If Greek letter kappa is expressed in SM1 and the concentration, C in mol N3, then the units of mol in SM2 mol 1. It may be noted that 1 mol N3 1000 LM3 x molarity mol L, and hence SCM2 mol 1 Greek letter kappa 131 SCM 1000 LM x molarity mol L if we use SCM1 as the units for Greek letter kappa and mol CM3. the units of concentration, than the units for mR SCM2 mol 1. It can be calculated by using the equation SCM2 mol 113 SCMX 1000 cm L molarity mol L Greek letter kappa. Both type of units are used in literature and are related to each other by the equations 1 SM2 mol 1 104 SCM2 mol 1 or 1 SCM2 mol 110-4 SM2 mol 1. Resistance of a conductivity cell filled with 0.1 mol L1 KCl solution is 100 Greek letter omega. If the resistance of the same cell when filled with 0.02 mol L1 KCl solution is 520 Greek letter omega, calculate the conductivity and molar conductivity of 0.02 mol L1 KCl solution. The conductivity of 0.1 mol L1 KCl solution is 1.29 sm. The cell constant is given by the equation cell constant G conductivity x resistance 1.29 sm x 100 Greek letter omega 129 m1 1.29 cm1 conductivity of 0.02 mol L1 KCl solution cell constant resistance Gr minus 1129 meters 520 Greek letter omega 0.248 sm1 concentration 0.02 mol L1 1000 x 0.02 mol M320 mol M3 molar conductivity MC Greek letter kappa Greek letter lambda minus 3 minus 1 minus 3 248 x 10 SM20 mol M124 x 10-4 SM2 mol 1 alternatively. Greek letter kappa minus 11.29 centimeters 520 Greek letter omega 0.248 x 10-2 SCM1 example 3.4 example 3.4 example 3.4 example 3.4 example 3.4 solution 80 chemistry and Greek letter kappa x 1000 cubic centimeters L1 molarity 1 minus 2 minus 1 3 minus 1 minus 1 0.248 x 10 SCM x 1000 centimeters L 0.02 mol L 124 SCM2 mol 1. The electrical resistance of a column of 0.05 mol L1 NaO solution of diameter 1 centimeters and length 50 centimeters is 5.55 x 103 ohm. Calculate its resistivity, conductivity and molar conductivity. A Greek letter pi r to 3.14 x 0.52 square centimeter 0.785 square centimeter 0.785 x 10-4 m2 L 50 centimeter 0.5 meters L r. A Greek letter rho r Greek letter rho x 325.55 10 0.785 centimeters 50 centimeters y L 87.135 Greek letter omega cm conductivity Greek letter kappa Greek letter rho 1 187.135 SCM 1 0.01148 SCM 1 molar. Conductivity, max 1000 C Greek letter kappa CM3L1 minus 1 3 minus 1 minus 1 0.01148 SCMX 1000 centimeters L 0.05 mol L 229.6 SCM2 mol 1. If we want to calculate the values of different quantities in terms of m instead of cm, Greek letter rho IL 3 minus 425.55 x 10 x 0.785 x 10 meters 0.5 meters Greek letter omega 87.135 x 10-2 Greek letter omega m1 Greek letter kappa Greek letter rho 100 meters 87.135 Greek letter omega 1.148 sm1 and MC Greek letter kappa Greek letter lambda minus 1 minus 3 1.148 sm50 mol m 229.6 x 10-4 sm2 mol 1. Example 3.5 Example 3.5 Example 3.5 Example 3.5 Example 3.5 Solution Capital S O L U T I O N Capital S O L U T I O N Capital S O L U T I O N Capital S O L U T I. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration both for weak and strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between 2 3 4 2 variation of conductivity and molar conductivity with concentration. 81 Electrochemistry platinum electrodes with unit area of cross-section and at a distance of unit length. This is clear from the equation. Ag Greek letter kappa L. Both A and L are unity and their appropriate units in m or cm. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte kept between 2 electrodes, with area of cross-section A and distance of unit length. Therefore, Greek letter kappa Greek letter lambda Greek letter kappa MAL since L1 and AV volume containing 1 mole of electrolyte and Greek letter kappa V 3.22 molar conductivity increases with decrease in concentration. This is because the total volume, V, of solution containing 1 mole of electrolyte also increases. It has been found that decrease in Greek letter kappa on dilution of a solution is more than compensated by increase in its volume. Physically, it means that at a given concentration, can be defined as the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance but having area of cross-section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches zero, the molar conductivity is known as limiting molar conductivity and is represented by the symbol Greek letter lambda degrees m. The variation in with concentration is different. Figure 3.6 for strong and weak electrolytes. Strong electrolytes for strong electrolytes increases slowly with dilution and can be represented by the equation Greek letter lambda degrees m, AC 1/2 3.23. It can be seen that if we plot Fig 3.12 against C12, we obtain a straight line with intercept equal to Greek letter lambda degrees m and slope equal to a. The value of the constant A for a given solvent and temperature depends on the type of electrolyte, that is, the charges on the cation and anion produced on the dissociation of the electrolyte in the solution. Thus, NaCl, KCl2, XO4 are known as 1,1, 2,1 and 2,2 electrolytes respectively. All electrolytes of a particular type have the same value for A. Figure 3.6, molar conductivity versus for acetic acid weak electrolyte and potassium chloride strong electrolyte in aqueous solutions. The molar conductivity of KCl solutions at different concentrations at 298 K are given below. C mol L1 Greek letter lambda Greek letter lambda Greek letter lambda SCM 2 mol 10.000198148 148.610.0003009 148.290.000521147.810 00098914709 show that a plot between min C12 is a straight line. Determine the values of Greek letter lambda degrees m and A for KCl. Taking the square root of concentration we obtain C12 mol L112 Greek letter lambda SCM2 mol 10.01407 148.610.01758 148.290.02283 147.810.03145 147.09. A plot of y-axis and C12 x-axis is shown in Fig 3.7. It can be seen that it is nearly a straight line. From the intercept C120, we find that Greek letter lambda degrees m 150.0 SCM2 mol 1 and A slope 87.46 SCM2 mol 1 mol L112. Example 3.6 Example 3.6 Example 3.6 Example 3.6 Example 3.6 Solution Fig 3.7. Variation of M against K. 83 Electrochemistry Kohlrausch examined Greek letter lambda degrees m values for a number of strong electrolytes and observed certain regularities. He noted that the difference in Greek letter lambda degrees m of the electrolytes NaX and Kx for any X is nearly constant. For example, at 298 K, Greek letter lambda degrees m KCl Greek letter lambda degrees m NaCl Greek letter lambda degrees m KBr Greek letter lambda degrees m NaBr Greek letter lambda degrees m Ki Greek letter lambda degrees m NaY 23.4 SCM2 mol 1 and similarly it was found that Greek letter lambda degrees m NaBr Greek letter lambda degrees m NaCl Greek letter lambda degrees m KBr Greek letter lambda degrees m KCl Y 1.8 SCM2 mol 1. On the basis of the above observations he enunciated Kohlrausch law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Thus, if Greek letter lambda degrees Na and Greek letter lambda degrees Cl are limiting molar conductivity of the sodium and chloride ions respectively, then the limiting molar conductivity for sodium chloride is given by the equation Greek letter lambda degrees m NaCl Greek letter lambda degrees Na Greek letter lambda degrees Cl 3.24 in general. If an electrolyte on dissociation gives Greek letter nu cations and Greek letter nu anions, then its limiting molar conductivity is given by Greek letter lambda degrees m Greek letter nu Greek letter lambda degrees Greek letter nu Greek letter lambda degrees 3.25 here. Greek letter lambda degrees and Greek letter lambda degrees are the limiting molar conductivities of the cation and anion respectively. The values of Greek letter lambda degrees for some cations and anions at 298 K are given in table 3.4. Table 3.4, limiting molar conductivity for some ions in water at 298 K. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentrations, and hence for such electrolytes, the change in with dilution is due to increase in the degree of dissociation and consequently the number of ions and total volume of solution that contains 1 mole of electrolyte. In such cases M increases steeply. Figure 3.12 on dilution, especially near lower concentrations. Therefore, Greek letter lambda degrees M cannot be obtained by extrapolation of M to zero concentration. At infinite dilution, that is, concentration C0, electrolyte dissociates completely. Greek letter alpha 1, but at such low concentration the conductivity of the solution is so low that it cannot be measured accurately. Therefore, Greek letter lambda degrees M for weak electrolytes is obtained by using Kohlrausch law of independent migration of ions. Example 3.8. At any concentration C, if Greek letter alpha is the degree of dissociation ion Greek letter lambda 0 SCM 2 mol 1 ion Greek letter lambda 0 SCM 2 mol 1 H 349.60 199.1 Na 50.1 Cl 76.3 K 73.5 Br 78.1 Ca 2 119.0 CH 3 COO 40.9 Mg 2 106.0 So 4 2 160.0. Then it can be approximated to the ratio of molar conductivity with the concentration C to limiting molar conductivity, Greek letter lambda 0 meters. Thus we have degrees mm Greek letter lambda alpha Greek letter lambda 3.26, but we know that for a weak electrolyte like acetic acid class I. Unit 7. 222 to 11 meters CCCK Greek letter lambda 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 Greek letter omicron Greek letter omicron Greek letter omicron Greek letter omicron Greek letter alpha 3.27 Applications of Kohlrausch law. Using Kohlrausch law of independent migration of ions, it is possible to calculate Greek letter lambda 0 meters for any electrolyte from the O of individual ions. Moreover, for weak electrolytes like acetic acid it is possible to determine the value of its dissociation constant once we know the Greek letter lambda 0 meters and at a given concentration C. Calculate Greek letter lambda 0 meters for Ca Cl2 and so forth from the data given in Table 3.4. We know from Kohlrausch law that 2 Ca Cl2 Greek letter omicron all Greek letter lambda 119.0 SCM 2 mol 1 276.3 SCM 2 mol 1 119.0 152.6 SCM 2 mol 1 271.6 SCM 2 mol 1 form XOM 2-24 mg. So Greek letter omicron all Greek letter lambda 106.0 SCM 2 mol 1 160.0 SCM 2 mol 1 266 SCM 2 mol 1. Greek letter lambda 0 meters for NaCl, HCl and NiOH are 126.4, 425.9 and 91.0 SCM 2 mol 1 respectively. Calculate Greek letter lambda 0 for HAC. HAC Greek letter omicron all Greek letter lambda HClAc NaCl Na Greek letter omicron 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 Greek letter lambda 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 HCl NiOH NaCl Greek letter lambda low Greek letter omicron 425.9 91.0 to 126.4 SCM 2 mol 1 390.5 SCM 2 mol 1. The conductivity of 0.001028 mol L1 acetic acid is 4.95 x 10-5 SCM1. Calculate its dissociation constant if Greek letter lambda 0 meters for acetic acid is 390.5 SCM2 mol 1. 513149510 SCM 1000 centimeters 0001028 mol LC Greek letter kappa XX 48.15 SCM 3 mol 1 Greek letter alpha Greek letter lambda Greek letter omicron 2121 48.15 SCM mol 390.5 SCM mol mm 0.1233 K. C1 minus 122.0001028 mol 0 1233 1233 Greek letter alpha x 1.78 x 10-5 mol L1 example 3.8 example 3.8 example 3.8 example 3.8 example 3.8 solution example 3.9 example 3.9 example 3.9 example 3.9 example 3.9 solution example 3.7 example 3.7 example 3.7 example 3.7 example 3.7 solution 85 Electrochemistry. In an electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical processes are of great importance in the laboratory and the chemical industry. One of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. If a DC voltage is applied to the two electrodes, then Cu2 ions discharge at the cathode negatively charged and the following reaction takes place. Cu2 Ag2 equals S3.28 copper metal is deposited on the cathode. At the anode, copper is converted into Cu2 ions by the reaction. Cu2S2E3.29 thus copper is dissolved oxidized at anode and deposited reduced at cathode. This is the basis for an industrial process in which impure copper is converted into copper of high purity. The impure copper is made an anode that dissolves on passing current and pure copper is deposited at the cathode. Many metals like Na, Mg, Al, etc. are produced on large scale by electrochemical reduction of their respective cations where no suitable chemical reducing agents are available for this purpose. Sodium and magnesium metals are produced by the electrolysis of their fused chlorides and aluminium is produced class 12, unit 6 by electrolysis of aluminium oxide in presence of chrylite. Quantitative aspects of electrolysis. Michael Faraday was the first scientist who described the quantitative aspects of electrolysis. Now Faraday's laws also flow from what has been discussed earlier, Faraday's laws of electrolysis after his extensive investigations on electrolysis of solutions and melts of electrolytes. Faraday published his results during 1833-34 in the form of the following well-known Faraday's two laws of electrolysis. First law, the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte solution or melt. Second law, the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights atomic mass of metal % number of electrons required to reduce the cation. 3.53 capital E, L, E, C, T, R, O, L, Y, T, I, C, capital E, L, E, C, T, R, O, L, Y, T, I, C, capital E, L, E, C, T, R, cells and cells and cells and cells and cells and, capital E, L, E, C, T, R, O, L, Y, S, I, S, capital E, L, E, C, T, R, O, L, Y, S, I, S, capital E, L, E, C, T, R. In text questions and text questions and text questions and text questions and text questions 3.7 Why does the conductivity of a solution decrease with dilution? 3.8 Suggest a way to determine the Greek letter lambda degrees m value of water. 3.9 The molar conductivity of 0.025 mol L1 methanoic acid is 46.1 ScM2 mol 1. Calculate its degree of dissociation and dissociation constant. Given Greek letter lambda 0H349.6 ScM2 mol 1 and Greek letter lambda 0HCOO 54.6 ScM2 mol 1. 86 Chemistry. There were no constant current sources available during Faraday's times. The general practice was to put a coulometer, a standard electrolytic cell for determining the quantity of electricity passed from the amount of metal, generally silver or copper, deposited or consumed. However, coulometers are now obsolete and we now have constant current I sources available and the quantity of electricity Q passed is given by Q. A Q is in coulombs when I is in ampere and T is in second. The amount of electricity or charge required for oxidation or reduction depends on the stoichiometry of the electrode reaction. For example, in the reaction, Ag-Ag 3.301 mol of the electron is required for the reduction of 1 mol of silver ions. We know that charge on one electron is equal to 1.6021 x 10-19 C, therefore, the charge on 1 mole of electrons is equal to NaX 1.6021 x 10-19 C 6.02 x 1023 mol 1 x 1.6021 x 10-19 C 96,487 C mol 1. This quantity of electricity is called Faraday and is represented by the symbol F. For approximate calculations we use 1 Fy 96,500 C mol 1. For the electrode reactions, Mg2L2E Mgs 3.31 Al3 L3E Ls 3.32 it is obvious that 1 mol of Mg2 and Al3 require 2 mol of electrons 2F and 3 mol of electrons 3F respectively. The charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and time in seconds. In commercial production of metals, current as high as 50,000 amperes are used that amounts to about 0.518 F per second. A solution of QSO4 is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at the cathode? T600S charge current X time 1.5 AX 600S 900C. According to the reaction, Cu2Ac2 equals we require 2F or 2X 96,487C to deposit 1 mole or 63 grams of Cu. For 900C, the mass of Cu deposited 63 grams mole 1x 900C 2x 96,487C mole 1 0.2938 grams. Example 3.10 Example 3.10 Example 3.10 Example 3.10 Example 3.10 Solution Products of electrolysis depend on the nature of material being electrolyzed and the type of electrodes being used. If the electrode is inert, e.g., platinum or gold, it does not participate in the chemical reaction and acts only as source or sink for electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction. Thus, the products of electrolysis may be different for reactive and inert. 3.5.1 Products of electrolysis. 87 Electrochemistry electrodes. The products of electrolysis depend on the different oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Moreover, some of the electrochemical processes, although feasible, are so slow kinetically that at lower voltages these do not seem to take place and extra potential called overpotential has to be applied, which makes such process more difficult to occur. For example, if we use molten NaCl, the products of electrolysis are sodium metal and Cl2 gas. Here we have only one cation Na which is reduced at the cathode Na and one anion Cl which is oxidized at the anode Cl2e. During the electrolysis of aqueous sodium chloride solution, the products are NaO, Cl2 and H2. In this case, besides Na and Cl ions we also have H and O ions along with the solvent molecules. H2O. At the cathode there is competition between the following reduction reactions: NaAc Na S cell Ve 2.71 VH Ac 1/2 H2G cell Ve 0.00 V. The reaction with higher value of Ej is preferred and therefore, the reaction at the cathode during electrolysis is HAc 1/2 H2G 3.33 but HAc is produced by the dissociation of H2O, that is, H2OLHACOAC 3.34. Therefore, the net reaction at the cathode may be written as the sum of 3.33 and 3.34 and we have H2OLU2GO 3.35 at the anode. The following oxidation reactions are possible: ClAc 1/2 Cl2GE cell Ve 1.36 V 3.362 H2OLO2G 4 HAc 4E cell Ve 1.23 V 3.37. The reaction at anode with lower value of Ej is preferred and therefore, water should get oxidized in preference to ClAc. However, on account of overpotential of oxygen, reaction 3.36 is preferred. Thus, the net reactions may be summarized as NaClAc HO2 NaAc ClAc cathode, H2OLE 1/2 H2GOAc anode, ClAc 1/2 Cl2GE net reaction, NaClAc H2OL NaAc OAc O2G Cl2G. The standard electrode potentials are replaced by electrode potentials given by Nernst equation EC. 3.8 To take into account the concentration effects, during the electrolysis of sulfuric acid, the following processes are possible at the anode: 2H2OLO2G4 HAc 4E cell V 1.23 V 3.38. 88 Chemistry 2SO4 2Ac S2O8 2Ac 2E cell V 1.96 V 3.39 for dilute sulfuric acid. Reaction 3.38 is preferred but at higher concentrations of H2SO4, reaction 3.39 is preferred. Any battery actually it may have one or more than one cell connected in series or cell that we use as a source of electrical energy is basically a galvanic cell where the chemical energy of the redox reaction is converted into electrical energy. However, for a battery to be of practical use it should be reasonably light, compact and its voltage should not vary appreciably during its use. There are mainly two types of batteries. In the primary batteries, the reaction occurs only once and after use over a period of time battery becomes dead and cannot be reused again. The most familiar example of this type is the dry cell known as Leclanche cell after its discoverer, which is used commonly in our transistors and clocks. The cell consists of a zinc container that also acts as anode and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon figure 3.8. The space between the electrodes is filled by a moist paste of ammonium chloride NH4Cl and zinc chloride ZnCl2. The electrode reactions are complex, but they can be written approximately as follows: anode, ZnSCN22E cathode, MnO2NH4E MnOONH3 in the reaction at cathode. Manganese is reduced from the 4-oxidation state to the 3-state. Ammonia produced in the reaction forms a complex with Zn2 to give ZnNH342. The cell has a potential of nearly 1.5 V. Mercury cell, Figure 3.9 suitable for low-current devices like hearing aids, watches, etc. Consists of zinc-mercury amalgam as anode and a paste of HgO and carbon as the cathode. The electrolyte is a paste of coenzyano. The electrode reactions for the cell are given below. Anode, ZnHg2O ZnOSH2O2e cathode, HgOH2O2e HgL2O 3.6 batteries 3.6 batteries 3.6 batteries 3.6 batteries 3.6 batteries 3, 6, 1 primary batteries Fig. 3.8. A commercial dry cell consists of a graphite carbon cathode in a zinc container. The latter acts as the anode. In text questions 3.10 if a current of 0.5 ampere flows through a metallic wire for 2 hours. Then how many electrons would flow through the wire? 3.11 suggest a list of metals that are extracted electrolytically. 3.12 Consider the reaction. Cr2O7214H6E2Cr37H2O. What is the quantity of electricity in coulombs needed to reduce 1 mole of Cr2O72? 89 Electrochemistry Figure 3.10. The lead storage battery. The overall reaction is represented by CnHgHgOSCnOSHgl. The cell potential is approximately 1.35 V and remains constant during its life as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage battery Fig. 3.10 Commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with lead dioxide PbO2 as cathode. A 38 solution of sulfuric acid is used as an electrolyte. The cell reactions when the battery is in use are given below. Anode, PbSO42 ActSO4S2e cathode, PbO2SO42 Ac4H Ac2e PbSO4S2H2OL. That is. Overall cell reaction consisting of cathode and anode reactions is PbS PbO2S2H2 SO4 Ac2 PbSO4S2H2OL. On charging the battery the reaction is reversed and PbSO4S on anode and cathode is converted into Pb and PbO2, respectively. Figure 3.9 Commonly used mercury cell. The reducing agent is zinc and the oxidizing agent is mercury 2 oxide. 3, 6, 2 secondary batteries. 90 Chemistry Positive plate separator negative plate. Another important secondary cell is the nickel-cadmium cell Fig. 3.11 which has longer life than the lead storage cell but more expensive to manufacture. We shall not go into details of working of the cell and the electrode reactions during charging and discharging. The overall reaction during discharges, CdS2NeO3SCDOS2NeO2SH2OL. Production of electricity by thermal plants is not a very efficient method and is a major source of pollution. In such plants, the chemical energy heat of combustion of fossil fuels coal, gas or oil is first used for converting water into high-pressure steam. This is then used to run a turbine to produce electricity. We know that a galvanic cell directly converts chemical energy into electricity and is highly efficient. It is now possible to make such cells in which reactants are fed continuously to the electrodes and products are removed continuously from the electrolyte compartment. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. One of the most successful fuel cells uses the reaction of hydrogen with oxygen to form water Fig. 3.12. The cell was used for providing electrical power in the Apollo space program. The water vapors produced during the reaction were condensed and added to the drinking water supply for the astronauts. In the cell, hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous sodium hydroxide solution. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of electrode reactions. The electrode reactions are given below. Cathode, O2G2H2OL4E4O anode, 2H2G4OAC4H2OL4E. Overall reaction being 2H2GO2G2H2OL. The cell runs continuously as long as the reactants are supplied. Fuel cells produce electricity with an efficiency of about 70 compared. Figure 3.11. A rechargeable nickel-cadmium cell in a jelly roll arrangement and separated by a layer soaked in moist sodium or potassium hydroxide. 3.7 Fuel cells 3.7 Fuel cells 3.7 Fuel cells 3.7 Fuel cells 3.7 Fuel cells. Figure 3.12. Fuel cell using H2 and O2 produces electricity. 91 Electrochemistry Fig. 3.13. Corrosion of iron in atmosphere oxidation. Fe2 Ac2E reduction. O2G4H Ac4E2H2OL atmospheric oxidation. 2Fe2 Ac2H2OL O2G Fe2O3S4H Actothermal plants whose efficiency is about 40. There has been tremendous progress in the development of new electrode materials, better catalysts and electrolytes for increasing the efficiency of fuel cells. These have been used in automobiles on an experimental basis. Fuel cells are pollution-free, and in view of their future importance, a variety of fuel cells have been fabricated and tried. Corrosion slowly coats the surfaces of metallic objects with oxides or other salts of the metal. The rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some of the examples of corrosion. It causes enormous damage to buildings, bridges, ships and to all objects made of metals, especially that of iron. We lose crores of rupees every year on account of corrosion. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxides. Corrosion of iron, commonly known as rusting, occurs in presence of water and air. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomenon. At a particular spot, figure 3.13 of an object made of iron. Oxidation takes place and that spot behaves as anode, and we can write the reaction anode. 2Fe2Fe242Fe VE0.44. The electrons released at anodic spot move through the metal and go to another spot on the metal and reduce oxygen in the presence of H, which is believed to be available from H2CO3 formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. This spot behaves as cathode with the reaction cathode. O2G4H Ac4E2H2OL22HOHO1.23 VeV. The overall reaction being 2Fe O2G4H Ac2Fe2 cell VE 1.67 V. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which come out as rust in the form of hydrated ferric oxide Fe2O3. XH2O. With further production of hydrogen ions, prevention of corrosion is of prime importance. It not only saves money but also helps in preventing accidents such as a bridge collapse or failure of a key component due to corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of the metallic object to come in contact with atmosphere. This can be done by covering the surface with paint or by some chemicals, e.g. bisphenol. Another simple method is to cover the surface by other metals Sn, Zn, etc. that are inert or react to save the object. An electrochemical method is to provide a sacrificial electrode of another metal like Mg, Zn, etc. which corrodes itself but saves the object. 3.83, 83, 83, 83, 8 Corrosion 92 Chemistry. The hydrogen economy. 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 At present, the main source of energy that is driving our economy is fossil fuels such as coal, oil and gas. As more people on the planet aspire to improve their standard of living, their energy requirement will increase. In fact, the per capita consumption of energy used is a measure of development. Of course, it is assumed that energy is used for productive purpose and not merely wasted. We are already aware that carbon dioxide produced by the combustion of fossil fuels is resulting in the greenhouse effect. This is leading to a rise in the temperature of the Earth's surface, causing polar ice to melt and ocean levels to rise. This will flood low-lying areas along the coast, and some island nations such as Maldives face total submergence. In order to avoid such a catastrophe, we need to limit our use of carbonaceous fuels. Hydrogen provides an ideal alternative as its combustion results in water only. Hydrogen production must come from splitting water using solar energy. Therefore, hydrogen can be used as a renewable and non-polluting source of energy. This is the vision of the hydrogen economy. Both the production of hydrogen by electrolysis of water and hydrogen combustion in a fuel cell will be important in the future. And both these technologies are based on electrochemical principles. In text questions 3.13 write the chemistry of recharging the lead storage battery. Highlighting all the materials that are involved during recharging. 3.14 suggest 2 materials other than hydrogen that can be used as fuels in fuel cells. 3.15 Explain how rusting of iron is envisaged as setting up with an electrochemical cell. Summary. An electrochemical cell consists of 2 metallic electrodes dipping in electrolytic solution S. Thus, an important component of the electrochemical cell is the ionic conductor or electrolyte. Electrochemical cells are of 2 types. In galvanic cell, The chemical energy of a spontaneous redox reaction is converted into electrical work, whereas in an electrolytic cell, electrical energy is used to carry out a non-spontaneous redox reaction. The standard electrode potential for any electrode dipping in an appropriate solution is defined with respect to standard electrode potential of hydrogen electrode taken as 0. The standard potential of the cell can be obtained by taking the difference of the standard potentials of cathode and anode cell VEV cathode, IV anode. The standard potential of the cells are related to standard Gibbs energy RGV-NF cell VE and equilibrium constant RGV-RTLNK of the reaction taking place in the cell. Concentration dependence of the potentials of the electrodes and the cells are given by Nernst equation. The conductivity, Greek letter kappa, of an electrolytic solution depends on the concentration of the electrolyte, nature of solvent and temperature. Molar conductivity is defined by Greek letter kappa C, where C is the concentration. Conductivity decreases but molar conductivity increases with decrease in concentration. It increases slowly with decrease in concentration for strong electrolytes, while the increase is very steep for weak electrolytes in very dilute solutions. Kohlrausch found that molar conductivity at infinite dilution, for an electrolyte, is sum of the contribution of the 93 electrochemistry molar conductivity of the ions in which it dissociates. It is known as law of independent migration of ions and has many applications. Ions conduct electricity through the solution, but oxidation and reduction of the ions take place at the electrodes in an electrochemical cell. Batteries and fuel cells are very useful forms of galvanic cell. Corrosion of metals is essentially an electrochemical phenomenon. Electrochemical principles are relevant to the hydrogen economy. 3. Chemistry, by its very nature, is concerned with change. Substances with well-defined properties are converted by chemical reactions into other substances with different properties. For any chemical reaction, chemists try to find out the feasibility of a chemical reaction which can be predicted by thermodynamics, as you know that a reaction with G0 at constant temperature and pressure is feasible. The extent to which a reaction will proceed can be determined from chemical equilibrium. See speed of a reaction, that is, time taken by a reaction to reach equilibrium, along with feasibility and extent. It is equally important to know the rate and the factors controlling the rate of a chemical reaction for its complete understanding. For example, which parameters determine as to how rapidly food gets spoiled, how to design a rapidly setting material for dental filling, or what controls the rate at which fuel burns in an auto engine. All these questions can be answered by the branch of chemistry which deals with the study of reaction rates and their mechanisms, called chemical kinetics. The word kinetics is derived from the Greek word kinesis, meaning movement. Thermodynamics tells only about the feasibility of a reaction, whereas chemical kinetics tells about the rate of a reaction. For example, thermodynamic data indicate that diamond shall convert to graphite, but in reality the conversion rate is so slow that the change is not perceptible at all. Therefore, most people think after studying this unit, you will be able to define the average and instantaneous rate of a reaction, express the rate of a reaction in terms of change in concentration of either of the reactants or products with time, distinguish between elementary and complex reactions, differentiate between the molecularity and order of a reaction, define rate constant, discuss the dependence of rate of reactions on concentration, temperature and catalyst, derive integrated rate equations for the zero and first order reactions, determine the rate constants for zeroth and first order reactions, describe collision theory. Objectives. Chemical kinetics helps us to understand how chemical reactions occur. For chemical kinetics, unit 4 chemical kinetics. That diamond is forever. Kinetic studies not only help us to determine the speed or rate of a chemical reaction, but also describe the conditions by which the reaction rates can be altered. The factors such as concentration, temperature, pressure and catalyst affect the rate of a reaction. At the macroscopic level, we are interested in amounts reacted or formed and the rates of their consumption or formation. At the molecular level, the reaction mechanisms involving orientation and energy of molecules undergoing collisions are discussed. In this unit, we shall be dealing with average and instantaneous rate of reaction and the factors affecting these. Some elementary ideas about the collision theory of reaction rates are also given. However, in order to understand all these, let us first learn about the reaction rate. Some reactions such as ionic reactions occur very fast. For example, precipitation of silver chloride occurs instantaneously by mixing of aqueous solutions of silver nitrate and sodium chloride. On the other hand, some reactions are very slow. For example, rusting of iron in the presence of air and moisture. Also, there are reactions like inversion of cane sugar and hydrolysis of starch, which proceed with a moderate speed. Can you think of more examples from each category? You must be knowing that speed of an automobile is expressed in terms of change in the position or distance covered by it in a certain period of time. Similarly, the speed of a reaction or the rate of a reaction can be defined as the change in concentration of a reactant or product in unit time. To be more specific, it can be expressed in terms of either rate of decrease in concentration of any one of the reactants, or to the rate of increase in concentration of any one of the products. Consider a hypothetical reaction. Assuming that the volume of the system remains constant, Rp 1 mole of the reactant R produces 1 mole of the product P. If R1 and P1 are the concentrations of R and P respectively at time T1 and R2 and P2 are their concentrations at time T2, then T2 T1 R2 R1 P P2 P1. The square brackets in the above expressions are used to express molar concentration. Rate of disappearance of R, decrease in concentration of R time taken T 4.14.14 1 rate of a chemical reaction rate of appearance of P, increase in concentration of PP time taken T 4.2. Since R is a negative quantity as concentration of reactants is decreasing, it is multiplied with -1 to make the rate of the reaction a positive quantity. Equations 4.1 and 4.2 given above represent the average rate of a reaction, RAV. Average rate depends upon the change in concentration of reactants or products and the time taken for that change to occur. Fig. 4.1. Figure 4.1. Instantaneous and average rate of a reaction. Units of rate of a reaction from equations 4.1 and 4.2. It is clear that units of rate are concentration time 1. For example, if concentration is in mol/1 and time is in seconds, then the units will be mol/1 s1. However, in gaseous reactions, when the concentration of gases is expressed in terms of their partial pressures, then the units of the rate equation will be atms1. From the concentrations of C4H9Cl butyl chloride at different times given below, calculate the average rate of the reaction, C4H9Cl H2O C4H9OHCl during different intervals of time. TS 0, 50, 100, 150, 200, 300, 400, 700, 800 C4H9Cl mol/1 0.100 0.09050.08200.07410.06710.05490.04390.04390.04439 0.02100.017. We can determine the difference in concentration over different intervals of time and thus determine the average rate by dividing R by T. Table 4.1. Example 4.1 Example 4.1 Example 4.1 Example 4.1 Example 4.1 Solution. It can be seen Table 4.1 that the average rate falls from 1.90 x 04 mol/1 s1 to 0.4 x 10 mol/1 s1. However, average rate cannot be used to predict the rate of a reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So, to express the rate at a particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, say dt, that is, when t approaches 0. Hence, mathematically, for an infinitesimally small dt, instantaneous rate is given by AVRPRTT 4.3 as T0 or inst DDRPDDRTT. Table 4.1. Average rates of hydrolysis of butyl chloride C4H9CiT1 C4H9CiT2 T1S T2 SRFX 104 mol/1 S1 mol/1 mol/1 X2 144949921 TTCHCl CHCl TT 10 0.100 0.0905051.90 0.09050.082050101.70 0.0820 0.0741 100 151.58 0.0741 0.0671 150 201.40 0.0671 0.0549 200 301.22 0.0549 0.0439 300 401.10 0.0439 0.0335 400 501.040 0.0210 0.017 700 800 0.4 Figure 4.2 Instantaneous rate of hydrolysis of butyl chloride C4H9Cl. It can be determined graphically by drawing a tangent at time t on either of the curves for concentration of R and P versus time t and calculating its slope. Fig. 4.1. So in problem 4.1, rinsed at 600 S, for example, can be calculated by plotting concentration of butyl chloride as a function of time. A tangent is drawn that touches the curve at T600 as figure 4.2. The slope of this tangent gives the instantaneous rate. So, rinsed at 600 s molal 1 5.12 x 10-5 molal 1 s1 at T250 s rinsed 1.22 x 10-4 molal 1 s1 T350 s rinsed 1.0 x 10-4 molal 1 s1 T450 s rinsed 6.4 x 10-5 molal 1 s1. Now consider a reaction HglCl2GHgCl2s where stoichiometric coefficients of the reactants and products are same. Then rate of the reaction is given as 2,2-HgCl rate of reaction TTT, that is, rate of disappearance of any of the reactants is same as the rate of appearance of the products. But in the following reaction, 2 moles of Hi decompose to produce 1 mole each of H2 and I2, 2 Hi GH2G I2G. For expressing the rate of such a reaction where stoichiometric coefficients of reactants or products are not equal to 1. Rate of disappearance of any of the reactants or the rate of appearance of products is divided by their respective stoichiometric coefficients. Since rate of consumption of Hi is twice the rate of formation of H2 or I2, to make them equal, the term Hi is divided by 2. The rate of this reaction is given by rate of reaction 2,2-Hi1 Hi 2TTT. Similarly, for the reaction 5Br Ac-Bro 3 Ac6 H-Ac3 Br2 Ac3 H2OL rate Br Bro H Br H1 516131332 TTT for a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of a species, and hence, rate can also be expressed as rate of change in partial pressure of the reactant or the product. 100 Chemistry in text questions 4.1 For the reaction Rp, the concentration of a reactant changes from 0.03 m to 0.02 m in 25 minutes. Calculate the average rate of reaction using units of time both in minutes and seconds. 4.2 In a reaction, 2A products, the concentration of A decreases from 0.5 molal 1 to 0.4 molal 1 in 10 minutes. Calculate the rate during this interval. Rate of reaction depends upon the experimental conditions such as concentration of reactants, pressure in case of gases, temperature and catalyst. The rate of a chemical reaction at a given temperature may depend on the concentration of one or more reactants and products. The representation of rate of reaction in terms of concentration of the reactants is known as rate law. It is also called as rate equation or rate expression. The results in Table 4.1 clearly show that rate of a reaction decreases with the passage of time as the concentration of reactants decrease. Conversely, rates generally increase when reactant concentrations increase, so, rate of a reaction depends upon the concentration of reactants. Example 4.2 Example 4.2 Example 4.2 Example 4.2 Example 4.24 2. Rate expression and rate constant. The decomposition of N2O5 in CCl4 at 318 K has been studied by monitoring the concentration of N2O5 in the solution. Initially the concentration of N2O5 is 2.33 molal 1 and after 184 minutes, it is reduced to 2.08 molal 1. The reaction takes place according to the equation 2N2O5G4 number 2GO2G. Calculate the average rate of this reaction in terms of hours, minutes and seconds. What is the rate of production of number 2 during this period? Average rate 121220823318425 NO mol T. Full stop. Min 6.79 x 10-4 molal 1 minutes 6.79 x 10-4 molal 1 minutes 1 x 60 minutes 1 h 4.07 x 10-2 molal 1 h 6.79 x 10-4 molal 1 x 1 minute 60s 1.13 x 10-5 molal 1 s1. It may be remembered that rate no 142 t2 no t 6.79 x 10-4 x 4 molal 1 minutes 1 2.72 x 10-3 molal 1 minutes 1 solution. Capital S O L U T I O N capital S O L U T I O N capital S O L U T I O N capital S O L U T I 4 24 24 24 24 2 factors influencing factors influencing factors influencing factors influencing factors influencing rate of a reaction 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 4 2 1 dependence of rate on concentration. 101 Chemical Kinetics. Consider a general reaction AABBCCDD where A, B, C and D are the stoichiometric coefficients of reactants and products. The rate expression for this reaction is rate AXBY 4.4 where exponents x and y may or may not be equal to the stoichiometric coefficients A and B of the reactants. Above equation can also be written as rate KAXBY 4.4 exit RABDKT 4.4b. This form of equation 4.4b is known as differential rate equation, where K is a proportionality constant called rate constant. The equation like 4.4, which relates the rate of a reaction to concentration of reactants, is called rate law or rate expression. Thus, rate law is the expression in which reaction rate is given in terms of molar concentration of reactants with each term raised to some power, which may or may not be same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. For example, 2NO-GO2G2 number 2G. We can measure the rate of this reaction as a function of initial concentrations, either by keeping the concentration of one of the reactants constant and changing the concentration of the other reactant, or by changing the concentration of both the reactants. The following results are obtained. Table 4.2. Table 4.2. Initial rate of formation of number 2 experiment. Initial No molal 1 initial O2 molal 1 initial rate of formation of number 2 molal 1 S11 0.30 0.30 0.0962 0.60 0.30 0.384 3 0.30 0.60 0.192 4 0.60 0.60 0.768. It is obvious, after looking at the results, that when the concentration of NO is doubled and that of O2 is kept constant, then the initial rate increases by a factor of 4 from 0.096 to 0.384 molal 1 S1. This indicates that the rate depends upon the square of the concentration of NO. When concentration of NO is kept constant and concentration of O2 is doubled, the rate also gets doubled, indicating that rate depends on concentration of O2 to the first power. Hence, the rate equation for this reaction will be rate K number 2 O2. 102 Chemistry. The differential form of this rate expression is given as 2,2 now. We observe that for this reaction in the rate equation derived from the experimental data, the exponents of the concentration terms are the same as their stoichiometric coefficients in the balanced chemical equation. Some other examples are given below. Reaction experimental rate expression 1, CHCl3Cl2CCl4HCl rate KCHCl3Cl2122. CH3 cook 2H5H2O CH3 Cu C2H5O rate KCH3 cook 2H51H2O0. In these reactions, the exponents of the concentration terms are not the same as their stoichiometric coefficients. Thus, we can say that rate law for any reaction cannot be predicted by merely looking at the balanced chemical equation, that is, theoretically, but must be determined experimentally. In the rate equation 4.48, KAXBY X and Y indicate how sensitive the rate is to the change in concentration of A and B. Some of these exponents, that is, XY in 4.4 gives the overall order of a reaction, whereas X and Y represent the order with respect to the reactants A and B respectively. Hence, the sum of powers of the concentration of the reactants in the rate law expression is called the order of the chemical reaction. Order of a reaction can be 0, 1, 2, 3 and even a fraction. A zero-order reaction means that the rate of reaction is independent of the concentration of reactants. 4, 2, 3 order of a reaction. Calculate the overall order of a reaction which has the rate expression rate Ka12b32b rate Ka32b-1 or rate Kaxby order XY, so order 1 2 3 2 2, that is, second order B order 3 2 -1 1 2, that is, half order. Example 4.3 Example 4.3 Example 4.3 Example 4.3 Example 4.3 Solution. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. The reactions taking place in one step are called elementary reactions. When a sequence of elementary reactions called mechanism gives us the products, the reactions are called complex reactions. 103 Chemical kinetics. Example 4.4 Example 4.4 Example 4.4 Example 4.4 Example 4.4 Solution. These may be consecutive reactions, e.g. oxidation of ethane to CO2 and H2O passes through a series of intermediate steps in which alcohol, aldehyde and acid are formed. Reverse reactions and side reactions, e.g. nitration of phenol yields O-nitrophenol and P-nitrophenol. Units of rate constant for a general reaction AABBCCDD rate KAXBY, where XYN order of the reaction, KX rate ABYN concentration 1X, where AB time concentration taking SI units of concentration, mole L1 and time, S. The units of K for different reaction order are listed in Table 4.3. Table 4.3. Units of rate constant reaction order. Units of rate constant 0 order reaction 0111101 mol 1 mol SS mol X first order reaction 11111 mol 1 SS mol X second order reaction 211121 mol 1 mol LSS mol X. Identify the reaction order from each of the following rate constants. IK 2.3 x 10-5 L mol 1 S1 2K 3 x 10-4 S1 I. The unit of second order rate constant is L mol 1 S1, therefore K 2.3 x 10-5 L mol 1 S1 represents a second order reaction. 2. The unit of a first order rate constant is S1, therefore K 3 x 10-4 S1 represents a first order reaction. 4. 2. For molecularity of a reaction. Another property of a reaction called molecularity helps in understanding its mechanism. The number of reacting species atoms, ions or molecules taking part in an elementary reaction, which must collide simultaneously in order to bring about a chemical reaction, is called molecularity of a reaction. The reaction can be unimolecular when one reacting species is involved, for example, decomposition of ammonium nitrite. 104 Chemistry NH4 number 2N22H2O. Bimolecular reactions involve simultaneous collision between two species, for example, dissociation of hydrogen iodide. 2H2I2 Trimolecular or termolecular reactions involve simultaneous collision between three reacting species. For example, 2NO2 number 2. The probability that more than three molecules can collide and react simultaneously is very small. Hence, reactions with the molecularity 3 are very rare and slow to proceed. It is, therefore, evident that complex reactions involving more than three molecules in the stoichiometric equation must take place in more than one step. KClO3 6-PeSO4 3H2SO4 KCl3 Fe2SO4 3H2O. This reaction, which apparently seems to be of 10th order, is actually a second-order reaction. This shows that this reaction takes place in several steps. Which step controls the rate of the overall reaction? The question can be answered if we go through the mechanism of reaction. For example, chances to win the relay race competition by a team depend upon the slowest person in the team. Similarly, the overall rate of the reaction is controlled by the slowest step in a reaction called the rate-determining step. Consider the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in an alkaline medium. 2H2O2I alkaline medium 2H2OO2. The rate equation for this reaction is found to be 2,2,2,2 rate HOI/dKt. This reaction is first order with respect to both H2O2 and I. Evidences suggest that this reaction takes place in two steps: 1H2O2I H2OIO2 H2O2IO H2OIO2. Both the steps are bimolecular elementary reactions. Species IO is called as an intermediate since it is formed during the course of the reaction but not in the overall balanced equation. The first step, being slow, is the rate-determining step. Thus, the rate of formation of intermediate will determine the rate of this reaction. Thus, from the discussion, till now, we conclude the following. I order of a reaction is an experimental quantity. It can be 0 and even a fraction, but molecularity cannot be 0 or a non-integer. 2 order is applicable to elementary as well as complex reactions, whereas molecularity is applicable only for elementary reactions. For complex reaction, molecularity has no meaning. 105 Chemical kinetics 3 For complex reaction, order is given by the slowest step and molecularity of the slowest step is same as the order of the overall reaction. In text questions 4.3 for a reaction, AB product, the rate law is given by RKA12B2. What is the order of the reaction? 4.4 The conversion of molecules X to Y follows second-order kinetics. If concentration of X is increased to 3 times, how will it affect the rate of formation of Y? We have already noted that the concentration dependence of rate is called differential rate equation. It is not always convenient to determine the instantaneous rate, as it is measured by determination of slope of the tangent at point T and concentration versus time plot Fig. 4.1. This makes it difficult to determine the rate law and hence the order of the reaction. In order to avoid this difficulty, we can integrate the differential rate equation to give a relation between directly measured experimental data, that is, concentrations at different times and rate constant. The integrated rate equations are different for the reactions of different reaction orders. We shall determine these equations only for 0 and first-order chemical reactions. 0-order reaction means that the rate of the reaction is proportional to 0 power of the concentration of reactants. Consider the reaction. Rp rate 0 drr dkt as any quantity raised to power 0 is unity rate dr1 dkxt drk dt integrating both sides rkti 4.5 where I is the constant of integration. At T0, the concentration of the reactant RR0, where R0 is initial concentration of the reactant. Substituting in equation 4.5 R0 kx0 I R0 I substituting the value of I in the equation 4.5 R kt R0 4.64.34 integrated rate equations 4 3 1 0 order reactions. 106 Chemistry Figure 4.3, Variation in the concentration versus time plot for a zero-order reaction time K-slope concentration of RR00 comparing 4.6 with equation of a straight line. YMXC, if we plot R against T, we get a straight line figure 4.3 with slope K and intercept equal to R0. Further simplifying equation 4.6, we get the rate constant, K is 0 RRKT 4.70 order reactions are relatively uncommon but they occur under special conditions. Some enzyme-catalyzed reactions and reactions which occur on metal surfaces are a few examples of zero-order reactions. The decomposition of gaseous ammonia on a hot platinum surface is a zero-order reaction at high pressure. 1130 K322 PT catalyst 2NHGNG3HG rate KNH30K in this reaction, platinum metal acts as a catalyst. At high pressure, the metal surface gets saturated with gas molecules, so, a further change in reaction conditions is unable to alter the amount of ammonia on the surface of the catalyst making rate of the reaction independent of its concentration. The thermal decomposition of ion gold surface is another example of zero-order reaction. In this class of reactions, the rate of the reaction is proportional to the first power of the concentration of the reactant R. For example, RPDR rate RDKT or drKT integrating this equation. We get ln RKTI 4.8 again, I is the constant of integration and its value can be determined easily. When T0, RR0, where R0 is the initial concentration of the reactant, therefore, equation 4.8 can be written as ln R0 kx0 I ln R0 I substituting the value of I in equation 4.8 ln RKT ln R0 4.94, 3, 2 first-order reactions. 107 Chemical Kinetics rearranging this equation 0R ln RKT or 0R1 ln RKT 4.10 at time T1 from equation 4.8 ln R1 KT1 ln R0 4.11 at time T2 ln R2 KT2 ln R0 4.12 where R1 and R2 are the concentrations of the reactants at time T1 and T2 respectively. Subtracting 4.12 from 4.11 ln R1 ln R2 KT1 KT2 1212 R ln KRTT 12121 R ln RKTT 4.13 equation 4.9 can also be written as 0 R ln RKT taking antilog of both sides are R0 EKT 4.14 comparing equation 4.9 with YMXC. If we plot ln R against T fig 4.4 we get a straight line with slope K and intercept equal to ln R0. The first order rate equation 4.10 can also be written in the form 0 R2.303 log RKT 4.150 R log 2.303 RKT if we plot a graph between log R0R versus T, fig. 4.5, the slope K 2.303 hydrogenation of ethene is an example of first-order reaction. C2H4GH2G C2H6G rate KC2H for all natural and artificial radioactive decay of unstable nuclei take place by first-order kinetics. Refer to Appendix IV for ln and log logarithms. 108 Chemistry Figure 4.4, a plot between ln R and T for a first-order reaction fig. 4.5, plot of log R0R versus time for a first-order reaction slope 2.303 K log RR0 times 0 226 4, 222, 88, 2, 86, Rahi-RN rate K raw decomposition of N2O5 and N2O are some more examples of first-order reactions. The initial concentration of N2O5 in the following first-order reaction N2O5G2 number 2G1202G was 1.24 x 10-2 mol L1 at 318 K. The concentration of N2O5 after 60 minutes was 0.20 x 10-2 mol L1. Calculate the rate constant of the reaction at 318 K. For a first-order reaction 1,2R log R2 12.303 KTTK 1212 2.303 log RTTR2 1211.2410 mol L2.303 log 60 minutes 0 minutes 0.2010 mol XX 12.303 log 6.2 minutes 60 K 0.0304 minutes 1 example 4.5 example 4.5 example 4.5 example 4.5 example 4.5 solution. Let us consider a typical first-order gas phase reaction. A GBGCG let pi be the initial pressure of A and PT the total pressure at time t. Integrated rate equation for such a reaction can be derived as total pressure PT Pa PBPC pressure units. 109 Chemical kinetics Pa, PB and PC are the partial pressures of A, B and C, respectively. If XATM be the decrease in pressure of A at time t and 1 mole each of B and C is being formed, the increase in pressure of B and C will also be XATM each. A GBGCG at T0 pi ATM 0 ATM 0 ATM at time t pi XATM XATM where pi is the initial pressure at time t0. PT pi, XXX pi XX PT pi where Pa pi, X pi PT, pi 2 pi, PT KIA 2.303 log P points 4.16 IIT 2.303 log 2 PPPT. The following data were obtained during the first-order thermal decomposition of N2O5G at constant volume, 25242 grams Gg2NO2NOOS no. Time S total pressure ATM 1, 00.52, 100 0.512. Calculate the rate constant. Let the pressure of N2O5G decrease by 2 times ATM. As 2 moles of N2O5 decompose to give 2 moles of N2O4G and 1 mole of O2G, the pressure of N2O4G increases by 2 times ATM and that of O2G increases by XATM. 25242 grams Gg2NO2NOO start T0 0.5 ATM 0 ATM 0 ATM at time T 0.5 to 2 times ATM XATM points 25242 NO op PP 0.5 to 2 times X 0.5 XX 0.5 TP 25 N op 0.5 to 2 times 0.5 to 2 points 0.5 1.5, 2 points at T100S. 0.512 ATM example 4.6 example 4.6 example 4.6 example 4.6 example 4.6 solution 110 Chemistry. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. It is represented as T12. For a zero-order reaction, rate constant is given by equation 4.7, 0 RRKT0121 rat. R2TT. The rate constant at T12 becomes 00121 to RRKT01 to R2TK. It is clear that T12 for a zero-order reaction is directly proportional to the initial concentration of the reactants and inversely proportional to the rate constant. For the first-order reaction, 2.303 R log RKT 4.15 at T120 RR2 4.16 so. The above equation becomes 0.122.303 R log 2 RKT or 122.303 log 2 TK 122.303, 0.301, TKX 120.693 TK 4.1725 N op 1.5 to 2x 0.512 0.476 ATM using equation 4.16 IA 410.5 ATM 2.303, 2.303, log 100S 0.476 ATM 2.303, 0.02164.9810 S 100 SPK TPXX 4, 3 half-life of a reaction. 111 Chemical kinetics. A first-order reaction is found to have a rate constant, K 5.5 x 1014 S1. Find the half-life of the reaction. Half-life for a first-order reaction is 12T 0.693 K 12T minus 14 minus 10 .693 5.5 x 10 S 1.26 x 1013 show that in a first-order reaction. Time required for completion of 99.9 is 10 times of half-life T12 of the reaction. When reaction is completed 99.9. RNR 0.999 R0 K 2.303 R log RT 2.303 R log 0.999 R RT 32.303 log 10 TT 6.909 K for half-life of the reaction T12 0.693 K12 TT 6.909 693 KKX. It can be seen that for a first-order reaction, half-life period is constant, that is, it is independent of initial concentration of the reacting species. The half-life of a first-order equation is readily calculated from the rate constant and vice versa. For zero-order reaction T1 to R0, for first-order reaction T12 is independent of R0. Example 4.7 Example 4.7 Example 4.7 Example 4.7 Example 4.7 Solution. Capital S O L U T I O N capital S O L U T I O N capital S O L U T I O N capital S O L U T I. Example 4.8 Example 4.8 Example 4.8 Example 4.8 Example 4.8 Solution Table 4.4 summarizes the mathematical features of integrated laws of zero and first-order reactions. Table 4.4 Integrated rate laws for the reactions of zero and first-order reaction differential integrated straight half units of K-type rate law line plot life 0 R PDR-DTK KTR0 RR versus TR02 K cont time 1 R mol L1 S11 R PDR-DTK RR0 E KTLN R versus TLN2 K time 1 R S1 or KTLN R0 R. Most of the chemical reactions are accelerated by increase in temperature, for example, in decomposition of N2O5. The time taken for half of the original amount of material to decompose is 12 minutes at 50 Oc, 5H at 25 Oc and 10 days at 0 Oc. You also know that in a mixture of potassium permanganate KMnO4 and oxalic acid H2C2O4, potassium permanganate gets decolorized faster at a higher temperature than that at a lower temperature. It has been found that for a chemical reaction with rise in temperature by 10 degrees, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation 4.18. It was first proposed by Dutch chemist J. H. van 't Hoff but Swedish chemist Arrhenius provided its physical justification and interpretation. 4.4 Temperature 4.4 Temperature 4.4 Temperature 4.4 Temperature 4.4 Temperature dependence of the rate of a reaction The order of a reaction is sometimes altered by conditions. There are many reactions which obey first-order rate law although they are higher-order reactions. Consider the hydrolysis of ethyl acetate, which is a chemical reaction between ethyl acetate and water. In reality, it is a second-order reaction and concentration of both ethyl acetate and water affect the rate of the reaction. But water is taken in large excess for hydrolysis, therefore, concentration of water is not altered much during the reaction. Thus, the rate of reaction is affected by concentration of ethyl acetate only. For example, during the hydrolysis of 0.01 mol of ethyl acetate with 10 mol of water, amounts of the reactants and products at the beginning T0 and completion T of the reaction are given as under. CH3 Cook 2H5H2OH CH3 Cu C2H5O T0 0.01 mol 10 mol 0 mol 0 mol T0 mol 9.9 mol 0.01 mol 0.01 mol. The concentration of water does not get altered much during the course of the reaction. So, the reaction behaves as first-order reaction. Such reactions are called pseudo-first-order reactions. Inversion of cane sugar is another pseudo-first-order reaction. C12H22O11H2OH C6H12O6 C6H12O6 cane sugar glucose fructose rate KC12H22O11 in text questions 4.5A first order reaction has a rate constant 1.15 x 10^3 How long will 5 grams of this reactant take to reduce to 3 grams? 4.6 time required to decompose SO2Cl2 to half of its initial amount is 60 minutes. If the decomposition is a first-order reaction, calculate the rate constant of the reaction. 113 Chemical Kinetics KAEART 4.18 Where A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. It is a constant specific to a particular reaction. R is gas constant and AI is activation energy measured in joules mol J mol -1. It can be understood clearly using the following simple reaction 2,2-HgIg2-Hig according to Arrhenius. This reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate Fig. 4.6. It exists for a very short time and then breaks up to form 2 molecules of hydrogen iodide. Figure 4.6. Formation of high through the intermediate Figure 4.7. Diagram showing plot of potential energy versus reaction coordinate Fig. 4.8. Distribution curve showing energies among gaseous molecules. The energy required to form this intermediate, called activated complex C, is known as activation energy Ea. Figure 4.7 is obtained by plotting potential energy versus reaction coordinate. Reaction coordinate represents the profile of energy change when reactants change into products. Some energy is released when the complex decomposes to form products, so the final enthalpy of the reaction depends upon the nature of reactants and products. All the molecules in the reacting species do not have the same kinetic energy. Since it is difficult to predict the behavior of any one molecule with precision, Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules Ne and T with a given kinetic energy E versus kinetic energy Fig. 4.8. Here, Ne is the number of molecules with energy E and Nt is total number of molecules. The peak of the curve corresponds to the most probable kinetic energy, that is, kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than this value, when the Figure 4.10, a plot between ln K and 1T and Figure 4.10, slope AR and intercept ln A so we can calculate AI and A using these values, at temperature T1. Equation 4.19 is ln K1 1 ERT ln A 4.20 at temperature T2. Equation 4.19 is ln K2 at 2 ERT ln A 4.21 since A is constant for a given reaction K1 and K2 are the values of rate constants at temperatures T1 and T2 respectively. Figure 4.9, distribution curve showing temperature dependence of rate of a reaction temperature is raised. The maximum of the curve moves to the higher energy value Fig. 4.9 and the curve broadens out, that is, spreads to the right such that there is a greater proportion of molecules with much higher energies. The area under the curve must be constant since total probability must be 1 at all times. We can mark the position of A on Maxwell-Boltzmann distribution curve Fig. 4.9. Increasing the temperature of the substance increases the fraction of molecules, which collide with energies greater than A. It is clear from the diagram that in the curve at T10, the area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled leading to doubling the rate of a reaction. In the Arrhenius equation 4.18 the factor EART corresponds to the fraction of molecules that have kinetic energy greater than A. Taking natural logarithm of both sides of equation 4.18 ln K ART ln A 4.19 the plot of ln K versus 1T gives a straight line according to the equation 4.19 as shown in Fig. 4.10. Thus, it has been found from Arrhenius equation 4.18 that increasing the temperature or decreasing the activation energy will result in an increase in the rate of the reaction and an exponential increase in the rate constant. 115 Chemical kinetics. The rate constants of a reaction at 500 K and 700 K are 0.02 S1 and 0.07 S1 respectively. Calculate the values of AI and A. 21 log KK 2101 22.303 T DETTR 0.07 log 0.0211 700 500 2 303 8.314 JMol 700 500 EKXX 0.544 AIX 5.714 X 10 419.15 AL 0.544 X 19 Doc 15 5.714 X 10-4 18230.8 J since KAEART 0.02 AE 18230.8 8.314 X 500 A 0.02 0.0121.61 The first order rate constant for the decomposition of ethyl iodide by the reaction C2H5Ig C2H4G at 600 K is 1.60 x 10-5 S1. Its energy of activation is 209 kJ/mol. Calculate the rate constant of the reaction at 700 K. We know that log K2 log K1 12112.303 ETTR subtracting equation 4.20 from 4.21. We obtain ln K2 ln K1 1 ERT, a 2 ERT ln KK ERT T2112111 a log. KK ERT T21122, 303, 1, 1, a 4.22 log. KKUTTT 2121122 303 R solution example 4.10 example 4.10 example 4.10 example 4.10 example 4.10 example 4.10 example 4.9 example 4.9 example 4.9 example 4.9 example 4.9 116 Chemistry. A catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyses the following reaction so as to increase its rate considerably: 2KClO3 MnO2 2KCl3O2. The word catalyst should not be used when the added substance reduces the rate of reaction. The substance is then called inhibitor. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products in the catalyst. It is believed that the catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and products and hence lowering the potential energy barrier as shown in Fig. 4.11. It is clear from Arrhenius equation 4.18 that lower the value of activation energy, faster will be the rate of a reaction. A small amount of the catalyst can catalyze a large amount of reactants. A catalyst does not alter Gibbs energy, G of a reaction. It catalyzes the spontaneous reactions but does not catalyze non-spontaneous reactions. It is also found that a catalyst does not change the equilibrium constant of a reaction, rather it helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as the backward reactions to the same extent so that the equilibrium state remains same but is reached earlier. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Trautz and William Lewis in 1916-18, provides a greater insight into the energetic and mechanistic aspects of reactions. It is based on kinetic theory of gases. According to this theory, the reactant molecules are 1 effect of catalyst 4.5 collision 4.5 collision 4.5 collision 4.5 collision 4.5 collision theory of chemical, capital C H E M I C A L, capital C H E M I C A L, capital C H E M I C A L, capital C H E M I C. Reactions Fig. 4.11, Figure 4.11, Figure 4.11, Figure 4.11, Fig. 4.11, Effect of catalyst on activation energy log K2O11211 log 2.303 EKTTR15111, 1209000, JMOL log 1.6010 K 700 K2, 303, 8, 314. JMOL KXX log K2 4.796 2.599 2.197 K2 6.36x 10-3s1. Assumed to be hard spheres and reaction is postulated to occur when molecules collide with each other. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency Z. Another factor which affects the rate of chemical reactions is activation energy, as we have already studied. For a bimolecular elementary reaction, AB product's rate of reaction can be expressed as AB rate ZEERT 4.23, where ZAB represents the collision frequency of reactants. A and B and DART represents the fraction of molecules with energies equal to or greater than A. Comparing 4.23 with Arrhenius equation, we can say that A is related to collision frequency. Equation 4.23 predicts the value of rate constants fairly accurately for the reactions that involve atomic species or simple molecules, but for complex molecules significant deviations are observed. The reason could be that all collisions do not lead to the formation of products. The collisions in which molecules collide with sufficient kinetic energy, called threshold energy, and proper orientation, so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products, are called as effective collisions. For example, formation of methanol from bromothane depends upon the orientation of reactant molecules as shown in Fig. 4.12. The proper orientation of reactant molecules led to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. To account for effective collisions, another factor P, called the probability or steric factor, is introduced. It takes into account the fact that in a collision, molecules must be properly oriented, it is, AB rate ZEERTP. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. Collision theory also has certain drawbacks, as it considers atoms molecules to be hard spheres and ignores their structural aspect. You will study details about this theory and more on other theories in your higher classes. Threshold energy, activation energy, energy possessed by reacting species. Figure 4.12, Figure 4.12, Figure 4.12, Figure 4.12, Figure 4.12, diagram showing molecules having proper and improper orientation. 118 Chemistry in text questions and text questions and text questions and text questions and text questions 4.7 What will be the effect of temperature on rate constant? 4.8 The rate of the chemical reaction doubles for an increase of 10 K in absolute temperature from 298 K. Calculate A. 4.9 The activation energy for the reaction 2-HGH2I2G is 209.5 kJ/mol1 at 581 K. Calculate the fraction of molecules of reactants having energy equal to or greater than activation energy. Summary Chemical kinetics is the study of chemical reactions with respect to reaction rates, effect of various variables, rearrangement of atoms and formation of intermediates. The rate of a reaction is concerned with decrease in concentration of reactants or increase in the concentration of products per unit time. It can be expressed as instantaneous rate at a particular instant of time and average rate over a large interval of time. A number of factors such as temperature, concentration of reactants, catalyst, affect the rate of a reaction. Mathematical representation of rate of a reaction is given by rate law. It has to be determined experimentally and cannot be predicted. Order of a reaction with respect to a reactant is the power of its concentration, which appears in the rate law equation. The order of a reaction is the sum of all such powers of concentration of terms for different reactants. Rate constant is the proportionality factor in the rate law. Rate constant and order of a reaction can be determined from rate law or its integrated rate equation. Molecularity is defined only for an elementary reaction. Its values are limited from 1 to 3, whereas order can be 0, 1, 2, 3 or even a fraction. Molecularity and order of an elementary reaction are same. Temperature dependence of rate constants is described by Arrhenius equation KAEART. AI corresponds to the activation energy and is given by the energy difference between activated complex and the reactant molecules. And A Arrhenius factor or pre-exponential factor corresponds to the collision frequency. The equation clearly shows that increase of temperature or lowering of AI will lead to an increase in the rate of reaction, and presence of a catalyst lowers the activation energy by providing an alternate path for the reaction. According to collision theory, another factor P called steric factor, which refers to the orientation of molecules which collide, is important and contributes to effective collisions, thus, modifying the Arrhenius equation to ABCERTKP. 4.1 From the rate expression. Surface chemistry deals with phenomena that occur at the surfaces or interfaces. The interface or surface is represented by separating the bulk phases by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by solid gas or solid gas. Due to complete miscibility, there is no interface between the gases. The bulk phases that we come across in surface chemistry may be pure compounds or solutions. The interface is normally a few molecules thick, but its area depends on the size of the particles of bulk phases. Many important phenomena, noticeable amongst these being corrosion, electrode processes, heterogeneous catalysis, dissolution and crystallization, occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface. Under very high vacuum of the order of 10-8 to 10-9 Pascal, it is now possible to obtain ultra-clean surface of the metals. Solid materials with such clean surfaces need to be stored in vacuum, otherwise these will be covered by molecules of the major components of air, namely dioxygen and dinitrogen. In this unit, you will be studying some important features of surface chemistry such as adsorption, catalysis and colloids, including emulsions and gels. Surface chemistry 5 Surface chemistry. After studying this unit, you will be able to describe interfacial phenomenon and its significance, define adsorption and classify it into physical and chemical adsorption, explain mechanism of adsorption, explain the factors controlling adsorption from gases and solutions on solids, explain adsorption results on the basis of Freundlich adsorption isotherms, appreciate the role of catalysts in industry, enumerate the nature of colloidal state, describe preparation, properties and purification of colloids, classify emulsions and describe their preparation and properties, describe the phenomenon of gel formation, list the uses of colloids. Objective: some of the most important chemicals are produced industrially by means of reactions that occur on the surfaces of solid catalysts. Unit 5. 124 Chemistry. There are several examples, which reveal that the surface of a solid has the tendency to attract and retain the molecules of the phase with which it comes into contact. These molecules remain only at the surface and do not go deeper into the bulk. The accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed adsorption. The molecular species or substance, which concentrates or accumulates at the surface is termed adsorbate, and the material on the surface of which the adsorption takes place is called adsorbent. Adsorption is essentially a surface phenomenon. Solids, particularly in finely divided state, have large surface area and therefore, charcoal, silica gel, alumina gel, clay, colloids, metals in finely divided state, etc. act as good adsorbents. Adsorption in action: if a gas like O2, H2, CO, Cl2, NH3 or SO2 is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas in the enclosed vessel decreases. The gas molecules concentrate at the surface of the charcoal, that is, gases are adsorbed at the surface. 2. In a solution of an organic dye, say methylene blue, when animal charcoal is added and the solution is well shaken, it is observed that the filtrate turns colorless. The molecules of the dye, thus, accumulate on the surface of charcoal, that is, are adsorbed. 3. Aqueous solution of raw sugar, when passed over beds of animal charcoal, becomes colorless as the coloring substances are adsorbed by the charcoal. The air becomes dry in the presence of silica gel because the water molecules get adsorbed on the surface of the gel. It is clear from the above examples that solid surfaces can hold the gas or liquid molecules by virtue of adsorption. The process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the adsorbent. While in absorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the surface retains the color of the ink due to adsorption of colored molecules, while the solvent of the ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from inside. A distinction can be made between absorption and adsorption by taking an example of water vapor. Water vapors are absorbed by anhydrous calcium chloride but adsorbed by silica gel. In other words, in adsorption the concentration of the adsorbate increases only at the surface of the adsorbent, while in absorption the concentration is uniform throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously also. The term sorption is used to describe both the processes. Adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particles inside the bulk. Inside the adsorbent all the forces acting between the particles are mutually 5.1. 1 distinction between adsorption and absorption. 5.1 Adsorption 5.1 Adsorption 5.1 Adsorption 5.1 Adsorption 5.1 Adsorption 5.1. 2 Mechanism of adsorption. 125 Surface chemistry balanced, but on the surface the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. The extent of adsorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption. During adsorption, there is always a decrease in residual forces of the surface, that is, there is decrease in surface energy which appears as heat. Adsorption, therefore, is invariably an exothermic process. In other words, H of adsorption is always negative. When a gas is adsorbed, the freedom of movement of its molecules become restricted. This amounts to decrease in the entropy of the gas after adsorption, that is, S is negative. Adsorption is thus accompanied by decrease in enthalpy as well as decrease in entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that, at constant temperature and pressure, G must be negative, that is, there is a decrease in Gibbs energy. On the basis of equation, GH, Ts, G can be negative if H has sufficiently high negative value as Ts is positive. Thus, in an adsorption process, which is spontaneous, a combination of these two factors makes G negative. As the adsorption proceeds, H becomes less and less negative. Ultimately H becomes equal to Ts and G becomes 0. At this state equilibrium is attained. There are mainly two types of adsorption of gases on solids. If accumulation of gas on the surface of a solid occurs on account of weak van der Waals forces, the adsorption is termed as physical adsorption or physisorption. When the gas molecules or atoms are held to the solid surface by chemical bonds, the adsorption is termed chemical adsorption or chemisorption. The chemical bonds may be covalent or ionic in nature. Chemisorption involves a high energy of activation and is, therefore, often referred to as activated adsorption. Sometimes these two processes occur simultaneously and it is not easy to ascertain the type of adsorption. A physical adsorption at low temperature may pass into chemisorption as the temperature is increased. For example, dihydrogen is first adsorbed on nickel by van der Waals forces. Molecules of hydrogen then dissociate to form hydrogen atoms which are held on the surface by chemisorption. Some of the important characteristics of both types of adsorption are described below. Characteristics of physisorption: I lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. 2. Nature of adsorbate. The amount of gas adsorbed by a solid depends on the nature of gas. In general, easily liquefiable gases, that is, with higher critical temperatures, are readily adsorbed as van der Waals forces are stronger near the critical temperatures. Thus, 1 gram of activated charcoal adsorbs more sulfur dioxide critical temperature 630 K than methane critical temperature 190 K, which is still more than 4.5 milliliters of dihydrogen critical temperature 33 K. 5. 1. 3 types of adsorption. 126. Chemistry. 3. Reversible nature. Physical adsorption of a gas by a solid is generally reversible. Thus, solid gas, gas, solid heat. More of gas is adsorbed when pressure is increased le volume of the gas decreases. Le Chatelier's principle, and the gas can be removed by decreasing pressure. Since the adsorption process is exothermic, the physical adsorption occurs readily at low temperature and decreases with increasing temperature. Le Chatelier's principle. I. Surface area of adsorbent. The extent of adsorption increases with the increase of surface area of the adsorbent. Thus, finely divided metals and porous substances having large surface areas are good adsorbents. The enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low, 2040 kJ-mol/1. This is because the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristics of chemisorption. I. High specificity. Chemisorption is highly specific and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbate. For example, oxygen is adsorbed on metals by virtue of oxide formation, and hydrogen is adsorbed by transition metals due to hydride formation. 2. Irreversibility. As chemisorption involves compound formation, it is usually irreversible in nature. Chemisorption is also an exothermic process, but the process is very slow at low temperatures on account of high energy of activation. Like most chemical changes, adsorption often increases with rise of temperature. Physisorption of a gas adsorbed at low temperature may change into chemisorption at a high temperature. Usually high pressure is also favorable for chemisorption. 3. Surface area. Like physical adsorption, chemisorption also increases with increase of surface area of the adsorbent. I. Enthalpy of adsorption. Enthalpy of chemisorption is high, 80 to 140 kJ-mol/1, as it involves chemical bond formation. 1. It arises because of van der Waals forces. 2. It is not specific in nature. 3. It is reversible in nature. 4. It depends on the nature of gas. More easily liquefiable gases are adsorbed readily. 5. Enthalpy of adsorption is low, 2040 kJ-mol/1 in this case. 1. It is caused by chemical bond formation. 2. It is highly specific in nature. 3. It is irreversible. 4. It also depends on the nature of gas. Gases which can react with the adsorbent show chemisorption. 5. Enthalpy of adsorption is high, 80 to 140 kJ-mol/1 in this case. Table 5.1. Comparison of physisorption and chemisorption. Physisorption, chemisorption. 127. Surface chemistry. The variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by means of a curve termed as adsorption isotherm. Freundlich adsorption isotherm. Freundlich, in 1909, gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed by the following equation: xmk, page 1, nn 1, 5.1, where x is the mass of the gas adsorbed on mass m of the adsorbent at pressure P. K and n are constants which depend on the nature of the adsorbent and the gas at a particular temperature. The relationship is generally represented in the form of a curve where mass of the gas adsorbed per gram of the adsorbent is plotted against pressure Fig. 5.1. These curves indicate that at a fixed pressure, there is a decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure, taking logarithm of ek 5.1 log xm log k1 n log p. 5.2. The validity of Freundlich isotherm can be verified by plotting log xm on y-axis ordinate and log p on x-axis abscissa. If it comes to be a straight line, the Freundlich isotherm is valid, otherwise not. Figure 5.2. The slope of the straight line gives the value of 1n. The intercept on the y-axis gives the value of log K. Freundlich isotherm explains the behavior of adsorption in an approximate manner. The factor 1n can have values between 0 and 1, probable range 0.1 to 0.5. Thus, equation 5.2 holds good over a limited range of pressure. 5.1. For adsorption isotherms, figure 5.2, Freundlich isotherm 6, low temperature is favorable for adsorption. It decreases with increase of temperature. 7. No appreciable activation energy is needed. 8. It depends on the surface area. It increases with an increase of surface area. 9. It results into multimolecular layers on adsorbent surface under high pressure. 6. High temperature is favorable for adsorption. It increases with the increase of temperature. 7. High activation energy is sometimes needed. 8. It also depends on the surface area. It too increases with an increase of surface area. 9. It results into unimolecular layer 195K 244K 273K XMP figure 5.1, adsorption isotherm. 128 Chemistry. When 1n0, xm constant, the adsorption is independent of pressure. When 1n1, xmkp, that is xmp, the adsorption varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherms always seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm. Thus, it fails at high pressure. Solids can adsorb solutes from solutions also. When a solution of acetic acid in water is shaken with charcoal, a part of the acid is adsorbed by the charcoal and the concentration of the acid decreases in the solution. Similarly, the litmus solution when shaken with charcoal becomes colorless. The precipitate of MgO2 attains blue color when precipitated in presence of Mainson reagent. The color is due to adsorption of Mainson. The following observations have been made in the case of adsorption from solution phase. I. The extent of adsorption decreases with an increase in temperature. 2. The extent of adsorption increases with an increase of surface area of the adsorbent. 3. The extent of adsorption depends on the concentration of the solute in solution. I. The extent of adsorption depends on the nature of the adsorbent and the adsorbate. The precise mechanism of adsorption from solution is not known. Freundlich's equation approximately describes the behavior of adsorption from solution with the difference that instead of pressure, concentration of the solution is taken into account, that is, xmkc1n, 5.3 C is the equilibrium concentration, that is, when adsorption is complete. On taking logarithm of the above equation, we have log xm log 1n log 5.4 plotting log xm against log C. A straight line is obtained which shows the validity of Freundlich isotherm. This can be tested experimentally by taking solutions of different concentrations of acetic acid. Equal volumes of solutions are added to equal amounts of charcoal in different flasks. The final concentration is determined in each flask after adsorption. The difference in the initial and final concentrations give the value of X using the above equation. Validity of Freundlich isotherm can be established. The phenomenon of adsorption finds a number of applications. Important ones are listed here. I. Production of high vacuum. The remaining traces of air can be adsorbed by charcoal from a vessel evacuated by a vacuum pump to give a very high vacuum. 5.1. 5. Adsorption from solution phase. 5.1. 6 applications of adsorption. 129 Surface chemistry. 2. Gas masks. Gas mask, a device which consists of activated charcoal or mixture of adsorbents, is usually used for breathing in coal mines to adsorb poisonous gases. 3. Control of humidity. Silica and aluminium gels are used as adsorbents for removing moisture and controlling humidity. I. Removal of coloring matter from solutions. Animal charcoal removes colors of solutions by adsorbing colored impurities. The heterogeneous catalysis. Adsorption of reactants on the solid surface of the catalysts increases the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalysts. Manufacture of ammonia using iron as a catalyst. Manufacture of H2SO4 by contact process and use of finely divided nickel and the hydrogenation of oils are excellent examples of heterogeneous catalysis. The separation of inert gases, due to the difference in degree of adsorption of gases by charcoal. A mixture of noble gases can be separated by adsorption on coconut charcoal at different temperatures. 7. In curing diseases, a number of drugs are used to kill germs by getting adsorbed on the made froth flotation process. A low-grade sulfate ore is concentrated by separating it from silica and other earthy matter by this method using pine oil and frothing agent. See Unit 6. 9. Adsorption indicators. Surfaces of certain precipitates such as silver halides have the property of adsorbing some dyes like eosin, fluorescein, etc. and thereby producing a characteristic color at the endpoint. X. Chromatographic analysis. Chromatographic analysis based on the phenomenon of adsorption finds a number of applications in analytical and industrial fields. In text questions 5.1 Write any two characteristics of chemisorption. 5.2 Why does physisorption decrease with the increase of temperature? 5.3 Why are powdered substances more effective adsorbents than their crystalline forms? Potassium chlorate, when heated, strongly decomposes, slowly giving dioxygen. The decomposition occurs in the temperature range of 653–873 K2 KClO3 to KCl3O2. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, that is, 473–633 K, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition. In a similar manner, the rates of a number of chemical reactions can be altered by the mere presence of a foreign substance. 5.2 Catalysis 5.2 Catalysis 5.2 Catalysis 5.2 Catalysis 5.2 Catalysis 130 Chemistry. The systematic study of the effect of various foreign substances on the rates of chemical reactions was first made by Berzelius, in 1835. He suggested the term catalyst for such substances which accelerate the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction, are known as catalysts, and the phenomenon is known as catalysis. You have already studied about catalysts and its functioning in section 4.5. Promoters and poisons. Promoters are substances that enhance the activity of a catalyst, while poisons decrease the activity of a catalyst. For example, in Haber's process for manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as a catalyst. N2G3H2G Phasmo-S2NH3G catalysis can be broadly divided into two groups: a homogeneous catalysis when the reactants, products and the catalyst are in the same phase, that is, liquid or gas. The process is said to be homogeneous catalysis. The following are some of the examples of homogeneous catalysis: oxidation of sulfur dioxide into sulfur trioxide with dioxygen in the presence of oxides of nitrogen as the catalyst in the Lee chamber process. 2SO2G O2G-NO-G2SO3G. The reactants, sulfur dioxide and oxygen, and the catalyst, nitric oxide, are all in the same phase. 2. Hydrolysis of methyl acetate is catalyzed by H ions furnished by hydrochloric acid, CH3COOH3LH2OLHClCH3COAC. Both the reactants and the catalyst are in the same phase. 3. Hydrolysis of sugar is catalyzed by H ions furnished by sulfuric acid, HCl2,4CHOX612,6,612,6 glucose fructose solution, CHOAC-HOL122211-2 solution. Both the reactants and the catalyst are in the same phase. B. Heterogeneous catalysis. The catalytic process in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are given below: oxidation of sulfur dioxide into sulfur trioxide in the presence of PT. PTS2SO-G32SO-G2. The reactant is in gaseous state while the catalyst is in the solid state. 5.2. 1 Homogeneous and heterogeneous catalysis. 131 Surface chemistry. 2 Combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron in Haber's process. Phas2NHG3NG3HG2. The reactants are in gaseous state while the catalyst is in the solid state. 3 Oxidation of ammonia into nitric oxide in the presence of platinum gauze in Ostwald's process. PTS4NOG6HOG24NHG5OG32. The reactants are in gaseous state while the catalyst is in the solid state. 5 Hydrogenation of vegetable oils in the presence of finely divided nickel as catalyst. NES vegetable oils LHG2. One of the reactants is in liquid state and the other in gaseous state while the catalyst is in the solid state. This theory explains the mechanism of heterogeneous catalysis. The old theory, known as adsorption theory of catalysis, was that the reactants in gaseous state or in solutions are adsorbed on the surface of the solid catalyst. The increase in concentration of the reactants on the surface increases the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of the reaction. The catalytic action can be explained in terms of the intermediate compound formation, the theory of which you have already studied in section 4.5. 1. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps. I. Diffusion of reactants to the surface of the catalyst. 2. Adsorption of reactant molecules on the surface of the catalyst. 3. Occurrence of chemical reaction on the catalyst surface through formation of an intermediate Fig. 5.3 I. Desorption of reaction products from the catalyst surface, and thereby making the surface available again for more reaction to occur. V. Diffusion of reaction products away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has 3 valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. Thus, formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of the reaction and is effective. 5.2. Adsorption theory of heterogeneous catalysis. 132. Chemistry. Even in small quantities, it however, does not explain the action of catalytic promoters and catalytic poisons. Important features of solid catalysts activity. The activity of a catalyst depends upon the strength of chemisorption to a large extent. The reactants must get adsorbed reasonably strongly onto the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by group 7-9 elements of the periodic table class Xi, Unit 3. Part 2 HOL22 HGOG22B. Selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product selectively. When under the same reaction conditions many products are possible, selectivity of different catalysts for same reactants is different. For example, starting with H2NCO, and using different catalysts, we get different products. Thus, it can be inferred that the action of a catalyst is highly selective in nature. As a result, a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant in product molecules is called shape-selective catalysis. Zeolites are good shape-selective catalysts because of their honeycomb-like structures. They are microporous ABAB reacting molecules. Catalyst surface having free valencies. Adsorption of reacting molecules. ABAB product catalyst. Intermediate adsorption of reacting molecules. Desorption of product molecules. Fig. 5.3 Adsorption of reacting molecules. Formation of intermediate and desorption of products. 5.2. 3 Shape-selective catalysis by zeolites. 133 Surface chemistry. Aluminar silicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atoms, giving LOC framework. The reactions taking place in zeolites depend upon the size and shape of reactant and product molecules as well as upon the pores and cavities of the zeolites. They are found in nature as well as synthesized for catalytic selectivity. Zeolites are being very widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in the petroleum industry is ZSM5. It converts alcohols directly into gasoline petrol by dehydrating them to give a mixture of hydrocarbons. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solutions in water. They are very effective catalysts, catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life process are catalyzed by enzymes. The enzymes are, thus, termed as biochemical catalysts, and the phenomenon is known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. The following are some of the examples of enzyme-catalyzed reactions. I. Inversion of cane sugar. The invertase enzyme converts cane sugar into glucose and fructose. 2. Conversion of glucose into ethyl alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. Zymase 2-CHOAC2COG252CHOAC612 ethyl alcohol glucose. 3. Conversion of starch into maltose. The diastase enzyme converts starch into maltose. Diastase NCHOAC 1222 112 CHOAC NHOL 610 5N2 maltose starch. IV. Conversion of maltose into glucose. The maltase enzyme converts maltose into glucose. Maltase 2-CHOAC 6-12-6-CHOAC HOL 12-22-11 2-glucose maltose V. Decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition. Urease 2-NHGCOG 3-2-NHCONHAC HOL 2-2-2-V in stomach. The pepsin enzyme converts proteins into peptides while in intestine. The pancreatic trypsin converts proteins into amino acids by hydrolysis. 7. Conversion of milk into curd. It is an enzymatic reaction brought about by lactobacilli enzyme present in curd. 5. 2-4 enzyme catalysis. 134 Chemistry characteristics of enzyme catalysis. Enzyme catalysis is unique in its efficiency and high degree of specificity. The following characteristics are exhibited by enzyme catalysts. Most highly efficient. 1 molecule of an enzyme may transform 1 million molecules of the reactant per minute. 2. Highly specific nature. Each enzyme is specific for a given reaction. That is, one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. 3. Highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature, called the optimum temperature. On either side of the optimum temperature, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298–310 K. Human body temperature being 310 K is suited for enzyme-catalyzed reactions. Highly active under optimum pH. The rate of an enzyme-catalyzed reaction is maximum at a particular pH called optimum pH, which is between pH values 5–7. The increasing activity in presence of activators and coenzymes. The enzymatic activity is increased in the presence of certain substances, known as coenzymes. It has been observed that when a small non-protein vitamin is present along with an enzyme, the catalytic activity is enhanced considerably. Activators are generally metal ions such as Na, Mn2, CO2, Cu2, etc. These metal ions, when weakly bonded to enzyme molecules, increase their catalytic activity. Amylase in presence of sodium chloride, that is, Na ions, are catalytically very active. The influence of inhibitors and poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action as enzyme inhibitors in the body. Mechanism of enzyme catalysis. There are a number of cavities present on the surface of colloidal particles of enzymes. These cavities are of characteristic shape and possess active groups such as NH2, Cu, SH, O, etc. These are actually the active table. 5.2. Some enzymatic reactions. Enzyme source. Enzymatic reaction: invertase yeast, sucrose, glucose and fructose, cymase yeast, glucose, ethyl alcohol and carbon dioxide, diastase, malt, starch, maltose, maltase yeast, maltose, glucose, urease, soybean, urea, ammonia and carbon dioxide, pepsin, stomach proteins, amino acids. Table 5.2 gives the summary of some important enzymatic reactions. 135 surface chemistry centers on the surface of enzyme particles. The molecules of the reactant substrate, which have complementary shape, fit into these cavities just like a key fits into a lock. On account of the presence of active groups, an activated complex is formed which then decomposes to yield the products. Thus, the enzyme-catalyzed reactions may be considered to proceed in 2 steps. Step 1. Binding of enzyme to substrate to form an activated complex. ESES. Step 2. Decomposition of the activated complex to form product. ESEP. Some of the important technical catalytic processes are listed in Table 5.3 to give an idea about the utility of catalysts in industries. 5.2. 5 catalysts in industry process. Catalyst: finely divided iron, molybdenum as promoter. Conditions: 200 bar pressure and 723–773 K temperature. Nowadays, a mixture of iron oxide, potassium oxide and alumina is used. Platinized asbestos, temperature 573 K. Platinized asbestos or vanadium pentoxide V2O5, temperature 673–723 K1. Haber's process for the manufacture of ammonia N2G3H2G2NH3G2. Ostwald's process for the manufacture of nitric acid 4NH3G5O2G4 No G6H2O G2 No GO2G2 number 2G4 number 2G2H2OLO2G4HNO3 AC3. Contact process for the manufacture of sulfuric acid. 2SO2GO2G2SO3G SO4H2SO4AC H2S2O7LOM H2S2O7LH2OL2H2SO4 AC. Table 5.3. Some industrial catalytic processes in text questions 5.4 in Haber's process. Hydrogen is obtained by reacting methane with steam in presence of NEO as catalyst. The process is known as steam reforming. Why is it necessary to remove CO when ammonia is obtained by Haber's process? 5.5 Why is the ester hydrolysis slow in the beginning and becomes faster after some time? 5.6 What is the role of desorption in the process of catalysis? Enzyme catalyst substrate reactants enzyme substrate complex enzyme product CSE, SEPEE active site SPSP Fig. 5.4 Mechanism of enzyme catalyzed reaction. 136 Chemistry. We have learned in Unit 2 that solutions are homogeneous systems. We also know that sand in water when stirred gives a suspension, which slowly settles down with time. Between the two extremes of suspensions and solutions we come across a large group of systems called colloidal dispersions or simply colloids. A colloid is a heterogeneous system in which one substance is dispersed. Dispersed phase is very fine particles in another substance called dispersion medium. The essential difference between a solution and a colloid is that of particle size. While in a solution, the constituent particles are ions or small molecules. In a colloid, the dispersed phase may consist of particles of a single macromolecule such as protein or synthetic polymer or an aggregate of many atoms, ions or molecules. Colloidal particles are larger than simple molecules but small enough to remain suspended. Their range of diameters is between 1 and 1000 nm 10-9 to 10-6 meters. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 centimeter's side. It has a total surface area of 6 square centimeters. If it were divided equally into 1012 cubes, the cubes would be the size of large colloidal particles and have a total surface area of 60,000 square centimeters or 6 square meters. This enormous surface area leads to some special properties of colloids to be discussed later in this unit. Colloids are classified on the basis of the following criteria: I. Physical state of dispersed phase and dispersion medium. 2. Nature of interaction between dispersed phase and dispersion medium. 3. Type of particles of the dispersed phase. Depending upon whether the dispersed phase and the dispersion medium are solids, liquids or gases, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and hence is not a colloidal system. The examples of the various types of colloids along with their typical names are listed in Table 5.4. Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in. 5.3 Colloids. 5.3 Colloids. 5.3 Colloids. 5.3 Colloids. 5.3 Colloids. 5.4 1. Classification based on physical state of dispersed phase and dispersion medium. Dispersed phase: solid, 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 liquid, 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 gas, gas. Dispersion medium: solid, liquid, gas, solid, liquid, gas, solid, liquid. Type of colloid: solid, sol, sol, aerosol, gel, emulsion, aerosol, solid, sol, foam. Examples: some colored glasses and gemstones, paints. Cell fluid: smoke, dust, cheese, jellies, milk, hair cream, butter, fog, mist, cloud, insecticide sprays, pumice stone. Foam, rubber, froth, whipped cream. Soap, leather. Table 5.4. Types of colloidal systems. 5.4 Classification. 5.4 Classification. 5.4 Classification. 5.4 Classification. 5.4 Classification of colloids. Of colloid soft colloids. Of colloid soft colloids. 137 Surface chemistry. Liquid, firefighting foams, used at emergency airplane landings are also colloidal systems. Most biological fluids are aqueous solids dispersed in water. Within a typical cell, proteins and nucleic acids are colloidal-sized particles dispersed in an aqueous solution of ions and small molecules. Out of the various types of colloids given in Table 5.4, the most common are solids in liquids, gels liquids in solids, and emulsions liquids in liquids. However, in the present unit, we shall take up discussion of the sols and emulsions only. Further, it may be mentioned that if the dispersion medium is water, the sol is called aquasol or hydrosol, and if the dispersion medium is alcohol, it is called alkasol, and so on. Depending upon the nature of interaction between the dispersed phase and the dispersion medium, colloidal sols are divided into 2 categories, namely, lyophilic solvent attracting and lyophobic solvent repelling. If water is the dispersion medium, the terms used are hydrophilic and hydrophobic. Lyophilic colloids. The word lyophilic means liquid-loving. Colloidal sols directly formed by mixing substances like gum, gelatin, starch, rubber, etc., with a suitable liquid, the dispersion medium, are called lyophilic sols. An important characteristic of these sols is that if the dispersion medium is separated from the dispersed phase, say by evaporation, The sol can be reconstituted by simply remixing with the dispersion medium. That is why these sols are also called reversible sols. Furthermore, these sols are quite stable and cannot be easily coagulated as discussed later. 2 Lyophobic colloids. The word lyophobic means liquid-hating. Substances like metals, their sulfides, etc., when simply mixed with the dispersion medium do not form the colloidal sol. Their colloidal sols can be prepared only by special methods as discussed later. Such sols are called lyophobic sols. These sols are readily precipitated or coagulated on the addition of small amounts of electrolytes, by heating or by shaking, and hence, are not stable. Further, once precipitated, they do not give back the colloidal sol by simple addition of the dispersion medium. Hence, these sols are also called irreversible sols. Lyophobic sols need stabilizing agents for their preservation. Depending upon the type of the particles of the dispersed phase, colloids are classified as multimolecular, macromolecular, and associated colloids. Multimolecular colloids, on dissolution, a large number of atoms or smaller molecules of a substance aggregate together to form species having size in the colloidal range 1-1000 nm. The species thus formed are called multimolecular colloids. For example, a gold sol may contain particles of various sizes having many atoms. Sulfur sol consists of particles containing 1,000 or more of S8 sulfur molecules. 2 Macromolecular colloids. Macromolecules unit 15 inches. Suitable solvents form solutions in which the size of the macromolecules 5, 4. 2 Classification based on nature of interaction between dispersed phase and dispersion medium 5, 4. 3 Classification based on type of particles, of the dispersed phase. Multimolecular, macromolecular, and associated colloids. 138 Chemistry Figure 5.5. Hydrophobic and hydrophilic parts of stearate ion may be in the colloidal range. Such systems are called macromolecular colloids. These colloids are quite stable and resemble true solutions in many respects. Examples of naturally occurring macromolecules are starch, cellulose, proteins and enzymes, and those of man-made macromolecules are polythene, nylon, polystyrene, synthetic rubber, etc. 3 Associated colloid micelles. There are some substances which at low concentrations behave as normal strong electrolytes, but at higher concentrations exhibit colloidal behavior due to the formation of aggregates. The aggregated particles thus formed are called micelles. These are also known as associated colloids. The formation of micelles takes place only above a particular temperature called Kraft temperature TK and above a particular concentration called critical micelle concentration CMC. On dilution, these colloids revert back to individual ions. Surface active agents such as soaps and synthetic detergents belong to this class. For soaps, the CMC is 10-4 to 10-3 mol/1. These colloids have both lyophobic and lyophilic parts. Micelles may contain as many as 100 molecules or more. Mechanism of micelle formation. Let us take the example of soap solutions. Soap is sodium or potassium salt of a higher fatty acid and may be represented as RCOO, e.g., sodium stearate CH3CH216COO, which is a major component of many bar soaps. When dissolved in water, it dissociates into RCOO and Na ions. The RCOO ions, however, consist of 2 parts. A long hydrocarbon chain are also called nonpolar tail, which is hydrophobic, water repelling, and a polar group COO, also called polar ionic head, which is hydrophilic, water loving. The RCOO ions are, therefore, present on the surface with their COO groups in water, and the hydrocarbon chains are staying away from it and remain at the surface. But at critical micelle concentration, the anions are pulled into the bulk of the solution and aggregate to form a spherical. 139 Surface Chemistry Medium Ice Bath Figure 5.8, Bredig-Zark Method Fig. 5.7. A grease on cloth. B stearate ions arranging around the grease droplet, and C grease droplet surrounded by stearate ions. Micelle formed a BC shape with their hydrocarbon chains pointing towards the center of the sphere with COO part remaining outward on the surface of the sphere. An aggregate thus formed is known as ionic micelle. These micelles may contain as many as 100 such ions. Similarly, in case of detergents, e.g., sodium lauryl sulfate, CH3CH211SO4 Na, the polar group is SO4 along with the long hydrocarbon chain. Hence, the mechanism of micelle formation here also is same as that of soaps. Cleansing action of soaps. It has been mentioned earlier that a micelle consists of a hydrophobic hydrocarbon-like central core. The cleansing action of soap is due to the fact that soap molecules form micelle around the oil droplet in such a way that hydrophobic part of the stearate ions is in the oil droplet and hydrophilic part projects out of the grease droplet, like the Brussels fig. 5.7. Since the polar groups can interact with water, the oil droplet surrounded by stearate ions is now pulled in water and removed from the dirty surface. Thus soap helps in emulsification and washing away of oils and fats. The negatively charged sheath around the globules prevents them from coming together and forming aggregates. A few important methods for the preparation of colloids are as follows. Chemical methods. Colloidal dispersions can be prepared by chemical reactions leading to formation of molecules by double decomposition, oxidation, reduction or hydrolysis. These molecules then aggregate leading to formation of sols. S2O33H2S double decomposition is 2S3 sol 3H2O SO2 2H2S oxidation 3S sol 2H2O 2OCl3 3HCHO 3H2O reduction 2O sol 3HCOOH 6HCl FeCl3 3H2O hydrolysis FeO3 sol 3HCl stearate ion water COO COO cook B ionic myselfig. 5.6. Arrangement of stearate ions on the surface of water at low concentrations of soap. Rearrangement of stearate ions inside the bulk of water. Ionic micelle at critical micelle concentrations of soap. 5.4. For preparation of colloids. B. Electrical disintegration or Bredig-Zark method. This process involves dispersion as well as condensation. Colloidal sols of metals such as gold, silver, platinum, etc., can be prepared by this method. In this method, electric arc is struck between electrodes of the metal immersed in the dispersion medium Fig. 5.8. The intense heat produced vaporizes the metal, which then condenses to form particles of colloidal size. 140. Chemistry. Figure 5.10. Electrodialysis. Fig. 5.9. Dialysis. C. Peptization. Peptization may be defined as the process of converting a precipitate into colloidal sol by shaking it with dispersion medium in the presence of a small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. This method is applied, generally, to convert a freshly prepared precipitate into a colloidal sol. During peptization, the precipitate absorbs one of the ions of the electrolyte on its surface. This causes the development of positive or negative charge on precipitates, which ultimately break up into smaller particles of the size of a colloid. You will learn about the phenomenon of development of charge on solid particles and their dispersion in section 5.4.6 under the heading Charge on colloidal particles. Colloidal solutions when prepared, generally contain excessive amount of electrolytes and some other soluble impurities. While the presence of traces of electrolyte is essential for the stability of the colloidal solution, larger quantities coagulate it. It is, therefore, necessary to reduce the concentration of these soluble impurities to a requisite minimum. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. The purification of colloidal solution is carried out by the following methods. Dialysis. It is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles, ions or smaller molecules in a true solution can pass through animal membrane bladder or parchment paper or cellophane sheet but not the colloidal particles. The membrane can be used for dialysis. The apparatus used for this purpose is called dialyzer. A bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. Fig. 5.9. The molecules and ions diffuse through membrane into the outer water and pure colloidal solution is left behind. 2. Electrodialysis. Ordinarily, the process of dialysis is quite slow. It can be made faster by applying an electric field if the dissolved substance in the impure colloidal solution is only an electrolyte. The process is then named electrodialysis. The colloidal solution is placed in a bag of suitable membrane while pure water is taken outside. Electrodes are fitted in the compartment as shown in figure 5.10. The ions present in the colloidal solution migrate out to the oppositely charged electrodes. 3. Ultrafiltration. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters, which are permeable to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper because the pores are too large. However, the pores of filter paper can be reduced in size by impregnating with collodion solution to stop the flow of colloidal particles. The usual collodion is a 4 solution of nitrocellulose in a mixture of alcohol and ether. An ultrafilter paper may be prepared by soaking the 5.4.5 purification of colloidal solutions. 141. Surface chemistry. Eye microscope. Tyndall cone scattered light source colloidal solution. Fig. 5.11. Tyndall effect. Filter paper in a collodion solution, hardening by formaldehyde and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles left on the ultrafilter paper are then stirred with fresh dispersion medium solvent to get a pure colloidal solution. Various properties exhibited by the colloidal solutions are described below. Colligative properties, colloidal particles being bigger aggregates. The number of particles in a colloidal solution is comparatively small as compared to a true solution. Hence, the values of colligative properties osmotic pressure, lowering in vapor pressure, depression in freezing point and elevation in boiling point are of small order as compared to values shown by true solutions at same concentrations. 2. Tyndall effect. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear, and, if it is observed from a direction at right angles to the direction of light beam, it appears perfectly dark. Colloidal solutions viewed in the same way may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong opalescence. When viewed at right angles to the passage of light, that is, the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. The bright cone of the light is called Tyndall cone figure 5.11. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. This scattering of light illuminates the path of beam in the colloidal dispersion. Tyndall effect can be observed during the projection of picture in the cinema hall due to scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the following two conditions are satisfied. The diameter of the dispersed particles is not much smaller than the wavelength of the light used, and the refractive indices of the disperse phase and the dispersion medium differ greatly in magnitude. Tyndall effect is used to distinguish between a colloidal and true solution. Zsigmondy, in 1903, used Tyndall effect to set up an apparatus known as ultramicroscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles to the beam. Individual colloidal particles appear as bright stars against a dark background. Ultramicroscope does not render the actual colloidal particles visible but only observe the light scattered by them. Thus, ultramicroscope does not provide any information about the size and shape of colloidal particles. 3. Color. The color of colloidal solution depends on the wavelength of light scattered by the dispersed particles. The wavelength of light further depends on the size and nature of the particles. The color 5, 4, 6 properties of colloidal solutions. Hydrated metallic oxides, e.g., Al2O3xH2O, Cro3xH2O and Fe2O3xH2O, etc. Basic dyestuffs, e.g., methylene blue sol. Hemoglobin blood oxides, e.g., SiO2 sol. Metals, e.g., copper, silver, gold sols. Metallic sulfides, e.g., S2S3, Sp2S3, CdS sols. Acid dyestuffs, e.g., eosin, Congo red sols, sols of starch, gum, gelatin, clay, charcoal, etc. Positively charged sols. Negatively charged sols of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by the reflected light and red when viewed by the transmitted light. Finest gold sol is red in color. As the size of particles increases, it appears purple, then blue and finally golden. Brownian movement. When colloidal solutions are viewed under a powerful ultramicroscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by the British botanist, Robert Brown, and is known as Brownian movement Fig. 5.12. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus, is responsible for the stability of sols. The charge on colloidal particles. Colloidal particles always carry an electric charge. The nature of this charge is the same on all the particles in a given colloidal solution and may be either positive or negative. A list of some common sols with the nature of charge on their particles is given below. Figure 5.12. Brownian movement. The presence of equal and similar charges on colloidal particles is largely responsible in providing stability to the colloidal solution. Because the repulsive forces between charged particles having same charge prevent them from coalescing or aggregating when they come closer to one another. The charge on the Sol particles is due to one or more reasons, viz., due to electron capture by Sol particles during electrodispersion of metals, due to preferential adsorption of ions from solution and/or due to formulation of electrical double layer. Development of charge on Sol particles by preferential adsorption of ions is described below. The Sol particles acquire positive or negative charge by preferential adsorption of positive or negative ions. When two or more ions are present in the dispersion medium, preferential adsorption of the ion. 143 Surface chemistry common to the colloidal particle usually takes place. This can be explained by taking the following examples. When highly diluted solution of silver nitrate is added to highly diluted potassium iodide solution. The precipitated silver iodide absorbs iodide ions from the dispersion medium and negatively charged colloidal Sol results. However, when key solution is added to AgNO3 solution, positively charged Sol results due to adsorption of Ag ions from dispersion medium. Ag negatively charged positively charged BF3 is added to the excess of hot water. A positively charged Sol of hydrated ferric oxide is formed due to adsorption of Fe3 ions. However, when ferric chloride is added to NaO solution, a negatively charged Sol is obtained with adsorption of O ions. Fe2O3XH2O Fe3 Fe2O3XH2O positively charged negatively charged having acquired a positive or a negative charge by selective adsorption on the surface of a colloidal particle as stated above. This layer attracts counter-ions from the medium forming a second layer, as shown below. Ag. The combination of the two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. According to modern views, the first layer of ions is firmly held and is termed fixed layer while the second layer is mobile, which is termed diffused layer. Figure 5.13 depicts the formation of double layer, since separation of charge is a seat of potential. The charges of opposite signs on the fixed and diffused parts of the double layer results in a difference in potential between these layers in the same manner as potential difference is developed in a capacitor. This potential difference between the fixed layer and the diffused layer of opposite charges is called the electrokinetic potential or zeta potential. If two particles of an insoluble material precipitate do not have double layers, they can come close enough and attractive van der Waals forces pull them together. When particles possess double layer as shown in figure 5.13, the overall effect is that particles repel each other at large distances of separation. This repulsion prevents their close approach. They remain dispersed and colloid is stabilized. The addition of more electrolytes to Sol suppresses the diffused double layer and reduces the zeta potential. This decreases the electrostatic repulsion between particles to a large extent in colloid precipitates. That is why colloid is particularly sensitive to oppositely charged ions via electrophoresis. The existence of charge on colloidal particles is confirmed by electrophoresis experiment. When electric potential is applied across two platinum electrodes dipping in a colloidal solution, the colloidal particles move towards one or the other electrode. The movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move towards the cathode while negatively charged solid fixed layer diffused layer Fig. 5.13 Formation of double layer. 144 Chemistry particles move towards the anode. This can be demonstrated by the following experimental setup. Fig. 5.14 When electrophoresis, that is, movement of particles is prevented by some suitable means, it is observed that the dispersion medium begins to move in an electric field. This phenomenon is termed electroosmosis. 7 Coagulation or precipitation. The stability of the lyophobic sols is due to the presence of charge on colloidal particles. If, somehow, the charge is removed, the particles will come nearer to each other to form aggregates or coagulate and settle down under the force of gravity. The process of settling of colloidal particles is called coagulation or precipitation of the Sol. The coagulation of the lyophobic sols can be carried out in the following ways. By electrophoresis, the colloidal particles move towards oppositely charged electrodes. Get discharged and precipitated. 2 By mixing two oppositely charged sols. Oppositely charged sols, when mixed in almost equal proportions, neutralize their charges and get partially or completely precipitated. Mixing of hydrated ferric oxide Vesol and arsenious sulfate Vesol bring them in the precipitated forms. This type of coagulation is called mutual coagulation. 3 By boiling. When a Sol is boiled, the adsorbed layer is disturbed due to increased collisions with the molecules of dispersion medium. This reduces the charge on the particles and ultimately leads to settling down in the form of a precipitate. By persistent dialysis. On prolonged dialysis, traces of the electrolyte present in the sole are removed almost completely and the colloids become unstable and ultimately coagulate. By addition of electrolytes, when excess of an electrolyte is added, the colloidal particles are precipitated. The reason is that colloids interact with ions carrying charge opposite to that present on themselves. This causes neutralization leading to their coagulation. The ion responsible for neutralization of charge on the particles is called the coagulating ion. A negative ion causes the precipitation of positively charged sole and vice versa. It has been observed that, generally, the greater the valence of the flocculating ion added, the greater is its power to cause precipitation. This is known as Hardy-Schulze rule. In the coagulation of a negative sol, the flocculating power is in the order Al3, Ba2, Na similarly. In the coagulation of a positive sol, the flocculating power is in the order Fa-CN64, PO43, So42, Cl. The minimum concentration of an electrolyte in millimoles per liter required to cause precipitation of a sol in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be the coagulating power of an ion. Figure 5.14, Electrophoresis. 145 Surface chemistry. Coagulation of lyophilic sols. There are two factors which are responsible for the stability of lyophilic sols. These factors are the charge and solvation of the colloidal particles. When these two factors are removed, a lyophilic sol can be coagulated. This is done I by adding an electrolyte and II by adding a suitable solvent. When solvents such as alcohol and acetone are added to hydrophilic sols, the dehydration of dispersed phase occurs. Under this condition, a small quantity of electrolyte can bring about coagulation. Protection of colloids. Lyophilic sols are more stable than lyophobic sols. This is due to the fact that lyophilic colloids are extensively solvated, that is, colloidal particles are covered by a sheath of the liquid in which they are dispersed. Lyophilic colloids have a unique property of protecting lyophobic colloids. When a lyophilic sol is added to the lyophobic sol, the lyophilic particles form a layer around lyophobic particles and thus protect the latter from electrolytes. Lyophilic colloids used for this purpose are called protected colloids. These are liquid-liquid colloidal systems, that is, the dispersion of finely divided droplets in another liquid. If a mixture of two immiscible or partially miscible liquids is shaken, a coarse dispersion of one liquid in the other is obtained, which is called emulsion. Generally, one of the two liquids is water. There are two types of emulsions: I oil dispersed in water OW type and II water dispersed in oil WO type. In the first system, water acts as dispersion medium. Examples of this type of emulsion are milk and vanishing cream. In milk, liquid fat is dispersed in water. In the second system, oil acts as dispersion medium. Common examples of this type are butter and cream. Emulsions of oil and water are unstable and sometimes they separate into two layers on standing. For stabilization of an emulsion, a third component called emulsifying agent is usually added. The emulsifying agent forms an interfacial film between suspended particles and the medium. The principal emulsifying agents for OW emulsions are proteins, gums, natural and synthetic soaps, etc., and for WO, heavy metal salts of fatty acids, long-chain alcohols, lamblac, etc. Emulsions can be diluted with any amount of the dispersion medium. On the other hand, the dispersed liquid when mixed, forms a separate layer. The droplets in emulsions are often negatively charged and can be precipitated by electrolytes. They also show Brownian movement and Tyndall effect. Emulsions can be broken into constituent liquids by heating, freezing, centrifuging, etc. Most of the substances we come across in our daily life are colloids. The meals we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read, are largely composed of colloids. Water and oil. Oiling water. Water oil. Fig. 5.14, Types of emulsions. 5.65, 65, 65, 65, 6 colloids. Colloids around us. 5.5 emulsions. 5.5 emulsions. 5.5 emulsions. 5.5 emulsions. 5.5 emulsions. 146 Chemistry. High voltage electrode. 30,000 volts or more. Gases free from carbon particles. Precipitated ash smoke. Following are the interesting and noteworthy examples of colloids. Blue color of the sky. Dust particles along with water suspended in air scatter blue light which reaches our eyes and the sky looks blue to us. 2. Fog, mist and rain. When a large mass of air containing dust particles is cooled below its dew point, the moisture from the air condenses on the surfaces of these particles forming fine droplets. These droplets, being colloidal in nature, continue to float in air in the form of mist or fog. Clouds are aerosols having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size, till they come down in the form of rain. Sometimes, the rainfall occurs when two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a soul-carrying charge opposite to the one on clouds from an aeroplane. 3 food articles, milk, butter, halwa, ice creams, fruit juices, etc., are all colloids in one form or the other. Blood. It is a colloidal solution of an albuminoid substance. The styptic action of alum and ferric chloride solution is due to coagulation of blood forming a clot which stops further bleeding. Soils. Fertile soils are colloidal in nature in which humus acts as a protective colloid. On account of colloidal nature, soils absorb moisture and nourishing materials. Formation of delta. River water is a colloidal solution of clay. Seawater contains a number of electrolytes. When river water meets the seawater, the electrolytes present in seawater coagulate the colloidal solution of clay, resulting in its deposition with the formation of delta. Applications of colloids. Colloids are widely used in the industry. Following are some examples. Electrical precipitation of smoke. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc., in air. The smoke, before it comes out from the chimney, is led through a chamber containing plates having a charge opposite to the carried by smoke particles. The particles on coming in contact with these plates lose their charge and get precipitated. The particles thus settle down on the floor of the chamber. The precipitator is called Cottrell precipitator. Figure 5.15. Purification of drinking water. The water obtained from natural sources often contains suspended impurities. Alum is added to such water to coagulate the suspended impurities and make water fit for drinking purposes. 3 medicines. Most of the medicines are colloidal in nature. For example, argyral is a silver sol used as an eye lotion. Colloidal antimony is used in curing calcer. Colloidal gold is used for intramuscular injection. Milk of magnesia, an emulsion, is used for stomach disorders. Colloidal medicines are more effective because they have large surface area and are therefore easily assimilated. Fig. 5.15. Cottrell smoke precipitator. 147. Surface chemistry. Tanning. Animal hides are colloidal in nature. When a hide, which has positively charged particles, is soaked in tannin, which contains negatively charged colloidal particles, mutual coagulation takes place. This results in the hardening of leather. This process is termed as tanning. Chromium salts are also used in place of tannin. Cleansing action of soaps and detergents. This has already been described in section 5.4.3. Photographic plates and films. Photographic plates or films are prepared by coating an emulsion of the light-sensitive silver bromide in gelatin over glass plates or celluloid films. 7. Rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. 8. Industrial products. Paints, inks, synthetic plastics, rubber, graphite lubricants, cement, etc., are all colloidal solutions. Summary. Adsorption is the phenomenon of attracting and retaining the molecules of a substance on the surface of a solid, resulting into a higher concentration on the surface than in the bulk. The substance adsorbed is known as adsorbate, and the substance on which adsorption takes place is called adsorbent. In physisorption, adsorbate is held to the adsorbent by weak van der Waals forces, and in chemisorption, adsorbate is held to the adsorbent by strong chemical bond. Almost all solids adsorb gases. The extent of adsorption of a gas on a solid depends upon nature of gas, nature of solid, surface area of the solid, pressure of gas and temperature of gas. The relationship between the extent of adsorption xm and pressure of the gas at constant temperature is known as adsorption isotherm. A catalyst is a substance which enhances the rate of a chemical reaction without itself getting used up in the reaction. The phenomenon using catalyst is known as catalysis. In homogeneous catalysis, the catalyst is in the same phase as are the reactants, and in heterogeneous catalysis the catalyst is in a different phase from that of the reactants. Colloidal solutions are intermediate between true solutions and suspensions. The size of the colloidal particles range from 1 to 1000 nm. A colloidal system consists of 2 phases: the disperse phase and the dispersion medium. Colloidal systems are classified in 3 ways depending upon physical states of the disperse phase and dispersion medium, 2 nature of interaction between the disperse phase and dispersion medium, and 3 nature of particles of dispersed phase. The colloidal systems show interesting optical, mechanical and electrical properties. The process of changing the colloidal particles in a sol into the insoluble precipitate by addition of some suitable electrolytes is known as coagulation. Emulsions are colloidal systems in which both dispersed phase and dispersion medium are liquids. These can be of I-oil in water type and 2-water in oil type. The process of making emulsion is known as emulsification. To stabilize an emulsion, an emulsifying agent or emulsifier is added. Soaps and detergents are most frequently used as emulsifiers. Colloids find several applications in industry as well as in daily life. In text questions 5.7 What modification can you suggest in the Hardy-Schulze law? 5.8 Why is it essential to wash the precipitate with water before estimating it quantitatively? 6 After studying this unit, you will be able to appreciate the contribution of Indian traditions in the metallurgical processes. Explain the terms minerals, ores, concentration, benefaction, calcination, roasting, refining, etc. Understand the principles of oxidation and reduction as applied to the extraction procedures. Apply the thermodynamic concepts like that of Gibbs energy and entropy to the principles of extraction of Al, Cu, Zn and Fe. Explain why reduction of certain oxides like Cu2O is much easier than that of Fe2O3. Explain why CO is a favorable reducing agent at certain temperatures while coke is better in some other cases. Explain why specific reducing agents are used for the reduction purposes. Thermodynamics illustrates why only a certain reducing element and a minimum specific temperature are suitable for reduction of a metal oxide to the metal in an extraction. General principles and processes of isolation of elements. General principles and processes of isolation of elements. 6 Unit. The history of civilization is linked to the use of metals in antiquity in many ways. Different periods of early human civilizations have been named after metals. The skill of extraction of metals gave many metals and brought about several changes in the human society. It gave weapons, tools, ornaments, utensils, etc., and enriched the cultural life. The 7 metals of antiquity, as they are sometimes called, are gold, copper, silver, lead, tin, iron and mercury. Although modern metallurgy had exponential growth after Industrial Revolution, it is interesting to note that many modern concepts in metallurgy have their roots in ancient practices that predated the Industrial Revolution. For over 7,000 years, India has had a rich tradition of metallurgical skills. The 2 important sources for the history of Indian metallurgy are archaeological excavations and literary evidences. The first evidence of metal in Indian subcontinent comes from Mehrgarh in Baluchistan, where a small copper bead, dated to about 6000 BCE was found. It is however thought to be native copper, which has not been extracted from the ore. Spectrometric studies on copper ore samples obtained from the ancient mine pits at Khetri in Rajasthan and on metal samples cut from representative Harappan objective. 150 chemistry artifacts recovered from Midithal in Haryana and 8 other sites distributed in Rajasthan, Gujarat, Madhya Pradesh and Maharashtra prove that copper metallurgy in India dates back to the Chalcolithic cultures in the subcontinent. Indian Chalcolithic copper objects were in all probability made indigenously. The ore for extraction of metal for making the objects was obtained from chalcopyrite ore deposits in Aravalli Hills. Collection of archaeological texts from copper plates and rock inscriptions have been compiled and published by the Archaeological Survey of India during the past century. Royal records were engraved on copper plates. Tamarapatra, earliest known copper plate, has a Mauryan record that mentions famine relief efforts. It has one of the very few pre-Ashoka Brahmi inscriptions in India. Harappans also used gold and silver, as well as their joint alloy electrum. Variety of ornaments such as pendants, bangles, beads and rings have been found in ceramic or bronze pots. Early gold and silver ornaments have been found from Indus Valley sites such as Mohenjo-daro 3000 BCE. These are on display in the National Museum, New Delhi. India has the distinction of having the deepest ancient gold mines in the world, in the Maski region of Karnataka. Carbon dating places them in mid-1st millennium BCE. Hymns of Rigveda give earliest indirect references to the alluvial placer gold deposits in India. The river Sindhu was an important source of gold in ancient times. It is interesting that the availability of alluvial placer gold in the river Sindhu has been reported in modern times also. It has been reported that there are great mines of gold in the region of Mansarovar and in Phokchalayug even now. The Pali text, Anguttaranaka, narrates the process of the recovery of gold dust or particles from alluvial placer gold deposits. Although evidence of gold refining is available in Vedic texts, it is Kautilaya's Arthashastra, authored probably in 3rd or 4th century BCE. During Mauryan era, which has much data on prevailing chemical practices in a long section on mines and minerals including metal ores of gold, silver, copper, lead, tin and iron. Kautilaya describes a variety of gold called rasvita, which is naturally occurring gold solution. Kalidas also mentioned about such solutions. It is astonishing how people recognized such solutions. The native gold has different colors depending upon the nature and amount of impurity present in it. It is likely that the different colors of native gold were a major driving force for the development of gold refining. Recent excavations in central parts of Ganges Valley and Vindhya Hills have shown that iron was produced there possibly as early as in 1800 BCE. In the recent excavations conducted by the Uttar Pradesh State Archaeological Department, iron furnaces, artifacts, 2 iron layers of slag have been found. Radiocarbon dating places them between BCE 1800 and 1000. The results of excavation indicate that the knowledge of iron smelting and manufacturing of iron artifacts was well known in eastern Vindhyas, and it was in use in the central Ganga plains. At least from the early 2nd millennium BCE, the quantity and types of iron artifacts and the level of technical advancements indicate that working of iron would have been introduced much earlier. General principles and processes of isolation of elements. 151. The evidence indicates early use of iron in other areas of the country, which proves that India was indeed an independent center for the development of the working of iron. Iron smelting and the use of iron was especially established in South Indian megalithic cultures. The forging of wrought iron seems to have been at peak in India in the 1st millennium CE. Greek accounts report the manufacture of steel in India by crucible process. In this process, iron, charcoal and glass were mixed together in a crucible and heated until the iron melted and absorbed the carbon. India was a major innovator in the production of advanced quality steel. Indian steel was called the wonder material of the Orient. A Roman historian, Quintus Curtius, records that one of the gifts Porus of Taxila 326 BCE gave to Alexander the Great was some 2.5 tons of Wootz steel. Wootz steel is primarily iron containing a high proportion of carbon 1.0 to 1.9. Wootz is the English version of the word ukku, which is used for steel in Karnataka and Andhra Pradesh. Literary accounts suggest that Indian Wootz steel from southern part of the Indian subcontinent was exported to Europe, China and Arab world. It became prominent in the Middle East, where it was named as Damascus steel. Michael Faraday tried to duplicate this steel by alloying iron with a variety of metals, including noble metals, but failed. When iron ore is reduced in solid state by using charcoal, porous iron blocks are formed. Therefore, reduced iron blocks are also called sponge iron blocks. Any useful product can be obtained from this material only after removing the porosity by hot forging. The iron so obtained is termed as wrought iron. An exciting example of wrought iron produced in ancient India is the world-famous iron pillar. It was erected in its present position in Delhi in 5th century CE. The Sanskrit inscription engraved on it suggests that it was brought here from elsewhere during the Gupta period. The average composition weight of the components present in the wrought iron of the pillar, besides iron, are 0.15 C, 0.05 C, 0.05 Mn, 0.25 P, 0.005 Ni, 0.03 Cu and 0.02 N. The most significant aspect of the pillar is that there is no sign of corrosion in spite of the fact that it has been exposed to the atmosphere for about 1,600 years. Radiocarbon dating of charcoal from iron slag revealed evidence of continuous smelting in Khasi Hills of Meghalaya. The slag layer, which is dated to 353 BCE CE 128, indicates that Khasi Hill region is the earliest iron smelting site studied in the entire region of northeast India. The remnants of former iron ore excavation and iron manufacturing are visible even now in the landscape of Khasi Hills. British naturalists who visited Meghalaya in early 19th century described the iron industry that had developed in the upper part of the Khasi Hills. There is archaeological evidence of zinc production in Rajasthan mines at Zar from the 6th or 5th BCE. India was the first country to master zinc distillation, due to low boiling point. Zinc tends to vaporize while its ore is smelted. Pure zinc could be produced after a sophisticated downward distillation technique in which the Vapau 152 chemistry was condensed in a lower container. This technique was also applied to mercury. Indian metallurgists were masters in this technique. This has been described in Sanskrit texts of 14th century. Indians had knowledge about mercury. They used it for medicinal purpose. Development of mining and metallurgy declined during the British colonial era. By the 19th century, once flourished mines of Rajasthan were mostly abandoned and became almost extinct. In 1947, when India got independence, European literature on science had already found its way slowly into the country. Thus, in post-independence era, the government of India initiated the process of nation-building through the establishment of various institutes of science and technology. In the following sections, we will learn about the modern methods of extraction of elements. A few elements like carbon, sulfur, gold and noble gases occur in free state while others are found in combined forms in the Earth's crust. Elements vary in abundance. Among metals, aluminium is the most abundant. In fact, it is the third most abundant element in Earth's crust, 8.3 approximately. By weight, it is a major component of many igneous minerals including mica and clays. Many gemstones are impure forms of Al2O3. For example, gems ruby and sapphire have Cr and company respectively as impurity. Iron is the second most abundant metal in the Earth's crust. It forms a variety of compounds and their various uses make it a very important element. It is one of the essential elements in biological systems as well. For obtaining a particular metal, first we look for minerals which are naturally occurring chemical substances in the Earth's crust and are obtained through mining. Out of many minerals in which a metal may be found, only a few are viable to be used as source of that metal. Such minerals are known as ores. The principal ores of aluminium, iron, copper and zinc are given in Table 6.1. 6.16 1 occurrence of metals aluminium bauxite Al-oxo3 2 times where 0 x 1 kaolinite a form of clay Al2O4C2O5 iron hematite Fe2O3 magnetite Fe3O4 siderite Feco3 iron pyrites Fes2 copper pyrites Cu Fes2 malachite Cuco3 Cuo2 cuprite Cu2O copper glance Cu2S zinc blenders sphalerite ZNS calamines and Co3 zincite ZNO metal ores composition table 6.1 Principal ores of some important metals. A particular element may occur in a variety of compounds. The process of isolation of element from its compound should be such that it is chemically feasible and commercially viable. General principles and processes of isolation of elements 153 For the purpose of extraction, bauxite is chosen for aluminium. For iron, usually the oxide ores which are abundant and do not produce polluting gases like SO2 that is produced in case of iron pyrites are taken. For copper and zinc, any of the ores listed in Table 6.1 may be used depending upon the availability and other relevant factors. The entire scientific and technological process used for isolation of the metal from its ore is known as metallurgy. The extraction and isolation of an element from its combined form involves various principles of chemistry. Still, some general principles are common to all the extraction processes of metals. An ore rarely contains only a desired substance. It is usually contaminated with earthly or undesired materials known as gangue. The extraction and isolation of metals from ores involves the following major steps: concentration of the ore, isolation of the metal from its concentrated ore, and purification of the metal. In the following sections, we shall first describe the various steps for effective concentration of ores. After that, principles of some of the common metallurgical processes will be discussed. Those principles will include the thermodynamic and electrochemical aspects involved in the effective reduction of the concentrated ore to the metal. Removal of the unwanted materials e.g., sand, clays, etc. from the ore is known as concentration, dressing or benefaction. Before proceeding for concentration, ores are graded and crushed to reasonable size. Concentration of ores involves several steps and selection of these steps depends upon the differences in physical properties of the compound of the metal present and that of the gangue. The type of the metal, the available facilities and the environmental factors are also taken into consideration. Some of the important procedures for concentration of ore are described below. This is based on the difference between specific gravities of the ore and the gangue particles. It is therefore a type of gravity separation. In one such process, an upward stream of running water is used to wash the powdered ore. The lighter gangue particles are washed away and the heavier ore particles are left behind. This is based on differences in magnetic properties of the ore components. If either the ore or the gangue is attracted towards magnetic field, then the separation is carried out by this method. For example, iron ores are attracted towards magnet, hence, non-magnetic impurities can be separated from them using magnetic separation. The powdered ore is dropped over a conveyor belt which moves over a magnetic roller. Figure 6.1 Magnetic substance remains attracted towards the belt and falls close to it. 6.2 1 Hydraulic washing 6.2 2 Magnetic separation 6.26 26 26 26 2 Capital C O N C E N T R A T I O N capital C O N C E N T R A T I O N capital C O N C of ores Fig. 6.1 Magnetic separation schematic. (154) Chemistry. This method is used for removing gangue from sulfide ores. In this process, a suspension of the powdered ore is made with water. Collectors and froth stabilizers are added to it. Collectors e.g., pine oils, fatty acids, xanthates, etc. enhance non-wettability of the mineral particles, and froth stabilizers e.g., cresols, aniline stabilize the froth. The mineral particles become wet by oils while the gangue particles by water. A rotating paddle agitates the mixture and draws air in it. As a result, froth is formed which carries the mineral particles. The froth is light and is skimmed off. It is then dried for recovery of the ore particles. Sometimes, it is possible to separate two sulfate ores by adjusting proportion of oil to water or by using depressants. For example, in the case of an ore containing ZNS and PBS, the depressant used is NACN. It selectively prevents ZNS from coming to the froth but allows PBS to come with the froth. Leaching is often used if the ore is soluble in some suitable solvent. Following examples illustrate the procedure. A leaching of alumina from bauxite. Bauxite is the principal ore of aluminium. It usually contains CO2, iron oxides and titanium oxide. CO2 as impurities. Concentration is carried out by heating the powdered ore with a concentrated solution of NaO at 473-523 K and 35-36 bar pressure. This process is called digestion. This way, Al2O3 is extracted out as sodium aluminate 6,2,4 leaching Fig. 6.2 Froth flotation process. 6.2.3 Froth flotation method. The innovative washerwoman. 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 One can do wonders if he or she has a scientific temperament and is attentive to observations. A washerwoman had an innovative mind too. While washing a miner's overalls, she noticed that sand and similar dirt fell to the bottom of the wash tub. What was peculiar, the copper-bearing compounds that had come to the clothes from the mines, were caught in the soap suds and so they came to the top. One of her clients, Mrs. Carrie Everson, was a chemist. The washerwoman told her experience to Mrs. Everson. The latter thought that the idea could be used for separating copper compounds from rocky and earth materials on large scale. This way an invention came up. At that time only those ores were used for extraction of copper, which contained large amounts of the metal. Invention of the froth flotation method made copper mining profitable even from the low-grade ores. World production of copper soared and the metal became cheaper. General principles and processes of isolation of elements. 155 The impurity, CO2 dissolves forming sodium silicate. Other impurities are left behind. Al2O3S2 NaOH3H2OL2 NiO4Ac 6.1 The sodium aluminate present in solution is neutralized by passing CO2 gas and hydrated Al2O3 is precipitated. At this stage, small amount of freshly prepared sample of hydrated Al2O3 is added to the solution. This is called seeding. It induces the precipitation to NiO4Ac CO2G Al2O3XH2OS2 NaCO3Ac 6.2 Sodium silicate remains in the solution and hydrated alumina is filtered, dried and heated to give back pure Al2O3. Al2O3XH2OS 1470 K Al2O3SXH2OG 6.3 B Other examples in the metallurgy of silver and gold. The respective metal is leached with a dilute solution of NaCN or KCN in the presence of air, which supplies O2. The metal is obtained later by replacement reaction. 4MS8CN Ac2H2O Ac O2G 4MCN2 Ac 4O Ac MAG or O 6.422 4MZN2 ZN2 MAC Ac CN Z 6.5 To extract metal from concentrated ore, it must be converted to a form which is suitable for reduction to metal. Usually sulfate ores are converted to oxide before reduction because oxides are easier to reduce. Thus isolation of metals from concentrated ore involves two major steps, viz., a conversion to oxide, and b. reduction of the oxide to metal. A conversion to oxide calcination, calcinatin involves heating. It removes the volatile matter which escapes leaving behind the metal oxide. Fe2O3XH2OSD Fe2O3SXH2OG 6.6 Co3SDZNOS CO2G 6.7 CaCO3 Co3SDCAOSMGOS2 CO2G 6.82 Roasting. In roasting, the ore is heated in a regular supply of air in a furnace at a temperature below the melting point of the metal. Some of the reactions involving sulfidors are, in text questions 6.1 which of the ores mentioned in table 6.1 can be concentrated by magnetic separation method? 6.2 What is the significance of leaching in the extraction of aluminium? 6.36 extraction, capital E, X, T, R, A, C, T, I, O, N, capital E, X, T, R, A, C, T, I, O, N, capital E, X, T, R, A, C, T, I, O, N, of crude metal from, capital C, O, N, C, E, N, T, R, A, T, E, D, capital C, O, N, C, E, N, T, R, A, T, E, D, capital C, O, N, C, E, N, or. 156 Chemistry to ZnS3O2 to ZnO2 SO2 6.92 PbS3O2 to PbO2 SO2 6.102 Cu2S3O2 to Cu2O2 SO2 6.11 The sulfidors of copper are heated in reverberatory furnace Fig. 6.3 If the ore contains iron, it is mixed with silica before heating. Iron oxide slags of iron silicate and copper is produced in the form of copper matte which contains Cu2S and Fes. FeO-CO2 Fe-CO3 6.12 slag The SO2 produced is utilized for manufacturing H2SO4b Reduction of oxide to the metal Reduction of the metal oxide usually involves heating it with a reducing agent, for example C, or CO or even another metal. The reducing agent e.g., carbon combines with the oxygen of the metal oxide, MXOIC XMYCO 6.13 Some metal oxides get reduced easily while others are very difficult to be reduced Reduction means electron gain by the metal ion. In any case, heating is required. Some basic concepts of thermodynamics help us in understanding the theory of metallurgical transformations. Gibbs energy is the most significant term, to understand the variation in the temperature required for thermal reductions and to predict which element will suit as the reducing agent for a given metal oxide MXOI. Gibbs energy interpretations are made. The criterion for the feasibility of a thermal reduction is that at a given temperature Gibbs energy change of the reaction must be negative. The change in Gibbs energy, G for any process at any specified temperature, is described by the equation, GH, TS 6.14 where, H is the enthalpy change and S is the entropy change for the process. When the value of G is negative in equation 6.14, only then the reaction will proceed. G can become negative in the following situations. 1. If S is positive, on increasing the temperature T, the value of Ts increases so that H, Ts, in this situation G will become negative on increasing temperature 2, if coupling of the two reactions, that is reduction and oxidation, results in negative value of G for overall reaction, the final reaction becomes feasible. Such coupling is easily understood. 6.46 capital T, H, E, R, M, O, D, Y, N, A, M, I, C, capital T, H, E, R, M, O, D, Y, N, A, M, I, C, capital T, H, E, R, principles of capital M, E, T, A, L, L, U, R, G, Y, capital M, E, T, A, L, L, U, R, G, Y, capital M, E, T, A, L, L, U, R, G, Y, Fig. 6.3, A. 6.3, a section of a modern reverberatory furnace during metallurgy, flux is added which combines with gangue to form slag. Slag separates more easily from the ore than the gangue. This way, removal of gangue becomes easier. General principles and processes of isolation of elements 157 through Gibbs energy RGB versus T plots for the formation of the oxides Fig. 6.4, these plots are drawn for free energy changes that occur when 1 gram-mole of oxygen is consumed. The graphical representation of Gibbs energy was first used by H.J.T. Ellingham. This provides a sound basis for considering the choice of reducing agent in the reduction of oxides. This is known as Ellingham diagram. Such diagrams help us in predicting the feasibility of thermal reduction of an ore. As we know, during reduction, the oxide of a metal decomposes and the reducing agent takes away the oxygen. The role of reducing agent is to provide RGV negative and large enough to make the sum of RGV of the two reactions. that is, oxidation of the reducing agent and reduction of the metal oxide negative, MXOSXM solid or Lic 12O2G6.15. If reduction is carried out by carbon, the oxidation of the reducing agent, that is, C, will be there. 2,1-CSOGCOG2 6.16. There may also be complete oxidation of carbon to CO2. 2,2,1,1-CSOGCOG2 Figure 6.4 gives energy RGV versus T plot schematic for the formation of some oxides per mole of oxygen consumed. Allingham diagram. Uncoupling Combing reaction 6.15 and 6.16 we get MXOSCSXMSRLCOG 6.18. Uncoupling reaction 6.15 and 6.17 we have MXOS12CSXMSRL12CO2G 6.19. Similarly, if carbon monoxide is reducing agent, reactions 6.15 and 6.20 given below need to be coupled. COG12O2G CO2G 6.20. Overall reaction will be as follows: MXOSCOGXMSRLCO2G 6.21. Ellingham diagram. Ellingham diagram. Ellingham diagram. Ellingham diagram. Ellingham diagram. Ellingham diagram normally consists of plots of FGV versus T for the formation of oxides of common metals and reducing agents, that is, for the reaction given below. 2xMSO2G2MXOS. In this reaction, gas is consumed in the formation of oxide, hence, molecular randomness decreases in the formation of oxide, which leads to a negative value of S. As a result, sign of TS term in equation 6.14 becomes positive. Subsequently, FGV shifts towards higher side despite rising T. The result is positive slope in the curve for most of the reactions for the formation of MXOS. B. Each plot is a straight line and slopes upwards except when some change in phase SL or LG takes place. The temperature at which such change occurs is indicated by an increase in the slope on positive side, e.g., in the ZNO plot, the melting is indicated by an abrupt change in the curve. Fig. 6.4 C. When temperature is raised, a point is reached in the curve where it crosses RGV 0 line. Below this temperature, RGV for the formation of oxide is negative, so MXO is stable. Above this point, free energy of formation of oxide is positive. The oxide, MXO, will decompose on its own. Similar diagrams are constructed for sulfides and halides also. From them it becomes clear that why reduction of MXS is difficult. Limitations of Ellingham diagram 1. The graph simply indicates whether a reaction is possible or not, that is, the tendency of reduction with a reducing agent is indicated. This is so because it is based only on the thermodynamic concepts. It does not explain the kinetics of the reduction process. It cannot answer questions like how fast reduction can proceed. However, it explains why the reactions are sluggish when every species is in solid state and smooth when the ore melts down. It is interesting to note here that H enthalpy change and the S entropy change values for any chemical reaction remain nearly constant even on varying temperature. So the only dominant variable in equation 6.14 becomes T. However, S depends much on the physical state of the compound. Since entropy depends on disorder or randomness in the system, it will increase if a compound melts SL or vaporizes LG, since molecular randomness increases on changing the phase from solid to liquid or from liquid to gas. 2. The interpretation of RGV is based on KGV, RTL and K, thus it is presumed that the reactants and products are in equilibrium, MXO or LXM and REDO. This is not always true because the reactant product may be solid. In commercial processes, reactants and products are in contact for a short time. General principles and processes of isolation of elements 159. The reactions 6.18 and 6.21 describe the actual reduction of the metal oxide, MXO, that we want to accomplish. The RG0 values for these reactions in general can be obtained from the corresponding FG0 values of oxides. As we have seen, heating, that is, increasing T, favors a negative value of RG0, therefore, the temperature is chosen such that the sum of RG0 in the two combined redox processes is negative. In RG0 versus T plots Ellingham diagram, figure 6.4, this is indicated by the point of intersection of the two curves, that is, the curve for the formation of MXO and that for the formation of the oxide of the reducing substance. After that point, the RG0 value becomes more negative for the combined process, making the reduction of MXO possible. The difference in the two RG0 values after that point determines whether reduction of the oxide of the element of the upper line is feasible by the element of which oxide formation is represented by the lower line. If the difference is large, the reduction is easier. Extraction of iron from its oxides after concentration. Mixture of oxide ores of iron Fe2O3, Fe3O4 is subjected to calcination roasting to remove water, to decompose carbonates and to oxidize sulfides. After that, these are mixed with limestone and coke and fed into a blast furnace from its top, in which the oxide is reduced to the metal. In the blast furnace, 6.4.1 applications suggest a condition under which magnesium could reduce alumina. The two equations are, A4,3-Al-O2,2,3-Al2O3 B 2 mg O2 to MgO at the point of intersection of the Al2O3 and MgO curves marked A in diagram 6.4. The Rg0 becomes 0 for the reaction, 2,3-Al2O3 2 mg to MgO 4,3-Al. Below that point, magnesium can reduce alumina. Although thermodynamically feasible, in practice, magnesium metal is not used for the reduction of alumina in the metallurgy of aluminium. Why temperatures below the point of intersection of Al2O3 and MgO curves, magnesium can reduce alumina. But the process will be uneconomical. Why is the reduction of a metal oxide easier if the metal formed is in liquid state at the temperature of reduction? The entropy is higher if the metal is in liquid state than when it is in solid state. The value of entropy change S of the reduction process is more on positive side when the metal formed is in liquid state and the metal oxide being reduced is in solid state. Thus the value of RGB becomes more on negative side and the reduction becomes easier. Example 6.2 Example 6.2 Example 6.2 Example 6.2 Example 6.2 Solution Example 6.3 Example 6.3 Example 6.3 Example 6.3 Example 6.3 Solution Example 6.1 Example 6.1 Example 6.1 Example 6.1 Example 6 160 Chemistry Figure 6.5, Blast Furnace Figure 6.5 Reduction of iron oxides takes place at different temperature ranges. A blast of hot air is blown from the bottom of the furnace by burning coke in the lower portion to give temperature up to about 2200 K. The burning of coke, therefore, supplies most of the heat required in the process. The CO and heat move to the upper part of the furnace. In upper part, the temperature is lower and the iron oxides Fe2O3 and Fe3O4 coming from the top are reduced in steps to FeO. These reactions can be summarized as follows. At 500-800 K lower temperature range in the blast furnace, Fe2O3 is first reduced to Fe3O4 and then to FeO3 Fe2O3 CO2 Fe3O4 CO2 6.22 Fe3O4 4CO3 Fe4 CO2 6.23 Fe2O3 CO2 FeO CO2 6.24 Limestone is also decomposed to CaO, which removes silicate impurity of the ore as slag. The slag is in molten state and separates out from iron. At 900-1500 K higher temperature range in the blast furnace, CCO2 2CO 6.25 FeOCO FeCO2 6.26 Thermodynamics helps us to understand how coke reduces the oxide and why this furnace is chosen. One of the main reduction steps in this process involves reaction 6.27 given below, FeOSCS FeSLCOG 6.27. This reaction can be seen as a reaction in which two simpler reactions have coupled. In one the reduction of FeO is taking place and in the other, C is being oxidized to CO. FeOS Fe12O2G 6.28 CS12O2G COG 6.29 when both the reactions take place to yield the equation 6.27. The net Gibbs energy change becomes Rg0C, CORg0 FeO, Fe-Rg0 6.30. Naturally, the resultant reaction will take place when the right-hand side in equation 6.30 is negative. In Rg0 versus T plot representing the change Fe-FeO in figure 6.6 goes upward and that representing the change CCOC, CO goes downward. They cross each other at about 1073 K. At temperatures above 1073 K approximately, the CO line is below the Fe-FeO line. So above 1073 K in the range of temperature 900-1500 K coke will reduce FeO and will itself be oxidized to company. Let us try to understand this through figure 6.6. Approximate values of Rg0 are given, at about 1673 K 1400 UC Rg0 value for the reaction. General principles and processes of isolation of elements 161 2 FeO2 FeO2 is 341 kmol1 because it is reverse of Fe-FeO change and for the reaction 2 CO2 2 CORg0 is 447 kmol1. If we calculate Rg0 value for overall reaction 6.27 the value will be 53 kmol1, therefore, reaction 6.27 becomes feasible. In a similar way, the reduction of Fe3O4 and Fe2O3 by CO at relatively lower temperatures can be explained on the basis of lower lying points of intersection of their curves with a CO. CO2 curve. The iron obtained from blast furnace contains about 4 carbon and many impurities in smaller amount, e.g., S, P, C, Mn. This is known as pig iron. It can be molded into variety of shapes. Cast iron is different from pig iron and is made by melting pig iron with scrap iron and coke using hot air blast. It has slightly lower carbon content, about 3, and is extremely hard and brittle. Further reductions: wrought iron or malleable iron is the purest form of commercial iron and is prepared from cast iron by oxidizing impurities in a reverberatory furnace lined with hematite. The hematite oxidizes carbon to carbon monoxide, Fe2O3 Fe3CO6.31. Limestone is added as a flux, and sulfur, silicon and phosphorus are oxidized and passed into the slag. The metal is removed and freed from the slag by passing through rollers. B. Extraction of copper from cuprous oxide. Copper ioxide in the graph of Rg0 versus T for the formation of oxides. Fig. 6.4. The Cu2O line is almost at the top, so it is quite easy to reduce oxide ores of copper directly to the metal by heating with coke. The lines C, CO and C, CO2 are at much lower positions in the graph, particularly after 500-600 K. However, many of the ores are sulfides and some may also contain iron. The sulfide ores are roasted, smelted to give oxides, 2Cu2S3O2, 2Cu2O2, SO2 6.32. The oxide can then be easily reduced to metallic copper using coke, Cu2OC, 2Cu CO 6.33. In actual process, the ore is heated in a reverberatory furnace after mixing with silica. In the furnace, iron oxide slags of iron silicate is formed. Copper is produced in the form of copper matte. This contains Cu2S and Fes. FeOCO2 FeCO3 6.34. Slag copper matte is then charged into silica line converter. Some silica is also added and hot air blast is blown to convert the remaining. Figure 6.6 gives energy versus T plot schematic for the formation of oxides of iron and carbon. Ellingham diagram. 162. Chemistry. Fes, Feo and Cu2S, Cu2O to the metallic copper. Following reactions take place: 2 Fes3O2, 2 Feo2 SO2 6.35, FeOCO2 FeCO3 6.36, 2 Cu2S3O2, 2 Cu2O2 SO2 6.37, 2 Cu2O Cu2S 6 SO2 6.38. The solidified copper obtained has blistered appearance due to the evolution of SO2, and so it is called blister copper. C. Extraction of zinc from zinc oxide. The reduction of zinc oxide is done using coke. The temperature in this case is higher than that in the case of copper. For the purpose of heating, the oxide is made into briquettes with coke and clay. ZnOC coke, 1673 K ZnCO 6.39. The metal is distilled off and collected by rapid chilling. We have seen how principles of thermodynamics are applied to pyrometallurgy. Similar principles are effective in the reductions of metal ions in solution or molten state. Here they are reduced by electrolysis or by adding some reducing element. In the reduction of a molten metal salt, electrolysis is done. Such methods are based on electrochemical principles which could be understood through the equation G0N0F6.40. Here N is the number of electrons and E0 is the electrode potential of the redox couple formed in the system. More reactive metals have large negative values of the electrode potential, so their reduction is difficult. If the difference of two E0 values corresponds to a positive E0 and consequently negative G0 in equation 6.40, then the less reactive metal will come out of the solution and the more reactive metal will go into the solution. E.g., Cu2 Fe S Cu2 6.41. In simple electrolysis, the Mn ions are discharged at negative electrodes cathodes and deposited there. Precautions are taken considering the reactivity of the metal produced and suitable materials are used as electrodes. Sometimes a flux is added for making the molten mass more conducting. In text questions 6.3. The reaction Cr2032 Al2032 CrRg0 421 kJ is thermodynamically feasible as is apparent from the Gibbs energy value. Why does it not take place at room temperature? 6.4. Is it true that under certain conditions, Mg can reduce Al2O3 and Al can reduce MgO? What are those conditions? 6.56, 56, 56, 56, 5, capital E, L, E, C, T, R, O, C, H, E, M, I, C, A, L, capital E, L, E, C, T, R, O, C, H, E, M, I, C, A, L. Principles of metallurgy metallurg. General principles and processes of isolation of elements 163 Aluminium in the metallurgy of aluminium. Purified Al2O3 is mixed with Na3Al6 or Ca2 which lowers the melting point of the mixture and brings conductivity. The fused matrix is electrolyzed. Steel vessel with lining of carbon acts as cathode and graphite anode is used. The overall reaction may be written as 2Al2O3 3C4Al3CO2 6.42. This process of electrolysis is widely known as Hall-Héroult process. Thus electrolysis of the molten mass is carried out in an electrolytic cell using carbon electrodes. The oxygen liberated at anode reacts with the carbon of anode producing CO and CO2. This way for each kg of aluminium produced, about 0.5 kilograms of carbon anode is burnt away. The electrolytic reactions are cathode, Al3 melt 3E Al 6.43 anode, CSO2 melt COG2E 6.44 CS2O2 melt CO2 G4E 6.45 copper from low-grade ores and scraps. Copper is extracted by hydrometallurgy from low-grade ores. It is leached out using acid or bacteria. The solution containing Cu2 is treated with scrap iron or H2 equation 6.40, 6.46. Cu2 Ag H2 Gqs2 Hx 6.46. Besides reductions, some extractions are based on oxidation, particularly for nonmetals. A very common example of extraction based on oxidation is the extraction of chlorine from brine. Chlorine is abundant in seawater as common salt. 2Cl-Ac2H2O-L2O-Ac-H2GCl2G 6.47. The G0 for this reaction is 422 kJ, when it is converted to E0 using G0 Ne0F. We get E0 2.2 V naturally. It will require an external EMF that is greater than 2.2 V, but the electrolysis requires an excess potential to overcome some other hindering reactions. Unit 3. Section 3, 5, 1. Thus, Cl2 is obtained by electrolysis giving out H2 and aqueous NaO as byproducts. Electrolysis of molten NaCl is also carried out, but in that case, nonmetal is produced and not NaO. 6, 6, 6, 6, 6, 6, 6, 6, 6, 6 Oxidation 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 Reduction 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 Fig. 6.7. Electrolytic cell for the extraction of aluminium at a site. Low-grade copper ores are available and zinc and iron scraps are also available. Which of the two scraps would be more suitable for reducing the leached copper ore, and why zinc being above iron in the electrochemical series more reactive metal is zinc? The reduction will be faster in case zinc scraps are used, but zinc is costlier metal than iron, so using iron scraps will be advisable and advantageous. Example 6.4 Example 6.4 Example 6.4 Example 6.4 Example 6.4 Solution 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 Solutio 164 Chemistry as studied earlier. Extraction of gold and silver involves leaching the metal with CN. This is also an oxidation reaction. Ag-Ag-Rao. The metal is later recovered by displacement method. 4OS8CN Ag2H2O-Ag-O2G4OCN2 Ag4OX6.482L-CN2X-CN4-2X6.49. In this reaction, zinc acts as a reducing agent. A metal extracted by any method is usually contaminated with some impurity. For obtaining metals of high purity, several techniques are used depending upon the differences in properties of the metal and the impurity. Some of them are listed below. A distillation B liquation, C electrolysis, D zone refining, E vapor phase refining, F chromatographic methods. These are described in detail here. A distillation. This is very useful for low boiling metals like zinc and mercury. The impure metal is evaporated to obtain the pure metal as distillate. B liquation. In this method, a low melting metal like tin can be made to flow on a sloping surface. In this way it is separated from higher melting impurities. C electrolytic refining. In this method, the impure metal is made to act as anode. A strip of the same metal in pure form is used as cathode. They are put in a suitable electrolytic bath containing soluble salt of the same metal. The more basic metal remains in the solution and the less basic ones go to the anode mud. This process is also explained using the concept of electrode potential, over potential, and gives energy, which you have seen in previous sections. The reactions are anode, MMN cathode, MN 6.50. Copper is refined using an electrolytic method. Anodes are of impure copper and pure copper strips are taken as cathode. The electrolyte is acidified solution of copper sulfate, and the net result of electrolysis is a transfer of copper in pure form from the anode to the cathode. Anode, Cu2E cathode, Cu2E 6.51. Impurities from the blister copper deposit as anode mud, which contains antimony, selenium, tellurium, silver, gold and platinum. Recovery of these elements may meet the cost of refining. Zinc may also be refined this way: 6.7676767677, capital R E F I N G, capital R E F I N G, capital R E F I N G, capital R E F I N I. D-zone refining. This method is based on the principle that the impurities are more soluble in the melt than in the solid state of the metal. A mobile heater surrounding the rod of impure metal is fixed at its one end, figure 6.8. The molten zone moves along with the heater, which is moved forward. As the heater moves forward, the pure metal crystallizes out of the melt left behind and the impurities pass on into the adjacent new molten zone created by movement of heaters. The process is repeated several times and the heater is moved in the same direction again and again. Impurities get concentrated at one end. This end is cut off. This method is very useful for producing semiconductor and other metals of very high purity, e.g., germanium, silicon, boron, gallium and indium. E-vapor phase refining. In this method, the metal is converted into its volatile compound, which is collected and decomposed to give pure metal. So, the two requirements are: I. The metal should form a volatile compound with an available reagent. 2. The volatile compound should be easily decomposable, so that the recovery is easy. Following examples will illustrate this technique. Mond process for refining nickel. In this process, nickel is heated in a stream of carbon monoxide, forming a volatile complex named as nickel tetracarbonyl. This complex is decomposed at higher temperature to obtain pure metal. Ni4CO 330 350 K, Ni-CO4 6.52, Ni-CO4 450 470 K, Ni4CO 6.53. Van Arkel method for refining zirconium or titanium. This method is very useful for removing all the oxygen and nitrogen present in the form of impurity in certain metals like Zr and T. The crude metal is heated in an evacuated vessel with iodine, the metal iodide being more covalent. Volatilysis. Zr2I to Zri4 6.54. The metal iodide is decomposed on a tungsten filament, electrically heated to about 1800 K. The pure metal deposits on the filament. Zri4 Zr2I2 6.55 F. Chromatographic methods. You have learnt about chromatographic technique of purification of substances in Class Sci Unit 12. Figure 6.8, Figure 6.8, Figure 6.8, Figure 6.8, Figure 6.8, Zone refining process. Summary. Although modern metallurgy had exponential growth after Industrial Revolution, many modern concepts in metallurgy have their roots in ancient practices that predated the Industrial Revolution. For over 7,000 years, India has had high tradition of metallurgical skills. Ancient Indian metallurgists have made major contributions which deserve their place in metallurgical history of the world. In the case of zinc and high-carbon steel, ancient India contributed significantly for the development of base for the modern metallurgical advancements which induced metallurgical study leading to Industrial Revolution. Metals are required for a variety of purposes. For this, we need their extraction from the minerals in which they are present and from which their extraction is commercially feasible. These minerals are known as ores. Ores of the metal are associated with many impurities. Removal of these impurities to certain extent is achieved in concentration steps. The concentrated ore is then treated chemically for obtaining the metal. Usually the metal compounds, e.g., oxides, sulfides, are reduced to the metal. The reducing agents used are carbon, CO, or even some metals. Column chromatography is very useful for purification of the elements which are available in minute quantities, and the impurities are not very different in chemical properties from the element to be purified. Aluminium foils are used as wrappers for food materials. The fine dust of the metal is used in paints and lacquers. Aluminium, being highly reactive, is also used in the extraction of chromium and manganese from their oxides. Wires of aluminium are used as electricity conductors. Alloys containing aluminium, being light, are very useful. Copper is used for making wires used in electrical industry and for water and steam pipes. It is also used in several alloys that are rather tougher than the metal itself, e.g., brass with zinc, bronze with tin and coinage alloy with nickel. Zinc is used for galvanizing iron. It is also used in large quantities in batteries. It is constituent of many alloys, e.g., brass, Cu60, Zn40, and German silver Cu2530, Zn2530, Ni40-50. Zinc dust is used as a reducing agent in the manufacture of dye stuffs, paints, etc. Cast iron, which is the most important form of iron, is used for casting stoves, railway sleepers, gutter pipes, toys, etc. It is used in the manufacture of wrought iron and steel. Wrought iron is used in making anchors, wires, bolts, chains, and agricultural implements. Steel finds a number of uses. Alloy steel is obtained when other metals are added to it. Nickel steel is used for making cables, automobiles and aeroplane parts, pendulum, measuring tapes. Chrome steel is used for cutting tools and crushing machines, and stainless steel is used for cycles, automobiles, utensils, pens, etc. 6.86 8 uses of aluminium, copper, zinc, and iron. In these reduction processes, the thermodynamic and electrochemical concepts are given due consideration. The metal oxide reacts with the reducing agent, the oxide is reduced to the metal and the reducing agent is oxidized. In the two reactions, the net Gibbs energy change is negative, which becomes more negative on raising the temperature. Conversion of the physical states from solid to liquid or to gas, and formation of gaseous states favors decrease in the Gibbs energy for the entire system. This concept is graphically displayed in plots of G0 versus T Ellingham diagram for such oxidation-reduction reactions at different temperatures. The concept of electrode potential is useful in the isolation of metals e.g., Al, Ag, A, where the sum of the two redox couples is positive so that the Gibbs energy change is negative. The metals obtained by usual methods still contain minor impurities. Getting pure metals requires refining. Refining process depends upon the differences in properties of the metal and the impurities. Extraction of aluminium is usually carried out from its bauxite ore by leaching it with NaO, sodium aluminate. Thus formed, is separated and then neutralized to give back dehydrated oxide, which is then electrolyzed using cryolite as a flux. Extraction of iron is done by reduction of its oxide ore in blast furnace. Copper is extracted by smelting and heating in a reverberatory furnace. Extraction of zinc from zinc oxides is done using coke. Several methods are employed in refining the metal. Metals, in general, are very widely used and have contributed significantly in the development of a variety of industries. A summary of the occurrence and extraction of some metals is presented in the following table. Metal occurrence. Common method. Remarks of extraction. Aluminium, iron, copper, zinc. 1. Bauxite, Al2O3XH2O2, cryolite, Nal3Alf61, hematite, Fe2032, magnetite, Fe3041, copper pyrites, Cu-Fes22. Copper glance, Cu2S3, malachite, Cu-Co3Cu024, cuprite, Cu2O1, zinc blende or sphalerite, ZnS2. Calamine, Zn-Co33, zincite. ZNO electrolysis of Al2O3 dissolved in molten Na3Alf6 reduction of the oxide with CO and coke in blast furnace roasting of sulfate partially and reduction roasting followed by reduction with coke for the extraction. A good source of electricity is required. Temperature approaching 2170 K is required. It is self-reduction in a specially designed converter. The reduction takes place easily. Sulfuric acid leaching is also used in hydrometallurgy for low-grade ores. The metal may be purified by fractional distillation. 170 Chemistry in Class Xi. You have learnt that the p-block elements are placed in groups 13 to 18 of the periodic table. Their valence shell electronic configuration is Ns2np1-6 except T, which has 1s2 configuration. The properties of p-block elements, like that of others, are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy and electronegativity. The absence of d orbitals in second period and presence of d and f orbitals in heavier elements starting from third period onwards have significant effects on the properties of elements. In addition, the presence of all the three types of elements, metals, metalloids and nonmetals, bring diversification in chemistry of these elements. Having learnt the chemistry of elements of groups 13 and 14 of the p-block of periodic table in Class Xi, you will learn the chemistry of the elements of subsequent groups in this unit. The p-block elements 7. The p-block elements. After studying this unit, you will be able to appreciate general trends in the chemistry of elements of groups 15, 16, 17 and 18. Learn the preparation, properties and uses of dinitrogen and phosphorus and some of their important compounds. Describe the preparation, properties and uses of dioxygen and ozone and chemistry of some simple oxides, no allotropic forms of sulfur. Chemistry of its important compounds and the structures of its oxosides. Describe the preparation, properties and uses of chlorine and hydrochloric acid. Know the chemistry of interhalogens and structures of oxosides of halogens. Enumerate the uses of noble gases, appreciate the importance of these elements and their compounds in our day-to-day life. Objectives: diversity in chemistry is the hallmark of p-block elements, manifested in their ability to react with the elements of S, D and F blocks as well as with their own. Group 15 includes nitrogen, phosphorus, arsenic, antimony, bismuth and moscovium. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Nitrogen and phosphorus are nonmetals, arsenic and antimony metalloids, bismuth and moscovium are typical metals. Molecular nitrogen comprises 78 by volume of the atmosphere. In the Earth's crust, it occurs as sodium nitrate, NaNO3 called Chile saltpeter and potassium nitrate Indian saltpeter. It is found in the form of proteins in plants and animals. Phosphorus occurs in mineral 7.17, 17, 17, 17, 1 group 15 group 15 group 15 group 15 group 15 elements 7, 1 occurrence unit 7. 171 The p-block elements of the apatite family: Ca9PO46, Cax2XF, ClROEG, fluorapatite Ca9PO46. Caf2, which are the main components of phosphate rocks. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as in living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony and bismuth are found mainly as sulfide minerals. Moscovium is a synthetic radioactive element. Its symbol is Mc, atomic number 115, atomic mass 289 and electronic configuration Rn5F14060-107s27 page 3. Due to very short half-life and availability in very little amount, its chemistry is yet to be established. Here, except for moscovium, important atomic and physical properties of other elements of this group along with their electronic configurations are given in Table 7.1. Table 7.1, Atomic and Physical Properties of Group 15 Elements: EIII single bond E element, Be3, Ce3, D white phosphorus, E gray Greek letter alpha form at 38.6 atm, F sublimation temperature, G at 63 K, H gray Greek letter alpha form, molecular N2. Trends of some of the atomic, physical and chemical properties of the group are discussed below. The valence shell electronic configuration of these elements is ns2np3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Covalent and ionic in a particular state radii increase in size down the group. There is a considerable increase in covalent radius from N to P, however. From S to B only a small increase in covalent radius is observed. This is due to the presence of completely filled E under F orbitals in heavier members. Ionization enthalpy decreases down the group due to gradual increase in atomic size, because of the extra stable half-filled p orbitals electronic configuration and smaller size. The ionization enthalpy of the group 15 elements is much greater than that of group 14 elements in the corresponding periods. The order of successive ionization enthalpies, as expected, is I1, I2, I3. Table 7.1. 7, 1, 2 electronic configuration 7, 1, 3 atomic and ionic radii 7, 1, 4 ionization enthalpy property NP is SBB atomic number 7 15 33 51 83 atomic mass G mol 114.0 130.97 74 92 121 75 208 98 electronic configuration E2S22 page 3 Ne3S23 page 3 R3D104S24 page 3 KR4D105S25 page 3 XE4F145D106S26 page 3 ionization enthalpy I1402 1012 947 834 703 IKJ mol 12 2856 1903 1798 1595 1610 3 4577 2910 2736 2443 2466 electronegativity 3.02.12.01.91.9 covalent radius PMA 70 110 121 141 148 ionic radius PM 171B 212B 222B 76C 103C melting point K63 317D 1089 E 904 544 boiling point K77.2 554D 888 F 1860 1837 density GCM 3 298 K 0.879 grams 1 823 5 778 H6 697 9 808 172 Chemistry. The electronegativity value, in general, decreases down the group with increasing atomic size. However, amongst the heavier elements, the difference is not that much pronounced. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas while all others are solids. Metallic character increases down the group. Nitrogen and phosphorus are nonmetals. Arsenic and antimony metalloids, and bismuth is a metal. This is due to decrease in ionization enthalpy and increase in atomic size. The boiling points, in general, increase from top to bottom in the group, but the melting point increases up to arsenic and then decreases up to bismuth. Except nitrogen, all the elements show allotropy, oxidation states and trends in chemical reactivity. The common oxidation states of these elements are -3, 3 and 5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. In fact, last member of the group, bismuth, hardly forms any compound in -3 oxidation state. The stability of 5 oxidation state decreases down the group. The only well-characterized BV compound is Bi5. The stability of 5 oxidation state decreases and that of 3 state increases due to inert pair effect down the group. Besides 5 oxidation state, nitrogen exhibits 1, 2, 4 oxidation states also when it reacts with oxygen. However, it does not form compounds in 5 oxidation state with halogens, as nitrogen does not have d orbitals to accommodate electrons from other elements to form bonds. Phosphorus also shows 1 and 4 oxidation states in some oxosides. In the case of nitrogen, all oxidation states from 1 to 4 tend to disproportionate in acid solution. For example, 3HNO2HNO3H2O2. No, similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into 5 and -3 both in alkali and acid. However, 3 oxidation state in case of arsenic, antimony and bismuth becomes increasingly stable with respect to disproportionation. Nitrogen is restricted to a maximum covalency of 4 since only 4 1s and 3 p orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell, which can be used for bonding covalency and hence expand their covalences in pF6. Anomalous properties of nitrogen. Nitrogen differs from the rest of the members of this group due to its small size. High electronegativity, high ionization enthalpy and non-availability of d orbitals. Nitrogen has unique ability to form Greek letter pi, Greek letter pi, Greek letter pi, Greek letter pipe, Greek letter pi, Greek letter pi, Greek letter pi, Greek letter pi, multiple bonds with itself and with other elements having small size and high electronegativity, e.g., C,O. Heavier elements of this group do not form bonds as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Thus, nitrogen exists as a diatomic molecule with a triple bond 1s and 2p between the two atoms. Consequently, its bond enthalpy 941.4 kJ/mol1 is very high. On the contrary, phosphorus, arsenic and antimony form single bonds as pp, as and sp-sp, while bismuth forms metallic bonds in elemental state. However, the single 7, 1, 5 electronegativity 7, 1, 6 physical properties 7, 1, 7 chemical properties. 173. The p-block element's N bond is weaker than the single pp bond because of high interelectronic repulsion of the non-bonding electrons, owing to the small bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects the chemistry of nitrogen is the absence of d orbitals in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form Greek letter pi, Greek letter pi, Greek letter pi, Greek letter pipe, Greek letter pi, Greek letter pi, Greek letter pi, Greek letter pi bond as the heavier elements can, e.g., R3PO or R3PCH2R alkyl group. Phosphorus and arsenic can form Greek letter pi, 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 Greek letter pi bond also with transition metals when their compounds like PC2H53 and C6H53 act as ligands. High reactivity towards hydrogen. All the elements of group 15 form hydrides of the type A3 where En, P, S, Sp or B. Some of the properties of these hydrides are shown in Table 7.2. The hydrides show regular gradation in their properties. The stability of hydrides decreases from NH3 to Bi3, which can be observed from their bond dissociation enthalpy. Consequently, the reducing character of the hydrides increases. Ammonia is only a mild reducing agent while Bi3 is the strongest reducing agent amongst all the hydrides. Basicity also decreases in the order NH3, PH3, Ash3, SPH3, Bi3, due to high electronegativity and small size of nitrogen. NH3 exhibits hydrogen bonding in solid as well as liquid state. Because of this, it has higher melting and boiling points than that of pH3, to reactivity towards oxygen. All these elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than that of lower oxidation state. Their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic, that of arsenic and antimony amphoteric, and those of bismuth predominantly basic. 3. Reactivity towards halogens. These elements react to form two series of halides, X3 and X5. Nitrogen does not form pentahalide due to non-availability of the d orbitals in its valence shell. Pentahalides are more covalent than trihalides. This is due to the fact that in pentahalides 5 oxidation state exists, while in the case of trihalides 3 oxidation state exists. Since elements in 5 oxidation property NH3 PH3 3 SBH3 P3 melting point K 195, 2, 139, 5, 156, 7, 185, boiling point K 238.5 185, 5, 210, 6, 254, 6, 290, EH distance PN 101.7 141, 9, 151, 9, 170, 7, Ha angle degrees 107.8 93.6 91.8 91.3 FHVKJ, mol 1 minus 46.1 13.466, 4, 145, 1, 278, dis HVEHKJ mol 1, 389, 322, 297, 255, Table 7.2, Properties of Hydrides of Group 15 Elements. 174 Chemistry. Low nitrogen exhibits 5 oxidation state. It does not form pentahalide. Give reason. Nitrogen with N2 has s and p orbitals only. It does not have d orbitals to expand its covalence beyond 4. That is why it does not form pentahalide. pH3 has lower boiling point than NH3. Why? Unlike NH3, pH3 molecules are not associated through hydrogen bonding in liquid state. That is why the boiling point of pH3 is lower than NH3. Preparation dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid dinitrogen B page 77.2 K distills out first, leaving behind liquid oxygen B page 90 K. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. NH4CiAc NaNO2Ac N2G2H2OLNaCl. Small amounts of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by the thermal decomposition of ammonium dichromate. NH42Cr2O7 heat N24H2OCr2O3. Very pure nitrogen can be obtained by the thermal decomposition of sodium or barium azide. By N32Bo3 N27.27, 27, 27, to dinitrogen to nitrogen to nitrogen to nitrogen to nitrogen. Example 7.1 Example 7.1 Example 7.1 Example 7.1 Example 7.1 Solution 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 Solution. Example 7.2 Example 7.2 Example 7.2 Example 7.2 Example 7.2 Solution 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 state will have more polarizing power than in 3 oxidation state. The covalent character of bonds is more in pentahalides. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except P3 are predominantly covalent in nature, i.e. reactivity towards metals. All these elements react with metals to form their binary compounds exhibiting -3 oxidation state, such as Ca3N2 calcium nitride, Ca3P2 calcium phosphide, Na3 is sodium arsenide, Zn3Sb2 zinc antimonide, and Mg3B2 magnesium bismuthide. In text questions 7.1. Why are pentahalides of P, S, Sb and B more covalent than their trihalides? 7.2. Why is B3 the strongest reducing agent amongst all the hydrides of group 15 elements? 175. The P-block elements preparation. Ammonia is present in small quantities in air and soil where it is formed by the decay of nitrogenous organic matter, e.g., urea. NHCO NHHO NHCO NHHO CO2 224233222. On a small scale, ammonia is obtained from ammonium salts which decompose when treated with caustic soda or calcium hydroxide. 2NH4Cl Ca2 2NH3 2H2O CaCl 2NH4 2SO4 2NaO 2NH3 2H2O Na2 SO4. Properties. Dinitrogen is a colorless, odorless, tasteless and non-toxic gas. Nitrogen atom has 2 stable isotopes, 14N and 15N. It has a very low solubility in water, 23.2 cubic centimeters per liter of water at 273 K and 1 bar pressure, and low freezing and boiling points. Table 7.1. Dinitrogen is rather inert at room temperature because of the high bond enthalpy of N bond. Reactivity, however, increases rapidly with rise in temperature. At higher temperatures, it directly combines with some metals to form predominantly ionic nitrides and with nonmetals, covalent nitrides. A few typical reactions are 6 Li and 2 heat 2 Li 3 and 3 mg and 2 heat Mg3 and 2. It combines with hydrogen at about 773 K in the presence of a catalyst Haber's process to form ammonia, N2G3H2G 773 K2NH3G, FHY-46.1 kmol-1 dinitrogen combines with dioxygen only at very high temperature at about 2000 K to form nitric oxide, NO. N2O2G heat 2 No G uses. The main use of dinitrogen is in the manufacture of ammonia and other industrial chemicals containing nitrogen. E.g., calcium cyanamide. It also finds use where an inert atmosphere is required, e.g., in iron and steel industry, inert diluent for reactive chemicals. Liquid dinitrogen is used as a refrigerant to preserve biological materials, food items and in cryosurgery. Write the reaction of thermal decomposition of sodium azide. Thermal decomposition of sodium azide gives dinitrogen gas. 322 non 2 Na 3 N example 7.3 example 7.3 example 7.3 example 7.3 example 7.3 solution in text question 7.3 Why is N2 less reactive at room temperature? 7.3 Ammonia 7.3 Ammonia 7.3 Ammonia 7.3 Ammonia 7.3 Ammonia 176 Chemistry properties. Ammonia is a colorless gas with a pungent odor. Its freezing and boiling points are 198.4 and 239.7 K respectively. In the solid and liquid states, it is associated through hydrogen bonds as in the case of water, and that accounts for its higher melting and boiling points than expected on the basis of its molecular mass. The ammonia molecule is trigonopyramidal with the nitrogen atom at the apex. It has 3 bond pairs and 1 lone pair of electrons as shown in the structure. Ammonia gas is highly soluble in water. Its aqueous solution is weakly basic due to the formation of O ions. NH3GH2OLLNH4-ACOAC. It forms ammonium salts with acids, e.g., NH4Cl, NH42SO4, etc. As a weak base, it precipitates the hydroxides, hydrated oxides in case of some metals of many metals from their salt solutions. For example, 44442 SO2NHOZNNHSO CAC white PPT 342324 ACAC FACLNHO FAO HONHCLS brown PPT XHHHN. Figure 7.1 flow chart for the manufacture of ammonia on a large scale. Ammonia is manufactured by Haber's process. N2G3H2G diaeresis 2NH3G, FH046.1 kmol-1. In accordance with Le Chatelier's principle, high pressure would favor the formation of ammonia. The optimum conditions for the production of ammonia are a pressure of 200 x 105 Pa about 200 atm. A temperature of 700 K and the use of a catalyst such as iron oxide with small amounts of K2O and Al2O3 to increase the rate of attainment of equilibrium. The flowchart for the production of ammonia is shown in Figure 7.1. Earlier, iron was used as a catalyst with molybdenum as a promoter. 177 The p-block elements. Example 7.4 Example 7.4 Example 7.4 Example 7.4 Example 7.4 Why does NH3 act as a Lewis base? Nitrogen atom in NH3 has 1 lone pair of electrons which is available for donation, therefore, it acts as a Lewis base. In text questions 7.4 mention the conditions required to maximize the yield of ammonia. 7.5 How does ammonia react with a solution of Cu2? 7.47 4 oxides of nitrogen solution uses. Ammonia is used to produce various nitrogenous fertilizers: ammonium nitrate, urea, ammonium phosphate and ammonium sulfate, and in the manufacture of some inorganic nitrogen compounds, the most important one being nitric acid. Liquid ammonia is also used as a refrigerant. Nitrogen forms a number of oxides in different oxidation states. The names, formulas, preparation and physical appearance of these oxides are given in Table 7.3. Dinitrogen oxide N2O1 heat 4322NH no NO2HO colorless gas. Nitrogen ioxide neutral nitrogen monoxide no 224242 non-O2 FeSO3H so colorless gas. Nitrogen 2 oxide 2443 FeSO2 NaSO neutral 22HO2 no Table 7.3. Oxides of nitrogen. Oxidation state of nitrogen. Name, formula, common methods of preparation, physical appearance and chemical nature. The presence of a lone pair of electrons on the nitrogen atom of the ammonia molecule makes it a Lewis base. It donates the electron pair and forms linkage with metal ions, and the formation of such complex compounds finds applications in detection of metal ions such as Cu2 Ag, Cu2 Ag 4 NH3 Ag Odiaresis Cu NH3 4 2 Ag Blue Deep Blue Ag Cl Ag Clac Ag S Colorless White PPT 33 2 NH Ag Ag Cl 2 NH Clac AQS White PPT Colorless. 178 Chemistry Table 7.4 Structures of oxides of nitrogen. Lewis. Main resonance structures and bond parameters of oxides are given in Table 7.4. Dinitrogen trioxide N2O3 250 K24232 NO2NO blue solid. Nitrogen 3 oxide acidic. Nitrogen dioxide number 24673 K32222 Pb number 4 number 2 PbOO brown gas. Nitrogen IV oxide acidic. Dinitrogen tetroxide N2O44 cool 224 heat 2 NO colorless solid liquid. Acidic. Nitrogen IV oxide. Dinitrogen pentoxide N2O5534 10325 HNOPO4 HPO2 NO colorless solid. Nitrogen V oxide acidic. 179 The P-block elements preparation in the laboratory. Nitric acid is prepared by heating NO3 or non-O3 and concentrated H2SO4 in a glass retort. 32443 nano-HSO-NaSO-HNO. On a large scale it is prepared mainly by Ostwald's process. This method is based upon catalytic oxidation of NH3 by atmospheric oxygen. PTRH gauge catalyst 322,500 K9 bar, from air 4NHG5OG4 no G6HOG nitric oxide thus formed combines with oxygen giving number 2. 222 no GOG2 no G nitrogen dioxide so formed, dissolves in water to give HNO3. 2233 no GHOL2 HNO AC no G no thus formed is recycled and the aqueous HNO3 can be concentrated by distillation up to 68 by mass. Further concentration to 98 can be achieved by dehydration with concentrated H2SO4. Properties: it is a colorless liquid FP. 231.4 K and B page 355.6 K. Laboratory grade nitric acid contains 68 of the HNO3 by mass and has a specific gravity of 1.504. In the gaseous state, HNO3 exists as a planar molecule with the structure as shown. In aqueous solution, nitric acid behaves as a strong acid giving hydronium and nitrate ions. HNO3 AC H2OLH3O AC number 3 AC. Concentrated nitric acid is a strong oxidizing agent and attacks most metals except noble metals such as gold and platinum. The Y does number 2 dimerase number 2 contains odd number of valence electrons. It behaves as a typical odd molecule. On dimerization, it is converted to stable N2O4 molecule with even number of electrons. In text question 7.6 What is the covalence of nitrogen in N2O5? 7, 5 7, 5 7, 5 7, 5 7, 5 Nitric acid nitrogen forms oxosides such as H2N2O2 hyponitrous acid, HNO2 nitrous acid and HNO3 nitric acid. Amongst them HNO3 is the most important. Solution example 7.5 example 7.5 example 7.5 example 7.5 180 Chemistry 7.67 67 phosphorus allotropic forms products of oxidation depend upon the concentration of the acid, temperature and the nature of the material undergoing oxidation. 3Cu8 HNO3 dilute 3Cu number 322 no 4H2O Cu 4HNO3 con Cu number 322 number 22H2O zinc reacts with dilute nitric acid to give N2O and with concentrated acid to give number 2. 4ZN10 HNO3 dilute 4ZN number 325H2O and 2OZN 4HNO3 conc ZN number 322H2O2 number 2 Some metals e.g. Cr, Al do not dissolve in concentrated nitric acid because of the formation of a passive film of oxide on the surface. Concentrated nitric acid also oxidizes nonmetals and their compounds. Iodine is oxidized to iodic acid, carbon to carbon dioxide, sulfur to H2SO4, and phosphorus to phosphoric acid. I210HNO3-2HYO310No248H2O C4HNO3C2O2H2O4No2SH48No216H2O P428No216H2O number 24H2O brown ring test. The familiar brown ring test for nitrates depends on the ability of Fe2 to reduce nitrates to nitric oxide, which reacts with Fe2 to form a brown-colored complex. The test is usually carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ion, and then carefully adding concentrated sulfuric acid along the sides of the test tube. A brown ring at the interface between the solution and sulfuric acid layers indicates the presence of nitrate ion in solution. Number 3 3Fe2 No 3Fe3 2H2O262OH Fe no Fe H2O5 No 2H2O brown uses. The major use of nitric acid is in the manufacture of ammonium nitrate for fertilizers and other nitrates for use in explosives and pyrotechnics. It is also used for the preparation of nitroglycerin, trinitrotoluene and other organic nitro compounds. Other major uses are in the pickling of stainless steel, etching of metals and as an oxidizer in raw-cut fuels. Phosphorus is found in many allotropic forms, the important ones being white, red and black. White phosphorus is a translucent white waxy solid. It is poisonous, insoluble in water but soluble in carbon disulfide and glows in dark chemiluminescence. It dissolves in boiling NaO solution in an inert atmosphere giving pH 3, 42322 sodium hypophosphite P3 NaO3HO pH 3 NaPO. 181 The p-block element's white phosphorus is less stable and therefore, more reactive than the other solid phases under normal conditions because of angular strain in the P4 molecule where the angles are only 60 degrees. It readily catches fire in air to give dense white fumes of P4O10, 42410 P5OPO. It consists of discrete tetrahedral P4 molecule as shown in Fig. 7.2. Red phosphorus is obtained by heating white phosphorus at 573 K in an inert atmosphere for several days. When red phosphorus is heated under high pressure, a series of phases of black phosphorus is formed. Red phosphorus possesses iron-gray luster. It is odorless, non-poisonous and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus. It does not glow in the dark. It is polymeric, consisting of chains of P4 tetrahedra linked together in the manner as shown in Fig. 7.3. Black phosphorus has two forms: Greek letter alpha black phosphorus and Greek letter beta black phosphorus. Greek letter alpha black phosphorus is formed when red phosphorus is heated in a seal tube at 803 K. It can be sublimed in air and has opaque monoclinic or rhombohedral crystals. It does not oxidize in air. Greek letter beta black phosphorus is prepared by heating white phosphorus at 473 K under high pressure. It does not burn in air up to 673 K. Preparation phosphine is prepared by the reaction of calcium phosphide with water or dilute HCl. Ca3P26H2O3 Ca2,2pH3 Ca3P26HCl3 Ca2,2pH3 in the laboratory. It is prepared by heating white phosphorus with concentrated NaO solution in an inert atmosphere of CO2. 42322P3 NaO3HO pH3 NaPO sodium hypophosphite. When pure, it is non-inflammable but becomes inflammable owing to the presence of P2H4 or P4 vapors. To purify it from the impurities, it is absorbed in high to form phosphonium iodide pH4I, which on treating with CoA gives off phosphine. 423pH icoCHO pH properties. It is a colorless gas with rotten fish smell and is highly poisonous. It explodes in contact with traces of oxidizing agents like HNO3, Cl2 and Br2 vapors. It is slightly soluble in water. The solution of pH3 in water decomposes in presence of light-giving red phosphorus and H2. When absorbed in PPPPPPPPPPPP figure 7.3, red phosphorus PPPP 60 degrees Fig. 7.2 White phosphorus 7 capital P H O S P H I N E capital P H O S P H I N E capital P H O S P H I N E capital P H O 182 Chemistry 7.8. 1 Phosphorus trichloride. Phosphorus forms two types of halides, PX3XF, Cl, Br, and PX5XF, Cl, Br. Preparation: it is obtained by passing dry chlorine over heated white phosphorus 423P6Cl4PCl. It is also obtained by the action of thionyl chloride with white phosphorus. 4232222P8 Socla 4 PCl4 SO2 SCl Properties. It is a colorless oily liquid in hydrolysis in the presence of moisture. 3233 PCl3HOHPO3 HCl. It reacts with organic compounds containing O group such as CH3Cu. C2H5O333333 CH2PCl3 CH HPO2532333 CHO PCl3 CHCl HPO. It has a pyramidal shape as shown, in which phosphorus is sp3 hybridized. 7.87, 87, 87, 87, 8 Phosphorus halides. Phosphorus halides. Phosphorus halides. Phosphorus halides. Phosphorus halides. Uses. The spontaneous combustion of phosphine is technically used in home signals. Containers containing calcium carbide and calcium phosphide are pierced and thrown in the sea when the gases evolved burn and serve as a signal. It is also used in smoke screens. PClClCl7, 8, 2-phosphorus pentachloride copper sulfate or mercuric chloride solution. The corresponding phosphides are obtained. 4332243 QZO2PHQ3HSO23323HGCl2PHHGP6HCl. Phosphine is weakly basic and like ammonia. Gives phosphonium compounds with acids e.g. 3,4-PHHBr example 7.6 example 7.6 example 7.6 example 7.6 example 7.6. In what way can it be proved that pH3 is basic in nature? pH3 reacts with acids like Hi to form pH4i, which shows that it is basic in nature. 3,4-PHI due to lone pair on phosphorus atom. pH3 is acting as a Lewis base in the above reaction. Solution in text questions 7.7. A bond angle in pH4 is higher than that in pH3. YB. What is formed when pH3 reacts with an acid? 7.8. What happens when white phosphorus is heated with concentrated NaO solution in an inert atmosphere of CO2? 183. The p-block elements preparation. Phosphorus pentachloride is prepared by the reaction of white phosphorus with excess of dry chlorine. 425P10Cl4PCl. It can also be prepared by the action of SO2Cl2 on phosphorus. 42252P10SOCl4PCl10. So properties. PCl5 is a yellowish-white powder and in moist air, it hydrolyzes to POCl3 and finally gets converted to phosphoric acid. 523PClHO POCl2HCl 3234 POCl3HOHPO3 HCl. When heated, it sublimes but decomposes on stronger heating. Heat 532PCl. It reacts with organic compounds containing O group, converting them to chloroderivatives. 255253CHO PCl POCl HCl 3533CH2 PCl POCl HCl. Finally, divided metals on heating with PCl5 give corresponding chlorides. 535432 Ag PCl2 Ag Cl PClSN2 PClSNCl2 PCl. It is used in the synthesis of some organic compounds, e.g., C2H5Cl, CH3Cl. In gaseous and liquid phases, it has a trigonal bipyramidal structure as shown. The 3 equatorial PCl bonds are equivalent, while the 2 axial bonds are longer than equatorial bonds. This is due to the fact that the axial bond pairs suffer more repulsion as compared to equatorial bond pairs. PClClClClCl 240 pm 202 pm. Why does PCl3 fume in moisture? PCl3 hydrolyzes in the presence of moisture, giving fumes of HCl. 3233 PCl3HOHPO3 HCl. Are all the 5 bonds in PCl5 molecule equivalent? Justify your answer. PCl5 has a trigonal bipyramidal structure and the 3 equatorial PCl bonds are equivalent, while the 2 axial bonds are different and longer than equatorial bonds. Example 7.7 Example 7.7 Example 7.7 Example 7.7 Example 7.7 Solution Example 7.8 Example 7.8 Example 7.8 Example 7.8 Example 7.8 Solution 184 Chemistry in text questions 7.9 What happens when PCl5 is heated? 7.10 Write a balanced equation for the reaction of PCl5 with water. Phosphorus forms a number of oxosides. The important oxosides of phosphorus with their formulas, methods of preparation and the presence of some characteristic bonds in their structures are given in Table 7.5. Exists in polymeric forms only. Characteristic bonds of HPO33 have been given in the table. The compositions of the oxosides are interrelated in terms of loss or gain of H2O molecule or O atom. The structures of some important oxosides are given next. In oxosides, phosphorus is tetrahedrally surrounded by other atoms. All these acids contain at least one PO bond and one PO bond. The oxosides in which phosphorus has lower oxidation state less than 5 contain, in addition to PO and PO bonds, either PPEG, in H4P2O6 or PHEG, in H3PO2 bonds but not both. These acids in 3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation states. For example, orthophosphorus acid or phosphorus acid on heating disproportionates to give orthophosphoric acid or phosphoric acid and phosphine. 333434 HPO3 HPO pH Table 7.5. Oxosides of phosphorus 7, 97, 97, 97, 97, 9 oxosides of capital P H O S P H O R U S capital P H O S P H O R U S capital P H O S P H O R U S hypophosphorus H3PO211P, a white P4 alkali phosphinic 2P, H1PO orthophosphorus H3PO332P, OP2O3H2O phosphonic 1P, H1PO pyrophosphorus H4P2O532P, OPCl3H3PO32P, H2PO hypophosphoric H4P2O644P, O red P4 alkali 2PO1P, P orthophosphoric H3PO453P, OP4010H2O1PO, pyrophosphoric H4P2O754P, O heat phosphoric 2PO acid 1P, O, P metaphosphoric HPO3N53P, O phosphorus acid 3PO-Br2. Heat in a 3P, O, P seal tube oxidation state of phosphorus characteristic bonds and their number preparation name formula. 185 The p-block elements. The acids which contain pH bond have strong reducing properties. Thus, hypophosphorus acid is a good reducing agent as it contains 2 pH bonds and reduces, for example, OGNO3 to metallic silver. 4-OGNO3 2H2O H3PO2 4Ag4HNO3 H3PO4 These pH bonds are not ionizable to give H and do not play any role in basicity. Only those H atoms which are attached with oxygen in PO form are ionizable and cause the basicity. Thus, H3PO3 and H3PO4 are dibasic and tribasic, respectively, as the structure of H3PO3 has 2 PO bonds and H3PO4 3. Oxygen, sulfur, selenium, tellurium, polonium and livermorium constitute group 16 of the periodic table. This is sometimes known as group of chalcogens. The name is derived from the Greek word for brass and points to the association of sulfur and its congeners with copper. Most copper minerals contain either oxygen or sulfur and frequently the other members of the group. 7.107, 107, 107, 107, 10, Group 16 Group 16 Group 16 Group 16 Group 16 Elements Fig. 7.4 Structures of some important oxosides of phosphorus OPHOHPO orthophosphoric acid 3,4,0,0,0,0 P orthophosphorus acid HPO3,3HHOOPPOHPO pyrophosphoric acid 4,2,7,0,0,0 PHHO hypophosphorus acid HPO3,2,0,0,0,0HO OOPPPO0,0,0,0,0,0,PPPO cyclotrimetaphosphoric acid HPO3,3 polymetaphosphoric acid HPO3N. In text questions 7.11 What is the basicity of H3PO4? 7.12 What happens when H3PO3 is heated? How do you account for the reducing behavior of H3PO2 on the basis of its structure? In H3PO2, 2 H atoms are bonded directly to P atom, which imparts reducing character to the acid. Example 7.9 Example 7.9 Example 7.9 Example 7.9 Example 7.9 Solution 186 Chemistry. Oxygen is the most abundant of all the elements on Earth. Oxygen forms about 46.6 by mass of Earth's crust. Dry air contains 20.946 oxygen by volume. However, the abundance of sulfur in the Earth's crust is only 0.030.1. Combined sulfur exists primarily as sulfates such as gypsum CaSO4.2H2O, Epsom salt MgSO4.7H2O, barite BaSO4 and sulfides such as galena PbS, zinc blende ZnS, copper pyrites CuFes2. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic materials such as eggs, proteins, garlic, onion, mustard, hair and wool contain sulfur. Selenium and tellurium are also found as metal selenides and tellurides in sulfidores. Polonium occurs in nature as a decay product of thorium and uranium minerals. Livermorium is a synthetic radioactive element. Its symbol is Lv, atomic number 116, atomic mass 292 and electronic configuration Rn5F146D107S27 page 4. It has been produced only in a very small amount and has very short half-life, only a small fraction of 1 second. This limits the study of properties of Lv, here, except for livermorium. Important atomic and physical properties of other elements of group 16 along with their electronic configurations are given in table 7.6. Some of the atomic, physical and chemical properties and their trends are discussed below. 7.10. 2 electronic configuration. 7.10. 3 atomic and ionic radii. The elements of group 16 have 6 electrons in the outermost shell and have ns2np4 general electronic configuration. Due to increase in the number of shells, atomic and ionic radii increase from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. A single bond, B approximate value, C at the melting point, G rhombic sulfur, E hexagonal gray, F monoclinic form. 673K oxygen shows oxidation states of 2 and 1 in oxygen fluorides of 2 and O2F2 respectively. Atomic number 8 16 34 52 84. Atomic mass G mol 116.00 32.06 78 96 127 60 210 00. Electronic configuration He2S22 page 4 Net3S23 page 4 R3D104S24 page 4 KR4D105S25 page 4 XE4F145D106S26 page 4 Covalent radius PM66 104 117 137 146 Ionic radius E2PM 140 184 198 221 230 B electron gain enthalpy minus 141 minus 200 minus 195 minus 190 minus 174 at kJ mol 1 ionization enthalpy I1 1314 1941 869 813 kJ mol 1 electronegativity 3.52.58 2.55 2.01 1.76 density GCM 3 298 K 1.32 C 2.06 D 4.19 E 6.25 melting point K 55 393 F 490 725, 520, boiling point K 9718, 958, 1260, 1235, oxidation states minus 2, minus 1, 1, 2 minus 2, 2, 4, 6 minus 2, 2, 4, 6 minus 2, 2, 4, 6 2, 4 property OS table 7.6, some physical properties of group 16 elements 7, 10, 1 occurrence. 187 The p-block elements 7, 10, 4 ionization enthalpy 7, 10, 5 electron gain enthalpy 7, 10, 6 electronegativity ionization enthalpy decreases down the group. It is due to increase in size. However, the elements of this group have lower ionization enthalpy values compared to those of group 15 in the corresponding periods. This is due to the fact that group 15 elements have extra stable half-filled p orbitals electronic configurations. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards the value again becomes less negative up to polonium. Next to fluorine, oxygen has the highest electronegativity value amongst the elements. Within the group, electronegativity decreases with an increase in atomic number. This implies that the metallic character increases from oxygen to polonium. Some of the physical properties of group 16 elements are given in table 7.6. Oxygen and sulfur are nonmetals, selenium and tellurium metalloids, whereas polonium is a metal. Polonium is radioactive and a short-lived half-life 13.8 days. All these elements exhibit allotropy. The melting and boiling points increase with an increase in atomic number down the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule O2 whereas sulfur exists as polyatomic molecule S8. Oxidation states and trends in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. Table 7.6. The stability of 2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2 except in the case of O2 where its oxidation state is 2. Other elements of the group exhibit 2, 4, 6 oxidation states, but 4 and 6 are more common. Sulfur, selenium and tellurium usually show 4 oxidation state in their compounds with oxygen and 6 with fluorine. The stability of 6 oxidation state decreases down the group and stability of 4 oxidation state increases inert pair effect. Bonding in 4 and 6 oxidation states is primarily covalent. Anomalous behavior of oxygen. The anomalous behavior of oxygen, like other members of p block present in second period, is due to its small size and high electronegativity. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. 7.10. 7 Physical properties. 7.10. 8 Chemical properties. Elements of group 16 generally show lower value of first ionization enthalpy compared to the corresponding periods of group 15. Why? Due to extra stable half-filled p orbitals. Electronic configurations of group 15 elements, larger amount of energy is required to remove electrons compared to group 16 elements. Example 7.10. Example 7.10. Example 7.10. Example 7.10. Example 7.10. Solution. 188 Chemistry. 2 Reactivity with oxygen. All these elements form oxides of the EO2 and EO3 types, where Es, Se, Te, Ozone O3 and sulfur dioxide SO2 are gases, while selenium dioxide CO2 is solid. Reducing property of dioxide decreases from SO2 to TO2. SO2 is reducing while TO2 is an oxidizing agent. Besides EO2 type, sulfur, selenium and tellurium also form EO3 type oxides SO3, CO3, TO3. Both types of oxides are acidic in nature. 3 Reactivity towards the halogens. Elements of group 16 form a large number of halides of the type X6, X4 and X2, where E is an element of the group and X is a halogen. The stability of the halides decreases in the order F, ClBr, I. Amongst hexahalides, hexafluorides are the only stable halides. All hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride, SF6, is exceptionally stable for steric reasons. Amongst tetrafluorides, SF4 is a gas, CF4 a liquid and TF4 a solid. These fluorides have sp3 dehybridization and thus have trigonal bipyramidal structures in which one of the equatorial positions is occupied by a lone pair of electrons. This geometry is also regarded as seesaw geometry. All elements except oxygen form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are dimeric in nature. Examples: the absence of d orbitals in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalence exceeds 4. I reactivity with hydrogen. All the elements of group 16 form hydrides of the type H2EO, S, Se, Te, Vo. Some properties of hydrides are given in Table 7.7. Their acidic character increases from H2O to H210. The increase in acidic character can be explained in terms of decrease in bond enthalpy for the dissociation of He bond down the group. Owing to the decrease in enthalpy for the dissociation of He bond down the group, the thermal stability of hydrides also decreases from H2O to H2PO. All the hydrides except water possess reducing property, and this character increases from H2S to H210. Property H2O, H2S, H2Cell, H210, pK 273, 188, 208, 222, BPK 373, 213, 232, 269, HE distance PM 96, 134, 146, 169, Ha angle degrees 104, 92, 91, 90 FHKJ mol 1 minus 286 minus 20, 73, 100 dis HHEKJ mol 1, 463, 347, 276, 238. Dissociation constance 1.8 x 10-16, 1.3 x 10-7, 1.3 x 10-4, 2.3 x 10-3. A aqueous solution. 298K. Table 7.7. Properties of hydrides of group 16 elements. 189. The p-block elements are S2F2, S2Cl2, S2Br2, Se2Cl2 and Se2Br2. These dimeric halides undergo disproportionation as given below. 2 Se2Cl2 Se-Cl4 3 Se7.11 7, 117, 117, 117, 11, Dioxygen preparation. Dioxygen can be obtained in the laboratory by the following ways. I. By heating oxygen-containing salts such as chlorates, nitrates and permanganates. 2. Heat 3,2-MnO2 KClO2 KCl3O2 by the thermal decomposition of the oxides of metals low in the electrochemical series and higher oxides of some metals. 2. Ag2OS4 AgSO2G, 2 Pb3O4S6 PbOSO2G, 2 HgOS2 HgLO2G, 2 PbO2S2 PbOSO2G. 3. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. 2. H2O2 Ag2H2O1O2G. On large scale it can be prepared from water or air. Electrolysis of water leads to the release of hydrogen at the cathode and oxygen at the anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then, the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Properties. Dioxygen is a colorless and odorless gas. Its solubility in water is to the extent of 3.08 cubic centimeters in 100 cubic centimeters water at 293 K, which is just sufficient for the vital support of marine and aquatic life. It liquefies at 90 K and freezes at 55 K. Oxygen atom has 3 stable isotopes, 16O, 17O and 18O, molecular oxygen. O2 is unique in being paramagnetic in spite of having even number of electrons. See Class Psi Chemistry Book, Unit 4. Dioxygen directly reacts with nearly all metals and nonmetals except some metals, e.g., Au, Pt and some noble gases. Its combination with other elements is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external H2S is less acidic than H210. Why? Due to the decrease in bond DH dissociation enthalpy down the group, acidic character increases. Example 7.11 Example 7.11 Example 7.11 Example 7.11 Example 7.11 Solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. In text questions. 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 7.13 List the important sources of sulfur. 7.14 Write the order of thermal stability of the hydrides of group 16 elements. 7.15 Why is H2O a liquid and H2S a gas? 190 Chemistry. A binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with most of the elements of the periodic table to form oxides. In many cases one element forms 2 or more oxides. The oxides vary widely in their nature and properties. Oxides can be simple, e.g., MgO, Al2O3 or mixed Pb3O4, Fe3O4. Simple oxides can be classified on the basis of their acidic, basic or amphoteric character. An oxide that combines with water to give an acid is termed acidic oxide, e.g., SO2, Cl2O7, CO2, N2O5. For example, SO2 combines with water to give H2SO3, an acid 2,2,2,3-SOHOH. So as a general rule, only nonmetal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character, e.g., Mn2O7, Cro3, B2O5. The oxides which give a base with water are known as basic oxides, e.g., Na2O, CaO, BaO. For example, CaO combines with water to give CaO2, a base. 2,2-CaOHO CaO 7.16 Which of the following does not react with oxygen directly? Zn, T, Pt. Fe 7.17 Complete the following reactions. IC2H4O224Al3O27.127, 127, 127, 127, 12. Simple oxides. In text questions. 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 Heating is required as bond dissociation. Enthalpy of oxygen oxygen double bond is high, 493.4 kJ mol 1. Some of the reactions of dioxygen with metals. Non-metals and other compounds are given below. 22 CaO2 CaO2 234 Al3O2 Al04 2410 P5O PO2 2 COCO to ZNS3O2 to ZNO2 SO2 4222 CH2O CO2 HO. Some compounds are catalytically oxidized. For example, 25VO2 232 SO2 SO2 CuCl2 224 HClO2 Cl2 HO. Uses. In addition to its importance in normal respiration and combustion processes, Oxygen is used in oxyacetylene welding, in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high-altitude flying and in mountaineering. The combustion of fuels, e.g., hydrazines and liquid oxygen, provides tremendous thrust in rockets. 191. The p-block elements in general. Metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acids as well as alkalis. For example, Al2O3 reacts with acids as well as alkalis. 3262 322 3236 Al-HOLO6 HCl9 HO26 ClAc-AQSL Al-ALO6 NaO3 HO2 NOC-ACOSL. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Examples of neutral oxides are CO, NO and N2O. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in the atmosphere at sea level, at a height of about 20 kilometers. It is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet UV radiations. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone 10 occurs. The product is known as ozonized oxygen 3O2203HV298K142 Since the formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. If concentrations of ozone greater than 10% are required, a battery of ozonizers can be used, and pure ozone BP 101.1 K can be condensed in a vessel surrounded by liquid oxygen. Properties. Pure ozone is a pale blue gas, dark blue liquid and violet black solid. Ozone has a characteristic smell and in small concentrations it is harmless. However, if the concentration rises above about 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in the liberation of heat. H is negative and an increase in entropy S is positive. These two effects reinforce each other, resulting in large negative Gibbs energy change G for its conversion into oxygen. It is not really surprising, therefore, high concentrations of ozone can be dangerously explosive. Due to the ease with which it liberates atoms of nascent oxygen O3 O2O, it acts as a powerful oxidizing agent. For example, it oxidizes lead sulfate to lead sulfate and iodide ions to iodine. PbSS4O3G So4S4O2G2IAC H2OLO3G2OAC I2SO2G. When ozone reacts with an excess of potassium iodide solution buffered with a borate buffer pH 9.2. Iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating O3 gas. 7, 137, 137, 137, 137, 13, ozone. Sulfur forms numerous allotropes, of which the yellow rhombic Greek letter alpha sulfur and monoclinic Greek letter beta sulfur forms are the most important. The stable form at room temperature is rhombic sulfur, which transforms to monoclinic sulfur when heated above 369 K. Rhombic sulfur Greek letter alpha 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 sulfur. This allotrope is yellow in color. M page 385.8 K and specific gravity 2.06. Rhombic sulfur crystals are formed on evaporating the solution of roll sulfur in CS2. It is insoluble in water but dissolves to some extent in benzene, alcohol and ether. It is readily soluble in CS2. Monoclinic sulfur Greek letter beta 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 sulfur. Its MP is 393 K and specific gravity 1.98. It is soluble in CS2. This form of sulfur is prepared by melting rhombic sulfur. In addition, cooling till crust is formed. 2 holes are made in the crust and the remaining liquid poured out. On removing the crust, colorless needle-shaped crystals of Greek letter beta sulfur are formed. It is stable above 369 K and transforms into Greek letter alpha sulfur below it. Conversely, Greek letter alpha sulfur is stable below 369 K and transforms into Greek letter beta sulfur above this. At 369 K both the forms are stable. This temperature is called transition temperature. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structures. The S8 ring in both the forms is puckered and has a crown shape. The molecular dimensions are given in figure 7.5a. 7.14 sulfur 7.14 sulfur 7.14 sulfur 7.14 sulfur 7.14 sulfur allotropic forms. Experiments have shown that nitrogen oxides, particularly nitrogen monoxide, combine very rapidly with ozone, and there is, thus, the possibility that nitrogen oxides emitted from the exhaust systems of supersonic jet aeroplanes might be slowly depleting the concentration of the ozone layer in the upper atmosphere. 322 No GOG. Another threat to this ozone layer is probably posed by the use of freons, which are used in aerosol sprays and as refrigerants. The two oxygen-oxygen bond lengths in the ozone molecule are identical 128 pm, and the molecule is angular as expected with a bond angle of about 117 It is a resonance hybrid of two main forms. 7.18 Why does O3 act as a powerful oxidizing agent? 7.19 How is O3 estimated quantitatively? In text questions. Uses. It is used as a germicide, disinfectant, and for sterilizing water. It is also used for bleaching oils, ivory, flour, starch, etc. It acts as an oxidizing agent in the manufacture of potassium permanganate. 193 The p-block elements which form of sulfur shows paramagnetic behavior in vapor state. Sulfur partly exists as S2 molecule which has two unpaired electrons in the antibonding Greek letter pi orbitals like O2 and, hence, exhibits paramagnetism. Example 7.12 Example 7.12 Example 7.12 Example 7.12 Example 7.12 Solution. Several other modifications of sulfur containing 620 sulfur atoms per ring have been synthesized in the last 2 decades. In cyclo S6, the ring adopts the chair form and the molecular dimensions are as shown in figure 7.5b. At elevated temperatures 1000 K, S2 is the dominant species and is paramagnetic like O2. Preparation sulfur dioxide is formed together with a little 6,8 sulfur trioxide when sulfur is burnt in air or oxygen, SSO2G. SO2G in the laboratory. It is readily generated by treating a sulfide with dilute sulfuric acid. So32Ac2H2H2OL. So2G industrially, it is produced as a byproduct of the roasting of sulfidors. 222324 Fs11O2 Fe08 SOG GSS. The gas after drying is liquefied under pressure and stored in steel cylinders. Properties: sulfur dioxide is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmospheres and boils at 263 K. Sulfur dioxide, when passed through water, forms a solution of sulfurous acid, SOGHOLH. So2223Ac. It reacts readily with sodium hydroxide solution, forming sodium sulfide, which then reacts with more sulfur dioxide to form sodium hydrogen sulfide. 2 NaO. So2 Na2 So3 H2O Na2 So3 H2O. So22 NaSO3. In its reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. 7.15 157 157 157 Sulfur dioxide A B Fig. 7.5 The structures of a S8 ring in rhombic sulfur and BS6 form. 194 Chemistry. Sulfur forms a number of oxosides such as H2SO3, H2S2O3, H2S2O4, H2S2O5, H2SXO6X2-5, H2SO4, H2S2O7, H2SO5, H2S2O8. Some of these acids are unstable and cannot be isolated. They are known in aqueous solution or in the form of their salts. Structures of some important oxosides are shown in figure 7.6, 7.16 7, 167, 167, 167, 16. Oxosides of sulfur Fig. 7.6 Structures of some important oxosides of sulfur. Sulfur dioxide reacts with chlorine in the presence of charcoal, which acts as a catalyst to give sulfuryl chloride, So2Cl2. It is oxidized to sulfur trioxide by oxygen in the presence of vanadium V oxide catalyst, So2GCl2G. So2Cl2L25VO2 232 SOGOG2 SOG. When moist, sulfur dioxide behaves as a reducing agent. For example, it converts iron 3 ions to iron 2 ions and decolorizes acidified potassium permanganate 7 solution. The latter reaction is a convenient test for the gas. 3222242224242 Fe. So2HO2 Fe. So4H5 So2MnO2HO5 So4H2Mn. The molecule of So2 is angular. It is a resonance hybrid of the two canonical forms. Uses. Sulfur dioxide is used I in refining petroleum and sugar, 2 inches bleaching wool and silk, and 3 as an anti-chlor. Disinfectant and preservative. Sulfuric acid, sodium hydrogen sulfide and calcium hydrogen sulfite. Industrial chemicals are manufactured from sulfur dioxide. Liquid SO2 is used as a solvent to dissolve a number of organic and inorganic chemicals. In text questions 7.20 What happens when sulfur dioxide is passed through an aqueous solution of Fe3 salt? 7.21 Comment on the nature of two SO bonds formed in SO2 molecule. Are the two SO bonds in this molecule equal? 7.22 How is the presence of SO2 detected? 195 The P-block elements manufacture. Sulfuric acid is one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by the contact process, which involves 3 steps: I. Burning of sulfur or sulfate ores in air to generate SO2. 2. Conversion of SO2 to SO3 by the reaction with oxygen in the presence of a catalyst V2O5, and 3. Absorption of SO3 and H2SO4 to give oleum H2S2O7. A flow diagram for the manufacture of sulfuric acid is shown in Figure 7.7. The SO2 produced is purified by removing dust and other impurities such as arsenic compounds. The key step in the manufacture of H2SO4 is the catalytic oxidation of SO2 with O2 to give SO3 in the presence of V2O5 catalyst. 25VO2 232 SOGOG2 SOG1R 196.6 kmol 0H. The reaction is exothermic, reversible, and the forward reaction leads to a decrease in volume. Therefore, low temperature and high pressure are the favorable conditions for maximum yield, but the temperature should not be very low, otherwise rate of reaction will become slow. In practice, the plant is operated at a pressure of 2 bar and a temperature of 720 K. The SO3 gas from the catalytic converter is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, 2 steps are carried out simultaneously to make the process a continuous one and also to reduce the cost. SO3 H2SO4 H2S2O7 oleum. The sulfuric acid obtained by contact process is 96-98 pure. 7.177, 177, 177, 177, 17, sulfuric acid dust precipitator sulfur burner waste water waste acid drying tower washing and cooling tower arsenic purifier containing gelatinous hydrated ferric oxide catalytic converter oleum HSO227 SO3 conc HSO24 dry SO2 water spray conc HSO spray 24 impure SO2 sulfur air preheater quartz VO25 Fig. 7.7 Flow diagram for the manufacture of sulfuric acid. 196 Chemistry properties. Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 K. The acid freezes at 283 K and boils at 611 K. It dissolves in water with the evolution of a large quantity of heat, hence. Care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly into water with constant stirring. The chemical reactions of sulfuric acid are as a result of the following characteristics: a low volatility, B strong acidic character, C strong affinity for water, and D ability to act as an oxidizing agent. In aqueous solution, sulfuric acid ionizes in 2 steps. H2SO4 AC H2OL H3O AC HSO4 AC 1 AC very large 1 AC 10 HSO4 AC H2OL H3O AC SO4 2 AC 2 AC 1.2 x 10-2. The larger value of 1 AC 1 AC 10 means that H2SO4 is largely dissociated into H and HSO4. Greater the value of dissociation constant K, the stronger is the acid. The acid forms 2 series of salts, normal sulfates such as sodium sulfate and copper sulfate, and acid sulfates, e.g., sodium hydrogen sulfate. Sulfuric acid, because of its low volatility, can be used to manufacture more volatile acids from their corresponding salts. 2MXH2SO4 2HXM2SO4XF, Cl. Number 3M metal concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid, provided the gases do not react with the acid. Sulfuric acid removes water from organic compounds. It is evident by its charring action on carbohydrates. C12H22O1124H SO12C11H2O. Hot concentrated sulfuric acid is a moderately strong oxidizing agent. In this respect, It is intermediate between phosphoric and nitric acids. Both metals and nonmetals are oxidized by concentrated sulfuric acid, which is reduced to SO2. Cu2H2SO4 Conc-SO4 SO2 2H2OS 2H2SO4 Conc3 SO2 2H2O C2H2SO4 Conc-CO2 2SO2 2H2O Uses. Sulfuric acid is a very important industrial chemical. A nation's industrial strength can be judged by the quantity of sulfuric acid it produces and consumes. It is needed for the manufacture of hundreds of other compounds and also in many industrial processes. The bulk of sulfuric acid produced is used in the manufacture of fertilizers, e.g., ammonium sulfate, superphosphate. Other uses are in a petroleum refining, B, manufacture of pigments, paints and dyestuff, intermediate, C, detergent industry, D, metallurgical applications, e.g., cleansing metals before enameling, electroplating and galvanizing, E, storage batteries, F, in the manufacture of nitrocellulose products, and G, as a laboratory reagent. 197. The P-block elements fluorine, chlorine, bromine, iodine, astadine and tannocine are members of group 17. These are collectively known as the halogens. Greek halo means salt and genes means born, that is, salt producers. The halogens are highly reactive non-metallic elements. Like groups 1 and 2, the elements of group 17 show great similarity amongst themselves. That much similarity is not found in the elements of other groups of the periodic table. Also, there is a regular gradation in their physical and chemical properties. Astadine and tannocine are radioactive elements. Fluorine and chlorine are fairly abundant, while bromine and iodine less so. Fluorine is present mainly as insoluble fluorides, fluorspar Ca2, chrylite Na3Alf6 and fluoropatite 3Ca3PO42 Ca2, and small quantities are present in soil, river water, plants and bones and teeth of animals. Seawater contains chlorides, bromides and iodides of sodium, potassium, magnesium and calcium, but is mainly sodium chloride solution 2.5 by mass. The deposits of dried up seas contain these compounds, e.g., sodium chloride and carnallite, KCl-MgCl2.6H2O. Certain forms of marine life contain iodine in their systems. Various seaweeds, for example, contain up to 0.5 of iodine, and Chile saltpeter contains up to 0.2 of sodium iodate. Here important atomic and physical properties of group 17 elements other than tannocine are given along with their electronic configurations. Table 7.8, page 198. Tannocine is a synthetic radioactive element. Its symbol is Ts, atomic number 117, atomic mass 294 and electronic configuration Rn5F14060-107s27, page 5. Only very small amount of the element could be prepared, also its half-life is in milliseconds only. That is why its chemistry could not be established. 7. 1-8, 1 occurrence 7.187, 187, 1-8, 7, 187, 1-8, Group 17 Group 17 Group 17 Group 17 Group 17 Elements in text questions 7.23 mention 3 areas in which H2SO4 plays an important role. 7.24 Write the conditions to maximize the yield of H2SO4 by contact process. 7.25 Why is kCa214 H2SO4 in water? What happens when a concentrated H2SO4 is added to calcium fluoride 2SO3 is passed through water? It forms hydrogen fluoride 2244 CaF so CaSO2HF2 it dissolves SO3 to give H2SO4. 3224 SOHOH so solution, capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I O N, capital S O L U T I. Example 7.13 Example 7.13 Example 7.13 Example 7.13 Example 7.13 The trends of some of the atomic, physical and chemical properties are discussed below. All these elements have 7 electrons in their outermost shell, Ns2 and P5, which is 1 electron short of the next noble gas. The halogens have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. The atomic radius of fluorine, like the other elements of second period, is extremely small. Atomic and ionic radii increase from fluorine to iodine due to increasing number of quantum shells. They have little tendency to lose electron, thus they have very high ionization enthalpy. Due to increase in atomic size, ionization enthalpy decreases down the group. Halogens have maximum negative electron gain enthalpy in the corresponding periods. This is due to the fact that the atoms of these elements have only one electron less than stable noble gas configurations. Electron gain enthalpy of the elements of a group becomes less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to small size of fluorine atom. As a result, there are strong interelectronic repulsions in the relatively small 2p orbitals of fluorine, and thus, the incoming electron does not experience much attraction. 7, 1, 8, 3 atomic and ionic radii 7, 1, 8, 4 ionization enthalpy 7, 1, 8, 5 electron gain enthalpy 7, 1, 8, 2 electronic configuration property FClBr iota atomic number 9 17 35 53 85 atomic mass G mol 1 19.0035.45 79.90 126.90 210 electronic configuration He 2s22 page 5 Na 3s23 page 5 R3d 104 s24 page 5 kr4d 105 s25 page 5 xe4 f145 d106 s26 page 5 covalent radius pm64 99 114 133 ionic radius xpm 133 184 196 220 ionization enthalpy kj mol 1 1680 1256 1142 1008 electron gain enthalpy kj mol 1 -333 -349 -325 -296 electronegativity 43.23.02.72.2 Hidx kj mol 1 515 381 347 305 F2Cl2Br2I2 melting point K54.4 172.0 265.8 386.6 boiling point K84.9 239.0 332.5 458.2 density GCM3 1.5 85 C 1.66 203 C3.19 273 C4.94 293 D distance x PM 143 199 228 266 bond dissociation enthalpy 158.8 242 6 192 8 151 1 kj mol 1 of A2.87 1.36 1.090.54 Table 7.8 Atomic and physical properties of halogens are radioactive. B Pauling scale. C for the liquid at temperatures K given in the parentheses. D solid. E the half-cell reaction is X2G2E2X-AC. 199 The p-block elements oxidation states and trends in chemical reactivity. All the halogens exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit 1, 3, 5 and 7 oxidation states, also as explained below. 7, 1, 8 chemical properties. Halogen atom in ground state other than fluorine. 1 unpaired electron accounts for -1 or 1 oxidation states. First excited state. 3 unpaired electrons account for 3 oxidation states. Second excited state. Third excited state. 5 unpaired electrons account for 5 oxidation states. 7 unpaired electrons account for 7 oxidation state. NSNPND 7, 1, 8, 6 electronegativity 7, 1, 8, 7 physical properties. They have very high electronegativity. The electronegativity decreases down the group. Fluorine is the most electronegative element in the periodic table. Halogens have maximum negative electron gain enthalpy in the respective periods of the periodic table. Why halogens have the smallest size in their respective periods and therefore high effective nuclear charge? As a consequence, they readily accept 1 electron to acquire noble gas electronic configuration. Example 7.14 Example 7.14 Example 7.14 Example 7.14 Example 7.14 Solution. Capital S O L U T I O N capital S O L U T I O N capital S O L U T I O N capital S O L U T I. Although electron gain enthalpy of fluorine is less negative as compared to chlorine, fluorine is a stronger oxidizing agent than chlorine. Why? It is due to a low enthalpy of dissociation of FF bond. Table 7.8. Too high hydration enthalpy of F. Table 7.8. Example 7.15 Example 7.15 Example 7.15 Example 7.15 Example 7.15 Solution Halogens display smooth variations in their physical properties. Fluorine and chlorine are gases, bromine is a liquid and iodine is a solid. Their melting and boiling points steadily increase with atomic number. All halogens are colored. This is due to absorption of radiations in visible region, which results in the excitation of outer electrons to higher energy level. By absorbing different quanta of radiation, they display different colors. For example, F2 has yellow, Cl2, greenish yellow, Br2, red, and I2, violet color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons to give colored solutions. One curious anomaly we notice from Table 7.8 is the smaller enthalpy of dissociation of F2 compared to that of Cl2, whereas XX bond dissociation enthalpies from chlorine onwards show the expected trend, Cl, ClBr, I. A reason for this anomaly is the relatively large electron-electron repulsion among the lone pairs in F2 molecule, where they are much closer to each other than in case of Cl2. 200 Chemistry. The higher oxidation states of chlorine, bromine, and iodine are realized mainly when the halogens are in combination with the small and highly electronegative fluorine and oxygen atoms. E.g., in interhalogens, oxides and oxosides, the oxidation states of 4 and 6 occur in the oxides and oxosides of chlorine and bromine. The fluorine atom has no d orbitals in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with metals and nonmetals to form halides. The reactivity of the halogens decreases down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogens. F2 is the strongest oxidizing halogen and it oxidizes other halide ions in solution or even in the solid phase. In general, a halogen oxidizes halide ions of higher atomic number, F2 2x2 Fx2xCl. Br or ICl2 2x2 ClX 2x Br or IBr2 2I2 Bri2. The decreasing oxidizing ability of the halogens in aqueous solution down the group is evident from their standard electrode potentials, Table 7.8, which are dependent on the parameters indicated below. Aldehydes 1221 xgxgxgx Act 2 HHHVVV. The relative oxidizing power of halogens can further be illustrated by their reactions with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acids. The reaction of iodine with water is non-spontaneous. In fact, I can be oxidized by oxygen in acidic medium, just the reverse of the reaction observed with fluorine. 222222222 Fg2HO4H4FOGAC-AQLXGHOHX-HOXAC-AQL, where XCl4I4HOG2I2HOGAC-SL. Anomalous behavior of fluorine. Like other elements of p block present in second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity, and electrode potentials are all higher for fluorine than expected from the trend set by other halogens. Also, ionic and covalent radii, MP and BP, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, highest electronegativity, low FF bond dissociation enthalpy, and non-availability of d orbitals in valence shell. Most of the reactions of fluorine are exothermic due to the small and strong bond formed by it with other elements. It forms only one oxoside while other halogens form a number of oxosides. Hydrogen fluoride is a liquid BP. 293 K. Due to strong hydrogen bonding, hydrogen bond is formed in HF due to small size and high. 201 The p-block elements electronegativity of fluorine. Other hydrogen halides which have bigger size and less electronegativity are gases. I reactivity towards hydrogen. They all react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. Hydrogen halides dissolve in water to form hydrohalic acids. Some of the properties of hydrogen halides are given in Table 7.9. The acidic strength of these acids varies in the order HF-HCl-HBr. High. The stability of these halides decreases down the group due to decrease in bond HX dissociation enthalpy in the order HF, HCl, HBr, HI. Property HF-HCl-HBr high melting point K 190 159 185 222 boiling point K 293 189 206 238 bond length H, XPM 91.7 127, 4, 141, 4, 160, 9, dis HVKJ mol 1, 574, 432, 363, 295. PCA 3.2-7.0-9.5-10.0 Table 7.9. Properties of hydrogen halides. 2 Reactivity towards oxygen. Halogens form many oxides with oxygen, but most of them are unstable. Fluorine forms 2 oxides of 2 and O2F2. However, only if 2 is thermally stable at 298 K. These oxides are essentially oxygen fluorides because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to Pu6 and the reaction is used in removing plutonium as Pu6 from spent nuclear fuel. Chlorine, bromine and iodine form oxides in which the oxidation states of these halogens range from 1 to 7. A combination of kinetic and thermodynamic factors led to the generally decreasing order of stability of oxides formed by halogens, I-ClBr. Higher stability of oxides of iodine is due to greater polarizability of bond between iodine and oxygen. In the case of chlorine, multiple bond formation between chlorine and oxygen takes place due to availability of d orbitals. This leads to increase in stability. Bromine lacks both the characteristics, hence stability of oxides of bromine is least. The higher oxides of halogens tend to be more stable than the lower ones. Chlorine oxides, Cl2O, Clo2, Cl2O6 and Cl2O7 are highly reactive oxidizing agents and tend to explode. Clo2 is used as a bleaching agent for paper pulp and textiles and in water treatment. The bromine oxides, Br2O, Bro2, Bro3 are the least stable halogen oxides middle row anomally and exist only at low temperatures. They are very powerful oxidizing agents. The iodine oxides, I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in the estimation of carbon monoxide 3 reactivity towards metals. Halogens react with metals to form metal halides. For example, bromine reacts with magnesium to give magnesium bromide. 202 Chemistry 2 mg SbRlMgBr. The ionic character of the halides decreases in the order Mf, Mcl, Mbr, Mi where M is a monovalent metal. If a metal exhibits more than one oxidation state, the halides in higher oxidation state will be more covalent than the one in lower oxidation state. For example, SnCl4, PbCl4, SbCl5 and UF6 are more covalent than SnCl2, PbCl2, SbCl3 and UF4 respectively. High reactivity of halogens towards other halogens. Halogens combine amongst themselves to form a number of compounds known as interhalogens of the types XX, XX3, XX5 and XX7 where X is a larger size halogen and X is smaller size halogen. Fluorine exhibits only -1 oxidation state whereas other halogens exhibit 1, 3, 5 and 7 oxidation states also. Explain. Fluorine is the most electronegative element and cannot exhibit any positive oxidation state. Other halogens have d orbitals and therefore, can expand their octets and show 1, 3, 5 and 7 oxidation states also. Example 7.16 Example 7.16 Example 7.16 Example 7.16 Example 7.16 Solution in text questions 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 7.26 Considering the parameters such as bond dissociation, enthalpy, electron gain enthalpy and hydration enthalpy, compare the oxidizing power of F2 and Cl2. 7.27 Give 2 examples to show the anomalous behavior of fluorine. 7.28 C is the greatest source of some halogens. Comment. Chlorine was discovered in 1774 by Scheele by the action of HCl on MnO2. In 1810 Davy established its elementary nature and suggested the name chlorine on account of its color Greek, chloris greenish yellow. Preparation. It can be prepared by any one of the following methods. I. By heating manganese dioxide with concentrated hydrochloric acid. MnO2,4HCl MnCl2 Cl2 However, a mixture of common salt and concentrated H2SO4 is used in place of HCl. 4-NaCl MnO2,4H2SO4 MnCl2,4-NaSO4 2H2O Cl2 by the action of HCl on potassium permanganate. 2K-MnO4-16HCl2 KCl2 MnCl2 8H2O5 Cl2 Manufacture of chlorine I. Deacon's process, by oxidation of hydrogen chloride gas by atmospheric oxygen in the presence of CuCl2 catalyst at 723 K. 2CuCl2 224HClO2 Cl2HO2 Electrolytic process, chlorine is obtained by the electrolysis of brine concentrated NaCl solution. Chlorine is liberated at anode. It is also obtained as a byproduct in many chemical industries. 7.197, 197, 197, 197, 19, chlorine 203 The P-block element's properties. It is a greenish-yellow gas with pungent and suffocating odor. It is about 25 times heavier than air. It can be liquefied easily into greenish-yellow liquid which boils at 239 K. It is soluble in water. Chlorine reacts with a number of metals and nonmetals to form chlorides 2Al3Cl2 2Alcl3, P46Cl2 4PCl3 2NaCl2 2NaCl, S84Cl2 4S2Cl2 2Fe3Cl2 2FeCl3. It has great affinity for hydrogen. It reacts with compounds containing hydrogen to form HCl. 2-2-2-2-10-16 2HCl 2HCl HSCl 2HCl SCH 8Cl 16 HCl10C with cold and dilute alkalis. Chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkalis it gives chloride and chlorate. 2 NaOCl 2 NaCl NaOCl H2O cold and dilute 6 NaO3Cl 5 NaCl NaCl 3 H2O hot and conc. With dry slaked lime it gives bleaching powder. 2 CaO 2 2Cl 2 CaOCl 2 CaCl 2 H2O. The composition of bleaching powder is CaOCl 2 CaCl 2 CaO 2.2 H2O. Chlorine reacts with hydrocarbons and gives substitution products with saturated hydrocarbons and addition products with unsaturated hydrocarbons. For example, CH4Cl2 UVCH3Cl HCl methane methyl chloride C2H4Cl2 room temp C2H4Cl2 ethene 1. 2-dichloroethane chlorine water on standing loses its yellow color due to the formation of HCl and HCl. Hypochlorous acid HCl so formed, gives nascent oxygen which is responsible for oxidizing and bleaching properties of chlorine. Chlorine oxidizes ferrous to ferric and sulfite to sulfate. Chlorine oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In the presence of water they form sulfuric acid and iodic acid respectively. 2-FeSO4H2SO4Cl2 Fe2SO4 3-2HCl Na2SO3Cl2H2O Na2SO4 2HCl SO2 2H2OCl2H2SO4 2HCl I26H2O 5Cl2 2HEO3 10HCl. Chlorine is a powerful bleaching agent. Bleaching action is due to oxidation. It bleaches vegetable or organic matter in the presence of moisture. Bleaching effect of chlorine is permanent. Cl2H2O 2HCl O colored substance O colorless substance. 204 Chemistry. Write the balanced chemical equation for the reaction of Cl2 with hot and concentrated NaO. Is this reaction a disproportionation reaction? Justify 3Cl2 6 NaO 5 NaCl NaCl 3 H2O. Yes, chlorine from 0 oxidation state is changed to -1 and 5 oxidation states. Example 7.17 Example 7.17 Example 7.17 Example 7.17 Example 7.17 Solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. Glauber prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davy in 1810 showed that it is a compound of hydrogen and chlorine. Preparation in laboratory. It is prepared by heating sodium chloride with concentrated sulfuric acid. NaClH2SO4 420K NaSO4 HCl NaSO4 NaCl 823K Na2SO4 HCl. HCl gas can be dried by passing through concentrated sulfuric acid. Properties. It is a colorless and pungent smelling gas. It is easily liquefied to a colorless liquid B page 189K and freezes to a white crystalline solid FP 159K. It is extremely soluble in water and ionizes as follows. 723-AcGHOHOCl10-AcAQLK. Its aqueous solution is called hydrochloric acid. High value of dissociation constant Ca indicates that it is a strong acid in water. It reacts with NH3 and gives white fumes of NH4Cl. NH3HCl NH4Cl. When 3 parts of concentrated HCl and 1 part of concentrated HNO3 are mixed, aqua regia is formed which is used for dissolving noble metals, e.g., gold, platinum. 3422362L4H number 4ClOCl number 2HO3 part 16H4 number 18Cl3 PTCl4 number 8HO7.27, 207, 207, 207, 20. Hydrogen 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 chloride 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 chloride. Uses. It is used for bleaching wood pulp required for the manufacture of paper and rayon, bleaching cotton and textiles. 2 inches the extraction of gold and platinum. 3 inches the manufacture of dyes, drugs and organic compounds such as CCl4, CHCl3, DDT, refrigerants, etc. I in sterilizing drinking water and the preparation of poisonous gases such as phosgene cockle 2, tear gas CCl3 number 2, mustard gas ClCH2CH2SCH2CH2Cl. In text questions 7.29 give the reason for bleaching action of Cl2. 7.30 name 2 poisonous gases which can be prepared from chlorine gas. 205 The P-block elements figure 7.8 The structures of oxosides of chlorine hydrochloric acid decomposes salts of weaker acids, e.g., carbonates, hydrogen carbonates, sulfides, etc. Na2CO3-2HCl2 NaClH2OCO2 NaCl3HCl NaClH2OCO2 Na2SO3-2HCl2 NaClH2OCO2 Table 7.10 Oxosides of halogens Halych acid Hothhochel Haberhoi Hippoholus acid Hypofluorous acid Hypochlorous acid Hypobromous acid Hippoitis acid Halych 3 acid Hoshiohalous acid Chlorous acid Halych V acid Hoshio2 Hobro2 Hoyo2 Halych acid Chloric acid Bromic acid Iotic acid Halych 7 acid Hoshio3 Hobro3 Hoyo3 Perhalic acid for chloric acid for bromic acid Periodic acid When HCl reacts with finely powdered iron, it forms ferrous chloride and not ferric chloride. Why its reaction with iron produces H222 Fe2HCl FeClH liberation of hydrogen prevents the formation of ferric chloride. Example 7.18 Example 7.18 Example 7.18 Example 7.18 Example 7.18 Solution Uses It is used in the manufacture of chlorine. NH4Cl and glucose from cornstarch, 2 for extracting glue from bones and purifying bone black, 3 inches medicine and as a laboratory reagent. Due to high electronegativity and small size, fluorine forms only one oxoside, half known as fluoric acid or hypofluorous acid. The other halogens form several oxosides. Most of them cannot be isolated in pure state. They are stable only in aqueous solutions or in the form of their salts. The oxosides of halogens are given in Table 7.10 and their structures are given in Figure 7.8, 7.21 Oxosides of 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 halogens 206 Chemistry When two different halogens react with each other, interhalogen compounds are formed. They can be assigned general compositions as XX, XX3, XX5 and XX7 where X is halogen of larger size and X of smaller size and X is more electropositive than X. As the ratio between radii of X and X increases, the number of atoms per molecule also increases. Thus, iodine 7 fluoride should have maximum number of atoms as the ratio of radii between I and F should be maximum. That is why its formula is F7 having maximum number of atoms. Preparation The interhalogen compounds can be prepared by the direct combination or by the action of halogen on lower interhalogen compounds. The product formed depends upon some specific conditions, for example, 7.22 227, 22, 7, 227, 22, capital I, N, T, E, R, H, A, L, O, G, E, N, capital I, N, T, E, R, H, A, L, O, G, E, N, capital I, N, T, E, R, H, compounds 2 to equimolar ICl2 573 K223 XSCl3 F2 CLF, 437 K22 equivolume CLF2 CLF. 223 XSI3 Cl2 ICl223 diluted with water Br3 F2 Brf225 XS Br5 F2 Brf Properties Some properties of interhalogen compounds are given in Table 7.11. Type formula Physical state and color structure XX1 CLF colorless gas, BRF pale brown gas, IFA detected spectroscopically, BRCLB gas ICL ruby red solid Greek letter alpha form brown red solid Greek letter beta form IBR black solid, XX3 CLF3 colorless gas bent T, shaped BRF3 yellow green liquid bent T shaped V3 yellow powder bent T shaped. ICl3C orange solid bent T-shaped XX5 F5 colorless gas but square solid below 77 K pyramidal BRF5 colorless liquid square pyramidal CLF5 colorless liquid square pyramidal XX7 F7 colorless gas pentagonal bipyramidal Table 7.11. Some properties of interhalogen compounds are very unstable. B. The pure solid is known at room temperature. C. Dimerizes as Cl bridge dimer I2Cl6. These are all covalent molecules and are diamagnetic in nature. They are volatile solids or liquids at 298 K except CLF which is a gas. Their physical properties are intermediate between those of constituent halogens except that their MP and BP are a little higher than expected. Their chemical reactions can be compared with the individual halogens. In general, interhalogen compounds are more reactive than halogens except fluorine. This is because XX bond in interhalogens is weaker than XX bond in halogens except FF bond. All these undergo hydrolysis giving halide ion derived from the smaller halogen and a hypohalite when XX. Halite when XX3, halite when XX5 and perhalite when XX7 anion derived from the larger halogen. 2XXHOHX. Their molecular structures are very interesting, which can be explained on the basis of VSEPR theory. Example 7.19. The XX3 compounds have the bent T shape, XX5 compound square pyramidal, and F7 has pentagonal bipyramidal structures. Table 7.11. Discuss the molecular shape of BRF3 on the basis of VSEPR theory. The central atom Br has 7 electrons in the valence shell. 3 of these will form electron pair bonds with 3 fluorine atoms, leaving behind 4 electrons. Thus, there are 3 bond pairs and 2 lone pairs. According to VSEPR theory, these will occupy the corners of a trigonal bipyramid. The 2 lone pairs will occupy the equatorial positions to minimize lone pair and the bond pair repulsions, which are greater than the bond pair repulsions. In addition, the axial fluorine atoms will be bent towards the equatorial fluorine in order to minimize the lone pair repulsions. The shape would be that of a slightly bent T. Example 7.19. Example 7.19. Example 7.19. Example 7.19. Example 7.19. Solution. Uses. These compounds can be used as non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents. ClF3 and BrF3 are used for the production of UF6 in the enrichment of 235U. US3ClF3L UF6G3ClFG. In text question 7.31. Why is ICl more reactive than I2? 208. Chemistry. Group 18 consists of elements: helium, neon, argon, krypton, xenon, radon and oganesson. All these are gases and chemically unreactive. They form very few compounds. Because of this they are termed as noble gases. All these gases except radon and oganesson occur in the atmosphere. Their atmospheric abundance in dry air is 1 by volume, of which argon is the major constituent. Helium and sometimes neon are found in minerals of radioactive origin, e.g., pitchblende, monazite, clevite. The main commercial source of helium is natural gas. Xenon and radon are the rarest elements of the group. Radon is obtained as a decay product of 226 Ra. 226 222 488 86 2 Ra and oganesson has been synthetically produced by collision of 249 98 Cf atoms and 48 20 Ca ions. 249 48 294 98 20 118 Cf Cog 3 and 7.237 237 237 237 23. Group 18 elements 7 2 3 1 occurrence. Why are the elements of group 18 known as noble gases? The elements present in group 18 have their valence shell orbitals completely filled and, therefore, react with a few elements only under certain conditions. Therefore, they are now known as noble gases. Example 7.20. Example 7.20. Example 7.20. Example 7.20. Example 7.20. Solution. Oganesson has its symbol Og. Atomic number 118, atomic mass 294 and electronic configuration Rn5F146D107S27. Page 6. Only very small amount of Ug has been produced. Its half-life is 0.7 milliseconds, therefore, mainly predictions about its chemistry have been made. Here, except for oganesson, important atomic and physical properties of other elements of group 18 along with their electronic configurations are given in table 7.12. The trends in some of the atomic, physical and chemical properties of the group are discussed here. Property net RKRXERN atomic number 210 1836 54 86 atomic mass Gmol 14.020.1839.9583.8131.3222.00 electronic configuration 1s2e2s22 page 6 Ne3s23 page 6 R3d104s24 page 6 Kr4d105s25 page 6 Xe4f145d106s26 page 6 atomic radius PM120 160 190 200 220 ionization enthalpy 2372 2080 1520 1351 1170 1037 kg mol 1 electron gain enthalpy 48 116 96 96 77 68 kg mol 1 density at STP-GCM 31.8 x 10-4 9.0 x 10-4 1.8 x 10-3 3.7 x 10-3 5.9 x 10-3 9.7 x 10-3 melting point K24.683 8 115 9 161 3 202 boiling point K4.227.187 2 119 7 165 0 211 atmospheric content 5.24 x 10-4 1.82 x 10-30.934 1.14 x 10-4 8.7 x 10-6 by volume table 7.12 atomic and physical properties of group 18 elements radioactive 209 The p-block elements. All noble gases have general electronic configuration ns2 and p6 except helium, which has 1s2 table 7.12. Many of the properties of noble gases, including their inactive nature, are ascribed to their closed shell structures. Due to stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radii increase down the group with increase in atomic number. Since noble gases have stable electronic configurations, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpy. Physical properties. All the noble gases are monoatomic. They are colorless, odorless and tasteless. They are sparingly soluble in water. They have very low melting and boiling points because the only type of interatomic interaction in these elements is weak dispersion forces. Helium has the lowest boiling point 4.2 K of any known substance. It has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass or plastics. 7, 2, 3, 2 electronic configuration 7, 2, 3, 3 ionization enthalpy 7, 2, 3, 4 atomic radii 7, 2, 3, 5 electron gain enthalpy. Chemical properties. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to the following reasons. The noble gases except helium-1s2 have completely filled ns2 and p6 electronic configuration in their valence shell. 2. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of noble gases has been investigated occasionally, ever since their discovery, but all attempts to force them to react to form the compounds were unsuccessful for quite a few years. In March 1962, Neil Bartlett, then at the University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2-PTF6. He then realized that the first ionization enthalpy of molecular oxygen 1175 kg-mol1 was almost identical with that of xenon 1170 kg-mol1. He made efforts to prepare same type of compound with Xe and was successful in preparing another red color compound XePTF6 by mixing PTF6 and xenon. After this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. The compounds of krypton are fewer. Only the difluoride KrF2 has been studied in detail. Compounds of radon have not been isolated. Noble gases have very low boiling points. Why noble gases, being monoatomic, have no interatomic forces except weak dispersion forces, and therefore, they are liquefied at very low temperatures. Hence, they have low boiling points. Example 7.21 Example 7.21 Example 7.21 Example 7.21 Example 7.21 Solution 210 Chemistry Fig. 7.9 The structures of AsF2 BsF4 CsF6 DzF4 and DZ3FFXE. A linear B-square planar FFFFXE distorted octahedral D-square pyramidal but only identified e.g. RNF2 by radiotracer technique. No true compounds of R, net or He are yet known as xenon fluorine compounds. Xenon forms 3 binary fluorides, ZF2, ZF4 and ZF6 by the direct reaction of elements under appropriate experimental conditions. XeG-F2G673K, 1 bars F2S xenon in excess XeG2F2G873K, 7 bars F4S1, 5 ratio XeG3F2G573K. 60-70 bars F6S1, 20 ratios. F6 can also be prepared by the interaction of ZF4 and O2F2 at 143K, 42262 ZFO F2. ZeF4 and ZeF6 are colorless crystalline solids and sublime readily at 298 K. They are powerful fluorinating agents. They are readily hydrolyzed even by traces of water. For example, ZeF2 is hydrolyzed to give Xe, HF and O2. 2ZeF2S2H2OL2Zg4HF-ACO2G. The structures of the three xenon fluorides can be deduced from VSEPR, and these are shown in Fig. 7.9. ZeF2 and ZeF4 have linear and square planar structures respectively. ZeF6 has 7 electron pairs, 6 bonding pairs and 1 lone pair, and would, thus, have a distorted octahedral structure as found experimentally in the gas phase. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoronions. ZeF2PF5 ZeFPF6, ZeF4SPF5 ZeF3SPF6 ZeF6MFM ZeF7M Na, K, RBRCsP. Xenon oxygen compounds hydrolysis of ZeF4 and ZeF6 with water gives Z03. 6 ZeF412H2O4 Z2 Z0324HF3O2 ZeF63H2O Z36HF. Partial hydrolysis of ZeF6 gives oxyfluorides, ZeO4 and ZeO2F2. ZeF6H2O ZeO4 2HF ZeF6 2H2O ZeO2F2 4HF. 211. The p-block element CF3 is a colorless explosive solid and has a pyramidal molecular structure. Fig. 7.9. ZeO4 is a colorless volatile liquid and has a square pyramidal molecular structure. Figure 7.9. Does the hydrolysis of ZeF6 lead to a redox reaction? No. The products of hydrolysis are ZeO4 and ZeO2F2, where the oxidation states of all the elements remained the same as it was in the reacting state. Example 7.22. Example 7.22. Example 7.22. Example 7.22. Example 7.22. Solution. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I O N. Capital S O L U T I. Uses. Helium is a non-inflammable and light gas. Hence, it is used in filling balloons for meteorological observations. It is also used in gas-cooled nuclear reactors. Liquid helium B. Page 4.2. K. Finds use as cryogenic agent for carrying out various experiments at low temperatures. It is used to produce and sustain powerful superconducting magnets, which form an essential part of modern NMR spectrometers and magnetic resonance imaging MRI systems for clinical diagnosis. It is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood. Neon is used in discharge tubes and fluorescent bulbs for advertisement display purposes. Neon bulbs are used in botanical gardens and in greenhouses. Argon is used mainly to provide an inert atmosphere in high-temperature metallurgical processes, arc welding of metals or alloys, and for filling electric bulbs. It is also used in the laboratory for handling substances that are air-sensitive. There are no significant uses of xenon and krypton. They are used in light bulbs designed for special purposes. In text questions 7.32. Why is helium used in diving apparatus? 7.33. Balance the following equation. ZeF6H2O ZeO2F2HF. 7.34. Why has it been difficult to study the chemistry of radon? 212. Chemistry summary. Groups 13 to 18 of the periodic table consist of p-block elements with their valence shell electronic configuration ns2np1-6. Groups 13 and 14 were dealt with in Class I. In this unit, remaining groups of the p-block have been discussed. Group 15 consists of 5 elements, namely N, P, S, Sp and B, which have general electronic configuration ns2np3. Nitrogen differs from other elements of this group due to small size. Formation of Greek letter pi, Greek letter pi, Greek letter pi, Greek letter pipe, Greek letter pi, Greek letter pi, Greek letter pi, Greek letter pi. Multiple bonds with itself and with highly electronegative atom like O or C, and non-availability of d orbitals to expand its valence shell. Elements of group 15 show gradation and properties. They react with oxygen, hydrogen and halogens. They exhibit 2 important oxidation states, 3 and 5, but 3 oxidation is favored by heavier elements due to inert pair effect. Dinitrogen can be prepared in laboratory as well as on industrial scale. It forms oxides in various oxidation states as N2O, NO, N2O3, number 2, N2O4 and N2O5. These oxides have resonating structures and have multiple bonds. Ammonia can be prepared on large scale by Haber's process. HNO3 is an important industrial chemical. It is a strong monobasic acid and is a powerful oxidizing agent. Metals and nonmetals react with HNO3 under different conditions to give NO or number 2. Phosphorus exists as P4 in elemental form. It exists in several allotropic forms. It forms hydride, pH3, which is a highly poisonous gas. It forms two types of halides as PX3 and PX5. PCl3 is prepared by the reaction of white phosphorus with dry chlorine, while PCl5 is prepared by the reaction of phosphorus with SO2Cl2. Phosphorus forms a number of oxosides. Depending upon the number of PO groups, their basicity varies. The oxosides which have pH bonds are good reducing agents. The group 16 elements have general electronic configuration NS2 and P4. They show maximum oxidation state. 6. Gradation in physical and chemical properties is observed in the group 16 elements. In laboratory, dioxygen is prepared by heating KClO3 in presence of MnO2. It forms a number of oxides with metals. Allotropic form of oxygen is O3, which is a highly oxidizing agent. Sulfur forms a number of allotropes. Of these, Greek letter alpha and Greek letter beta forms of sulfur are the most important. Sulfur combines with oxygen to give oxides such as SO2 and SO3. SO2 is prepared by the direct union of sulfur with oxygen. SO2 is used in the manufacture of H2SO4. Sulfur forms a number of oxosides. Amongst them, the most important is H2SO4. It is prepared by contact process. It is a dehydrating and oxidizing agent. It is used in the manufacture of several compounds. Group 17 of the periodic table consists of the following elements: F, Cl, Br, and that these elements are extremely reactive and as such they are found in the combined state only. The common oxidation state of these elements is -1. However, highest oxidation state can be 7. They show regular gradation in physical and chemical properties. They form oxides, hydrogen halides, interhalogen compounds and oxosides. Chlorine is conveniently obtained by the reaction of HCl with KMnO4. HCl is prepared by heating NaCl with concentrated H2SO4. Halogens combine with one another to form interhalogen compounds of the type XX1 and N1. 3, 5, 7 where X1 is lighter than X. A number of oxosides of halogens are known. In the structures of these oxosides, halogen is the central atom which is bonded in each case with one O bond as XO. In some cases X0 bonds are also found. Group 18 of the periodic table consists of noble gases. They have Ns2 and P6 valence shell electronic configuration except T, which has one S2. All the gases except Rn occur in atmosphere. Rn is obtained as the decay product of 226 Ra. Due to complete octet of outermost shell, they have less tendency to form compounds. The best characterized compounds are those of xenon with fluorine and oxygen only under certain conditions. These gases have several uses. Argon is used to provide inert atmosphere. Helium is used in filling balloons for meteorological observations. Neon is used in discharge tubes and fluorescent bulbs. The d block of the periodic table contains the elements of the groups 312 in which the d orbitals are progressively filled in each of the 4 long periods. The f block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The names transition metals and inner transition metals are often used to refer to the elements of d and f blocks respectively. There are mainly 4 series of the transition metals: 3d series Sc to Zn, 4d series Y to Cd, 5d series La and Hf to Hg, and 6d series which has Ac and elements from Rf to Cn. The 2 series of the inner transition metals, 4f Se to Lu and 5fdh to Lr, are known as lanthanoids and actinoids respectively. Originally the name transition metals was derived from the fact that their chemical properties were transitional between those of S and P block elements. Now according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation states and hence, are not regarded as transition metals. However, being the end members of the 3D, 4D and 5D transition series, respectively, their chemistry is studied along with the chemistry of the transition metals. The presence of partly filled d or f orbitals in their atoms makes transition elements different from that of the d and f block elements. The d and f block elements, after studying this unit, you will be able to learn the positions of the d and f block elements in the periodic table, know the electronic configurations of the transition d block and the inner transition f block elements, appreciate the relative stability of various oxidation states in terms of electrode potential values, describe the preparation, properties, structures and uses of some important compounds such as K2Cr2O7 and KMnO4, understand the general characteristics of the d and f block elements and the general horizontal and group trends in them, describe the properties of the F-block elements and give a comparative account of the lanthanoids and actinoids with respect to their electronic configurations, oxidation states and chemical behavior. Objectives: iron, copper, silver and gold are among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as Th, Pa and U are proving excellent sources of nuclear energy in modern times. 8 Unit 8. The non-transition elements, hence, transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold and platinum and industrially important metals like iron, copper and titanium belong to the transition metals series. In this unit, we shall first deal with the electronic configuration. Occurrence and general characteristics of transition elements with special emphasis on the trends in the properties of the first row 3D transition metals along with the preparation and properties of some important compounds. This will be followed by consideration of certain general aspects such as electronic configurations, oxidation states and chemical reactivity of the inner transition metals. The transition elements D block. The D block occupies the large middle section of the periodic table flanked between S and P blocks in the periodic table. The d orbitals of the penultimate energy level of atoms receive electrons giving rise to 4 O's of the transition metals, that is, 3D, 4D, 5D and 6D. All these series of transition elements are shown in Table 8.1. In general, the electronic configuration of outer orbitals of these elements is N1D1-10NS1-2. The N1 stands for the inner d orbitals which may have 1 to 10 electrons and the outermost NS orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference between N1D and NS orbitals. Furthermore, half and completely filled sets of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configurations of Cr and Cu in the 3D series. For example, consider the case of Cr, which has 3D54S1 configuration instead of 3D44S2. The energy gap between the two sets 3D and 4S of orbitals is small enough to prevent electron entering the 3D orbitals. Similarly, in case of Cu, the configuration is 3D104S1 and not 3D94S2. The ground state electronic configurations of the outer orbitals of transition elements are given in Table 8.1. 8.18, 18, 18, 18, 1 position in the 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 periodic table periodic table periodic table periodic table periodic table 8.28, 28, 28, 28, 2 electronic 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 electronic. Capital C O N F I G U R A T I O N S. Capital C O N F I G U R A T I O N S. Capital C O of the D block 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 elements SCTVCRMN FACO NECUZNZ 21 22 23 24 25 26 27 28 29 34 S2 2 2 1 2 2 2 2 1 2 3 D 1 2 3 5 5 6 7 8 10 10 First Series Table 8.1 Electronic configurations of outer orbitals of the transition elements ground state. 217 The D and F block elements. The electronic configurations of outer orbitals of Cn, Cd, Hg and Cn are represented by the general formula N1D10NS2. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals, that is, S and P. Hence, they are more influenced by the surroundings as well as affect the atoms or molecules surrounding them. In some respects, ions of a given DN configuration N19 have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristic properties such as display of a variety of oxidation states, formation of colored ions and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of the transition elements of a horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics and their trends in the horizontal rows, particularly 3D row, and then consider some group similarities. Second series YZRNB MOTC RUR HPD AG CTZ 39 40 41 42 43 44 45 46 47 48 5 S 2211111012 D 124 5 6 7 8 10 10 10 Third series LA HF TA W RIOS IRP TO HGZ 57 72 73 74 75 76 77 78 79 86 S 2222222112 D 1234 5 6 7 9 10 10 ACRF DB SGBHH's MTDs RGCNZ 89, 104, 105, 106, 107, 108, 109, 110 111 112 7 S 2222222221 123 5 6 7 8 10 10 Fourth series On what ground can you say that scandium Z21 is a transition element but zinc Z30 is not on the basis of incompletely filled 3d orbitals in case of scandium atom in its ground state 3d1, it is regarded as a transition element. On the other hand, zinc atom has completely filled d orbitals 3d10 in its ground state as well as in its oxidized state, hence it is not regarded as a transition element. Example 8.1 Example 8.1 Example 8.1 Example 8.1 Example 8.1 Solution 218 Chemistry 1 2 3 4 M page 10 K3 TZRHFW Retos IRUMO NBTCRHCRVMN FACONI PDPT QOAG Atomic number in text question 8.1 Silver atom has completely filled d orbitals 4d10 in its ground state. How can you say that it is a transition element? We will discuss the properties of elements of first transition series only in the following sections. 8.3.1 Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity and metallic luster. With the exceptions of Cn, Cd, Hg and Mn, they have one or more typical metallic structures at normal temperatures. 8.38 capital G E N E R A L 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 capital G E Properties of the transition elements D block BCC body centered cubic, HCP hexagonal close packed, CCP cubic close packed, X a typical metal structure. Figure 8.1, trends in melting points of transition elements. The transition metals with the exception of Cn, Cd and Hg are very hard and have low volatility. Their melting and boiling points are high. Figure 8.1 depicts the melting points of transition metals belonging to 3D, 4D and 5D series. The high melting points of these metals are attributed to the involvement of greater number of electrons from N1D in addition to the Ns electrons in the interatomic metallic bonding. In any row the melting points of these metals rise to a maximum at D5 except for anomalous values of Mn and Tc and fall regularly as the atomic number increases. They have high enthalpies of atomization which are shown in figure 8.2. The maxima at about the middle of each series indicate that one unpaired electron per d orbital is particularly lattice structures of transition metals SCTBCRMN FACONICUZN HCPHCPBCCBCCXBCCCCCPXBCCBCCBCC CCPHCPHCPHCPYZRNB MOTC RUR HPD AG CDHCPHCPBCCBCCHCPHCPCCPCCPXBCCBCCHCP LHF TA W RIOS IRP TOHG HCPHCPBCCBCCHCPCCPCCPCCPXCCP BCCBCC 219 The D and F block elements favorable for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal. Metals with very high enthalpy of atomization, that is, very high boiling point, tend to be noble in their reactions. See later for electrode potentials. Another generalization that may be drawn from Fig. 8.2 is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor in accounting for the occurrence of much more frequent metal bonding in compounds of the heavy transition metals. Figure 8.2 Trends in enthalpies of atomization of transition elements. In general, ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases by unity. It may be recalled that the shielding effect of a d electron is not that effective, hence the net electrostatic attraction between the nuclear charge and the outermost electron increases and the ionic radius decreases. The same trend is observed in the atomic radii of a given series, however, the variation within a series is quite small. An interesting point emerges when atomic sizes of one series are compared with those of the corresponding elements in the other series. The curves in Fig. 8.3 show an increase from the first 3D to the second 4D series of the elements, but the radii of the third 5D series are virtually the same as those of the corresponding members of the second series. This phenomenon is associated with the intervention of the 4f orbitals, which must be filled before the 5D series of elements begin. The filling of 4f before 5d orbital results in a regular decrease in atomic radii called lanthanoid contraction, which essentially compensates for the expected 8.3.2 variation in atomic and ionic sizes of transition metals DAV-Kjmal-1. Increase in atomic size with increasing atomic number. The net result of the lanthanoid contraction is that the second and the third D series exhibit similar radii, e.g. ZR 160 pm, HF 159 pm, and have very similar physical and chemical properties, much more than that expected on the basis of usual family relationship. The factor responsible for the lanthanoid contraction is somewhat similar to that observed in an ordinary transition series and is attributed to similar cause. That is, the imperfect shielding of one electron by another in the same set of orbitals. However, the shielding of one 4f electron by another is less than that of one d electron by another. And as the nuclear charge increases along the series, there is fairly regular decrease in the size of the entire 4fn orbitals. The decrease in metallic radius coupled with increase in atomic mass results in a general increase in the density of these elements. Thus, from titanium Z22 to copper Z29, the significant increase in the density may be noted. Table 8.2. 19, 18, 16, 15, 13, 12 SCTV CRMN FACO NICU ZNY ZRNB MO TC RUR HPD AG CD LA HF TA W RIOS IRP TAO HG radius NM 17, 14 Fig. 8.3. Trends in atomic radii of transition elements. Atomic number 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Electronic configuration M3D 14s, 2 3D 24s, 2 3D 34s, 2 3D 54s, 1 3D 54s, 2 3D 64s, 2 3D 74s, 2 3D 84s, 2 3D 104s, 1 3D 104s, 2 M3D 14s, 1 3D 24s, 1 3D 34s, 1 3D 5 3D 54s, 1 3D 64s, 1 3D 74s, 1 3D 84s, 1 3D 10 3D 104s, 1 M2 3D 1 3D 2 3D 3 3D 4 3D 5 3D 6 3D 7 3D 8 3D 9 3D 10 M3R 3D 1 3D 2 3D 3 3D 4 3D 5 3D 6 3D 7. Enthalpy of atomization. AVVVVKJMOL 326 473 515 397 281 416 425 430 339 126. Ionization enthalpy IVVVVKJMOL 1 IVI 631 656 650 653 717 762 758 736 745 906 IV2 1235 1309 1414 1592 1509 1561 1644 1752 1958 1734 IV3 2393 2657 2833 2990 3260 2962 3243 3402 3556 3837. Metallic ionic M164 147 135 129 137 126 125 125 128 137. Radii PMM 279 82 82 77 74 70 73 75 M3 73 67 64 62 65 65 61 60. Standard electrode M2M- 1.63 minus 1.18 minus 0.90 18 to 0.44 0.28 to 0.25 0.34 0.76. Potential EV VM3M20 37 to 0.26 minus 0.41 1.57 0.77 1.97. Density GCM33.43 4.16.07.19.7.21.7.88.78.98.97.1 Element SCTVCRMN FACO NICUZI and Table 8.2 Electronic configurations and some other properties of the first series of transition elements. 221. The D and F block elements. Why do the transition elements exhibit higher enthalpies of atomization? Because of large number of unpaired electrons in their atoms, they have stronger interatomic interaction and hence stronger bonding between atoms, resulting in higher enthalpies of atomization. Example 8.2. Example 8.2. Example 8.2. Example 8.2. Example 8.2. Solution. There is an increase in ionization enthalpy along each series of the transition elements from left to right due to an increase in nuclear charge, which accompanies the filling of the inner d orbitals. Table 8.2 gives the values of the first three ionization enthalpies of the first series of transition elements. These values show that the successive enthalpies of these elements do not increase as steeply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition elements. The first ionization enthalpy, in general, increases, but the magnitude of the increase in the second and third ionization enthalpies for the successive elements is much higher along a series. The irregular trend in the first ionization enthalpy of the metals of 3D series, though of little chemical significance, can be accounted for by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. You have learnt that when d block elements form ions, ns electrons are lost before n1d electrons. As we move along the period in 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to the orbital of inner subshell, that is, 3d orbitals. These 3d electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decrease less rapidly, thus, ionization energies increase only slightly along the 3D series. The doubly or more highly charged ions have dn configurations with number 4s electrons. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases, because one d electron does not shield another electron from the influence of nuclear charge because d orbitals differ in direction. However, the trend of steady increase in second and third ionization enthalpy breaks for the formation of Mn2 and Fe3 respectively. In both the cases, ions have d5 configuration. Similar breaks occur at corresponding elements in the later transition series. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. The three terms responsible for the value of ionization enthalpy are attraction of each electron towards nucleus, repulsion between the 3 ionization enthalpies in text question 8.2 in the series SCZ21 to ZNZ30. The enthalpy of atomization of zinc is the lowest, that is, 126 kJ-mol-1. Why? Electrons and the exchange energy. Exchange energy is responsible for the stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. Hund's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Mn has 3d54s 1 configuration and configuration of Cr is d5. Therefore, ionization enthalpy of Mn is lower than Cr. In the same way, Fe2 has d6 configuration and Mn2 has 3d5 configuration. Hence, ionization enthalpy of Fe2 is lower than the Mn2. In other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn. The lowest common oxidation state of these metals is 2. To form the M2 ions from the gaseous atoms, the sum of the first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term is the second ionization enthalpy, which shows unusually high values for Cr and Cu, where M ions have the d5 and d10 configurations respectively. The value for Cn is correspondingly low as the ionization causes the removal of one s electron, which results in the formation of stable d10 configuration. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the d5Mn2 and d10Cn2 ions. In general, the third ionization enthalpies are quite high. Also, the high values for third ionization enthalpies of copper, nickel and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements. Although ionization enthalpies give some guidance concerning the relative stabilities of oxidation states, this problem is very complex and not amenable to ready generalization. One of the notable features of a transition elements is the great variety of oxidation states these may show in their compounds. Table 8.3 lists the common oxidation states of the first row transition elements. SCTVCRMN FACO NICUZIAN 2222222233333333444444455566667. Table 8.3 Oxidation states of the first row transition metals. The most common ones are in bold types 8, 3, 4 oxidation states. 223 The D and F block elements. The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibits all the oxidation states from 2 to 7. The lesser number of oxidation states at the extreme end stems from either too few electrons to lose or share Sc. T or too many d electrons, hence fewer orbitals available in which to share electrons with others for higher valence Cu, Zn. Thus, early in the series scandium-2 is virtually unknown and titanium IV is more stable than T3 or T2. At the other end, the only oxidation state of zinc is 2 nor d electrons are involved. The maximum oxidation states of reasonable stability correspond in value to the sum of the S and d electrons up to manganese TiVo2. VVO2, CrV1042, ViO4 followed by a rather abrupt decrease in stability of higher oxidation states. So that the typical species to follow are Fe3, Coi3, Ni, Qui2, Zni. The variability of oxidation states, a characteristic of transition elements, arises out of incomplete filling of d orbitals in such a way that their oxidation states differ from each other by unity. E.g., 7, 8, Viv, Vv. This is in contrast with the variability of oxidation states of non-transition elements where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation states of the d-block elements is noticed among the groups 4 through 10. Although in the p-block the lower oxidation states are favored by the heavier members due to inert pair effect, the opposite is true in the groups of d-block. For example, in group 6, Mo6 and W6 are found to be more stable than Cr6, thus Cr6 is the form of dichrome made in acidic medium is a strong oxidizing agent, whereas Mu3 and WO3 are not. Low oxidation states are found when a complex compound has ligands capable of Greek letter pi acceptor character in addition to the Greek letter sigma bonding. For example, in NiCO4 and FeCO5, the oxidation state of nickel and iron is 0. Name a transition element which does not exhibit variable oxidation states. Scandium Z21 does not exhibit variable oxidation states. Example 8.3 Example 8.3 Example 8.3 Example 8.3 Example 8.3 Solution in text question 8.3 Which of the 3D series of the transition metals exhibits the largest number of oxidation states and why? 224 Chemistry Table 8.4 contains the thermochemical parameters related to the transformation of the solid metal atoms to M2 ions in solution and their standard electrode potentials. The observed values of EV and those calculated using the data of Table 8.4 are compared in Fig. 8.4. The unique behavior of Cu, having a positive EV, accounts for its inability to liberate H2 from acids. Only oxidizing acids nitric and hot concentrated sulfuric react with Cu, the acids being reduced. The high energy to transform CuS to Cu2Ac is not balanced by its hydration enthalpy. The general trend towards less negative EV values across the 8, 3, 5 trends in the M2M standard electrode potentials in text question 8.4 The EV M2M value for copper is positive, 0.34 V. What is possible reason for this hint? Consider its high AV and low VY is Cr2 reducing and Mn3 oxidizing when both have D4 configuration. Cr2 is reducing as its configuration changes from D4 to D3. The latter having a half-filled T2G level C unit 9. On the other hand, the change from Mn3 to Mn2 results in the half-filled D5 configuration which has extra stability. Example 8.4 Example 8.4 Example 8.4 Example 8.4 Example 8.4 Solution Fig. 8.4 Observed and calculated values for the standard electrode potentials M2M degrees of the elements T to Zn series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of EV for Mn, Ni and Zn are more negative than expected from the trend. 225 The D and F block elements element MAV Mi1 V1 H2 VHID VM2 EV VT469, 656, 1309, 1866 1.63 V515, 650, 1414, 1895 1.18 CR398, 653, 1592, 1925 0.90 Mn279, 717, 1509, 1862 1.18 Fe418, 762, 1561, 1998, 0.44 Co427, 758, 1644, 2079 0.28 Ni431, 736, 1752, 2121 0.25 Cu339, 745, 1958, 2121 0.34 Zn130, 906, 1734, 2059 0.76 Table 8.4, Thermochemical data kJ-mol1 for the first row transition elements and the standard electrode potentials for the reduction of Mi to M. The stability of the half-filled D subshell in Mn2 and the completely filled D10 configuration in Zn2 are related to their EV values. Whereas EV for Ni is related to the highest negative hit V, an examination of the EV-M3-M2 values Table 8.2 shows the varying trends. The low value for SC reflects the stability of SC3 which has a noble gas configuration. The highest value for Zn is due to the removal of an electron from the stable D10 configuration of Zn2. The comparatively high value for Mn shows that Mn2D5 is particularly stable, whereas comparatively low value for Fe shows the extra stability of Fe3D5. The comparatively low value for V is related to the stability of V2 half-filled T2G level, Unit 9. Table 8.5 shows the stable halides of the 3D series of transition metals. The highest oxidation numbers are achieved in TiX4 tetrahalides, VF5 and CrF6. The 7-state for Mn is not represented in simple halides but MnO3F is known, and beyond Mn no metal has a trihalide except Fex3 and COF3. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy as in the case of COF3, or higher bond enthalpy terms for the higher covalent compounds, e.g., VF5 and CrF6, although V5 is represented only by VF5. The other halides, however, undergo hydrolysis to give oxahalides, VOX3. Another feature of fluorides is their instability in the low oxidation states e.g., VX2XCI. BR or I8, 3, 6 trends in the M3-M2 standard electrode potentials 8, 3, 7 trends in stability of higher oxidation states 6 CrF6 5 VF5 CrF5 4 TiX4 VXI4 CrX4 MnF4 3 TiX3 VX3 CrX3 MnF3 FeXi3 CoF3 2 TiX2 3 VX2 CrX2 MnX2 FeX2 COX2 NiX2 COX2 to ZnX2 1 QXI oxidation number Table 8.5, formulas of halides of 3D metals Ki, XFI, ZiFBr, 12F. C, 13Ci. 226 Chemistry and the same applies to COX. On the other hand, all Ki halides are known except the iodide. In this case, Cu2 oxidizes I2I2, 22222 Cu4I Cu-I is however, many copper I compounds are unstable in aqueous solution and undergo disproportionation. 2Cu2Cu the stability of Cu2Ac rather than Cu-Ac is due to the much more negative hit V of Cu2Ac than Cu, which more than compensates for the second ionization enthalpy of Cu. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides Table 8.6 coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of Fe above Fe2O3 are known, although Fe86VO42 are formed in alkaline media but they readily decompose to Fe2O3 and O2. Besides the oxides, oxidation stabilize VV as VO2, VIV as VO2 and TI as CO2. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus the highest Mn fluoride is MnF4 whereas the highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metals explains its superiority. In the covalent oxide Mn2O7, each Mn is tetrahedrally surrounded by Os including a MnO-Mn bridge. The tetrahedral MO4N ions are known for VV, CrVl, MnV, MnVl and Vi. 7 Mn2076 Cro3 5V2O5 4 CO2 V2O4 Cro2 MnO23 Sc2O3 T2O3 V2O3 Cr2O3 Mn2O3 Fe2O3 Mn3O4 Fe3O4 Co3O4 2 COVO Cro MnO Fio Cu Nia CuOZNO1 Cu2O Table 8.6 Oxides of 3D metals. Mixed oxides groups 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oxidation number in text question. 8.5. How would you account for the irregular variation of ionization enthalpies? First and second in the first series of the transition elements. Example 8.5. Example 8.5. Example 8.5. Example 8.5. Example 8.5. How would you account for the increasing oxidizing power in the series VO2? Cr2072, MnO4. This is due to the increasing stability of the lower species to which they are reduced. Solution. 227. The D and F block elements for the first row transition metals. The EO values are EOVCRMN FACO NiCu M2M-1.18 to 0.91 to 0.18 to 0.44 to 0.28 to 0.25 Explain the irregularity in the above values. The EVM2M values are not regular, which can be explained from the irregular variation of ionization enthalpies II12HH and also the sublimation enthalpies, which are relatively much less for manganese and vanadium. Why is the EV value for the Mn3-Mn2 couple much more positive than that for Cr3-Cr2 or Fe3-Fe2? Explain. Much larger third ionization energy of Mn, where the required change is D5 to D4, is mainly responsible for this. This also explains why the pre-state of Mn is of little importance. 8.3. 9. Magnetic properties. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they are unaffected by single acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1mH. Though the actual rate at which these metals react with oxidizing agents like hydrogen ion H is sometimes slow. For example, titanium and vanadium, in practice, are passive to dilute non-oxidizing acids at room temperature. The EV values for M2M table 8.2 indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative EV values is related to the increase in the sum of the first and second ionization enthalpies. It is interesting to note that the EV values for Mn, Ni and Zn are more negative than expected from the general trend. Whereas the stabilities of half-filled D subshell D5 in Mn2 and completely filled D subshell D10 in zinc are related to their EE values. For nickel, EO value is related to the highest negative enthalpy of hydration. An examination of the EV values for the redox couple M3-M2 table 8.2 shows that Mn3 and Co3 ions are the strongest oxidizing agents in aqueous solutions. The ions T2, V2 and Cr2 are strong reducing agents and will liberate hydrogen from a dilute acid. E.g. 2Cr2 Ac2H Ac2 Cr3 Ac H2G8. 3. 8. Chemical reactivity and EVVV values. Example 8.6. Example 8.6. Example 8.6. Example 8.6. Example 8.6. In text questions. 8.6. Why is the highest oxidation state of a metal exhibited in its oxide or fluoride only? 8.7. Which is a stronger reducing agent, Cr2 or Fe2, and why, when a magnetic field is applied to substances, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Unit 1. Diamagnetic substances are repelled by the applied field, while the paramagnetic substances are attracted. Substances which are solution. Example 8.7. Example 8.7. Example 8.7. Example 8.7. Example 8.7. Solution. 228. Chemistry attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition metal ions are paramagnetic. Paramagnetism arises from the presence of unpaired electrons, each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of the first series of transition metals, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using the spin-only formula. That is, N2 micro, where N is the number of unpaired electrons and micro O is the magnetic moment in units of Bohr magneton bm. A single unpaired electron has a magnetic moment of 1.73 Bohr magnetons bm. The magnetic moment increases with the increasing number of unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom, molecule or ion. The magnetic moments calculated from the spin-only formula and those derived experimentally for some ions of the first row transition elements are given in Table 8.7. The experimental data are mainly for hydrated ions in solution or in the solid state. SC33D0000T33D111.73 1.75 TL23D222.84 2.76 V23D333.87 3.86 CR23D444.94.80 MN23D555.92 5.96 Fe23D644.95.3 to 5.5 CO23D733.87 4.4 to 5.2 Ni23D822.84 2.9 to 3. 4 Cu23D911.73 1.8 to 2.2 Zn23D1000 Ion configuration unpaired electron s magnetic moment calculated observed table 8.7 Calculated and observed magnetic moments BM Calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number is 25. With atomic number 25, the divalent ion in aqueous solution will have D5 configuration 5 unpaired electrons. The magnetic moment, micro is 5.92 bm 5.2 micro example 8.8 example 8.8 example 8.8 example 8.8 example 8.8 solution 229 The D and F block elements 3D0 SC3 colorless 3D0 T4 colorless 3D1 T3 purple 3D1 V4 blue 3D2 V3 green 3D3 V2 violet 3D3 CR3 violet 3D4 MN3 violet 3D4 CR2 blue 3D5 MN2 pink 3D5 Fe3 yellow 3D6 Fe2 green 3D60 3D7 Co3 CO2 blue pink 3D8 Ni2 green 3D9 Cu2 blue 3D10 Zn2 colorless configuration example color table 8.8 Colors of some of the first row aqueous transition metal ions August 3, 2011 Formation of complex compounds in text question 8.8 Calculate the spin-only magnetic moment of N2 Ag ion Z27. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed unit 9. This frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligand. In aqueous solutions where water molecules are the ligands, the colors of the ions observed are listed in Table 8.8. A few colored solutions of D-block elements are illustrated in Figure 8.5, August 3, 2010 Formation of colored ions Fig. 8.5, Colors of some of the first-row transition metal ions in aqueous solutions, from left to right, V4, V3, Mn2, Fe3, CO2, Ni2 and Cu2. Complex compounds are those in which the metal ions bind a number of anions or neutral molecules giving complex species with characteristic properties. A few examples are FeCN63, FeCN64, CuNH342 and PTCl42. The chemistry of complex compounds is 230 Chemistry dealt with in detail in Unit 9. The transition metals form a large number of complex compounds. This is due to the comparatively smaller sizes of the metal ions, their high ionic charges and the availability of d orbitals for bond formation. The transition metals and their compounds are known for their catalytic activity. This activity is ascribed to their ability to adopt multiple oxidation states and to form complexes. Vanadium V oxide in contact process, finely divided iron in Haber's process, and nickel in catalytic hydrogenation are some of the examples. Catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms of the surface of the catalyst. First-row transition metals utilize 3d and 4s electrons for bonding. This has the effect of increasing the concentration of the reactants at the catalyst surface and also weakening of the bonds in the reacting molecules. The activation energy is lowering. Also, because the transition metal ions can change their oxidation states, they become more effective as catalysts. For example, iron 3 catalyzes the reaction between iodide and persulfate ions. 2Is2O8 2I22SO4 An explanation of this catalytic action can be given as 2Fe3 2I2 Fe2I2 2Fe2S2O8 2Fe3 2SO4 Interstitial compounds are those which are formed when small atoms like H, C or N are trapped inside the crystal lattices of metals. They are usually non-stoichiometric and are neither typically ionic nor covalent. For example, TiC, Mn4n, Fe3H, VH0.56 and to 1.7, etc. The formulas quoted do not, of course, correspond to any normal oxidation state of the metal. Because of the nature of their composition, these compounds are referred to as interstitial compounds. The principal physical and chemical characteristics of these compounds are as follows. I. They have high melting points, higher than those of pure metals. 2. They are very hard. Some borides approach diamond in hardness. 3. They retain metallic conductivity. I. They are chemically inert. An alloy is a blend of metals prepared by mixing the components. Alloys may be homogeneous solid solutions in which the atoms of one metal are distributed randomly among the atoms of the other. Such alloys are formed by atoms with metallic radii that are within about 15% of each other. Because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. The alloys so formed are hard and have often high melting points. The best known are ferrous alloys. Chromium, vanadium, tungsten, molybdenum and manganese are used for the production of a variety of steels and stainless steel. Alloys of transition metals with non-transition metals such as brass, copper, zinc and bronze, copper, tin, are also of considerable industrial importance. August 3, 2012 Catalytic properties. August 3, 2013 Formation of interstitial compounds. August 3, 2014 Alloy formation. 231 The D and F block elements in text question 8.9 Explain why cation is not stable in aqueous solutions. 48 some capital I M P O R T A N T capital I M P O R T A N T capital I M P O R T A N T capital I M P compounds of capital T R A N S I T I O N capital T R A N S I T I O N capital T R A N S I T I O N Elements. What is meant by disproportionation of an oxidation state? Give an example. When a particular oxidation state becomes less stable relative to other oxidation states, one lower, one higher, it is said to undergo disproportionation. For example, manganese 6 becomes unstable relative to manganese 7 and manganese IV in acidic solution. 3 VO4 24H2 and VIO4 NiVO 22H2O. Example 8.9 Example 8.9 Example 8.9 Example 8.9 Example 8.9 Solution 8. 4. 1 Oxides and oxonions of metals. These oxides are generally formed by the reaction of metals with oxygen at high temperatures. All the metals except scandium form MO oxides which are ionic. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Besides the oxides, the oxidations stabilize VV as VO2, VIV as VO2 and TI as CO2. As the oxidation number of a metal increases, ionic character decreases. In the case of Mn2O7 is a covalent green oil. Even Cro3 and V2O5 have low melting points. In these higher oxides, the acidic character is predominant. Thus, Mn2O7 gives HMnO4 and Cro3 gives H2Cro4 and H2Cr2O7. V2O5 is, however, amphoteric though mainly acidic and it gives VO43 as well as VO2 salts. In vanadium there is gradual change from the basic V2O3 to less basic V2O4 and to amphoteric V2O5. V2O4 dissolves in acids to give VO2 salts. Similarly, V2O5 reacts with alkalis as well as acids to give 3,4-VO and 4-VO respectively. The well-characterized Cro is basic but Cr2O3 is amphoteric. Potassium dichromate K2Cr2O7. Potassium dichromate is a very important chemical used in leather industry and as an oxidant for preparation of many azo compounds. Dichromates are generally prepared from chromate, which in turn are obtained by the fusion of chromite or FeCr2O4 with sodium or potassium carbonate in free access of air. The reaction with sodium carbonate occurs as follows. 4 FeCr2O4 8 Na2CO3 7O2 8 Na2Cro4 2 Fe2O3 8 CO. To the yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromate, Na2Cr2O7. 2H2O can be crystallized 2 Na2Cro4 2H Na2Cr2O7 2 NaH2O. 232 Chemistry. Sodium dichromate is more soluble than potassium dichromate. The latter is therefore prepared by treating the solution of sodium dichromate with potassium chloride. Na2Cr2O7 2 KClK2Cr2O7 2 NaCl. Orange crystals of potassium dichromate crystallize out. The chromates and dichromates are interconvertible in aqueous solution depending upon pH of the solution. The oxidation state of chromium and chromate and dichromate is the same. 2Cro4 2 2HCr2O7 2H2OCr2O7 2 2O2 Cro4 2H2O. The structures of chromate ion, Cro4 2 and the dichromate ion, Cr2O7 2 are shown below. The chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedra sharing one corner with CrO-Cr bond angle of 126 degrees. Sodium and potassium dichromates are strong oxidizing agents. The sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. Potassium dichromate is used as a primary standard in volumetric analysis. In acidic solution, its oxidizing action can be represented as follows: Cr2O7214H62CR37H2OEV1.33V. Thus, acidified potassium dichromate will oxidize iodides to iodine, sulfides to sulfur, tin 2 to tin IV, and iron 2 salts to iron 3. The half reactions are noted below: 6I3I2 6E, 3SN2 3SN4 6E 3H2S6 H3S 6E, 6Fe2 6Fe3 6E. The full ionic equation may be obtained by adding the half reaction for potassium dichromate to the half reaction for the reducing agent. For e.g., Cr2O7214H6Fe22 Cr36Fe37H2O potassium permanganate KMnO4. Potassium permanganate is prepared by fusion of MnO2 with an alkali metal hydroxide and an oxidizing agent like NO3. This produces the dark green K2MnO4, which disproportionates in a neutral or acidic solution to give permanganate. 2MnO2 4GO02 2K2MnO4 2H2O 3MnO4 24H2 MnO4 MnO2 2H2O. Commercially, it is prepared by the alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate Vl. F fused with Co. Oxidize with air or no 2324MnO manganate ion 244 electrolytic oxidation in alkaline solution MnO manganate permanganate ion. In the laboratory, a manganese 2 ion salt is oxidized by peroxidisulfate to permanganate 2Mn2,5S2O8H2O2MnO4 tenso4 216H. Potassium permanganate forms dark purple almost black crystals which are isostructural with those of KClO4. The salt is not very soluble in water, 6.4 grams 100 grams of water at 293 K, but when heated it decomposes at 513 K. 2KMnO4 K2MnO4 MnO2O2. It has two physical properties of considerable interest: its intense color and its diamagnetism, along with temperature-dependent weak paramagnetism. These can be explained by the use of molecular orbital theory, which is beyond the present scope. The manganate and permanganate ions are tetrahedral. The Greek letter pi bonding takes place by overlap of p orbitals of oxygen with d orbitals of manganese. The green manganate is paramagnetic because of one unpaired electron, but the permanganate is diamagnetic due to the absence of unpaired electron. Acidified permanganate solution oxidizes oxalates to carbon dioxide, iron 2 to iron 3, nitrides to nitrates, and iodides to free iodine. The half reactions of reductants are COO 5 10 CO2 10 E5 Fe2 5 Fe3 5 E5 number 2 5 H2O 5 number 3 10 HL0 E10 I5 I2 10 E. The full reaction can be written by adding the half reaction for KMnO4 to the half reaction of the reducing agent, balancing wherever necessary. If we represent the reduction of permanganate to manganate, manganese dioxide and manganese 2 salt by half reactions, MnO4 EMnO4 2F 0.56 VMnO4 4H3 EMnO2 2H2O F 1.69 VMnO4 8H5 EMn2 4H2O F 1.52 V. We can very well see that the hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although many reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Permanganate at H1 should oxidize water, but in practice the reaction is extremely slow unless either manganese Ll ions are present or the temperature is raised. A few important oxidizing reactions of KMnO4 are given below. 1. In acid solutions, a iodine is liberated from potassium iodide. 10I2MnO4 16H2Mn2 8H2O5 I2B Fe2 ion green is converted to Fe3 yellow. 5 Fe2MnO4 8HMn2 4H2O5 Fe3. 234 Chemistry. C oxalate ion or oxalic acid is oxidized at 333 K. 5C2O422MnO4 16H. 2Mn2 8H2O 10 CO2 dihydrogen sulfate is oxidized. Sulfur being precipitated. H2S. 2HS25S2 2MnO4 16H. 2Mn2 8H2O5 Se sulfurous acid or sulfide is oxidized to a sulfate or sulfuric acid. 5So322 2MnO4 6H. 2Mn2 3H2O5 So4 2F nitrite is oxidized to nitrate. 5 number 2 2MnO4 6H. 2Mn2 5 number 3 3H2O2. in neutral or faintly alkaline solutions. A notable reaction is the oxidation of iodide to iodate. 2MnO4H2OI, 2MnO2,2OIO3 thiasulfate is oxidized almost quantitatively to sulfate. 8MnO4,3S2O32H2O, 8MnO2,6O422O. Manganese salt is oxidized to MnO2. The presence of zinc sulfate or zinc oxide catalyzes the oxidation. 2MnO4,3Mn22H2O, 5MnO2,4H. Note: permanganate titrations in presence of hydrochloric acid are unsatisfactory since hydrochloric acid is oxidized to chlorine. Uses. Besides its use in analytical chemistry, potassium permanganate is used as a favored oxidant in preparative organic chemistry. Its uses for the bleaching of wool, cotton, silk and other textile fibers and for the decolorization of oils are also dependent on its strong oxidizing power. The inner transition elements F block. The F block consists of the two series, lanthanoids, the 14 elements following lanthanum, and actinoids, the 14 elements following actinium. Because lanthanum closely resembles the lanthanoids, it is usually included in any discussion of the lanthanoids for which the general symbol Ln is often used. Similarly, a discussion of the actinoids includes actinium besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than do the members of ordinary transition elements in any series. They have only one stable oxidation state and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. The chemistry of the actinoids is, on the other hand, much more complicated. The complication arises partly owing to the occurrence of a wide range of oxidation states in these elements and partly because their radioactivity creates special problems in their study. The two series will be considered separately here. The names, symbols, electronic configurations of atomic and some ionic states and atomic and ionic radii of lanthanum and lanthanoids for which the general symbol Ln is used are given in Table 8.9. 8.58, 58, 58, 58, 5 capital L, A, N, T, H, A, N, O, I, D, S, capital L, A, N, T, H, A, N, O, I, D, S, capital L, A, N, T, H, A, N, O. 235 The D and F block elements Law 3 Se3 PR3 ND3 PN3 SM3 EU3 GD3 TB3 Di3 Ho3 or 3 TM3 3 Lu 3 Se4 PR4 TB4 2 TM2 SM2 EU2 110 190 57 61 6559 63 67 69 71 Ionic radii PM atomic number 8 5 1 Electronic configurations 8 5 2. Atomic and ionic sizes. It may be noted that atoms of these elements have electronic configuration with 6s2 common but with variable occupancy of 4f level Table 8.9. However, the electronic configurations of all the tripositive ions, the most stable oxidation state of all the lanthanoids, are of the form 4FNN1 to 14 with increasing atomic number. The overall decrease in atomic and ionic radii from lanthanum to lutetium, the lanthanoid contraction, is a unique feature in the chemistry of the lanthanoids. It has far-reaching consequences in the chemistry of the third transition series of the elements. The decrease in atomic radii derived from the structures of metals is not quite regular as it is regular in M3 ions Fig. 8.6. This contraction is, of course, similar to that observed in an ordinary transition series and is attributed to the same cause, the imperfect shielding of one electron by another in the same subshell. However, the shielding of one 4f electron by another is less than 1d electron by another with the increase in nuclear charge along the series. There is fairly regular decrease in the sizes with increasing atomic number, the cumulative effect of the contraction of the lanthanoid series, known as lanthanoid contraction, causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. The almost identical radii of ZR 160 pm and HF 159 pm, a consequence of the lanthanoid contraction, account for their occurrence together in nature and for the difficulty faced in their separation. In the lanthanoids, La2 and Ln3 compounds are predominant species. However, occasionally 2 and 4 ions in solution or in solid compounds are also obtained. This irregularity as in ionization enthalpies arises mainly from the extra stability of empty, half-filled or filled F subshell. Thus, the formation of Sieve is favored by its noble gas configuration, but it is a strong oxidant reverting to the common 3 state. The EO value for Se4 Se3 is 1.74 V, which suggests that it can oxidize water. However, the reaction rate is very slow and hence SeIV is a good analytical reagent. PR, ND, TB and Di also exhibit 4 state but only in oxides, MO2, Eu2 is formed by losing the 2s electrons, and its F7 configuration accounts for the formation of this ion. However, Eu2 is a strong reducing agent changing to the common 3 state. Similarly, Eu2, which has F14 configuration, is a reductant. It has half-filled f orbitals and is an oxidant. The behavior of samarium is very much like europium, exhibiting both 2 and 3 oxidation states. 8, 5, 3 oxidation states. Figure 8.6, trends in ionic radii of lanthanoids. 236 Chemistry Electronic Configurations Radii PM Atomic Name Symbol Ln Ln2 Ln3 Ln4 Ln Ln3 Number 57 Lanthanum La5D16s 2 5D1 4F0 187 106 58 Cerium Se4 F15D16s 2 4F2 4F1 4F0 183 103 59 Praseodymium PR4 F36s 2 4F3 4F2 4F1 182 101 60 Neodymium ND4 F46s 2 4F4 4F3 4F2 181 99 61 Promethium PM4 F56s 2 4F5 4F4 181 98 62 Samarium SM4 F66s 2 4F6 4F5 180 96 63 Europium U4 F76s 2 4F7 4F6 199 95 64 Gadolinium GD4 F75 D16s 2 4F75 D1 4F7 180 94 65 Terbium TB4 F96s 2 4F9 4F8 4F7 178 92 66 Dysprosium Di4 F106s 2 4F10 4F9 4F8 177 91 67 Holmium Ho4 F116s 2 4F11 4F10 176 89 68 Erbium Er4 F126s 2 4F12 4F11 175 88 69 Thulium TM4 F136s 2 4F13 4F12 174 87 70 Ytterbium Ib4 F146s 2 4F14 4F13 173 86 71 Lutetium Lu4 F145 D16s 2 4F 145 D1 4F14 Table 8.9 Electronic configurations and radii of lanthanum and lanthanoids. Only electrons outside Xe core are indicated. All the lanthanoids are silvery white soft metals and tarnish rapidly in air. The hardness increases with increasing atomic number, samarium being steel hard. Their melting points range between 1000 to 1200 K, but samarium melts at 1623 K. They have typical metallic structure and are good conductors of heat and electricity. Density and other properties change smoothly except for U and Ib and occasionally for Sm and Tm. Many trivalent lanthanoid ions are colored both in the solid state and in aqueous solutions. Color of these ions may be attributed to the presence of F electrons. Neither La3 nor Lu3 ion shows any color, but the rest do so. However, absorption bands are narrow, probably because of the excitation within F level. The lanthanoid ions other than the F0 type La3 and Se4 and the F14 type Ib2 and Lu3 are all paramagnetic. The first ionization enthalpies of the lanthanoids are around 600 kJ-mol1, the second about 1200 kJ-mol1, comparable with those of calcium. A detailed discussion of the variation of the third ionization enthalpies indicates that the exchange enthalpy considerations as in 3d orbitals of the first transition series appear to impart a certain degree of stability to empty, half-filled and completely filled orbitals F level. This is indicated from the abnormally low value of the third ionization enthalpy of lanthanum, gadolinium and lutetium. In their chemical behavior, in general, the earlier members of the series are quite reactive, similar to calcium, but, with increasing atomic number, they behave more like aluminium. Values for F for the half reaction, Ln3 Ac3 ELNS8, 5, 4 general characteristics. 237 The D and F block elements LnC2 with C2773 Kn Ln heated with N with HO2 LnO2 3H2 with acids Bierns in O2 heated with S with halogens LnX3 LnO3 H2 LnS2 3 Ln8.68 68 68 68 6 The actinoids The actinoids are in the range of -2.2 to -2.4 V except for U, for which the value is 2.0 V. This is, of course, a small variation. The metals combine with hydrogen when gently heated in the gas. The carbides, Ln3C, Ln2C3 and Lnc2 are formed when the metals are heated with carbon. They liberate hydrogen from dilute acids and burn in halogens to form halides. They form oxides Am2O3 and hydroxides Am03. The hydroxides are definite compounds, not just hydrated oxides. They are basic like alkaline earth metal oxides and hydroxides. Their general reactions are depicted in Fig. 8.7. The best single use of the lanthanoids is for the production of alloy steels for plates and pipes. A well-known alloy is mischmetal, which consists of a lanthanoid metal 95 and iron 5 and traces of S, C, Ca and Al. A good deal of mischmetal is used in Mg-based alloy to produce bullets, shell and lighter flint. Mixed oxides of lanthanoids are employed as catalysts in petroleum cracking. Some individual Al-N oxides are used as phosphors in television screens and similar fluorescing surfaces. The actinoids include the 14 elements from DH to Lr. The names, symbols and some properties of these elements are given in Table 8.10. Table 8.10. Some properties of actinium and actinoids. Electronic configurations. Radii PM. Atomic name symbol MM3 M4 M3 M4 number 89. Actinium AC6D17s 25F0 111 90. Thorium DH6D27s 25F15 F0 99 91. Protactinium Pa5 F26D17s 25F 25F 196 92. Uranium U5F 36D17s 25F35 F2 103 93 93. Neptunium NP5F 46D17s 25F4 5F3 101 92 94. Plutonium Pu5 F67s 25F55 F4 100 90 95. Americium M5F77s 25F65 F5 99 89 96. Curium CM5 F76D17s 25F7 5F6 99 88 97. Berkelium BK5 F97s 25F85 F7 98 87 98. Californium CF 5F107s 25F9 5F8 98 86 99. Instinium Us 5F117s 25F10 5F9 100. Fermium FM5 F127s 25F11 5F10 101. Mendelevium MD5 F137s 25F12 5F11 102. Nobelium number 5 F147s 25F13 5F12 103. Lawrencium LR5 F146 D17s 25F14 5F13. Figure 8.7. Chemical reactions of the lanthanoids. 238. Chemistry. The actinoids are radioactive elements and the earlier members have relatively long half-lives. The latter ones have half-life values ranging from a day to 3 minutes. For Lawrencium Z103, the latter members could be prepared only in nanogram quantities. These facts render their study more difficult. All the actinoids are believed to have the electronic configuration of 7s2 and variable occupancy of the 5f and 6d subshells. The 14 electrons are formally added to 5f, though not in thorium Z90 but from Pa onwards the 5f orbitals are complete at element 103. The irregularities in the electronic configurations of the actinoids, like those in the lanthanoids, are related to the stabilities of the F0, F7 and F14 occupancies of the 5f orbitals. Thus, the configurations of M and Cm are Rn5F77s 2 and Rn5F76D17s 2, although the 5f orbitals resemble the 4f orbitals in their angular part of the wave function. They are not as buried as 4f orbitals and hence 5f electrons can participate in bonding to a far greater extent. The general trend in lanthanoids is observable in the actinoids as well. There is a gradual decrease in the size of atoms or M3 ions across the series. This may be referred to as the actinoid contraction, like lanthanoid contraction. The contraction is, however, greater from element to element in this series, resulting from poor shielding by 5f electrons. There is a greater range of oxidation states, which is in part attributed to the fact that the 5f, 6d and 7s levels are of comparable energies. The known oxidation states of actinoids are listed in Table 8.11. The actinoids show in general 3 oxidation states. The elements, in the first half of the series, frequently exhibit higher oxidation states. For example, the maximum oxidation state increases from 4 in DH to 5, 6 and 7 respectively in Pa, U and NP, but decreases in succeeding elements. Table 8.11. The actinoids resemble the lanthanoids in having more compounds in 3 state than in the 4 state. However, 3 and 4 ions tend to hydrolyze. Because the distribution of oxidation states among the actinoids is so uneven and so different for the former and later elements, it is unsatisfactory to review their chemistry in terms of oxidation states. 8, 6, 1 electronic configurations. 8, 6, 2 ionic sizes. 8, 6, 3 oxidation states. The actinoid metals are all silvery in appearance but display a variety of structures. The structural variability is obtained due to irregularities in metallic radii which are far greater than in lanthanoids. 8, 6, 4 general characteristics and comparison with lanthanoids ACTH PIUNP PUM CMB KCFEs FMMD no LR 33333333333333333333333333333333333333333333333333333333333333333 Table 8.11 Oxidation states of actinium and actinoids. 239 The D and F block elements. The actinoids are highly reactive metals, especially when finely divided. The action of boiling water on them, for example, gives a mixture of oxide and hydride in combination with most nonmetals takes place at moderate temperatures. Hydrochloric acid attacks all metals but most are slightly affected by nitric acid owing to the formation of protective oxide layers. Alkalis have no action. The magnetic properties of the actinoids are more complex than those of the lanthanoids, although the variation in the magnetic susceptibility of the actinoids with the number of unpaired 5f electrons is roughly parallel to the corresponding results for the lanthanoids. The latter have higher values. It is evident from the behavior of the actinoids that the ionization enthalpies of the early actinoids, though not accurately known, but are lower than for the early lanthanoids. This is quite reasonable since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of electrons. The 5f electrons will therefore be more effectively shielded from the nuclear charge than the 4f electrons of the corresponding lanthanoids. Because the outer electrons are less firmly held, they are available for bonding in the actinoids. A comparison of the actinoids with the lanthanoids, with respect to different characteristics as discussed above, reveals that behavior similar to that of the lanthanoids is not evident until the second half of the actinoid series. However, even the early actinoids resemble the lanthanoids in showing close similarities with each other and in gradual variation in properties which do not entail change in oxidation state. The lanthanoid and actinoid contractions have extended effects on the sizes, and therefore, the properties of the elements succeeding them in their respective periods. The lanthanoid contraction is more important because the chemistry of elements succeeding the actinoids are much less known at the present time. 8.78, 78, 78, 78, 7 Some applications of D and 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 F block elements iron and steels are the most important construction materials. Their production is based on the reduction of iron oxides, the removal of impurities and the addition of carbon and alloying metals such as Cr, Mn and Ni. Some compounds are manufactured for special purposes such as SHIO for the pigment industry and MnO2 for use in dry battery cells. The battery industry also requires Zn and NiCd. The elements of group 11 are still worthy of being called the coinage metals, although Ag and Dow name a member of the lanthanoid series which is well known to exhibit 4 oxidation state. Cerium Z58 Example 8.10 Example 8.10 Example 8.10 Example 8.10 Example 8.10 Solution in text question 8.10 Actinoid contraction is greater from element 2 element than lanthanoid contraction. Why? 240 Chemistry are restricted to collection items and the contemporary UK copper coins are copper-coated steel. The silver UK coins are a Cu-Ni alloy. Many of the metals and/or their compounds are essential catalysts in the chemical industry. V2O5 catalyses the oxidation of SO2 in the manufacture of sulfuric acid. TCl4 with A1CH33 forms the basis of the Ziegler catalysts used to manufacture polyethylene polythene. Iron catalysts are used in the Haber process for the production of ammonia from N2H2 mixtures. Nickel catalysts enable the hydrogenation of fats to proceed. In the Wacker process the oxidation of ethene to ethanol is catalyzed by PDCl2. Nickel complexes are useful in the polymerization of alkynes and other organic compounds such as benzene. The photographic industry relies on the special light-sensitive properties of Ag-Br. The D block consisting of groups 312 occupies the large middle section of the periodic table. In these elements the inner d orbitals are progressively filled. The F block is placed outside at the bottom of the periodic table and in the elements of this block, 4f and 5f orbitals are progressively filled. Corresponding to the filling of 3d, 4d and 5d orbitals, 3 series of transition elements are well recognized. All the transition elements exhibit typical metallic properties such as high tensile strength, ductility, malleability, thermal and electrical conductivity and metallic character. Their melting and boiling points are high which are attributed to the involvement of N1d electrons resulting into strong interatomic bonding. In many of these properties, the maxima occur at about the middle of each series which indicates that one unpaired electron per d orbital is particularly a favorable configuration for strong interatomic interaction. Successive ionization enthalpies do not increase as steeply as in the main group elements with increasing atomic number. Hence, the loss of variable number of electrons from N1d orbitals is not energetically unfavorable. The involvement of N1d electrons in the behavior of transition elements imparts certain distinct characteristics to these elements. Thus, in addition to variable oxidation states, they exhibit paramagnetic behavior, catalytic properties and tendency for the formation of colored ions, interstitial compounds and complexes. The transition elements vary widely in their chemical behavior. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble. Of the first series, with the exception of copper, all the metals are relatively reactive. The transition metals react with a number of nonmetals like oxygen, nitrogen, sulfur and halogens to form binary compounds. The first series transition metal oxides are generally formed from the reaction of metals with oxygen at high temperatures. These oxides dissolve in acids and bases to form oxymetallic salts. Potassium dichromate and potassium permanganate are common examples. Potassium dichromate is prepared from the chromite ore by fusion with alkaline presence of air and acidifying the extract. Pyrolusite or MnO2 is used for the preparation of potassium permanganate. Both the dichromate and the permanganate ions are strong oxidizing agents. The two series of inner transition elements, lanthanoids and actinoids, constitute the F block of the periodic table. With the successive filling of the inner orbitals, 4f, there is a gradual decrease in the atomic and ionic sizes of these metals along the series lanthanoid contraction. This has far-reaching consequences in the chemistry of the elements succeeding them. Lanthanum and all the lanthanoids are rather soft white metals. They react easily with water to give solutions giving 3 ions. The principal oxidation state is 3. Although 4 and 2 oxidation states are also exhibited by some summary. 241 The D and F block elements occasionally. The chemistry of the actinoids is more complex in view of their ability to exist in different oxidation states. Furthermore, many of the actinoid elements are radioactive, which make the study of these elements rather difficult. There are many useful applications of the D and F block elements and their compounds, notable among them being in varieties of steels, catalysts, complexes, organic syntheses, etc. 244 Chemistry. In the previous unit we learnt that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules by sharing of electrons. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of biological systems. Chlorophyll, hemoglobin and vitamin B12 are coordination compounds of magnesium, iron and cobalt respectively. Variety of metallurgical processes, industrial catalysts and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing and medicinal chemistry. Coordination compounds. After studying this unit, you will be able to appreciate the postulates of Werner's theory of coordination compounds, know the meaning of the terms, coordination entity, central atom ion, ligand, coordination number, coordination sphere, coordination polyhedron, oxidation number, homoleptic and heteroleptic. Learn the rules of nomenclature of coordination compounds, write the formulas and names of mononuclear coordination compounds, define different types of isomerism in coordination compounds, understand the nature of bonding in coordination compounds in terms of the valence bond and crystal field theories, appreciate the importance and applications of coordination compounds in our day-to-day life. Objectives. Coordination compounds are the backbone of modern inorganic and bioinorganic chemistry and chemical industry. Coordination compounds. Alfred Werner 1866–1919, a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of a primary valence and a secondary valence for a metal ion. Binary compounds such as CrCl3, CoCl2 or PdCl2 have primary valence of 3, 2 and 2 respectively. In a series of compounds of cobalt-3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold, but some remained in solution. 9.19.19.19.19.19. Werner's SSSS theory of capital C-O-O-R-D-I-N-A-T-I-O-N, capital C-O-O-R-D-I-N-A-T-I-O-N, capital C-O-O-R-D-I, compounds 9 unit 9. 245 coordination compounds 1 mol Co-Cl3.6 NH3 yellow gave 3 mol AgCl 1 mol Co-Cl3.5 NH3 purple gave 2 mol AgCl 1 mol Co-Cl3.4 NH3 green gave 1 mol AgCl 1 mol Co-Cl3.4 NH3 violet gave 1 mol AgCl. These observations, together with the results of conductivity measurements in solution, can be explained if I6 groups in all, either chloride ions or ammonia molecules or both, remain bonded to the cobalt ion during the reaction, and the compounds are formulated as shown in Table 9.1, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples the secondary valences are 6. Note that the last two compounds in Table 9.1 have identical empirical formula, Co-Cl3.4 NH3, but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are: 1. In coordination compounds metals show two types of linkages, valences primary and secondary. 2. The primary valences are normally ionizable and are satisfied by negative ions. 3. The secondary valences are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. 4. The ions groups bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination numbers. In modern formulations, such spatial arrangements are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counterions. He further postulated that octahedral, tetrahedral and square planar geometrical shapes are more common in coordination compounds of transition metals. Thus, Co-NH363, Co-ClNH352 and Co-Cl2NH34 are octahedral entities, while NiCO4 and PtCl42 are tetrahedral and square planar, respectively. Color formula solution conductivity corresponds to Table 9.1. Formulation of cobalt-3 chloride ammonia complexes: yellow Co-NH3633Cl1, 3 electrolyte purple Co-ClNH3522Cl1, 2 electrolyte green Co-Cl2NH34Cl1, 1 electrolyte violet Co-Cl2NH34Cl1, 1 electrolyte. I secondary 4 2 secondary 6 3 secondary 6 5 secondary 6 volt secondary 4 on the basis of the following observations made with aqueous solutions. Assign secondary valences to metals in the following compounds. Solution difference between a double salt and a complex. Both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, KCl-MgCl2.6H2O, more salt, FeSO4, NH4-2SO4.6H2O, potash alum, CalSO4 2.12H2O, etc. Dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN6 of K4 FeCN6 do not dissociate into Fe2 and Cn ions. Formula: moles of AgCl precipitated per mole of the compounds with excess OGNO3 IPDCl2.4NH322 NiCl2.6H2O23 PTCl4.2HCl0 Co-Cl3.4NH3 1 volt PTCl2.2NH30 Example 9.1 Example 9.1 Example 9.1 Example 9.1 Example 9.1 Werner was born on December 12, 1866, in Mulhouse, a small community in the French province of Alsace. His study of chemistry began in Karlsruhe, Germany and continued in Zurich, Switzerland, where in his doctoral thesis in 1890, he explained the difference in properties of certain nitrogen-containing organic substances on the basis of isomerism. He extended Van 't Hoff's theory of tetrahedral carbon atom and modified it for nitrogen. Werner showed optical and electrical differences between complex compounds based on physical measurements. In fact, Werner was the first to discover optical activity in certain coordination compounds. He, at the age of 29 years, became a full professor at Technische Hochschule in Zurich in 1895. Alfred Werner was a chemist and educationist. His accomplishments included the development of the theory of coordination compounds. This theory, in which Werner proposed revolutionary ideas about how atoms and molecules are linked together, was formulated in a span of only 3 years, from 1890 to 1893. The remainder of his career was spent gathering the experimental support required to validate his new ideas. Werner became the first Swiss chemist to win the Nobel Prize in 1913 for his work on the linkage of atoms and the coordination theory. 1866-1919, 1866-1919, 1866-1919, 1866-1919, 1866-1919. 247 Coordination compounds. A coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, CoCl3NH33 is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples are NiCO4, PtCl2NH32, FeCN64, CoNH363b. Central atom ion. In a coordination entity, the atom ion to which a fixed number of ions groups are bound in a definite geometrical arrangement around it, is called the central atom or ion. For example, the central atom ion in the coordination entities, NiCl2H2O4, CoClNH352 and FeCN63 are Ni2, Co3 and Fe3, respectively. These central atoms ions are also referred to as Lewis acid C ligands. The ions or molecules bound to the central atom ion in the coordination entity are called ligands. These may be simple ions such as Cl, small molecules such as H2O or NH3, larger molecules such as H2NCH2CH2NH2 or NCH2CH2NH23, or even macromolecules, such as proteins. When a ligand is bound to a metal ion through a single donor atom, as with Cl, H2O or NH3, the ligand is said to be unidentate. When a ligand combined through 2 donor atoms as in H2NCH2CH2NH2 ethane 1, 2-diamine or C2O4-2-oxalate, the ligand is said to be didentate, and when several donor atoms are present in a single ligand as in NCH2CH2NH23, the ligand is said to be polydentate. Ethylene diaminidotrocetate ion EDTA4 is an important hexadentate ligand. It combined through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydentate ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes, called chelate complexes, tend to be more stable than similar complexes containing unidentate ligands. Ligand which has 2 different donor atoms and either of the 2 ligates in the complex is called ambidentate ligand. Examples of such ligands are the number 2 and SCN ions. Number 2 ion can coordinate either through nitrogen or through oxygen to a central metal atom ion. Similarly, SCN ion can coordinate through the sulfur or nitrogen atom. D coordination number. The coordination number Cn of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ions, PtCl62 and NiNH342, the coordination number of Pt and Ni are 6 and 4 respectively. Similarly, in the complex ions, Fe2O433 and CoN33, the coordination number of both, Fe and company, is 6 because C2O42 and N-ethane 1, 2-diamine are didentate ligands. 9.29, 29, 29, 29, 2 definitions of definitions of definitions of definitions of definitions of some important terms pertaining to 2. Capital C O O R D I N A T I O N. Capital C O O R D I N A T I O N. Capital C O O R D I. Compounds. 248 Chemistry. It is important to note here that coordination number of the central atom ion is determined only by the number of sigma bonds formed by the ligand with the central atom ion. Pi bonds, if formed between the ligand and the central atom ion, are not counted for this purpose. Coordination sphere. The central atom ion and the ligands attached to it are enclosed in square bracket and is collectively termed as the coordination sphere. The ionizable groups are written outside the bracket and are called counterions. For example, in the complex K4 FeCN6, the coordination sphere is FeCN64 and the counterion is K. F. Coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom ion defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar and tetrahedral. For example, CoNH363 is octahedral, NiCO4 is tetrahedral and PtCl42 is square planar. Figure 9.1 shows the shapes of different coordination polyhedra. 9.39, 39, 39, 39, 3. capital N-O-M-E-N-C-L-A-T-U-R-E, capital N-O-M-E-N-C-L-A-T-U-R-E, capital N-O-M-E-N-C, Off, capital C-O-O-R-D-I-N-A-T-I-O-N, capital C-O-O-R-D-I-N-A-T-I-O-N, capital C-O-O-R-D-I, capital C-O-M-P-O-U-N-D-S, capital C-O-M-P-O-U-N-D-S, capital C-O-M-P-O-U-N-D-S, capital C-O-M. G. Oxidation number of central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses following the name of the coordination entity. For example, oxidation number of copper in CuCN43 is 1 and it is written as CuIH. Homoleptic and heteroleptic complexes in which a metal is bound to only one kind of donor groups, e.g., CoNH363, are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor groups, e.g., CoNH34Cl2, are known as heteroleptic. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names, particularly when dealing with isomers. The formulas and names adopted for coordination entities are based on the recommendations of the International Union of Pure and Applied Chemistry IUPAC. Figure 9.1, Shapes of different coordination polyhedra. M represents the central atom ion and L, a unidentate ligand. 249 Coordination compounds. The formula of a compound is a shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. The following rules are applied while writing the formulas. I. The central atom is listed first. 2. The ligands are then listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. 3. Polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. I. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. V. There should be no space between the ligands and the metal within a coordination sphere V when the formula of a charged coordination entity is to be written without that of the counter-ion. The charge is indicated outside the square brackets as a right superscript with the number before the sign. For example, CoCN63, CrH2O63, etc. 7. The charge of the cation S is balanced by the charge of the anion S. The names of coordination compounds are derived by following the principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. I. The cation is named first in both positively and negatively charged coordination entities. 2. The ligands are named in an alphabetical order before the name of the central atom ion. This procedure is reversed from writing formula. 3. Names of the anionic ligands and NO, those of neutral and cationic ligands are the same except aqua for H2O, amine for NH3, carbonyl for CO and nitrosyl for NO, while writing the formula of coordination entity. These are enclosed in brackets. I. Prefixes mono, di, tri, etc. are used to indicate the number of the individual ligands in the coordination entity. When the names of the ligands include a numerical prefix, then the terms bis, tris, tetrachus are used, the ligand to which they refer being placed in parentheses. For example, NiCl2PPH32 is named as dichloroetibus triphenylphosphine nickel 2V. Oxidation state of the metal in cation, anion or neutral coordination entity is indicated by Roman numeral in parenthesis. V. If the complex ion is a cation, the metal is named same as the element. For example, Co in a complex cation is called cobalt and Pt is called platinum. If the complex ion is an anion, the name of the metal ends with the suffix ate. For example, Co in a complex anion, 2,4-CoSCN is called cobaltate. For some metals, the Latin names are used in the complex anions, e.g., ferrate for Fe9, 3. 2. Naming of mononuclear coordination compounds. Note, the 2004 IUPAC draft recommends that ligands will be sorted alphabetically, irrespective of charge. Note, the 2004 IUPAC draft recommends that anionic ligands will end with -ido so the chloro would become chlorido, etc. 9. 3. 1 Formulas of mononuclear coordination entities. 250 Chemistry 7. The neutral complex molecule is named similar to that of the complex cation. The following examples illustrate the nomenclature for coordination compounds. 1. CrNH33H2O3Cl3 is named as triamine triacylchromium-free chloride. Explanation: the complex ion is inside the square bracket, which is a cation. The amine ligands are named before the aqua ligands according to alphabetical order. Since there are 3 chloride ions in the compound, the charge on the complex ion must be 3 since the compound is electrically neutral. From the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number of the metal. In this example, all the ligands are neutral molecules, therefore, the oxidation number of chromium must be the same as the charge of the complex ion, 3. 2. CoH2NCH2CH2NH232 So 4,3 is named as trisethane 1, 2-diamine cobalt 3 sulfate. Explanation: the sulfate is the counteranion in this molecule. Since it takes 3 sulfates to bond with 2 complex cations, the charge on each complex cation must be 3. Further, ethane 1, 2-diamine is a neutral molecule, so the oxidation number of cobalt in the complex ion must be 3. Remember that you never have to indicate the number of cations and anions in the name of an ionic compound. 3. AgNH32AgCN2 is named as diaminosilveride cyanide argentate. I write the formulas for the following coordination compounds: a tetraamine equichloroidocobalt 3 chloride B potassium tetrahydroxidizing 2 C potassium trioxalate aluminate 3 dichloroidobus ethane 1, 2-diamine cobalt 3 E tetracarbonyl nickel 0 a CONH34H2OCl2BK2ZNO4CK3Al C2043 DCO-Cl2 and 2 EnCO4. Write the IUPAC names of the following coordination compounds: a PTNH32Cl number 2 BK3CrC2043 CCO-Cl2 and 2 CLD-CoNH35CO3 ClEHG-CoSCN4 a diamine echloroidonitride and platinum 2 B potassium trioxalate ochromate 3 C dichloridobus ethane 1, 2-diamine cobalt 3 chloride D pentamine carbonatocobalt 3 chloride E mercury I tetrathiocyanado S cobalt 3. Example 9.2 Example 9.2 Example 9.2 Example 9.2 Example 9.2 Solution Example 9.3 Example 9.3 Example 9.3 Example 9.3 Example 9.3 Solution. Notice how the name of the metal differs in cation and anion even though they contain the same metal ions. 251 Coordination compounds 9. 4. 1. Geometric isomerism. Isomers are 2 or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical or chemical properties. 2 principal types of isomerism are known among coordination compounds, each of which can be further subdivided. A stereoisomerism, I geometrical isomerism, 2 optical isomerism, B structural isomerism, I linkage isomerism, 2 coordination isomerism, 3 ionization isomerism, I solvate isomerism. Stereoisomers have the same chemical formula and chemical bonds but they have different spatial arrangement. Structural isomers have different bonds. A detailed account of these isomers are given below. This type of isomerism arises in heteroleptic complexes due to different possible geometric arrangements of the ligands. Important examples of this behavior are found with coordination numbers 4 and 6, in a square planar complex of formula MX2L2X and L are unidentate. The 2 ligands X may be arranged adjacent to each other in a cis isomer, or opposite to each other in a trans isomer as depicted in Fig. 9.2. Other square planar complex of the type MABXL where A, B, X, L are unidentates shows 3 isomers 2 cis and 1 trans. You may attempt to draw these structures. Such isomerism is not possible for a tetrahedral geometry but similar behavior is possible in octahedral complexes of formula MX2L4 in which the 2 ligands X may be oriented cis or trans to each other. Fig. 9.39.49, 49. For isomerism in capital COORDINATION, capital COORDINATION, capital COORDI, compounds. Fig. 9.2. Geometrical isomer cis and trans of PTNH32Cl2 CoCl2NH3NH3NH3NH3 CoCl2NH3NH3NH3 cis trans. Fig. 9.3. Geometrical isomer cis and trans of CoNH34Cl2 in text questions. 9.1 Write the formulas for the following coordination compounds: I-tetraaminidia coacobal 3 chloride 2 potassium tetracyanide nickel 2 3 trisethane 1, 2-diamine chromium trichloride ivaminobromide ichloridenitridone platinate 2v-dichloridobis ethane 1, 2-diamine platinum IV nitrate V iron 3-hexocyanidopherate 2 9. To write the IUPAC names of the following coordination compounds: ICO-NH36Cl32 CO-NH35Cl Cl23K3FeCN6 IV K3FeC2O43VK2PDCl4VPTNH32ClNH2CH3Cl 252 Chemistry. This type of isomerism also arises when didn't ligands LLEG, NH2CH2CH2NH2N are present in complexes of formula MX2LL2 Fig. 9.4. Another type of geometrical isomerism occurs in octahedral coordination entities of the type MO3B3 like CONH33 number 23. If three donor atoms of the same ligands occupy adjacent positions at the corners of an octahedral face, we have the facial Fag isomer. When the positions are around the meridian of the octahedron, we get the meridian-Ulmer isomer Fig. 9.5. Fig. 9.4. Geometrical isomer cis and trans of Co-Cl2 and 2Y is geometrical isomerism not possible in tetrahedral complexes having two different types of unident ligands coordinated with the central metal ion. Tetrahedral complexes do not show geometrical isomerism because the relative positions of the unident ligands attached to the central metal atom are the same with respect to each other. Solution. Optical isomers are mirror images that cannot be superimposed on one another. These are called as enantiomers. The molecules or ions that cannot be superimposed are called chiral. The two forms are called dextro D and levo L depending upon the direction they rotate. The plane of polarized light in a polarimeter D rotates to the right, L to the left. Optical isomerism is common in octahedral complexes involving dident ligands. Figure 9.6. In a coordination entity of the type PTCl2 and 2,2, only the cis isomer shows optical activity. Fig. 9.79. 4. 2 optical isomerism. Figure 9.6. Optical isomers D and L of CON33. Figure 9.7. Optical isomers D and L of cis PTCl2 and 2,2. Fig. 9.5. The facial Fag and meridian-Ulmer isomers of CONH33 number 23. Example 9.4. Example 9.4. Example 9.4. Example 9.4. Example 9.4. 253 Coordination compounds. Linkage isomerism arises in a coordination compound containing an ambident ligand. A simple example is provided by complexes containing the thiocyanate ligand, NCS, which may bind through the nitrogen to give MnCS or through sulfur to give MsCN. Jornsen discovered such behavior in the complex CONH35 number 2 Cl2, which is obtained as the red form, in which the nitrite ligand is bound through oxygen ONO, and as the yellow form, in which the nitrite ligand is bound through nitrogen number 2. This type of isomerism arises from the interchange of ligands between cationic and anionic entities of different metal ions present in a complex. An example is provided by CONH36CrCN6, in which the NH3 ligands are bound to CO3 and the CN ligands to Cr3. In its coordination isomer CrNH36CoCN6, the NH3 ligands are bound to Cr3 and the CN ligands to CO3. This form of isomerism arises when the counterion in a complex salt is itself a potential ligand and can displace a ligand which can then become the counterion. An example is provided by the ionization isomers CONH35SO4Br and CONH35BrSO4, 9, 4, 3 linkage isomerism 9, 4, 4 coordination isomerism 9, 4, 5 ionization isomerism. Out of the following two coordination entities which is chiral optically active? A cis CrCl2OX23B trans CrCl2OX23. The two entities are represented as draw structures of geometrical isomers of FeNH32CN4. Solution. Out of the two, a cis CrCl2OX23 is chiral optically active. Example 9.5. Example 9.5. Example 9.5. Example 9.5. Example 9.5. Solution. Example 9.6. Example 9.6. Example 9.6. Example 9.6. Example 9.6. 254 Chemistry. This form of isomerism is known as hydrate isomerism in case where water is involved as a solvent. This is similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. An example is provided by the aqua complex CrH2O6Cl3 violet and its solvate isomer CrH2O5Cl2H2O gray-green. 9, 4, 6 Solvate isomerism. Werner was the first to describe the bonding features in coordination compounds. But his theory could not answer basic questions like, why only certain elements possess the remarkable property of forming coordination compounds. 2. Why the bonds in coordination compounds have directional properties. 3. Why coordination compounds have characteristic magnetic and optical properties. Many approaches have been put forth to explain the nature of bonding in coordination compounds, viz. valence bond theory VBT, crystal field theory CFT, ligand field theory LFT, and molecular orbital theory MO. We shall focus our attention on elementary treatment of the application of VBT and CFT to coordination compounds. According to this theory, the metal atom or ion under the influence of ligands can use its N1D, NS, NP or NS, NP, ND orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar and so on. Table 9.2. These hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. This is illustrated by the following examples. 9.59, 59, 59, 59, 5 bonding in bonding in bonding in bonding in bonding in, capital C O O R D I N A T I O N, capital C O O R D I N A T I O N, capital C O O R D I, compounds 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 9, 5. 1. Valence bond theory. Table 9.2. Number of orbitals and types of hybridizations. 4 sp3 tetrahedral, 4 dsp2 square planar, 5 sp3d trigonal bipyramidal, 6 sp3d to octahedral, 6 d2 sp3 octahedral. Coordination. Number, type of hybridization, distribution of hybrid orbitals in space. In text questions. 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 9.3. Indicate the types of isomerism exhibited by the following complexes and draw the structures for these isomers. IKCrH2O2C2O422 CoN3Cl33 CoNH35 number 2 number 3 2 5PTNH3H2OCl2 9.4. Give evidence that CoNH35Cl-SO4 and CoNH35SO4Cl are ionization isomers. 255. Coordination compounds. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. In the diamagnetic octahedral complex, CoNH363, the cobalt ion is in 3 oxidation state and has the electronic configuration 3d6. The hybridization scheme is as shown in diagram. Orbitals of co-ion 3 sp(d)3 to 3 hybridized orbitals of co-COF outer orbital or high-spin complex 636 pairs of electrons from 6 f ions 3d4s4p sp(d3 3 hybrid 4d3d3d6 pairs of electrons, 1 from each NH3 molecule, occupy the 6 hybrid orbitals. Thus, the complex has octahedral geometry and is diamagnetic because of the absence of unpaired electron. In the formation of this complex, since the inner d orbital 3d is used in hybridization, the complex, CoNH363 is called an inner orbital or low spin or spin paired complex. The paramagnetic octahedral complex, COF63 uses outer orbital 4d in hybridization sp3d2, it is thus called outer orbital or high spin or spin-free complex. Thus, in tetrahedral complexes 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. This is illustrated below for NiCl42. Here nickel is into oxidation state and the ion has the electronic configuration 3d8. The hybridization scheme is as shown in diagram. Each Cl ion donates a pair of electrons. The compound is paramagnetic since it contains 2 unpaired electrons. Similarly, NiCO4 has tetrahedral geometry but is diamagnetic since nickel is in 0 oxidation state and contains no unpaired electron. 256. Chemistry. Orbitals of Ni ion 2dsp hybridized orbitals of Ni2 to Ni-Cn low spin complex 423d4s4p 4 pairs of electrons from 4 Cn groups dsp2 hydrid 3d4 page 9, 5. 2 magnetic properties of coordination compounds in the square planar complexes. The hybridization involved is dsp2. An example is NiCN42. Here nickel is into oxidation state and has the electronic configuration 3d8. The hybridization scheme is as shown in diagram. Each of the hybridized orbitals receives a pair of electrons from a cyanide ion. The compound is diamagnetic as evident from the absence of unpaired electron. It is important to note that the hybrid orbitals do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the number of unpaired electrons, page 228, and hence structures adopted by metal complexes. A critical study of the magnetic data of coordination compounds of metals of the first transition series reveals some complications. For metal ions with up to 3 electrons in the d orbitals, like T3d1, V3d2, Cr3d3, 2 vacant d orbitals are available for octahedral hybridization with 4s and 4p orbitals. The magnetic behavior of these free ions and their coordination entities is similar. When more than 3 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Thus, for D4Cr2, Mn3, D5Mn2, Fe3, D6 Fe2, Co3 cases, a vacant pair of d orbitals results only by pairing of 3d electrons, which leaves 2, 1 and 0 unpaired electrons, respectively. The magnetic data agree with maximum spin pairing in many cases, especially with coordination compounds containing d6 ions. However, with species containing d4 and d5 ions there are complications. MnCN63 has magnetic moment of 2 unpaired electrons while MnCl63 has a paramagnetic moment of 4 unpaired electrons. FeCN63 has magnetic moment of a single unpaired electron while Fef63 has a paramagnetic moment of 5 unpaired electrons. COF63 is paramagnetic with 4 unpaired electrons while CoC2O433 is diamagnetic. This apparent anomaly is explained by valence bond theory in terms of formation of inner orbital and outer orbital coordination entities. MnCN63, FeCN63 and CoC2O433 are inner orbital complexes involving D2sp3 hybridization. The former two complexes are paramagnetic and the latter diamagnetic. On the other hand, MnCl63, Fef63 and COF63 are outer orbital complexes involving sp3d2 hybridization and are paramagnetic corresponding to 4, 5 and 4 unpaired electrons. 257 coordination compounds. The spin-only magnetic moment of MnBr42 is 5.9 bm. Predict the geometry of the complex ion since the coordination number of Mn2 ion in the complex ion is 4. It will be either tetrahedral sp3 hybridization or square planar dsp2 hybridization. But the fact that the magnetic moment of the complex ion is 5.9 bm, it should be tetrahedral in shape rather than square planar because of the presence of 5 unpaired electrons in the d orbitals. Example 9.7 Example 9.7 Example 9.7 Example 9.7 Example 9.7 Solution 9. 5. 3 limitations of valence bond theory 9. 5. 4 crystal field theory. While the VB theory, to a larger extent, explains the formation, structures and magnetic behavior of coordination compounds, it suffers from the following shortcomings. It involves a number of assumptions. 2. It does not give quantitative interpretation of magnetic data. 3. It does not explain the color exhibited by coordination compounds. 5. It does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. B. It does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. B. It does not distinguish between weak and strong ligands. The crystal field theory CFD is an electrostatic model which considers the metal-ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and the ligand. Ligands are treated as point charges in case of anions or point dipoles in case of neutral molecules. The 5 d orbitals in an isolated gaseous metal atom ion have same energy, that is, they are degenerate. This degeneracy is maintained if a spherically symmetrical field of negative charges surrounds the metal atom ion. However, when this negative field is due to ligands, either anions or the negative ends of dipolar molecules like NH3 and H2O in a complex, it becomes asymmetrical and the degeneracy of the d orbitals is lifted. It results in splitting of the d orbitals. The pattern of splitting depends upon the nature of the crystal field. Let us explain this splitting in different crystal fields. A crystal field splitting in octahedral coordination entities. In an octahedral coordination entity with 6 ligands surrounding the metal atom ion, there will be repulsion between the electrons in metal d orbitals and the electrons or negative charges of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, the 2 times yd and 2 zd orbitals which point towards the axes along the direction of the ligand will experience more repulsion and will be raised in energy, and the dxy, ds and dxz orbitals which are directed between the axes will be lowered in energy relative to the average energy in the spherical crystal field. Thus, the degeneracy of the d orbitals has been removed due to ligand electron-metal electron repulsions in the octahedral complex to yield 3 orbitals of lower energy, T2G set and 2 orbitals of higher energy, X set. This splitting of the 258 chemistry degenerate levels due to the presence of ligands in a definite geometry is termed as crystal field splitting, and the energy separation is denoted by O. The subscript O is for octahedral figure 9.8. Thus, the energy of the 2 egg orbitals will increase by 350 and that of the 3 T2G will decrease by 250. The crystal field splitting, O, depends upon the field produced by the ligand and charge on the metal ion. Some ligands are able to produce strong fields, in which case, the splitting will be large, whereas others produce weak fields and consequently result in small splitting of d orbitals. In general, ligands can be arranged in a series in the order of increasing field strength as given below: I, BRSCN, Cl, S2F, O, C2042, H2O, NCSZ4, NH3, N, Cn, CO. Such a series is termed as spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Let us assign electrons in the d orbitals of metal ion and octahedral coordination entities. Obviously, the single d electron occupies one of the lower energy T2g orbitals. In d2 and d3 coordination entities, the d electrons occupy the T2g orbital singly in accordance with the Hund's rule. For d4 ions, two possible patterns of electron distribution arise. The fourth electron could either enter the T2g level and pair with an existing electron, or two, it could avoid paying the price of the pairing energy by occupying the egg level. Which of these possibilities occurs depends on the relative magnitude of the crystal field splitting, O, and the pairing energy. Pp represents the energy required for electron pairing in a single orbital. The two options are, if O, P, the fourth electron enters one of the egg orbitals, giving the configuration 312 grams GTE. Ligands for which O, P are known as weak field ligands and form high spin complexes. 2. If O, P, it becomes more energetically favorable for the fourth electron to occupy a T2g orbital with configuration T2g4x0. Ligands which produce this effect are known as strong field ligands and form low spin complexes. Calculations show that D4 to D7 coordination entities are more stable for strong field as compared to weak field cases. Figure 9.8, d orbital splitting in an octahedral crystal field. 259 coordination compounds. Figure 9.9, d orbital splitting in a tetrahedral crystal field. In the previous unit, we learned that one of the most distinctive properties of transition metal complexes is their wide range of colors. This means that some of the visible spectrum is being removed from white light as it passes through the sample, so the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. The complementary color is the color generated from the wavelength left over. If green light is absorbed by the complex, it appears red. Table 9.3 gives the relationship of the different wavelength absorbed and the color observed. 9.5. 5 color in coordination compounds. Coordinate entity wavelength of light absorbed and color of light absorbed. Color of coordination entity. Table 9.3. Relationship between the wavelength of light absorbed and the color observed in some coordination entities. Co-ClNH352 535 yellow violet Co-NH35 H2O3 500 blue green red Co-NH363 475 blue yellow orange Co-CN63 310 ultraviolet pale yellow Co-H2O42 600 red blue DH2O63 498 blue green violet. The color in the coordination compounds can be readily explained in terms of the crystal field theory. Consider, for example, the complex TH2O63, which is violet in color. This is an octahedral complex where the single electron T3 is a 3d1 system in the metal d orbital is in the T2g level in the ground state of the complex. The next higher state available for the electron is the empty egg level. If light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from T2g level to the egg level T2g1 egg 0 T2g0 egg 1. Consequently, the complex appears violet in color. Figure 9.10. The crystal field theory attributes the color of the coordination compounds to d transition of the electron. B. Crystal field splitting in tetrahedral coordination entities. In tetrahedral coordination entity formation, the d orbital splitting Fig. 9.9 is inverted into smaller as compared to the octahedral field splitting. For the same metal, the same ligands and metal ligand distances, it can be shown that T490. Consequently, the orbital splitting energies are not sufficiently large for forcing pairing and, therefore, low spin configurations are rarely observed. The G subscript is used for the octahedral and square planar complexes which have center of symmetry. Since tetrahedral complexes lack symmetry, G subscript is not used with energy levels, not in visible region. 260 Chemistry. It is important to note that in the absence of ligand, crystal field splitting does not occur and hence the substance is colorless. For example, removal of water from TH2O6Cl3 on heating renders it colorless. Similarly, anhydrous QSO4 is white, but QSO4.5H2O is blue in color. The influence of the ligand on the color of a complex may be illustrated by considering the NiH2O62 complex, which forms when nickel 2 chloride is dissolved in water. If the didn't ligand, ethane 1, 2-diamine N is progressively added in the molar ratios N, Ni, 1, 1, 2, 1, 3, 1. The following series of reactions and their associated color changes occur. NiH2O6 2 Ac Ni H2O4 and 2 Ac 2 H2O green pale blue NiH2O4 and 2 Ac Ni H2O2 and 2 Ac 2 H2O blue purple NiH2O2 and 2 Ac Ni and 3 Ac 2 H2O violet. This sequence is shown in Fig. 9.11, Figure 9.11 aqueous solutions of complexes of nickel 2 with an increasing number of ethane 1, 2-diamine ligands. NiHOAc 262 NiHOAc 242 and NiHOAc 242 and 2 NiAc 32 Color of some gemstones. The colors produced by electronic transitions within the d orbitals of a transition metal ion occur frequently in everyday life. Ruby Figure 9.12a is aluminium oxide Al2O3 containing about 0.51 Cr3 ions D3, which are randomly distributed in positions normally occupied by Al3. We may view these chromium-3 species as octahedral chromium-3 complexes incorporated into the alumina lattice. DD transitions at these centers give rise to the color. Figure 9.10, Transition of an electron in DH2O63. 261 Coordination compounds. The crystal field model is successful in explaining the formation, structures, color and magnetic properties of coordination compounds to a large extent. However, from the assumptions that the ligands are point charges, it follows that anionic ligands should exert the greatest splitting effect. The anionic ligands actually are found at the low end of the spectrochemical series. Further, it does not take into account the covalent character of bonding between the ligand and the central atom. These are some of the weaknesses of CFT, which are explained by ligand field theory, LFT, and molecular orbital theory, which are beyond the scope of the present study. 9.5.6 Limitations of crystal field theory. The homoleptic carbonyls compounds containing carbonyl ligands only are formed by most of the transition metals. These carbonyls have simple, well-defined structures. Tetracarbonyl nickel 0 is tetrahedral, pentacarbonyl iron 0 is trigonalbipyramidal, while hexacarbonyl chromium 0 is octahedral. Decacarbonyl dimanganese 0 is made up of two square pyramidal MnCO5 units joined by a Mn bond. Octacarbonyl dicobalt 0 has a co-bond bridged by two CO groups. Figure 9.13 9.6 Bonding in 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 metal capital C A R B O N Y L S capital C A R B O N Y L S capital C A R B O N Y L S capital C A R in emerald. Figure 9.12b. Cr3 ions occupy octahedral sites in the mineral beryl B3Al2C6018. The absorption bands seen in the ruby shift to longer wavelength, namely yellow, red and blue, causing emerald to transmit light in the green region. Figure 9.12, a ruby. This gemstone was found in marble from Mogok, Myanmar. B emerald. This gemstone was found in Muso, Colombia. A B in text questions and text questions and text questions and text questions and text questions. 9.5 Explain on the basis of valence bond theory that NiCN42 ion with square planar structure is diamagnetic and a NiCl42 ion with tetrahedral geometry is paramagnetic. 9.6 NiCl42 is paramagnetic while NiCO4 is diamagnetic, though both are tetrahedral. Why 9.7 Fe-H2O63 is strongly paramagnetic whereas Fe-CN63 is weakly paramagnetic. Explain 9.8 Explain CoNH363 is an inner orbital complex whereas NiNH362 is an outer orbital complex. 9.9 Predict the number of unpaired electrons in the square planar PTCN42 ion. 9.10 The hexaquomanganese 2 ion contains 5 unpaired electrons, while the hexacyanoin contains only 1 unpaired electron. Explain using crystal field theory. 262 Chemistry 9.79, 79, 79, 79, 7 Importance, capital I, M, P, O, R, T, A, N, C, E, capital I, M, P, O, R, T, A, N, C, E, capital I, M, P, O, R, T, A, N, C, E, and applications of capital C O O R D I N A T I O N capital C O O R D I N A T I O N capital C O O R D I Compounds. Necio cooxio necio tetrahedral 4 fe co c fe co trigonal bipyramidal 5 co mn octahedral 6 mnco 2 10 co coco co 2 8 c fig. 9.13 Figure 9.13 Figure 9.13 Figure 9.13 Figure 9.13 Structures of some representative homoleptic metal carbonyls. The metal carbon bond in metal carbonyls possess both Greek letter sigma and Greek letter pi character. The MC Greek letter sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant orbital of the metal. The MC Greek letter pi bond is formed by the donation of a pair of electrons from a filled d orbital of metal into the vacant antibonding Greek letter pi orbital of carbon monoxide. The metal-to-ligand bonding creates a synergic effect which strengthens the bond between CO and the metal. Figure 9.14. Figure 9.14. Figure 9.14. Figure 9.14. Figure 9.14. Figure 9.14. Example of synergic bonding interactions in a carbonyl complex. The coordination compounds are of great importance. These compounds are widely present in the mineral, plant and animal worlds and are known to play many important functions in the area of analytical chemistry, metallurgy, biological systems, industry and medicine. These are described below. Coordination compounds find use in many qualitative and quantitative chemical analysis. The familiar color reactions given by metal ions with a number of ligands, especially chelating ligands, as a result of formation of coordination entities, form the basis for their detection and estimation by classical and instrumental methods of analysis. Examples of such reagents include EDTA, DMG dimethylglyoxime, Greek letter alpha nitroso, Greek letter beta naphthol, cuprin, etc. Hardness of water is estimated by simple titration with Na2-EDTA. The Ca2 and Mg2 ions form stable complexes with EDTA. The selective estimation of these ions can be done due to difference in the stability constants of calcium and magnesium complexes. Some important extraction processes of metals, like those of silver and gold, make use of complex formation. Gold, for example, combines with cyanide in the presence of oxygen and water to form the coordination entity AuCN2 in aqueous solution. Gold can be separated in metallic form from this solution by the addition of zinc unit 6. Similarly, purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. 263 Coordination compound summary. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. During the last 50 years, advances in this area have provided development of new concepts and models of bonding and molecular structure, novel breakthroughs in chemical industry and vital insights into the functioning of critical components of biological systems. The first systematic attempt at explaining the formation, reactions, structure and bonding of a coordination compound was made by A. Werner. His theory postulated the use of two types of linkages, primary and secondary, by a metal atom ion in a coordination compound. In the modern language of chemistry, these linkages are recognized as the ionizable ionic and non-ionizable covalent bonds, respectively. Using the property of isomerism, Werner predicted the geometrical shapes of a large number of coordination entities. The valence bond theory (VBT) explains with reasonable success the formation, magnetic behavior and geometrical shapes of coordination compounds. It, however, fails to provide a quantitative interpretation of magnetic behavior and has nothing to say about the optical properties of these compounds. The crystal field theory (CFT) to coordination compounds is based on the effect of different crystal fields provided by the ligands taken as point charges. For example, impure nickel is converted to NiCO4, which is decomposed to yield pure nickel. Coordination compounds are of great importance in biological systems. The pigment responsible for photosynthesis, chlorophyll, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood which acts as oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, the anti-pernicious anemia factor, is a coordination compound of cobalt. Among the other compounds of biological importance with coordinated metal ions are the enzymes like carboxypeptidase A and carbonic anhydrase, catalysts of biological systems. Coordination compounds are used as catalysts for many industrial processes. Examples include rhodium complex, PH3P3RHCl, a Wilkinson catalyst, is used for the hydrogenation of alkenes. Articles can be electroplated with silver and gold much more smoothly and evenly from solutions of the complexes AgCN2 and AuCN2 than from a solution of simple metal ions. In black and white photography, the developed film is fixed by washing with hypo solution which dissolves the undecomposed NAgBr to form a complex ion, Ag2O323. There is growing interest in the use of chelate therapy in medicinal chemistry. An example is the treatment of problems caused by the presence of metals in toxic proportions in plant-animal systems. Thus, excessive copper and iron are removed by the chelating ligands D-penicillamine and desferrioxime B via the formation of coordination compounds. EDTA is used in the treatment of lead poisoning. Some coordination compounds of platinum effectively inhibit the growth of tumors. Examples are cisplatin and related compounds. On the degeneracy of d orbital energies of the central metal atom ion, the splitting of the d orbitals provides different electronic arrangements in strong and weak crystal fields. The treatment provides for quantitative estimations of orbital separation energies, magnetic moments and spectral instability parameters. However, the assumption that ligands constitute point charges creates many theoretical difficulties. The metal-carbon bond in metal carbonyls possesses both Greek letter sigma and Greek letter pi character. The ligand to metal is Greek letter sigma bond and metal to ligand is Greek letter pi bond. This unique synergic bonding provides stability to metal carbonyls. Coordination compounds are of great importance. These compounds provide critical insights into the functioning and structures of vital components of biological systems. Coordination compounds also find extensive applications in metallurgical processes, analytical and medicinal chemistry,